The design and analysis of algorithms is the interplay between, on the one hand, general principles, and on the other hand, instantiations of those principles to solve specific problems. While there's no silver bullet in algorithm design, no one technique which solves every computational problem that's ever going to come up, there are general design principles which have proven useful over and over again over the decades for solving problems that arise in different application domains. Those, of course, are the principles that we focus on in this class. For example, in part 1, we studied the divide and conquer algorithm design paradigm and principles of graph search, amongst others. On the other hand, we study specific instantiations of these techniques. So in part 1, we studied divide and conquer and how it applies to, say, Strasson's matrix multiplication, merge sort, and quick sort. In graph search, we culminated with the rightfully famous Dijkstra's algorithm for computing shortest paths. This, of course, is useful not just because as any card-carrying computer scientist or programmer, you want to know about what these algorithms are and what they do, but it also gives us a toolbox, a suite of for-free primitives which we can apply to our own computational problems as a building block in some larger program. Part 2 of the course will continue this narrative. We'll learn very general algorithm design paradigms like greedy algorithms, dynamic programming algorithms, and many applications, including a number of algorithms for the greatest hits compilation. And in this video and the next, I want to whet your appetite for what's to come by plucking out 2 of the applications that we'll study in detail later in the course, specifically in the dynamic programming section of the course. First of all, for both of these problems, I think their importance is self-evident. I don't think I'll have to really discuss why these are interesting problems, why in some sense we really need to solve these 2 problems. Secondly, these are quite tricky computational problems, and I would expect that most of you do not currently know good algorithms for these problems, and it would be challenging to design one. Third, by the end of this class, you will know efficient algorithms for both of these problems. In fact, you'll know something much better. You'll know general algorithm design techniques which solve as a special case these 2 problems and have the potential to solve problems coming up in your own projects as well. And one comment before we get started on these 2 videos, they're both at a higher level than most of the class, by which I mean there won't be any equations or math, there won't be any concrete pseudocode, and I'll be glossing over lots of the details. The point is just to convey the spirit of what we're going to be studying and to illustrate the range of applications of the techniques that we're going to learn. So what I want to talk about first is distributed shortest path routing and why it's fundamental to how the internet works. So let me begin with a kind of very non-mathematical claim. I claim that we can usefully think of the internet as a graph, as a collection of vertices and a collection of edges. So this is clearly an ambiguous statement. There's many things I might mean, as we'll discuss, but here's the primary interpretation I want you to have for this particular video. So to specify this, the vertices I intend to be the end hosts and the routers of the internet. So machines that generate traffic, machines that consume traffic, and machines that help traffic get from one place to another. So the edges are going to be directed, and they're meant to represent physical or wireless connections, indicating that one machine can talk directly to another one via either a physical link between the 2 or a direct wireless connection. So it's common that you'll have edges in both directions, so that if machine A can talk to machine B directly, then also machine B can talk directly to machine A, but you definitely want to allow the possibility of asymmetric communication. So, for example, imagine I send an email from my Stanford account to one of my old mentors at Cornell, where I did my graduate studies. So this piece of data, this email, has to somehow migrate from my machine local at Stanford to my mentor's machine over at Cornell. So how does that actually happen? Well, initially there's a phase of sort of local transportation. So this piece of data has to get from my local machine to a place within the Stanford network that can talk to the rest of the world. Just like if I was trying to travel to Cornell, I would have to first use local transportation to get to San Francisco Airport, and only from there could I take an airplane. So this machine from which data can escape from the Stanford network to the outside world is called the gateway router. The Stanford Gateway Router passes it on to a network whose job is to cross the country. So last I checked, the commercial internet service provider of Stanford was Cogent. So they, of course, have their own gateway router, which can talk to the Stanford one and vice versa. And of course, these 2 nodes and the edges between them are just this tiny, tiny, tiny piece embedded in this massive graph comprising all the end hosts and routers of the internet. So that's the main version of a graph that we're going to talk about in this video. But let me just pause to mention a couple of other graphs that are related to the internet and quite interesting in their own right. So one graph that has generated an enormous amount of interest and study is the graph induced by the web. So here the vertices are going to represent web pages, and the edges, which are certainly directed, represent hyperlinks, that one web page points to another one. So for example, my home page is one node in this massive graph. And as you might expect, there is a link from my home page to the course page for this class. It is, of course, essential to use directed edges to faithfully model the web. There is, for example, no directed edge from this course's homepage to my own homepage at Stanford. So the web really exploded around mid-90s, late 90s. So for the past 15 plus years, there's been lots of research about the web graph. I'm sure you won't be surprised to hear that around the middle of the last decade, people got extremely excited about properties of social networks. Those, of course, can also be fruitfully thought of as graphs. Here, the vertices are going to be people, and the links are going to denote relationships. So for example, friend relationships in Facebook, or the following relationship on Twitter. So notice that different social networks may correspond to undirected or directed graphs. Facebook, for example, corresponding to an undirected graph, Twitter corresponding to a directed graph. So let's now return to the first interpretation I wanted to focus on, that where the vertices are in hosts and routers, and edges represent direct physical or wireless connections, indicating that two machines can talk directly to each other. So going back to that graph, let's go back to the story where I'm sending an email to somebody at Cornell, and this data has to somehow travel from my local machine to some local machine at Cornell. So in particular, this piece of data has to get from the Stanford Gateway router, in effect the airport for Stanford's network, to the Cornell Gateway router, so the landing airport over on Cornell's side. Now, it's not easy to figure out exactly what the structure of the routes between Stanford and Cornell look like, but the one thing I can promise you is that there is not a direct physical link between the Stanford Gateway router and the Cornell Gateway router. Any route between the two is going to comprise multiple hops. It will have intermediate stops. And there's not going to be a unique such route. So if you have the choice between taking one route, which stops in Houston and then Atlanta and then in Washington, D.C., how would you compare that to one which stops in Salt Lake City and Chicago? Well, hopefully your first instinct and a perfectly good idea is, all else being equal, prefer the path that is in some sense the shortest. Now, in this context, shortest could mean many things, and it's interesting to think about different definitions. But for simplicity, let's just focus on the fewest number of hops, equivalently the fewest number of intermediate stops. Well, if we want to actually execute this idea, we clearly need an algorithm that, given to a source and a destination, computes the shortest path between the two. So hopefully you feel well equipped to discuss this problem, because one of the highlights of part one of this class was the discussion of Dijkstra's shortest path algorithm and a blazingly fast implementation using heaps that runs in almost linear time. We did mention one caveat when we discussed Dijkstra's algorithm, namely that it requires all edge links to be non-negative, but in the context of internet routing, almost any edge metric you'd imagine using will satisfy this non-negativity assumption. There is, however, a serious issue with trying to apply Dijkstra's shortest path algorithm off the shelf to solve this distributed internet routing problem. And the issue is caused by the just massive distributed scale of the modern day internet. Probably back in the 1960s when you had the 12-node ARPANET, you could get away with running Dijkstra's shortest path algorithm, but not in the 21st century. It's not feasible for the Stanford Gateway router to maintain locally a reasonably accurate model of the entire internet graph. So how can we elude this issue? Is it fundamental that because the internet is so massive, it's impossible to run any shortest path algorithm? Well, the ray of hope would be if we could have a shortest path algorithm that admitted a distributed implementation, whereby a node could just interact, perhaps iteratively, with its neighbors, with the machines to which it's directly connected, and yet somehow converge to having accurate shortest paths to all of the destinations. So perhaps the first thing you try would be to seek out an implementation of Dijkstra's algorithm where each vertex uses only local computation. That seems hard to do. If you look at the pseudocode of Dijkstra, it just doesn't seem like a localizable algorithm. So instead what we're going to do is we're going to learn a different shortest path algorithm. It's also a classic, definitely on the greatest hits compilation. It's called the Bellman-Ford algorithm. So the Bellman-Ford algorithm, as you'll see, can be thought of as a dynamic programming algorithm, and indeed it correctly computes shortest path using only local computation. Each vertex only communicates in rounds with the other vertices to which it's directly connected. As a bonus, we'll see this algorithm also handles negative edge lengths, which of course Dijkstra's algorithm does not. But don't think Dijkstra's algorithm is obsolete. It still has faster running time in situations where you can get away with centralized computation. Now, what's really kind of amazing here is that the Bellman-Ford algorithm, it dates back to the 1950s. So that's not just pre-internet, that's pre-ARPANET. So that's before the internet was even a glimmer in anybody's eye. And yet it really is the foundation for modern internet routing protocols. Needless to say, there's a lot of really hard engineering work and further ideas required to translate the concepts from Bellman-Ford to actually doing routing in the very complex modern day internet. But yet, those protocols at their foundation go all the way back to the Bellman-Ford algorithm. In this video, we'll cover a second problem to whet your appetite for things to come, namely the problem of sequence alignment. So this is a fundamental problem in computational genomics. If you take a class on the subject, it's very likely to occupy the very first couple of lectures. So in this problem, you're given two strings over an alphabet and no prizes for guessing which is the alphabet we're most likely to care about. Typically, these strings represent portions of one or more genomes. And just as a toy running example, you can imagine that the two strings we're given are A, G, 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 C, T, and A, G, G, C, A. Note that the two input strings do not necessarily need to be of the same length. Informally speaking, the goal of this sequence alignment problem is to figure out how similar the two input strings are. Obviously, I haven't told you what I mean by two strings being similar. That's something we'll develop over the next couple of slides. Why might you want to solve this problem? Well, there's actually a lot of reasons. Let me just give you two of many examples. One would be to conjecture the function of regions of a genome that you don't understand, like say the human genome, from similar regions that exist in genomes that you do understand, or at least understand better, say the mouse genome. If you see a string that has a known function in the well-understood genome and you see something similar in the poorly understood genome, you might conjecture it has the same or a similar function. A totally different reason you might want to compare the genomes of two different species is to figure out whether one evolved directly from the other and when. A second totally different reason you might want to compare the genomes of two different species is to understand their evolutionary relationship. So for example, maybe you have three species, A, B, and C, and you're wondering whether B evolved from A and then C evolved from B, or whether B and C evolved independently from a common ancestor A. And you might then take genome similarity as a measure of proximity in the evolutionary tree. So having motivated the informal version of the problem, let's work toward making it more formal. In particular, I owe you a discussion of what I mean by two strings being similar. So to develop intuition for this, let's revisit the two strings that we introduced on the previous slide, AGGGCT and AGGCA. Now, if we just sort of eyeball these two strings, I mean, clearly they're not the same string, but we somehow feel like they're more similar than they are different. So where does that intuition come from? Well, one way to make it more precise is to notice that these two strings can be nicely aligned in the following sense. Let's write down the longer string, AGGGCT, and I'm going to write the shorter string under it, and I'll insert a gap, a space, to make the two strings have the same length. I'm going to put the space where there seems to be a quote-unquote missing G. And in what sense is this a nice alignment? Well, it's clearly not perfect. We don't get a character-by-character match of the two strings, but there's only two minor flaws. So on the one hand, we did have to insert a gap, and we do have to suffer one mismatch in the final column. So this intuition motivates defining similarity between two strings with respect to their highest quality alignment, their nicest alignment. So we're getting closer to a formal problem statement, but it's still somewhat underdetermined. Specifically, we need to make precise why we might prefer one alignment over another. For example, is it better to have three gaps and no mismatches, or is it better to have one gap and one mismatch? So for this video, we're effectively going to punt on this question. We're going to assume this problem's already been solved experimentally, that it's known and provided as part of the input which is more costly, gaps and various types of mismatches. So here then is the formal problem statement. So in addition to the two strings over ACGT, we are provided as part of the input a non-negative number indicating the cost we incur in an alignment for each gap that we insert. Similarly, for each possible mismatch of two characters, like for example mismatching an A and T, we're given as part of the input a corresponding penalty. Given this input, the responsibility of a sequence alignment algorithm is to output the alignment that minimizes the sum of the penalties. Another way to think of this output, the minimum penalty alignment, is we're trying to find in effect the minimum cost explanation for how one of these strings would have turned into the other. So we can think of a gap as sort of undoing a deletion that occurred sometime in the past, and we can think of a mismatch as representing a mutation. So this minimum possible total penalty, that is the value of this optimal alignment, is famous and fundamental enough to have its own name, namely the Needleman-Wunsch score. So this quantity is named after the two authors that proposed efficient algorithm for computing the optimal alignment. That appeared way back in 1970 in the Journal of Molecular Biology. And now at last we have a formal definition of what it means for two strings to be similar. It means they have a small NW score, a score close to 0. So for example, if you have a database with a whole bunch of genome fragments, according to this, you're going to define the most similar fragments to be those with the smallest NW score. So to bring the discussion back squarely into the land of algorithms, let me point out that this definition of genome similarity is intrinsically algorithmic. This definition would be totally useless unless there existed an efficient algorithm that, given two strings and these penalties, computes the best alignment between those two strings. If you couldn't compute this score, you would never use it as a measure of similarity. So this observation puts us under a lot of pressure to devise an efficient algorithm for finding the best alignment. So how are we going to do that? Well, we could always fall back to brute force search, where we iterate over all of the conceivable alignments of the two strings, compute the total penalty of each of those alignments, and remember the best one. Clearly, correctness is not going to be an issue for brute force search. It's correct essentially by definition. The issue is how long does it take? So let's ask a simpler question. Let's just think about how many different alignments there are. How many possibilities do we have to try? So for concrete, let's imagine I gave you two strings of length 500, which is a not unreasonable length. Which of the following English phrases best describes the number of possibilities, the number of alignments given two strings with 500 characters each? So I realize this is sort of a cheeky question, but I hope you could gather that what I was looking for was part D. So, so how big are each of these quantities anyways? Well, in a typical version of this class, you might have about 50,000 students enrolled or so. So that's somewhere between 10 to the 4 and 10 to the 5. The number of people on Earth is roughly 7 billion, so that's somewhere between 10 to the 9 and 10 to the 10. The most common estimate I see for the number of atoms in the known universe is 10 to the 80. And believe it or not, the number of possible alignments of two strings of length 500 is even bigger than that. So I'll leave it for you to convince yourself that the number of possibilities is at least 2 raised to the 500. The real number is actually noticeably bigger than that. And because 10 is at most 2 to the 4th, we can lower bound this number by 10 raised to the 125, quite a bit bigger than the number of atoms in the universe. And the point, of course, is just that it's utterly absurd to envision implementing brute force search even at the scale of a few hundred characters. And forgetting about these sort of astronomical, if you will, comparisons, even if you had string lengths much smaller, say in the a dozen or two, you'd never ever run brute force search. It's just not going to work. And of course, notice this is not the kind of problem, this control explosion. This doesn't go away if you wait a little while for Moore's law to help you. This is a fundamental limitation. It says you are never going to compute alignments of the strings that you care about unless you have a fast, clever algorithm. I'm happy to report that you will indeed learn such a fast and clever algorithm later on in this course. Even better, it's just going to be a straightforward instantiation of a much more general algorithm design paradigm, that of dynamic programming. In this video, I'll talk about various aspects of the course, the topics that we'll cover, the kinds of skills you can expect to acquire, the kind of background that I expect, the supporting materials, and the available tools for self-assessment. Let's start with the specific topics that this course is going to cover. The course material corresponds to the first half of a 10-week Stanford course that's taken by all computer science undergraduates, as well as many of our graduate students. There will be 5 high-level topics, and at times these will overlap. The 5 topics are, first of all, the vocabulary for reasoning about algorithm performance, the design and conquer algorithm design paradigm, randomization and algorithm design, primitives for reasoning about graphs, and the use and implementation of basic data structures. The goal is to provide an introduction to and basic literacy in each of these topics. Much more can be said about each of them than we'll have time for here. The first topic is the shortest and probably also the driest, but it's a prerequisite for thinking seriously about the design and analysis of algorithms. The key concept here is big O notation, which conceptually is a modeling choice about the granularity with which we measure a performance metric, like the running time of an algorithm. It turns out that the sweet spot for clear, high-level thinking about algorithm design is to ignore constant factors and lower-order terms and to concentrate on how well algorithm performance scales with large input sizes. Big O notation is the way to mathematicize this sweet spot. Now, there's no one silver bullet in algorithm design, no single problem-solving method that's guaranteed to unlock all of the computational problems that you're likely to face. That said, there are a few general algorithm design techniques, high-level approaches to algorithm design that find successful application across a range of different domains. These relatively widely applicable techniques are the backbone of a general algorithms course like this one. In this course, we'll only have time to deeply explore one such algorithm design paradigm, namely that of divide and conquer algorithms. In the sequel course, as we'll discuss, there's 2 other major algorithm design paradigms that get covered. But for now, a divide and conquer algorithm, the idea is to first break the problem into smaller subproblems, which then get solved recursively, and then to somehow quickly combine the solutions to the subproblems into one for the original problem that you actually care about. So for example, in the last video, we saw 2 algorithms of this sort, 2 divide and conquer algorithms for multiplying 2 large integers. In later videos, we'll see a number of different applications. We'll see how to design fast divide and conquer algorithms for problems ranging from sorting to matrix multiplication to nearest neighbor type problems in computational geometry. In addition, we'll cover some powerful methods for reasoning about the running time of recursive algorithms like these. As for the third topic, a randomized algorithm is one that, in some sense, flips coins while it executes. That is, a randomized algorithm will actually have different executions if you run it over and over again on a fixed input. It turns out, and this is definitely not intuitive, that allowing randomization internal to an algorithm often leads to simple, elegant, and practical solutions to various computational problems. The canonical example is randomized quicksort, and that algorithm and analysis we will cover in detail in a few lectures. Randomized primality testing is another killer application that we'll touch on, and we'll also discuss a randomized approach to graph partitioning, and finally we'll discuss how randomization is used to reason about hash functions and hash maps. One of the themes of this course, and one of the concrete skills that I hope you take away from the course, is literacy with a number of computational primitives for operating on data that are so fast that they're in some sense essentially free. That is, the amount of time it takes to invoke one of these computational primitives is barely more than the amount of time you're already spending just examining or reading the input. When you have a primitive which is so fast that the running time is barely more than what it takes to read the input, you should be ready to apply it, for example, in a pre-processing step, whenever it seems like it might be helpful. It should just be there on the shelf waiting to be applied at will. Sorting is one canonical example of a very fast, almost for-free primitive of this form. But there are ones that operate on more complex data as well. So recall that a graph is a data structure that has, on the one hand, vertices, and on the other hand, edges, which connect pairs of vertices. Graphs model, among many other things, different types of networks. So even though graphs are much more complicated than mere arrays, there are still a number of blazingly fast primitives for reasoning about their structure. In this class, we'll focus on primitives for computing connectivity information and also shortest paths. We'll also touch on how such primitives have been used to investigate the structure of information in social networks. Finally, data structures are often a crucial ingredient in the design of fast algorithms. A data structure is responsible for organizing data in a way that supports fast queries. Different data structures support different types of queries. I'll assume that you're familiar with the structures that you typically encounter in a basic programming class, including arrays and vectors, lists, stacks, and queues. Hopefully, you've seen at some point both trees and heaps, or you're willing to read a bit about them outside of the course, but we'll also include a brief review of each of those data structures as we go along. There's two extremely useful data structures that we'll discuss in detail. The first is balanced binary search trees. These data structures dynamically maintain an ordering on a set of elements while supporting a large number of queries that run in time logarithmic in the size of the set. The second data structure we'll talk a fair bit about is hash tables or hash maps, which keep track of a dynamic set while supporting extremely fast insert and lookup queries. We'll talk about some canonical uses of such data structures, as well as what's going on under the hood in a typical implementation of such a data structure. There's a number of important concepts in the design and analysis of algorithms that we won't have time to cover in this 5-week course. Some of these will be covered in the sequel course, Design and Analysis of Algorithms 2, which corresponds to the second half of Stanford's 10-week course on this topic. The first part of this sequel course focuses on two more algorithm design paradigms. First of all, the design and analysis of greedy algorithms with applications to minimum spanning trees, scheduling, and information theoretic coding. And secondly, the design and analysis of dynamic programming algorithms, with example applications being in genome sequence alignment and shortest path protocols in communication networks. The second part of the sequel course concerns NP-complete problems and what to do about them. Now, NP-complete problems are problems that, assuming a famous mathematical conjecture you might have heard of, which is called the P0 equal to NP conjecture, are problems that cannot be solved under this conjecture by any computationally efficient algorithm. We'll discuss the theory of NP-completeness, and with a focus on what it means for you as an algorithm designer. We'll also talk about several ways to approach NP-complete problems, including fast algorithms that correctly solve special cases, fast heuristics with provable performance guarantees, and exponential time algorithms that are qualitatively faster than brute force search. Of course, there are plenty of important topics that can't be fit into either of these two 5-week courses. Depending on the demand, there might well be further courses on more advanced topics. Following this course is going to involve a fair amount of time and effort on your part. So, it's only reasonable to ask, what can you hope to get out of it? What skills will you learn? Well, primarily, even though this isn't a programming class per se, it should make you a better programmer. You'll get lots of practice describing and reasoning about algorithms. You'll learn algorithm design paradigms, so really high-level problem-solving strategies that are relevant for many different problems across different domains, and tools for predicting the performance of such algorithms. You'll learn several extremely fast subroutines for processing data, and several useful data structures for organizing data that can be deployed directly in your own programs. Second, while this is not a math class per se, we'll wind up doing a fair amount of mathematical analysis, and this in turn will sharpen your mathematical and analytical skills. You might ask, why is mathematics relevant for a class in the design and analysis of algorithms, seemingly more of a programming class? Well, let me be clear. I am totally uninterested in merely telling you facts or regurgitating code that you can already find on the web or in any number of good programming books. My goal here in this class, and the way I think I can best supplement the resources that you probably already have access to, is to explain why things are the way they are, why we analyze the algorithms in the way that we do, why various superfast algorithms are in fact superfast, and so on. And it turns out that good algorithmic ideas usually require non-trivial mathematical analysis to understand properly. You'll acquire fundamental insights into the specific algorithms and data structures that we discuss in the course, and hopefully many of these insights will prove useful more generally in your other work. Third, and perhaps most relevant for those of you who work in some other discipline, this course should help you learn how to think algorithmically. Indeed, after studying algorithms, it's hard not to see them pretty much everywhere. Whether you're riding an elevator, watching a flock of birds, buying and selling stocks out of your portfolio, or even watching an infant learn. As I said in the previous video, algorithmic thinking is becoming increasingly useful and prevalent in fields outside of computer science and technology, like in biology, statistics, and economics. Fourth, if you're interested in feeling like a card-carrying computer scientist in some sense, then you'll definitely want basic literacy in all of the topics that we'll be covering. Indeed, one of the things that makes studying algorithms so fun is it really feels like you're studying a lot of the greatest hits from the last 50 years of computer science. So after this class, no longer will you feel excluded at that computer science cocktail party when someone cracks a joke about Dijkstra's algorithm. Now you'll know exactly what they mean. Finally, there's no question that studying this material is helpful for technical interview questions. To be clear, my sole goal here is to teach you algorithms and not to prepare you for interviews per se. But over the years, countless students of mine have regaled me with stories about how mastering the concepts in this class enabled them to ace every technical question they were ever asked. I told you, this is fundamental stuff. So what do I expect from you? Well, honestly, the answer is nothing. After all, isn't the whole point of a free online class like this one that anyone can take it and devote as much effort to it as they like? So that said, as a teacher, it's still useful to have one or more canonical students in mind, and I thought I'd go ahead and be transparent with you about how I'm thinking about these lectures, who I have in mind that I'm teaching to. Though again, please don't feel discouraged if you don't conform to this canonical student template. I'm happy to have the opportunity to teach you about algorithms, no matter who you are. So first, I have in mind someone who knows at least some programming. For example, consider the previous lecture. We talked about a recursive approach to multiplying two numbers, and I mentioned how a certain mathematical expression, back then we labeled it star and circled it in green, how that expression naturally translated into a recursive algorithm. In particular, I was certainly assuming that you had some familiarity with recursive programs. If you feel comfortable with my statement in that lecture, if you feel like you could code up a recursive integer multiplication algorithm based on the high-level outline that I gave you, then you should be in good shape for this course. You should be good to go. If you weren't comfortable with that statement, well, you might not be comfortable with the relatively high and conceptual level at which we discuss programs in this course. But I encourage you to watch the next several videos anyways to see if you get enough out of them to make it worth your while. Now, while I'm aiming these lectures at people who know some programming, I'm not making any assumptions whatsoever about exactly which programming languages you know. Any standard imperative language, something like C, Java, or Python, is totally fine for this course. Now, to make these lectures accessible to as many programmers as possible, and to be honest, also to promote thinking about programming at a relatively abstract and conceptual level, I won't be describing algorithms in any particular programming language. Rather, when I discuss algorithms, I'll use only high-level pseudocode or often simply English. My inductive hypothesis is that you are capable of translating such a high-level description into a working program in your favorite programming language. In fact, I strongly encourage everyone watching these lectures to do such a translation of all of the algorithms that we discuss. This will ensure your comprehension and appreciation of them. Indeed, many professional computer scientists and programmers don't feel that they really understand an algorithm until they've coded it up. Many of the course's assignments will have a problem in which we ask you to do precisely this. Put another way, if you're looking for a sort of coding cookbook, code that you can copy and paste directly into your own programs without necessarily understanding how it works, then this is definitely not the course for you. There are several books out there that cater to programmers looking for such coding cookbooks. Second, for these lectures I have in mind someone who has at least a modest amount of mathematical experience, though perhaps with a fair bit of accumulated rust. Concretely, I expect you to be able to recognize a logical argument, that is, a proof. In addition, two methods of proof that I hope you've seen before are proofs by induction and proofs by contradiction. I also need you to be familiar with basic mathematical notation, like the standard quantifier and summation symbols. A few of the lectures on randomized algorithms and hashing will go down much easier for you if you've seen discrete probability at some point in your life. But beyond these basics, the lectures will be self-contained. You don't even need to know any calculus, save for a single simple integral that magically pops up in the analysis of the randomized quicksort algorithm. I imagine that many of you have studied math in the past, but you could use a refresher. You're a bit rusty. And there's plenty of free resources out there on the web, and I encourage you to explore and find some that you like. But one that I want to particularly recommend is a great set of free lecture notes. It's called Mathematics for Computer Science. It's authored by Eric Lehman and Tom Layton, and it's quite easy to find on the web if you just do a web search. And those notes cover all of the prerequisites that we'll need in addition to tons of other stuff. In the spirit of keeping this course as widely accessible as possible, we're keeping the required supporting materials to an absolute minimum. Lectures are meant to be self-contained, and we'll always provide you with the lecture notes in PowerPoint and PDF format. Once in a while, we'll also provide some additional lecture notes. No textbook is required for this class, but that said, most of the material that we'll study is well covered in a number of excellent algorithms books that are out there. So I'll single out 4 such books here. The first 3 I mentioned because they've all had a significant influence on the way that I both think about and teach algorithms. So it's natural to acknowledge that debt here. One very cool thing about the second book, the one by Dasgupta, Papadimitriou, and Vazirani, is that the authors have made a version of it available online for free. And again, if you search on the authors' names and the textbook title, you should have no trouble coming up with it with a web search. Similarly, that's the reason I've listed the 4th book. Those authors have likewise made a essentially complete version of that book available online, and it's a good match with the material that we're going to cover here. If you're looking for more details about something covered in this class or simply a different explanation than the one that I give you, all of these books are going to be good resources for you. There are also a number of excellent algorithms textbooks that I haven't put on this list. I encourage you to explore and find your own favorite. In our assignments, we'll sometimes ask you to code up an algorithm and use it to solve a concrete problem that is too large to solve by hand. Now, we don't care what programming language or development environment you use to do this, as we're only going to be asking you for the final answer. Thus, we're not requiring anything specific, just that you are able to write and execute programs. If you need help or advice about how to get set up with a suitable coding environment, we suggest that you ask other students for help via the course discussion forum. Finally, let's talk a bit more about assessment. Now, this course doesn't have official grades per se, but we will be assigning weekly homeworks. Now, we're going to assign homeworks for 3 different reasons. The first is just for self-assessment. It's to give you the opportunity to test your understanding of the material so that you can figure out which topics you've mastered and which ones that you haven't. The second reason we do it is to impose some structure on the course, including deadlines, to provide you with some additional motivation to work through all of the topics. Deadlines also have a very important side effect that it synchronizes a lot of the students in the class, and this of course makes the course discussion forum a far more effective tool for students to seek and provide help in understanding the course material. The final reason that we give homeworks is to satisfy those of you who, on top of learning the course material, are looking to challenge yourself intellectually. Now, this class has tens of thousands of students, so it's obviously essential that the assignments can be graded automatically. Now, we're currently only in the 1.0 generation of free online courses such as this one, so the available tools for auto-graded assessment are currently rather primitive. So we'll do the best we can, but I have to be honest with you. It's difficult or maybe even impossible to test deep understanding of the design and analysis of algorithms using the current set of tools. Thus, while the lecture content in this online course is in no way watered down from the original Stanford version, the required assignments and exams we'll give you are not as demanding as those that are given in the on-campus version of the course. To make up for this fact, we'll occasionally propose optional algorithm design problems, either in a video or via a supplementary assignment. We don't have the ability to grade these, but we hope that you'll find them interesting and challenging, and that you'll discuss possible solutions with other students via the course discussion forum. So I hope this discussion answered most of the questions that you have about the course. Let's move on to the real reason that we're all here, to learn more about algorithms. Welcome to this first course in the design and analysis of algorithms. I imagine many of you are already clear on your reasons for taking this course, but let me begin by justifying the course's existence and giving you several different motivations for learning about algorithms. So what is an algorithm? Well, we're not going to be needing a precise definition in this course, but essentially an algorithm is a well-defined set of rules, a recipe in effect, for solving some kind of computational problem. So for example, maybe you're given a bunch of numbers and you want to rearrange them into sorted order. Maybe you're given a road network with an origin and a destination and you want to compute the shortest path from point A to point B. Maybe you're given a bunch of tasks with deadlines and you want to know whether or not it's feasible to accomplish all of those tasks by their respective deadlines. So why study algorithms? Well, first of all, understanding the field of algorithms and also the related field of data structures is crucial for doing serious work in pretty much any other branch of computer science. That's the precise reason why, here at Stanford University, this is the course that's required for all of the degrees that the computer science department grants. Be it a bachelor's, a master's, or a PhD degree, we insist that you have mastery of the field of algorithms. So what are some examples of uses in the rest of computer science? Well, if you're doing routing in a communication network, that piggybacks on classical shortest path algorithms. The effectiveness of public key cryptography really rests on that of number theoretic algorithms. In, say, computer graphics, you need the computational primitives that are supplied by the study of geometric algorithms. Database indices rely on balanced search tree data structures, as covered in this course. And computational biology uses dynamic programming algorithms to measure the similarity among genomes. And the list goes on and on. A second reason to study algorithms is that they play a key role in modern technological innovation. Obviously, I could give any number of examples here. Let me just state one super obvious one, which is that search engines use a tapestry of algorithms to efficiently compute the relevance of various web pages. The most famous such algorithm, which you may have heard of, is the PageRank algorithm in use by Google. Indeed, in a December 2010 report to the United States White House, the President's Council of Advisors on Science and Technology argued that, in many areas, performance gains due to improvements in algorithms have vastly exceeded even the dramatic performance gains due to increased processor speed, as you'd be familiar with in the form of Moore's Law. Third, although this is getting significantly outside the scope of this course, algorithms are increasingly being used to provide a novel lens on processes outside of computer science and technology. For example, the study of quantum computation has provided a new and computational viewpoint on quantum mechanics Price fluctuations in economic markets can be fruitfully viewed as an algorithmic process, and even evolution can be usefully thought of as a surprisingly effective search algorithm. The last two reasons I'm going to give you might sound a little flippant, but I think there's more than a grain of truth to both of them. Now, I don't know about you, but back when I was a student, my favorite classes were always challenging classes, but after I struggled through them, I somehow felt like I had a few more IQ points than when I started. So I hope this course provides a similar experience for many of you, that on the one hand, it's a bit of a struggle, you find the concepts challenging, but perhaps you feel just a tinge smarter after we're done. Finally, I hope that by the end of the course, a constant fraction of you will agree with me that designing and analyzing algorithms, it's simply fun. It's an endeavor that requires a rare blend of creativity and precision, and it can certainly be frustrating at times, but even more than that, it is addictive. So let's now descend from these lofty generalities and get much more concrete. And also, let's remember that we've all been learning and using algorithms since we were little kids. So once upon a time, in roughly third grade or so, you learned how to multiply two numbers. Now, you probably weren't thinking in these terms at the time, but multiplying two numbers is certainly a well-defined computational problem, and that procedure you learned back in third grade or so is indeed an algorithm. So let's just make that a little bit more precise. In this computational problem, we're given as input two numbers, let's say with n digits. And to make things interesting, why don't you think about n as being really quite large, say in the thousands. Maybe we're implementing an algorithm that's going to be used in a cryptography application where you need to keep track of really quite large numbers. So if we call the two input numbers x and y, the problem is simply to compute their product, x times y. So a quick digression. I'll certainly be the first to admit that my handwriting is not the greatest. I got a C in penmanship back in elementary school, and I think the teacher was being a little generous. But it's an acquired taste, but trust me, you will get used to it. Okay, back to integer multiplication. Now, when we talk about procedures for multiplying two numbers, we're going to be interested in counting how many steps are required in order to execute the multiplication. So how do we count a step? We'll talk more about this later, but for multiplying two numbers, let's just call a step the addition or multiplication of two single-digit numbers. So let's review the integer multiplication algorithm that we learned back in grade school just by working through a concrete example. Specifically, let's think of n equal 4, so let's look at two 4-digit numbers. Let's say 5, 6, 7, 8, and 1, 2, 3, 4. Now, as you'll recall, the procedure we learned way back when was just to take each digit of the bottom number and multiply it by each of the top numbers, and then to take each of those n partial products and add them up. So for example, you start with the 4, you multiply it by 8, you get 32, carry the 3, 4 times 7 is 28, add the 3, you get 1, carry the 3, and so on. So that gives you this first partial product, 22, 7, 12. Then you do a shift, so you effectively put a 0 in this final digit, and you repeat that procedure using the next digit, the 3. So again, 3 times 8 is 4, carry the 2, and so on. And you compute the final two partial products using the 2 and the 1. And having computed all of the partial products, you just add them up to get the final product. Now the question I'm interested in is how much work, how many primitive operations did we do to multiply these two numbers? And more generally, how many does it require to multiply two n-digit numbers as a function of n? Well, just to get sort of a ballpark viewpoint for what's going on, we started with two n-digit numbers, and at the end of the day, we basically filled out a grid of size roughly n by n, give or take a little bit. So just in ballpark terms, it seems that multiplying two n-digit numbers required essentially a quadratic number of operations, a small number of operations to fill in each entry in this grid. The grid is n by n, roughly, so that's roughly n squared operations. In a little more detail, we could look at each of the partial products separately. So to compute, say, this first partial product, what did we do? We took the 4, we multiplied it by each of the n digits on top. We also did some carries, so that affects things a little bit. But in the end, we did somewhere between, say, n and 2n primitive operations to compute this first partial product. And that's true, of course, for each of the n partial products. So that's roughly n operations for each of the n partial products. So that's roughly n squared operations to compute all of the partial products. Then we have to add it all up at the end, but that takes just an extra number of constant times n primitive operations to do all of those additions. So summarizing, overall, the number of primitive operations required to multiply two n-digit numbers using this procedure grows quadratically with the length n. So for example, if you double the length of two numbers, you expect to do roughly 4 times as many primitive operations if you use this iterative algorithm for multiplying two numbers. Now, depending on what type of third grader you were, you might well have accepted this procedure as being the unique, or at least the optimal way of multiplying two n-digit numbers together. And if you want to be an expert algorithm designer, that kind of obedient attitude is something you're going to have to learn to discard. Here's a favorite quote of mine. It's from a quite early textbook in the field, The Design and Analysis of Computer Algorithms by A.O. Hopcroft and Ullman. And after highlighting a number of algorithmic design techniques, they conclude by saying, perhaps the most important principle for the good algorithm designer is to refuse to be content. So that's a beautifully accurate quote. I might rephrase it more succinctly by just saying, if you want to be a good algorithm designer, you should adopt the following mantra. You should always be asking, can we do better? This is a particularly appropriate question to ask when you're faced with some kind of naive or obvious algorithm for solving a problem like the third grade algorithm for integer multiplication. But this will come up over and over again. We'll see an algorithm, there'll be an obvious solution, but with some extra algorithmic ingenuity, by detecting subtle structure in the problem, we'll be able to do significantly, qualitatively better than the naive or the obvious solution to the problem. So let's apply this cocky attitude to the problem of multiplying two integers. Let's just suppose as a working hypothesis that there is some procedure which is better than what we learned back in elementary school. What could it possibly look like? So as someone with some programming experience, you know that there are not only iterative algorithms, iterative programs, like the one we just outlined for multiplying two integers, but there are also recursive programs. These are programs that call themselves typically on an input of a similar form, but with smaller size. So as a working hypothesis, let's imagine that there's some interesting recursive approach to multiplying two integers. What must such an algorithm look like? Well, it must somehow fundamentally involve calling itself on smaller problems, that is, on smaller numbers, numbers with fewer digits. So what kind of decomposition on numbers could we use to enable this kind of recursive approach? Well, if you think about it, there's a pretty natural way to break a number with a bunch of digits into a couple numbers with fewer digits. Namely, just take the first half of the digits, the first n over 2 digits, regard that as a number in its own right, and the second half of the digits, regard that as a number in its own right. So perhaps this decomposition will have some use in enabling a recursive attack on how to multiply two integers. So we're going to investigate that in more detail on this next slide. Given x and y, each with n over 2 digits, we're going to represent x as terms of its first half of the digits a and its second half of the digits b. Similarly, we will write y, the second input, in terms of its first half and second half of digits c and d. And in this expansion, a, b, c, and d are all n over 2 digit numbers. I'm assuming for convenience here that n is even. This would extend to the case where n is odd in the natural way, where you break it into n over 2 rounded up and n over 2 rounded down. So in our previous example, where x was 5678 and y was 1234, we would have a being equal to 56, the first two digits of the 4 in x, and then b would be the other two digits, and then similarly for c and d, being a decomposition of y. So now in a just purely mechanical way, we can expand the product of x times y in terms of this representation, in terms of these smaller numbers, a, b, c, and d. So x times y by a representation is just the same thing as 10n over 2 times a plus b times quantity 10 to the n over 2 c plus d. And now if we expand this in group-like terms, we get a 10 to the n times ac plus a 10 to the n over 2 times AD plus BC, so that's combining two terms from the expansion, plus BD. And I'm going to call this expression circled in green star. Now what I want you to think about and make sure you understand is that this expansion that I've circled and called star immediately suggests a recursive algorithm for multiplying two integers. Now it's not clear whether that algorithm is going to be fast or slow, whether this is a good idea or a crackpot idea, but certainly it's a legitimate recursive approach to multiplying two integers. Specifically, the relevant products in star, namely AC, AD, BC, and BD, all involve smaller numbers than what we started with. Those are all n over 2-digit numbers, whereas our original inputs had n digits. So we can legitimately solve those recursively. We can invoke our same algorithm to compute those in a recursive way. Now, once we've invoked our multiplication algorithm recursively 4 times to compute these 4 relevant products, now we can just compute the expression in star in the obvious way. We take AD and BC, we add them together using the just standard first grade iterative addition algorithm. Then we pad both AC and the result of that addition by a bunch of zeros, n over 2 zeros or n zeros as appropriate. Now we have these 3 constituent terms and we just add them up again using the grade school algorithm to compute the overall expression. So to keep this intro lecture brisk, I haven't discussed the base case of this recursive algorithm. As hopefully you all know, recursive algorithms do need base cases. At some point the recursion has got to stop, otherwise your algorithm is never going to terminate. So in multiplication, all you do is if you were passed as input 2 single-digit numbers, you'd multiply them in one primitive operation and return the result. If the numbers have 2 or more digits, you would recurse in the way we've described here. If there's 1 digit, you just compute them and you're done. So who knows whether this recursive algorithm is a good idea or not? It's totally not obvious. You should not even necessarily have any intuition about how this compares to the iterative algorithm you learned back in elementary school. So in lieu of answering that question, although we will answer it several lectures hence, I want to show you a second, still more clever recursive algorithm for integer multiplication. So this goes by the name of Karatsuba Multiplication after the founder, although really sort of the key point is a trick pointed out by the mathematician Gauss in the early 19th century. So to explain this algorithm, let me write once again our expansion in terms of the n over 2-digit numbers. So we have the product x times y, which we wrote as 10 to the n AC plus 10 to the n over 2 AD plus BC plus BD. Now, the previous approach was, in recognition of the 4 products that we see in this expression, we made 4 recursive calls. So here's the trick, and this is really what Gauss figured out over 200 years ago, which is that it seems there are 4 products, but fundamentally in this expression, there's really only 3 quantities that we care about. There's the AC, the coefficient of this first term, there's AD plus BC, the coefficient of this middle term, and there's BD. So we care about AD and BC as quantities individually only in as much as we care about their sum. We really don't care about them individually. So that motivates the question, perhaps we can somehow uncover these 3 different quantities using only 3 recursive calls rather than 4. And in fact, we can, and that's Karatsuba multiplication. So to be more specific, our first 2 recursive calls are shared with the previous recursive algorithm. We go ahead and compute AC and BD recursively. The third step is the clever one, where we recursively compute the product of quantity A plus B with C plus D. Now, expanding, what are we going to get when we recursively compute this product? We're going to get AC plus BD plus AD plus BC. And here is Gauss's trick, or observation, which is that the result of the third recursive call minus each of the first 2, what happens? Well, the AC is going to cancel the AC, the BD is going to cancel the BD, and we will be left with AD plus BC, which is exactly that middle coefficient that we cared about. So we can indeed compute the sum of AD and BC without separately computing each of them, and that's exactly what we wanted. So what is this bias? This gives us a second recursive algorithm for multiplying 2 integers that makes use of fewer recursive calls, only 3 recursive calls rather than 4. And as before, there's a little bit of work to do beyond the recursive calls, but not much. You just have to do some padding by zeros and adding up the results. So there's 2 points I want you to appreciate about all these integer multiplication algorithms. The first point is that the algorithm design space is incredibly rich, much richer than you might have initially had intuition for. Multiplying 2 integers, what else could you do other than the elementary school algorithm? Well, what have we seen? You can do a lot of other things. In particular, the second recursive algorithm looks nothing like what we learned back in grade school. And we'll see this over and over again, that with sufficient ingenuity, sufficient cleverness, you can solve problems in ways much differently and sometimes much better than using the naive, straightforward algorithm. The second takeaway point from this discussion of integer multiplication algorithms is that sometimes you have interesting algorithmic ideas for which it's totally not obvious what kinds of properties or what kind of performance guarantees those algorithms enjoy. So in particular, confronted with these 3 different integer multiplication algorithms, how could we not wonder which of the 3 is the best? Which of these requires the fewest number of primitive operations to multiply 2 integers? In particular, does one of these novel recursive approaches do better than the algorithm we learned back in elementary school? The answer to that question is totally non-obvious, and it requires non-trivial mathematical analysis to answer. In the upcoming lectures, I'll provide you with the tools to not only precisely understand and answer this question, but more generally to predict the running times of an entire genre of divide and conquer algorithms like Karatsuba multiplication. So, stay tuned. Having completed our first analysis of an algorithm, namely an upper bound on the running time of the merge sort algorithm, what I want to do next is take a step back and be explicit about 3 assumptions, 3 biases that we made when we did this analysis of merge sort and interpreted the results. These 3 assumptions we will adopt as guiding principles for how to reason about algorithms and how to define a so-called fast algorithm for the rest of the course. So the first guiding principle is that we used what's often called worst case analysis. By worst case analysis, I simply mean that our upper bound of 6n log n plus 6n applies to the number of lines of executed for every single input array of length n. We made absolutely no assumptions about the input, where it comes from, what it looks like, beyond what the input length n was. Put differently, if hypothetically we had some adversary whose sole purpose in life was to concoct some malevolent input designed to make our algorithm run as slow as possible, the worst this adversary could do is upper bounded by this same number, 6n log n plus 6n. Now, this sort of worst case guarantee popped out so naturally from our analysis of merge sort, you might well be wondering, what else could you do? Well, 2 other methods of analysis, which do have their place, although we won't really discuss them in this course, are quote-unquote average case analysis and also the use of a set of pre-specified benchmarks. By average case analysis, I mean you analyze the average running time of an algorithm under some assumption about the relative frequencies of different inputs. So for example, in the sorting problem, one thing you could do, although it's not what we did here, you could assume that every possible input array is equally likely and then analyze the average running time of an algorithm. By benchmarks, I just mean that one agrees up front about some set, say 10 or 20, benchmark inputs which are thought to represent practical or typical inputs for the algorithm. Now, both average case analysis and benchmarks are useful in certain settings, but for them to make sense, you really have to have domain knowledge about your problem. You need to have some understanding of what inputs are more common than others, what inputs better represent typical inputs than others. By contrast, in worst case analysis, by definition, you're making absolutely no assumptions about where the input comes from. So as a result, worst case analysis is particularly appropriate for general purpose subroutines. Subroutines that you design without having any knowledge of how they will be used or what kind of inputs they will be used on. And happily, another bonus of doing worst case analysis, as we will in this course, it's usually mathematically much more tractable than trying to analyze the average performance of an algorithm under some distribution over inputs, or to understand the detailed behavior of an algorithm on a particular set of benchmark inputs. This mathematical tractability was reflected in our merge sort analysis, where we had no a priori goal of analyzing the worst case per se, but it's naturally what popped out of our reasoning about the algorithm's running time. The second and third guiding principles are closely related. The second one is that in this course, when we analyze algorithms, we won't worry unduly about small constant factors or lower order terms. We saw this philosophy at work very early on in our analysis of merge sort. When we discussed the number of lines of code that the merge subroutine requires, we first upper bounded it by 4m plus 2 for an array of length m, but then we said, let's just think about it as 6m instead. Let's have a simpler, sloppy upper bound and work with that. So that was already an example of not worrying about small changes in the constant factors. Now, the question you should be wondering about is, why do we do this, and can we really get away with it? So let me tell you about the justifications for this guiding principle. So the first motivation is clear, and we used it already in our merge sort analysis, which is it's simply way easier mathematically if we don't have to precisely pin down what the leading constant factors and lower order terms are. The second justification is a little less obvious, but is extremely important. So I claim that given the level at which we're describing and analyzing algorithms in this course, it would be totally inappropriate to obsess unduly about exactly what the constant factors are. Recall our discussion of the merge subroutine. So we wrote that subroutine down in pseudocode, and we gave an analysis of 4m plus 2 on the number of lines of code executed, given an input of length m. We also noted that it was somewhat ambiguous exactly how many lines of code we should count it as, depending on how you count loop increments, and so on. So even there, small constant factors could creep in given the underspecification of the pseudocode. Depending on how that pseudocode gets translated into an actual programming language, like C or Java, you'll see the number of lines of code deviate even further. Not by a lot, but again by small constant factors. When such a program is then compiled down into machine code, you'll see even greater variance depending on the exact processor, the compiler optimizations, the programming implementation, and so on. So to summarize, because we're going to describe algorithms at a level that transcends any particular programming language, it would be inappropriate to specify precise constants. The precise constants will ultimately be determined by more machine-dependent aspects, like who the programmer is, what the compiler is, what the processor is, and so on. And now the third justification is, frankly, we're just going to be able to get away with it. That is, one might be concerned that ignoring things like small constant factors leads us astray, that we wind up deriving results which suggest that an algorithm is fast when it's really slow in practice, or vice versa. But for the problems that we discuss in this course, we'll get extremely accurate predictive power, even though we won't be keeping track of lower order terms and constant factors. When the mathematical analysis we do suggests that an algorithm is fast, indeed it will be. When it suggests that it's not fast, indeed that will be the case. So we lose a little bit of granularity of information, but we don't lose in what we really care about, which is accurate guidance about what algorithms are going to be faster than others. So the first two justifications, I think, are pretty self-evident. This third justification is more of an assertion, but it's one we'll be backing up over and over again as we proceed through this course. Now, don't get me wrong. I'm not saying constant factors aren't important in practice. Obviously, for crucial programs, the constant factors are hugely important. If you're running the sort of crucial loop for, that your startup's survival depends on, by all means, optimize the constant like crazy. The point is just that understanding tiny constant factors in the analysis is an inappropriate level of granularity for the kind of algorithm analysis we're going to be doing in this course. Okay, let's move on to the third and final guiding principle. So the third principle is that we're going to use what's called asymptotic analysis, by which I mean we will focus on the case of large input sizes, the performance of an algorithm as the size n of the input grows large, that is, tends to infinity. Now, this focus on large input sizes was already evident when we interpreted our bound on merge sort. So how did we describe the bound on merge sort? We said, oh, well, it needs a number of operations proportional, a constant factor times, n log n. And we very cavalierly declared that this was better than any algorithm which has quadratic dependence of its running time on the number of operations. So for example, we argued that merge sort is a better, a faster algorithm than something like insertion sort without actually discussing the constant factors at all. So mathematically, we were saying the running time of merge sort, which we know we can represent as the function 6n log base 2 of n plus 6n, is better than any function which has a quadratic dependence on n, even one with a small constant, like let's say 1/2 n squared, which might be roughly the running time of insertion sort. And this is a mathematical statement that is true if and only if n is sufficiently large. Once n grows large, it's certainly true that the expression on the left is smaller than the expression on the right, but for small n, the expression on the right is actually going to be smaller because of the smaller leading term. So in saying that merge sort is superior to insertion sort, the bias is that we're focusing on problems with large n. So the question you should have is that reasonable? Is that a justified assumption to focus on large input sizes? And the answer is certainly yes. So the reason we focus on large input sizes is because frankly, those are the only problems which are at all interesting. If all you need to do is sort 100 numbers, use whatever method you want, and it's going to happen instantaneously on modern computers. You don't need to know, say, the divide and conquer paradigm if all you need to do is sort 100 numbers. So one thing you might be wondering is if, with computers getting faster all the time, according to Moore's law, if really it doesn't even matter to think about algorithmic analysis, if eventually all problem sizes will just be trivially solvable on super fast computers. But in fact, the opposite is true. Moore's law, with computers getting faster, actually says that our computational ambitions will naturally grow. We naturally focus on ever larger problem sizes, and the gulf between an n-squared algorithm and an n log n algorithm will become ever wider. A different way to think about it is in terms of how much bigger a problem size you can solve as computers get faster. If you're using an algorithm with a running time which is proportional to the input size, then if computers get faster by a factor of 4, then you can solve problems which are a factor of 4 larger. Whereas if you're using an algorithm whose running time is proportional to the square of the input size, then if computers get faster by a factor of 4, you can only solve double the problem size. And we'll see even starker examples of this gulf between different algorithmic approaches as time goes on. So to drive this point home, let me show you a couple of graphs. So what we're looking at here is we're looking at a graph of two functions. So the solid function is the upper bound that we proved on merge sort. So this is going to be 6n log base 2 of n plus 6n. And the dotted line is an estimate, a rather generous estimate about the running time of insertion sort, namely 1/2 times n squared. And we see here in the graph exactly the behavior we discussed earlier, which is that for small n, down here, in fact, because 1/2 n squared has a smaller leading constant, it's actually a smaller function. And this is true up to this crossing point of maybe 90 or so. But then beyond n equal 90, the quadratic growth in the n squared term overwhelms the fact that it had a smaller constant, and it starts being bigger than this other function, 6n log n plus 6n. So in the regime below 90, it's predicting that insertion sort will be better, and in the regime above 90, it's predicting that merge sort will be faster. Now here's what's interesting. Let's scale the x-axis. Let's look well beyond this crossing point of 90. Let's just increase it in order of magnitude up to arrays of size 1500. And I want to emphasize these are still very small problem sizes. If all you need to do is sort arrays of size 1500, you really don't need to know divide and conquer or anything else I'll talk about. That's a pretty trivial problem on modern computers. So what we're seeing is that even for very modest problem sizes, here array of size say 1500, the quadratic dependence in the insertion sort bound is more than dwarfing the fact that it had a lower constant factor. So in this large regime, the gulf between the two algorithms is growing, and of course if I increased it another 10x or 100x or 1000x to get to genuinely interesting problem sizes, the gap between these two algorithms would be even bigger. It would be huge. That said, I'm not saying you should be completely ignorant of constant factors when you implement algorithms. It's still good to have a general sense of what these constant factors are. So for example, in highly tuned versions of merge sort, which you'll find in many programming libraries, in fact, because of the difference in constant factors, the algorithm will actually switch from merge sort over to insertion sort once the problem size drops below some particular threshold, say 7 elements or something like that. So for small problem sizes, you use the algorithm with smaller constant factors, namely insertion sort. For larger problem sizes, you use the algorithm with better rate of growth, namely merge sort. So to review, our first guiding principle is that we're going to pursue worst-case analysis. We're going to look to bounds on the performance, on the running time of an algorithm, which make no domain assumptions, which make no assumptions about which input of a given length the algorithm is provided. The second guiding principle is we're not going to focus on constant factors or lower order terms. That would be inappropriate given the level of granularity at which we're describing algorithms. And third is we're going to focus on the rate of growth of algorithms for large problem sizes. Putting these three principles together, we get a mathematical definition of a fast algorithm. Namely, we're going to pursue algorithms whose worst case running time grows slowly as a function of the input size. So let me tell you how you should interpret what I just wrote down in this box. So on the left-hand side is clearly what we want. Okay, we want algorithms which run quickly if we implement them. And on the right-hand side is a proposed mathematical surrogate of a fast algorithm. Right? The left-hand side is not a mathematical definition. The right-hand side is, as will become clear in the next set of lectures. So we're identifying fast algorithms, which those that have good asymptotic runtime, running time which grows slowly with the input size. Now, what would we want from a mathematical definition? We'd want a sweet spot. Okay, on the one hand, we want something we can actually reason about. This is why we zoom out and squint and ignore things like constant factors and lower order terms. We can't keep track of everything, otherwise we'd never be able to analyze stuff. On the other hand, we don't want to throw out the baby with the bathwater. We want to retain predictive power. And this definition turns out for the problems we're going to talk about in this course to be the sweet spot for reasoning about algorithms. Okay, worst case analysis using the asymptotic running time. We'll be able to prove lots of theorems. We'll be able to establish a lot of performance guarantees for fundamental algorithms. But at the same time, we'll have good predictive power. What the theory advocates will in fact be algorithms that are well known to be fast in practice. So the final explanation I owe you is, what do I mean by the running time grows slowly with respect to the input size? Well, the answer depends a little bit on the context, but for almost all of the problems we're going to discuss, the holy grail will be to have what's called a linear time algorithm, an algorithm whose number of instructions grows proportional to the input size. So we won't always be able to achieve linear time, but that's in some sense the best case scenario. Notice linear time is even better than what we achieved with our merge sort algorithm for sorting. Merge sort runs a little bit superlinear. It's n times log n, where n is the input size. If possible, we'd love to be linear time. It's not always going to be possible, but that is what we will aspire toward for most of the problems we'll discuss in this course. Looking ahead, the next series of videos is going to have two goals. First of all, on the analysis side, I'll describe formally what I mean by asymptotic running time. I'll introduce big O notation and its variants, explain its mathematical definitions, and give a number of examples. On the design side, we'll get more experience applying the divide and conquer paradigm to further problems. See you then. In the following series of videos, we'll give a formal treatment of asymptotic notation, in particular big O notation, as well as work through a number of examples. Big O notation concerns functions defined on the positive integers. We'll call it T of n. We'll pretty much always have the same semantics for T of n. We're going to be concerned about the worst case running time of an algorithm as a function of the input size n. So the question I want to answer for you in the rest of this video is, what does it mean when we say a function T of n is big O of f of n? Where here f of n is some basic function like, for example, n log n. So I'll give you a number of answers, a number of ways to think about what big O notation really means. But for starters, let's begin with an English definition. What does it mean for a function to be big O of f of n? It means eventually, for all sufficiently large values of n, it's bounded above by a constant multiple of f of n. Let's think about it in a couple other ways. So next I'm going to translate this English definition into a picture, and then I'll translate it into formal mathematics. So pictorially, you could imagine that perhaps we have T of n denoted by this blue function here, and perhaps f of n is denoted by this green function here, which lies below T of n. But when we double f of n, we get a function that eventually crosses T of n and forevermore is larger than it. So in this event, we would say that T of n indeed is big O of f of n. The reason being that for all sufficiently large n, once we go far enough outright on this graph, indeed a constant multiple times f of n, twice f of n, is an upper bound on T of n. So finally, let me give you an actual mathematical definition that you could use to do formal proofs. So how do we say in mathematics that eventually it should be bounded above by a constant multiple of f of n? We say that there exist two constants, which I'll call c and n naught, so that T of n is no more than c times f of n for all n that exceed or equal n naught. So the role of these two constants is to quantify what we mean by a constant multiple and what we mean by sufficiently large in the English definition. C obviously quantifies the constant multiple of f of n, and n naught is quantifying sufficiently large. That's the threshold beyond which we insist that c times f of n is an upper bound on T of n. So going back to the picture, what are c and n naught? Well, c of course is just going to be 2. And n naught is the crossing point. So if we look at where 2f of n and t of n cross, and then we drop the asymptote, this would be the relevant value of n naught in this picture. So that's the formal definition. The way to prove that something's big O of f of n, you exhibit these two constants, c and n naught, and it better be the case that for all n at least n naught, c times f of n upper bounds t of n. One way to think about it, if you're trying to establish that something is big O of some function, it's like you're playing a game against an opponent. And you want to prove that this inequality here holds, and your opponent wants to show that it doesn't hold for sufficiently large n. You have to go first. Your job is to pick a strategy in the form of a constant c and a constant n naught, and your opponent is then allowed to pick any number n larger than n naughts. So the function is big O of f of n if and only if you have a winning strategy in this game. If you can upfront commit to constants c and n naught so that no matter how big an n your opponent picks, this inequality holds. If you have no winning strategy, then it's not big O of f of n. No matter what c and n naught you choose, your opponent can always flip this inequality by choosing a suitable large value of n. I want to emphasize one last thing, which is that these constants, what do I mean by a constant? I mean they are independent of n. So when you apply this definition and you choose your constant c and n naught, it better be that n does not appear anywhere. So c should just be something like 1,000 or 1,000,000, some constant independent of n. So those are a bunch of ways to think about big O notation. In English, you want to have a bound above for sufficiently large numbers n. I've shown you how to translate that into mathematics. I give you a pictorial representation and also a sort of game theoretic way to think about it. Now let's move on to a video that explores a number of examples. Okay, so this video is not about any particular graph problem, not about any particular graph algorithm, just sort of the preliminaries we need to discuss algorithms on graphs. How do we measure their size? How do we represent them? And so on. Remember what a graph is. It really has two ingredients. First of all, there's the set of objects we're talking about. Those might be called vertices. Synonymously, we might call them nodes. We represent pairwise relationships using edges. These can be either undirected, in which case they're ordered pairs, or an edge can be directed from one to another. In that case, they're ordered pairs and we have a directed graph. Now, when we talk about, say, the size of a graph or the running time of an algorithm that operates on a graph, we need to think about what we mean by input size. In particular, for a graph, there's really two different parameters that control how big it is, unlike an array. For arrays, we just had a single number, the length. For graphs, we have the number of vertices and we have the number of edges. Usually we'll use the notation n for the number of vertices, m for the number of edges. So the next quiz asks you to think about how the number of edges m can depend on the number of vertices n. So in particular, I want you to think for this quiz about an undirected graph. It has n vertices. There's no parallel edges. Okay, so for a given pair of vertices, there's either 0 or 1 edge between them. Moreover, let's assume that the graph is unconnected. Okay, so I don't want you to think about graphs that have 0 edges. Now, I haven't defined what a graph is, what it means for a graph to be connected formally yet, but I hope you get the idea. It means it's in one piece. You can't break it into two parts that have no edges crossing between them. So for such a graph, no parallel edges in one piece, n vertices, think about what is the minimum number of edges it could possibly have, and what is the maximum number of edges as a function of n that it could possibly have. All right, so the correct option is the first one. The fewest number of edges that a connected undirected graph can have is n minus 1, and the maximum number of edges that an undirected graph with no parallel edges can have is n times n minus 1 over 2, better known as n choose 2. So why does it need at least n minus 1 edges if it's going to be in one piece? Well, think about adding the edges one at a time, okay, each of the edges of the graph. Now, initially, you just have a graph with 0 edges. The graph has n different pieces, n isolated vertices, and there's no edges at all. Now, each time you add one edge, what you do is you take two of the existing pieces, at best, and fuse them into one. So the maximum decrease you can have in the number of different pieces of a graph is it can decrease by 1 each time you add an edge. So from a starting point of n different pieces, you got to get down to one piece. So that requires the addition of n minus 1 edges. You can also convince yourself of this by drawing a few pictures and noticing that trees achieve this bound exactly. So for example, here is a 4-vertex tree that has 3 edges. So this is a case where m is indeed n minus 1. Now, for the upper bound, why can't you have more than n choose 2? Well, it's clear that the largest number of edges you can have is for the complete graph, where every single pair of edges has one between them. Again, there's no parallel arcs, and edges are unordered, so there's at most n choose 2 possibilities of where to put an edge. So again, if n equals 4, here would be an example with the maximum possible number, 6 edges. So now that I've got you thinking about how the number of edges can vary with the number of vertices, let me talk about the distinction between sparse and dense graphs. It's important to distinguish between these two concepts because some data structures and algorithms are better suited for sparse graphs, other data structures and algorithms are better suited for dense graphs. So to make this precise, let me just put down this very common notation. N is the number of vertices of the graph under discussion. M is the number of edges. This is quite standard notation. please get used to it and use it yourself. If you reverse these, you will confuse a lot of people who have familiarity with graph algorithms and data structures. Now, one thing we learned from the previous quiz is the following. So in most applications, not all applications, but most applications, m is at least linear in n. Remember in the quiz you saw it was at least n minus 1 if you wanted the graph to be connected. And it's also big O of n squared. This is under the assumption that there's no parallel arcs. Now, there are cases where we want to allow parallel arcs. In fact, we'll do that in the contraction algorithm for the min-cut problem. There are cases where we want to allow the number of edges to drop so low that the graph breaks into multiple pieces. For example, when we talk about connected components. But more often than not, we're thinking about a connected graph with no parallel edges, and then we can pin down the number of edges m to be somewhere between linear in the number of nodes, linear in n, and quadratic in n. Now, I'm not going to give you a super formal definition of what a sparse or a dense graph is, and people are a little loose with this terminology in practice. But basically, sparse means you're closer to the lower bound, closer to linear. Dense means you're closer to the upper bound, closer to quadratic. Now, I know this leaves ambiguity when the number of edges is something, like n to the 3/2. Usually in that case, you'd think of it as a dense graph. So usually anything which is more than n times some logarithmic terms, you'd think about as a dense graph. But again, people are a little bit sloppy with this when they talk about graphs. Next, I want to discuss two representations of graphs, and we're mostly going to be using the second one in this course. But this first one, the adjacency matrix, I do want to mention just briefly, just on this slide. This is a supernatural idea where you represent the edges in a graph using a matrix. Let me describe it first for undirected graphs. So the matrix is going to be denoted by capital A, and it's a square n by n matrix where n is the number of vertices of the graph. And the semantics are the ijth entry of the matrix is 1 if and only if there's an edge between the vertices I and j in the graph. I'm assuming here that the vertices are named 1, 2, 3, 4, etc. all the way up to n. It's easy to add bells and whistles to the adjacency matrix to accommodate parallel edges, to accommodate edge weights, which is accommodate directed arcs, directed edges. If you wanted to have parallel arcs, you could just have aij denote the number of arcs that are between I and j. If edges have different weights, you can just have aij be the weight of the ij edge. And for the directed graph, you can use +1s and -1s. So if the arc is directed from I to j, you'd set aij to be +1. If the arc is directed from j to I, you'd set aij to -1. There are many metrics by which you can evaluate a data structure or a representation. Two important ones I want to discuss here are, first of all, the number of resources it requires, and in this context, that's the amount of space that the data structure needs. The second thing is, what are the operations that the data structure supports? So let's just begin with the space requirements. What are they for the adjacency matrix? All right, so the answer, at least with the sort of straightforward way of storing a matrix, is n squared. And this is independent of the number of edges. So you could try to beat this down for sparse graphs using sparse matrix tricks. But for the basic idea of just actually representing an n by n matrix, you got n squared entries. You got to store 1 bit in each, whether the edge is there or not. So that's going to give you n squared space. The constants are, of course, very small because you're just storing 1 bit per entry. But nonetheless, this is quadratic in the number of vertices. Now that's going to be fine if you have a dense graph. If the number of edges is as high as n squared, then you're not really wasting anything in this representation. But in a sparse graph, if m is much closer to linear, then this is a super wasteful representation. Let's talk about the adjacency list representation. This is the dominant one we'll be using in this class. This has several ingredients. So first, you keep track of both the vertices and the edges as independent entities. So you're going to have an array or a list of each. And then we want these two arrays to cross-reference each other in the obvious way. So given a vertex, you want to know which edges it's involved in. Given an edge, you want to know what its endpoints are. So let's say first, most simply, each edge is going to have 2 pointers, one for each of the 2 endpoints. In a directed graph, of course, it would keep track of which one is the head and which one is the tail. Now each vertex is going to point to all of the edges of which it's a member. Now in an undirected graph, it's clear what I mean by that. In a directed graph, you could do it in a couple ways. Generally, you'd have a vertex keep track of all of the edges for which it is the tail. That is, all of the edges which you can follow one hop out from the edge. If you wanted to, you could also have a second array at more expensive storage where the vertex also keeps track of the edges pointing to it, the edges for which it's the head. So let me ask you the same question I did with an adjacency matrix. What is the space required of an adjacency list as a function of the number of edges m and the number of vertices n of the graph? So the correct answer to this question is the third option, theta of m plus n, which we're going to think of as linear space in the size of the graph. So this quiz is a little tricky, so to explain the answer, let me return to the slide with the ingredients of adjacency lists, and let's compute the space for each of these four ingredients separately. Most of them are straightforward. For example, consider the first ingredient. This is just an array or a list of the n vertices, and we just need constant space per vertex to keep track of its existence. So this is going to be theta of n, linear in the number of vertices. Similarly, for the m edges, we just need linear space in the number of edges to remember their existence. So that's going to be theta of m. Now, each edge has to keep track of both of its endpoints. So that's 2 pointers, but 2 is a constant. For each of the m edges, we have a constant space to keep track of endpoints. So that's going to give us another theta of m, constant per edge. Now, this fourth case, you might be feeling kind of nervous, because a vertex, in principle, could have edges involving all n-1 other vertices. So the number of pointers at a single vertex could be theta of n. Also, you could have, you do have n vertices, so that could be theta of n squared. And certainly in something like a complete graph, you really would have that much. But the point is, in sparse graphs, n squared is way overkill to the space needed by this fourth set of pointers. Actually, if you think about it, for each pointer in the fourth category, a vertex pointing to a given edge, there is a pointer in the third category pointing in the opposite direction, from that edge back to that vertex. So there's actually a one-to-one correspondence between pointers in the third category and pointers in the fourth category. Since the third category has space theta of m, so does all of the pointers in the fourth category. So adding up over the 4 ingredients, we have 1 theta of n and 3 theta of m's, so that's going to give us overall a theta of m plus n. If you prefer, another way you could think about this would be theta of the max of m and n. These are the same up to a constant factor. Now, as we discussed in a previous slide, often m is going to be bigger than n, but I wanted to do a generic analysis here, which applies even if the graph is not connected, even if it is in multiple pieces. So the space of the adjacency list is within a constant factor, the same as the number of ingredients in the graph, the number of vertices plus the number of edges. So in that sense, that's exactly what you want. Now, being confronted with these 2 graph representations that I've shown you, I'm sure you're asking, well, which one should you remember? Which one should you use? And the answer, as it so often is it depends. It depends on 2 things. It depends on the density of your graph. It depends on how m compares to n, and it also depends on what kind of operations that you want to support. Now, given what we're covering in this class, and also the motivating applications I have in mind, I can give you basically a clean answer to this question for the purposes of these 5 weeks, which is we're going to be focusing on adjacency lists. The reason we're going to focus on adjacency lists in this class is for both of these reasons, both because of the operations we want and both because of the graph density and motivating applications. So first of all, most of the graph primitives, not all, but most will be dealing with graph search, and adjacency lists are perfect for doing graph search. You get to a node, you follow an outgoing arc, you go to another node, you follow an outgoing arc, and so on. And so adjacency lists are the perfect thing to do graph search. Adjacency matrices are definitely good for certain kinds of graph operations, but they're not things we're really going to be covering in this class. So that's reason 1. Reason 2 is a lot of the motivations for graph primitives these days comes from massive networks. I mentioned earlier how the web can be fruitfully thought of as a directed graph, where the vertices are individual web pages and directed arcs correspond to hyperlinks, going from the page with the hyperlink pointing to the one that the hyperlink goes to. Now, it's hard to get an exact measurement of the web graph, but a conservative lower bound on the number of vertices is something like 10 billion. So that's 10 to the 10. Now, that's pushing the limits of what computers can do, but it's within the limits. So if you work hard, you can actually operate on graphs with 10 to the 10 nodes. Now, suppose we use an adjacency matrix representation. So if n is 10 to the 10, then n squared is going to be like 10 to the 20. And now we're getting close to the estimated number of atoms in the known universe. So that is clearly not feasible now, and is not going to be feasible ever. So the adjacency matrix representation is totally out for huge sparse graphs like the web graph. Adjacency lists, well, the degree on average in the web is thought to be something like 10. So the number of edges is only going to be something like 10 to the 11, and then the adjacency list representation will be proportional to that. And again, that's really pushing what we can do with current technology, but it is within the limits. So using that representation, we can do non-trivial computations on graphs, even at the scale of the web graph. So let's talk about the absolutely fundamental problem of searching a graph and the very related problem of finding paths through graphs. So why would one be interested in searching a graph or figuring out if there's a path from point A to point B? Well, there's many, many reasons. I'm going to give you a highly non-exhaustive list on this slide. So let me begin with a very sort of obvious and literal example, which is if you have a physical network. Then often you want to make sure that the network is fully connected in the sense that you can get from any starting point to any other point. So for example, think back to the phone network. It would have been a disaster if callers from California could only reach callers in Nevada, but not their family members in Utah. So obviously a minimal condition for functionality of something like a phone network is that you can get from any one place to any other place. Similarly for road networks within a given country, and so on. It can also be fun to think about other non-physical networks and ask if they're connected. So one network that's fun to play around with is the movie network. So this is the graph where the nodes correspond to actors and actresses, and you have an edge between two nodes if they played a role in a common movie. So this is going to be an undirected graph, where the edges correspond to not necessarily co-starring, but both the actors appearing at least at some point in the same movie. So versions of this movie network you should be able to find publicly available on the web, and there's lots of fun questions you can ask about the movie network, like for example, what's the minimum number of hops, where a hop here again is a movie that two people both played a role in, the minimum number of hops or edges you can get from one actor to another actor. So perhaps the most famous statistic that's been thought about with the movie network is the Bacon number. So this refers to the fairly ubiquitous actor Kevin Bacon, and the question, the Bacon number of an actor is defined as the minimum number of hops you need in this movie graph to get to Kevin Bacon. So for example, you could ask about John Hamm, also known as Don Draper from Mad Men, and you could ask how many edges do you need on a path through the movie graph to get to Kevin Bacon, and it turns out that the answer is two edges. You need one intermediate point, namely Colin Firth, and that's because Colin Firth and Kevin Bacon both starred in the Adam Agoyan movie Where the Truth Lies, and John Hamm and Colin Firth were both in the movie A Single Man. So that would give John Hamm a Bacon number of 2. So these are the kind of questions you can ask about connectivity, not just in physical networks like telephone and telecommunication networks, but also logical networks about pairwise relationships between objects more generally. So the Bacon number is fundamentally not just about any path, but actually shortest paths, the minimum number of edges you need to traverse to get from one actor to Kevin Bacon. And shortest paths also have a very practical use that you might use yourself in driving directions. So when you use a website or a phone app and you ask for the best way to get from where you are now to, say, some restaurant where you're going to have dinner, obviously you're trying to find some kind of path through a network, through a graph, and indeed often you want the shortest path, perhaps in mileage or perhaps in anticipated travel time. Now I realize that when you're thinking about paths and graphs, it's natural to focus on sort of very literal paths and quite literal physical networks. Things like routes through a road network or paths through the internet and so on. But you should really think more abstractly as a path as just a sequence of decisions, taking you from some initial state to some final state. And it's this abstract mentality which is what makes graph search so ubiquitous and feels like artificial intelligence, where you want to formulate a plan of how to get from an initial state to some goal state. So to give a simple recreational example, you could imagine just trying to understand how to compute automatically a way to fill in a Sudoku puzzle so that you solve the puzzle correctly. So you might ask, what is the graph that we're talking about when we want to solve a Sudoku puzzle? Well, this is going to be a directed graph, where here the nodes correspond to partially completed puzzles. So for example, at one node of this extremely large graph, perhaps 40 out of the 81 cells are filled in with some kind of number. And now, again, remember a path is supposed to correspond to a sequence of decisions. So what are the actions that you take in solving Sudoku? Well, you fill in a number into a square. So an edge, which here is going to be directed, is going to move you from one partially completed puzzle to another, where one previously empty square gets filled in with one number. And of course, then the path that you're interested in computing, or what you're searching for when you search this graph, you begin with the initial state of the Sudoku puzzle, and you want to reach some goal state where the Sudoku puzzle is completely filled in without any violations of the rules of Sudoku. And of course, it's easy to imagine millions of other situations where you want to formulate some kind of plan like this. Like, for example, if you have a robotic hand and you just want to grasp some object, you need to think about exactly how to approach the object with this robotic hand so that you can grab it without, for example, first knocking it over. And you can think of millions of other examples. Another thing which turns out to be closely related to graph search, as we'll see, and has many applications in its own right, is that of computing connectivity information about graphs. So in particular, the connected components. So this, especially for undirected graphs, corresponds to the pieces of a graph. We'll talk about these topics in their own right, and I'll give you applications for them later. So for undirected graphs, I'll briefly mention an easy clustering heuristic you can derive out of computing connected components. For directed graphs, where the very definition of computing components is a bit more subtle, I'll show you applications to understanding the structure of the web. So these are a few of the reasons why it's important for you to understand how to efficiently search graphs. It's a fundamental and widely applicable graph primitive. And I'm happy to report that in this section of the course, pretty much any questions we want to answer about graph search, computing connected components, and so on, there's going to be really fast algorithms to do it. So this will be a part of the course where there's lots of what I call for-free primitives, processing steps, subroutines you can run without even thinking about it. All of these algorithms we're going to discuss in the next several lectures are going to run in linear time, and they're going to have quite reasonable constants. So they're really barely slower than reading the input. So if you have a graph and you're trying to reason about it, you're trying to make sense about it, you should, in some sense, feel free to apply any of these subroutines we're going to discuss to try and glean some more information about what they look like, how you might use the network data. There's a lot of different approaches to systematically searching a graph. So there's many methods. In this class, we're going to focus on two very important ones, namely breadth-first search and depth-first search. But all of the graph search methods share some things in common. So on this slide, let me just tell you the high-order bits of really any graph search algorithm. So graph search subroutines generally are passed as input a starting vertex from which the search originates. So that's often called a source vertex. And your goal then is to find everything findable from this search vertex. And obviously you're not going to find anything that you can't find, that's not findable. What do I mean by findable? I mean there's a path from the starting point to this other node. So for any other node to which you can get along a path from the starting point, you should discover it. So for example, if you're given an undirected graph that has 3 different pieces, like this one I'm drawing on the right, and perhaps S is this leftmost node here, then the findable vertices starting from S, i.e. the ones to which you can reach from a path to S, is clearly precisely these 4 vertices. So you would want graph search to automatically discover and efficiently discover these 4 vertices if you started at S. You could also think about a directed version of the exact same graph, where I'm going to direct the vertices like so. So now the definition of the findable nodes is a little bit different. We're only expecting to follow arcs forward along the forward direction. So we should only expect at best to find all of the nodes that you can reach by following a succession of forward arcs. That is, any node that there's a path to from S. So in this case, these 3 nodes would be the ones we'd be hoping to find. This blue node to the right, we would no longer expect to find because the only way to get there from S is by going backward along arcs. And that's not what we're going to be thinking about in our graph searches. So we want to find everything findable, i.e. that we can get to along paths, but we want to do it efficiently. And efficiently means we don't explore anything twice. Right? So the graph has m arcs, m edges, and n nodes or n vertices, and really we want to just look at each piece of the graph only once or a small constant number of times. So we're looking for running time, which is linear in the size of the graph, that is big O of m plus n. Now, when we were talking about representing graphs, I said that in many applications it's natural to focus on connected graphs, in which case M is going to dominate N. You're going to have at least as many edges as nodes, essentially. But connectivity is the classic case where you might have the number of edges being much smaller than the number of nodes. There might be many pieces, and the whole point of what you're trying to do is discover them. So for this sequence of lectures where we talk about graph search and connectivity, we will usually write M plus N. We'll think that either one could be bigger or smaller than the other. So let me now give you a generic approach to graph search. So it's going to be underspecified. There'll be many different ways to instantiate it. Two particular instantiations will get us breadth first search and depth first search. But here's just a general systematic method for finding everything findable without exploring anything more than once. So motivated by the second goal, the fact that we don't want to explore anything twice, with each node, with each vertex, we're going to remember whether or not we've explored it before. So we just need one Boolean per node, and we'll initialize it by having everything unexplored, except S, our starting point, will have it start off as explored. And it's useful to think of the nodes thus far as being in some sense territory conquered by the algorithm. And then there's going to be a frontier in between the conquered and unconquered territory. And the goal of the generic algorithm is at each step we supplement the conquered territory by one new node, assuming that there is one adjacent to the territory we've already conquered. So, for example, in this top example with the undirected network, initially the only thing we've explored is the starting point S. So that's sort of our home base. It's all that we have conquered so far. And then in our main while loop, which we iterate as many times as we can until we don't have any edges meeting the following criterion, we look for an edge with one endpoint that we've already explored, one endpoint inside the conquered territory, and then the other endpoint outside. So this is how we can, in one hop, supplement the number of nodes we've seen by one new one. If we can't find such an edge, then this is where the search stops. If we can find such an edge, well, then we suck V into the conquered territory. We think of it being explored. And we return to the main while loop. So for example, in this example on the right, we start with the only explored node being S. Now, there's actually two edges that cross the frontier, in the sense one of the endpoints is explored, namely one of the endpoints is S, and the other one is some other vertex, right? There's these two edges to the left, two vertices adjacent to S. So in this algorithm, we pick either one. It's underspecified which one we pick, but maybe we pick the top one, and so then all of a sudden this second top vertex is now also explored. So the conquered territory is the union of them. And so now we have a new frontier. So now again we have two edges that cross from the explored nodes to the unexplored nodes. These are the edges that are in some sense going from northwest to southeast. Again, we pick one of them. It's not clear how. The algorithm doesn't tell us. We just pick any of them. So maybe, for example, we pick this rightmost edge crossing the frontier. Now the rightmost edge of these rightmost vertex of these four is explored, so our conquered territory is the top three vertices. And now again we have two edges crossing the frontier, the two edges that are incident to the bottom node. We pick one of them, not clear which one, maybe this one. And now the bottom node is also explored, and now there are no edges crossing the frontier. So there are no edges who on the one hand have one endpoint being explored and the other endpoint being unexplored. So these will be the four vertices, as one would hope, that the search will explore started from S. More generally, the claim is that this generic graph search algorithm does what we wanted. It finds everything findable from the starting point, and moreover, it doesn't explore anything twice. I think it's fairly clear that it doesn't explore anything twice, right? As soon as you look at a node for the first time, you suck it into the conquered territory, never to look at it again. Similarly, as soon as you look at an edge, you suck it in. But when we explore breadth and depth first search, we'll be more precise about the running time and exactly what I mean by you don't explore something twice. So at this level of generality, I just want to focus on the first point, that any way you instantiate this search algorithm, it's going to find everything findable. So what do I really mean by that? The formal claim is that at the termination of this algorithm, the nodes that we've marked explored are precisely the ones that can be reached via a path from S. That's the sense in which the algorithm explores everything that could potentially be findable from the starting point S. And one thing I want to mention is that this claim and the proof I'm going to give of it holds whether or not G is an undirected graph or a directed graph. In fact, almost all of the things that I'm going to say about graph search, and in particular about breadth first search and depth first search, work in essentially the same way, either in undirected graphs or directed graphs. The obvious difference being in an undirected graph, you can traverse an edge in either direction. In a directed graph, we're only supposed to traverse it in the forward direction, from the tail to the head. The one big difference between undirected and directed graphs is when we do connectivity computations, and I'll remind you when we get to that point which one we're talking about. Okay, but for the most part, when we just talk about basic graph search, it works essentially the same way, whether it's undirected or directed. So keep that in mind. All right, so why is this true? Why are the nodes that get explored precisely the nodes for which there's a path to them from S? Well, one direction is easy, which is you can't find anything which is not findable. That is, if you wind up exploring a node, the only reason that can happen is because you traversed a sequence of edges that got you there. And that sequence of edges obviously defines a path from S to V. If you really want to be pedantic about the forward direction, that explored nodes have to have paths from S, then you can just do an easy induction. And I'll leave this for you to check if you want in the privacy of your own home. So the important direction of this claim is really the opposite. Why is it that no matter how we instantiate this generic graph search procedure, it's impossible for us to miss anything? That's the crucial point. We don't miss anything that we could in principle find via a path. Well, we're going to proceed by contradiction. So what does that mean? We're going to assume that the statement that we want to prove is true is not true, which means that it's possible that G has a path from S to V, and yet somehow our algorithm misses it, doesn't mark it as explored, right? That's the thing we're really hoping doesn't happen. So let's suppose it does happen and then derive a contradiction. So suppose G does have a path from S to some vertex V, call the path P. I'm going to draw the picture for an undirected graph, but the situation would be same in the directed case. So there's a bunch of hops, there's a bunch of edges, and then eventually this path ends at V. Now, the bad situation, the situation from which we want to derive a contradiction, is that V is unexplored at the end of this algorithm. So let's take stock of what we know. S, for sure, is explored, right? We initialize the search procedure so that S is marked as explored. V, by hypothesis, in this proof by contradiction, is unexplored. So S is explored, V is unexplored. So now imagine we, just in our heads, as a thought experiment, we traverse this path P. We start at S and we know it's explored. We go to the next vertex. It may or may not have been explored. We're not sure. We go to the third vertex again. Who knows? Might be explored, might be unexplored, and so on. But by the time we get to V, we know it's unexplored. So we start at S, it's been explored. We get to V, it's been unexplored. So at some point, there's some hop along this path P from which we move from an explored vertex to an unexplored vertex. There has to be a switch at some point, because at the end of the day, at the end of the path, we're at an unexplored node. So consider the first edge, and there must be one, that we switch from being at an explored node to being at an unexplored node. So I'm going to call the endpoints of this purported edge U and W, where U is the explored one and W is the unexplored one. Now, for all we know, U could be exactly the same as S. That's a possibility. Or for all we know, W could be the same as V. That's also a possibility. In the picture, I'll draw it as if this edge UX was somewhere in the middle of this path. But again, it may be at one of the ends. That's totally fine. But now in this case, there's something I need you to explain to me. How is it possible that, on the one hand, our algorithm terminated, and on the other hand, there's this edge, U comma X, where U has been explored and X has not been explored? That, my friends, is impossible. Our generic search algorithm does not give up. It does not terminate unless there are no edges where the one endpoint is explored and the other endpoint is unexplored. As long as there's such an edge, it's going to suck in that unexplored vertex into the conquered territory. It's going to keep going. So the upshot is there's no way that our algorithm terminated with this picture, with there being an edge UX, U explored, X unexplored. So that's the contradiction. This contradicts the fact that our algorithm terminated with V unexplored. So that is a general approach to graph search. So that, I hope, gives you the flavor of how this is going to work. But now there's two particular instantiations of this generic method that are really important and have their own suites of applications. So we're going to focus on breadth-first search and depth-first search. We'll cover them in detail in the next couple of videos. I want to give you the highlights to conclude this video. Now let me just make sure it's clear where the ambiguity in our generic method is, why we can have different instantiations of it that potentially have different properties and different applications. The question is, at a given iteration of this while loop, what do you got? You got your nodes that you've already explored, so that includes S plus probably some other stuff. And then you've got your nodes that are unexplored. And then you have your crossing edges, right? So they're edges with one point in each side. And for an undirected graph, there's no orientation to worry about. These crossing edges just have one endpoint on the explored side, one endpoint on the unexplored side. In the directed case, you focus on edges where the tail of the edge is on the explored side and the head of the edge is on the unexplored side. So they go from the explored side to the unexplored side. And the question is, in general, in an iteration of this while loop, there's going to be many such crossing edges. There are many different unexplored nodes we could go to next. And different strategies for picking the unexplored node to explore next leads us to different graph search algorithms with different properties. So the first specific search strategy we're going to study is breadth-first search, colloquially known as BFS. So let me tell you sort of the high-level idea and applications of breadth-first search. So the goal is going to be to explore the nodes in what I call layers. So the starting point S will be in its own layer, layer 0. The neighbors of S will constitute layer 1. And then layer 2 will be the nodes that are neighbors of layer 1, but that are not already in layer 0 or layer 1, and so on. So layer I plus 1 is the stuff next to layer I that you haven't already seen yet. You can think of this as a fairly cautious and tentative exploration of the graph. And it's going to turn out that there's a close correspondence between these layers and shortest path distances. So if you want to know the minimum number of hops, the minimum number of edges you need in a path to get from point A to point B in a graph, the way we wanted to know the fewest number of edges in the movie graph necessary to connect John Hamm to Kevin Bacon, that corresponds directly to these layers. So if a node is in layer I, then you need I edges to get from S to I in the graph. Once we discuss breadth-first search, we'll also discuss how to compute the connected components, or the different pieces, of an undirected graph. Turns out this isn't that special to breadth-first search. You can use any number of graph search strategies to compute connected components in undirected graphs, but I'll show you how to do it using a simple looped version of breadth-first search. And we'll be able to do this stuff in the linear time that we want, the very ambitious goal of getting linear time. To get the linear time implementation, you do want to use the right data structure, but it's a super simple data structure, something probably you've seen in the past, namely a queue, so something that's first in, first out. So the second search strategy that's super important to know is depth-first search, also known as DFS to its friends. Depth-first search has a rather different feel than breadth-first search. It's a much more aggressive search where you immediately try and plunge as deeply as you can. It's very much in the spirit of how you might explore a maze, where you go as deeply as you can, only backtracking when absolutely necessary. Depth-first search will also have its own set of applications. It's not, for example, very useful for computing shortest path information, but especially in directed graphs, it's going to do some remarkable things for us. So in a directed acyclic graph, so a directed graph with no directed cycles, it will give us what's called the topological ordering. So it'll sequence the nodes in a linear ordering from the first to the last so that all of the arcs of the directed graph go forward. So this is useful, for example, if you have a number of tasks that have to get completed with certain precedence constraints. Like, for example, you have to take all of the classes in your undergraduate major and there are certain prerequisites. Topological ordering will give you a way in which to do it, respecting all of the prerequisites. And finally, where for undirected graphs, it doesn't really matter whether you use BFS or DFS to compute connected components. In directed graphs, where even defining connected components is a little tricky, it turns out depth-first search is exactly what you want. That's what you're going to get a linear time implementation for computing the right notion of connected components in the directed graph case. Time-wise, both of these are superb strategies for exploring a graph. They're both linear time with very good constants. So depth-first search again, we're going to get O of m plus n time in a graph with m edges and n vertices. You do want to use a different data structure reflecting the different search strategy. So here, because you're exploring aggressively, as soon as you get to a node, you immediately start exploring its neighbors. You want a last in, first out data structure, also known as a stack. Depth-first search also admits a very elegant recursive formulation, and in that formulation you don't even need to maintain a stack data structure explicitly. The stack is implicitly taken care of in the recursion. So that concludes this overview of graph search, both what it is, what our goals are, what kind of applications they have, and two of the most common strategies. The next couple of videos are going to explore these search strategies as well as a couple of these applications in greater depth. We've arrived at another one of computer science's greatest hits, namely Dijkstra's shortest path algorithm. So let me tell you about the problem. It's a problem called single source shortest paths. Basically what we want to do is compute something like driving directions. So we're given as input a graph. In this lecture I'm going to work with directed graphs, although the same algorithm would work for undirected graphs with cosmetic changes. As usual, we'll use m to denote the number of edges and n to denote the number of vertices. The input also includes two extra ingredients. First of all, for each edge E, we're given as input a non-negative length, which I'll denote by L sub E. In the context of a driving directions application, L sub E could denote the mileage, how long this particular road is, or it could also denote the expected travel time along the edge. The second ingredient is a vertex from which we are looking for paths. This is exactly the same as we had in breadth first search and depth first search. We have an originating vertex, which we'll call here the source. Our responsibility then is to, given this input, compute for every other vertex V in this network the length of a shortest path from the source vertex S to that destination vertex V. And so just to be clear, what is the length of a path that has, say, 3 edges in it? Well, it's just the sum of the length of the first edge in the path plus the length of the second edge in the path plus the length of the third edge in the path. So if you had a path like this with 3 edges and lengths 1, 2, and 3, then the length of the path would just be 6. And then we define the shortest SV path in the natural way. So amongst all of the paths directed from S to V, each one has its own respective path length, and then the minimum over all SV paths is the shortest path distance in the graph G. So I'm going to make 2 assumptions for these lectures. One is really just for convenience. The other is really important. The other assumption without which Dijkstra's algorithm is not correct, as we'll see. So for convenience, we'll assume that there is a directed path from S to every other vertex V in the graph. Otherwise, the shortest path distance is something we define to be plus infinity. And the reason this is not a big assumption is if you think about it, you could detect which vertices are not reachable from S just in a pre-processing step using, say, breadth first or depth first search. And then you could delete the irrelevant part of the graph and run Dijkstra's algorithm as we'll describe it on what remains. Alternatively, Dijkstra's algorithm will quite naturally figure out which vertices there are paths to from S and which ones there are not. So this won't really come up. So to keep it simple, just think about we have an input graph where you can get from S to V for every different vertex V, and the challenge then is amongst all the ways to get from S to V, what is the shortest way to do it? So the second assumption already appears in the problem statement, but I want to reiterate it just so it's really clear. When we analyze Dijkstra's algorithm, we always focus on graphs where every length is non-negative. No negative edge lengths are allowed, and we'll see why a little bit later in the video. Now, in the context of a driving directions application, it's natural to ask the question, why would you ever care about negative edge lengths? Until we invent a time machine, it doesn't seem like negative edge lengths are going to be relevant when you're computing literal paths through literal networks. But again, remember that paths can be thought of as more abstractly as a just sequence of decisions, and some of the most powerful applications of shortest paths are coming up with optimal weight such sequences. So, for example, maybe you're engaging in financial transactions and you have the option of both buying and selling assets at different times. If you sell, then you get some kind of profit, and that would correspond to a negative edge length. So there are quite interesting applications in which negative edge lengths are relevant. If you are dealing with such an application, Dijkstra's algorithm is not the algorithm to use. There's a different shortest path algorithm, a couple other ones, but the most well-known one is called Bellman-Ford. That's something based on dynamic programming, which we may well cover in a sequel course. Okay, so for Dijkstra's algorithm, we always focus on graphs that have only non-negative edge lengths. So with the next quiz, I just want to make sure that you understand the single source shortest path problem. Okay, let me draw for you here a simple Ford node network and ask you for what are the 4 shortest path lengths. So from the source vertex S to each of the 4 vertices in the network. All right, so the answer to this quiz is the final option, 0, 1, 3, 6. To see why that's true, well, all of the options had 0 as the shortest path distance from S to itself, so that just seemed kind of obvious. So the empty path will get you from S to itself and have 0 length. Now suppose you wanted to get from S to V. Well, there's actually only one way to do that. You have to go along this one-hop path. So the only path has length 1. So the shortest path distance from S to V is 1. Now W is more interesting. There's a direct one-hop path, SW, that has length 4, but that is not the shortest path from S to W. In fact, the 2-hop path that goes through V as an intermediary has total path length 3, which is less than the length of the direct arc from S to W. So therefore, the shortest path distance from S to W is going to be 3. And finally, for the vertex t, there's three different paths going from S to t. There's the two-hop path that goes through V. There's the two-hop path which goes through W. Both of those have path length 7. And then there's the three-hop path which goes through both V and W. And that actually has a path length of 1 plus 2 plus 3 equal to 6. So despite having the largest number of edges, the zigzag path is in fact the shortest path from S to T, and it has length 6. Alright, so before I tell you how Dijkstra's algorithm works, I feel like I should justify the existence of this video a little bit, right? Because this is not the first time we've seen shortest paths. You might be thinking, rightfully so, we already know how to compute shortest paths. That was one of the applications of breadth first search. So the answer to this question is both yes and no. Breadth first search does indeed compute shortest paths. We had an entire video about that. But it works only in the special case where the length of every edge of the graph is 1. At the moment, we're trying to solve a more general problem. We're trying to solve shortest paths when edges can have arbitrary non-negative edge lengths. So, for example, in the graph that we explored in the previous quiz, if we ran breadth first search starting from the vertex S, it would say that the shortest path distance from S to T is 2. And that's because there's a path with 2 hops going from S to T. Put differently, T is in the second layer emanating from S. But as we saw in the quiz, there is not in fact a shortest 2-hop path from S to T if you care about the edge lengths. Rather, the minimum length path, the shortest path with respect to the edge weights, is this 3-hop path, which has a total length of 6. So breadth first search is not going to give us what we want when the edge lengths are not all the same. And if you think about an application like driving directions, then needless to say, it's not the case that every edge in the network is the same. Some roads are much longer than others, some roads will have much larger travel times than others, so we really do need to solve this more general shortest path problem. Similarly, if you're thinking more abstractly about a sequence of decisions like financial transactions, in general, different transactions will have different values. So you really want to solve general shortest paths. You're not in the special case that breadth first search solves. Now, if you're feeling particularly sharp today, you might have the following objection to what I just said. You might say, big deal. General edge weights, unit edge weights, it's basically the same. Say you have an edge that has length 3. How is that fundamentally different than having a path with 3 edges, each of which has length 1? So why not just replace all the edges with a path of edges of the appropriate length? Now we have a network in which every edge has unit length, and now we can just run breadth first search. So, put succinctly, isn't it the case that computing shortest paths with general edge weights reduces to computing shortest paths with unit edge weights? Well, the first comment I want to make is I think this would be an excellent objection to raise. And indeed, as programmers, as computer scientists, this is the way you should be thinking. If you see a problem that seems superficially harder than another one, you always want to ask, well, maybe just with a clever trick, I can reduce it to a problem I already know how to solve. That's a great attitude in general for problem solving. And indeed, if all of the edge lengths were just small numbers like 1, 2, and 3, and so on, this trick would work fine. The issue is when you have a network where the different edges can have very different lengths. And that's certainly the case in many applications. Definitely road networks would be one, where you have both sort of long highways and you have neighborhood streets. And potentially in financial transaction-based networks, you would also have a wide variance between the value of different transactions. And the problem then is some of these edge lengths might be really big. They might be 100, they might be 1,000. It's very hard to put a priori bounds on how large these edge weights could be. So if you start wantonly replacing single edges with these really long paths of like 1,000, you've blown up the size of your graph way too much. So you do have a faithful representation of your old network, but it's too wasteful. So even though breadth first search runs in linear time, it's now on this much larger graph, and we'd much prefer something which is linear time or almost linear time that works directly on the original graph. And that is exactly what Dijkstra's shortest path algorithm is going to accomplish. Let's now move on to the pseudocode for Dijkstra's shortest path algorithm. So this is another one of those algorithms where no matter how many times I explain it, it's always just super fun to teach. And the main reason is because it exposes the beauty that pops up in good algorithm design. So the pseudocode, as you'll see in a second, is itself very elegant. We're just going to have one loop, and in each iteration of the loop, we will compute the shortest path distance to one additional vertex. And by the end of the loop, we'll have computed shortest path distances to everybody. The proof of correctness, which we'll do in the next video, is a little bit subtle, but also quite natural, quite pretty. And then finally, Dijkstra's algorithm will give us our first opportunity to see the interplay between good algorithm design and good data structure design. So with a suitable application of the heap data structure, we'll be able to implement Dijkstra's algorithm so it runs blazingly fast, almost linear time, namely m times log n. But I'm getting a little ahead of myself. Let me actually show you this pseudocode. At a high level, you really should think of Dijkstra's algorithm as being a close cousin of breadth first search. And indeed, if all of the edge lengths are equal to 1, Dijkstra's algorithm becomes breadth first search. So this is sort of the slick generalization of breadth first search when edges can have different lengths. So like our generic graph search procedures, we're going to start at the source vertex S, and in each iteration we're going to conquer one new vertex, and we'll do that once each iteration. After n-1 iterations, we'll be done. And in each iteration we'll correctly compute the shortest path distance to one new possible destination vertex V. So let me just start by initializing some notation. So capital X is going to denote the vertices that we've dealt with so far. And by dealt with, I mean we've correctly computed shortest path distance from the source vertex to every vertex in X. We're going to augment X by one new vertex in each iteration of the main loop. Remember that we're responsible for outputting n numbers, one for each vertex. We're not just computing one thing, we're computing the shortest path distance from the source vertex S to every other vertex. So I'm going to frame the output in terms of this array capital A. So for each vertex, we're going to have an entry in the array A, and the goal is at the end of the algorithm, A will be populated with the correct shortest path distances. Now, to help you understand Dijkstra's algorithm, I'm going to do some additional bookkeeping, which you would not do in a real implementation of Dijkstra's algorithm. Specifically, in addition to this array capital A, in which we compute shortest path distances from the source vertex to every other destination, there's going to be an array capital B, in which we'll keep track of the actual shortest path itself from the source vertex S to each destination V. So the arrays A and B will be indexed in the same way. There'll be one entry for each possible destination vertex V. Capital A will store just a number for each destination, shortest path distance. The array B in each position will store an actual path, the shortest path from S to V. But again, you would not include this in an actual implementation. I just find, in my experience, it's easier for students to understand this algorithm if we think of the paths being carried along as well. So now that I've told you the semantics of these two arrays, I hope it's no surprise how we initialize them for the source vertex itself, S. Right, the shortest path distance from S to itself is 0. The empty path gets you from S to S with length 0. There's no negative edges by assumption, so there's no way you can get from S back to S with non-positive length. So this is definitely the shortest path distance for S. By the same reasoning, the shortest path from S to S is just the empty path, the path with no edges in it. So now let's proceed to the main while loop. So the plan is we want to grow this set capital X like a mold until it covers the entire graph. So in each iteration it's going to grow and cover up one new vertex, and that vertex will then be processed, and at the time of processing we're responsible for computing the shortest path distance from S to this vertex and also figuring out what the actual shortest path from S to this vertex is. So in each iteration, we need to grow X by one node to ensure that we make progress. So the obvious question is, which node should we pick? Which one do we add to X next? So there's going to be two ideas here. The first one we've already seen in terms of all of these generic graph search procedures, which is we're going to look at the edges and the vertices which are on the frontier. So we're going to look at the vertices that are just one hop away from vertices we've already put into X. So that motivates at a given iteration of the while loop to look at the stuff we've already processed, that's X, and the stuff we haven't already processed, that's V minus X. S, of course, starts in X, and we never take anything out of X, so S is still there. You know, in some generic iteration of the while loop, we might have some other vertices that are in X, and in a generic iteration of this while loop, there might be multiple vertices which are not in X. And now, as we've seen in our graph search procedures, there are edges crossing this cut. So there are edges which have one endpoint in each side, one endpoint in X and one endpoint outside of X. This is a directed graph, so they can cross in two directions. They can cross from left to right, or they can cross from right to left. So you might have some edges internal to X. Those are things we don't care about at this point. You might have edges which are internal to V minus X. We also don't care about those, at least not quite yet. And then you have edges which can cross from X to V minus X, as well as edges that can cross in the reverse direction, from V minus X back to X. And the ones we're going to be interested in, just like when we did graph search and directed graphs, are the edges crossing from left to right. The edges whose tail is amongst the vertices we've already seen and whose head is some not yet explored vertex. So the first idea is that at each iteration of the while loop, we scan or we examine all of the edges with tail in X and head outside of X. One of those is going to lead us to the vertex that we pick next. So that's the first idea, but now we need a second idea, because this is again quite underdetermined. There could be multiple such vertices which meet this criterion. So for example, in the cartoon in the bottom left part of this slide, you'll notice that there's one vertex here, which is the head of an arc that crosses from left to right, and there's yet another vertex down here in v minus x, which again is the head of an arc which crosses from left to right. So there are two options of which of those two to suck into our set X, and we might want some guidance about which one to pick next. So the key idea in Dijkstra is to give each vertex a score corresponding to how close that vertex seems to the source vertex S, and then to pick among all candidate vertices the one that has the minimum score. Let me be more precise. So among all crossing edges with tail on the left side and head on the right side, we pick the edge that minimizes the following criterion: the shortest path distance that we previously computed from S to the vertex V, plus the length of the edge that connects V to W. So this is quite an important expression, so I will call this Dijkstra's greedy criterion. This is a very good idea to use this method to choose which vertex to add to the set X, as we'll see. I need to give a name to this edge, which minimizes this quantity over all crossing edges. So let's call it V star W star. So for example, in the cartoon in the bottom left, maybe of the two edges crossing from left to right, maybe the top one is the one that has a smaller value of Dijkstra's greedy criterion. So in that case, this would be the vertex V star, and the other end of the edge would be the vertex W star. So this edge V star W star is going to do wonders for us. It will both guide us to the vertex that we should add to X next. That's going to be W star. It's going to tell us how we should compute the shortest path distance to W star, as well as what the actual shortest path from S to W star is. So specifically, in this iteration of the while loop, after we've chosen this edge V star W star, we add W star to X. Remember, by definition, W star was previously not in capital X, so we're making progress by adding it to X. That's one more vertex in X. Now, X is supposed to represent all of the nodes that we've already processed. So an invariant of this algorithm is that we've computed shortest path distances for everybody in X, as well as the actual shortest paths. So now that we're putting W star in X, we're responsible for all of this information, shortest path information. So what we're going to do is we're going to set our estimate of W star's shortest path distance from S to be equal to the value of this Dijkstra greedy criterion for this edge. That is, whatever our previously computed shortest path distance from S to V star was, plus the length of the direct edge from V star to W star. Now, a key point is to realize that this code does make sense, by which I mean, if you think about this quantity AV, this has been previously computed. And that's because an invariant of this algorithm is we've always computed shortest path distances to everything that's in capital X. And of course, the same thing holds when we need to assign W star its shortest path distance, because V star was a member of capital X. We had already computed its shortest path distance, so we can just look up the V star entry position in the array A. So over in our picture on our left, we would just say, well, what did we compute the shortest path distance to V star previously? Maybe it's something like 17. And then we'd say, what is the length of this direct edge from V star to W star? Maybe that's 6. Then we would just add 17 and 6, and we would put 23 as our estimate of the shortest path distance from S to W star. So we do something analogous with the shortest paths itself and the array B. That is, again, we're responsible, since we just added W star to capital X, we're responsible for suggesting a path from S to W star in the B array. So what we're going to do is we're just going to inherit the previously computed path to V star, and we're just going to tack on the end one extra hop, namely the direct edge from V star to W star. That'll give us a path from S all the way to W star via V star as an intermediate bit stop. And that is the entirety of Dijkstra's algorithm. I've explained all of the ingredients about how it works at a conceptual level. So the two things I owe you is, why is it correct? Why does it actually compute shortest paths correctly to all of the different vertices? And then secondly, how fast can we implement it? So the next two videos are going to answer both of those questions. But before we do that, let's go through an example to get a better feel for how this algorithm actually works. And I also want to go through a non-example so that you can appreciate how it breaks down when there are negative edges. And that'll make it clearer why we do need a proof of correctness, because it's not correct without any assumptions about the edge lengths. In this video, I'm going to tell you a little bit about my approach toward teaching data structures in this course. So knowing when and how to use basic data structures is an essential skill for the serious programmer. Data structures are used in pretty much every major piece of software. So let me remind you what's the point, the raison d'etre of a data structure. Its job is to organize data in a way that you can access it quickly and usefully. There's many examples of data structures, and hopefully you've seen a few of them and perhaps even used a few of them in your own programs. And they range from very simple examples like lists, stacks, and queues, to more intricate but still very useful ones like heaps, search trees, hash tables, relatives thereof like Bloom filters, union find structures, and so on. So why do we have such a laundry list of data structures? Why is there such a bewildering assortment? It's because different data structures support different sets of operations and are therefore well suited for different types of tasks. Let me remind you of a concrete example that we saw back when we were discussing graph search, and in particular breadth first search and depth first search. So we discussed how implementing breadth first search, the right data structure to use is a queue. This is something that supports fast, meaning constant time insertion to the back and constant time deletion from the front. Depth first search, by contrast, is a different algorithm with different needs, and because of its recursive nature, a stack is much more appropriate for depth first search. That's because it supports constant time deletion from the front, but constant time insertion to the front. So the last in, first out support of a stack is good for depth first search. The first in, first out operations of a queue work for breadth first search. Now, because different data structures are suitable for different types of tasks, you should learn the pros and cons of the basic ones. Generally speaking, the fewer operations that a data structure supports, the faster the operations will be and the smaller the space overhead required by the data structure. Thus, as a programmer, it's important that you think carefully about the needs of your application. What are the operations that you need a data structure to export? And then you should choose the right data structure, meaning the one that supports all of the operations you need, but ideally no superfluous ones. Let me suggest 4 levels of data structure knowledge that someone might have. So level 0 is the level of ignorance for someone who's never heard of a data structure and is unaware of the fact that organizing your data can produce fundamentally better software. For example, fundamentally faster algorithms. Level 1 I think of as being cocktail party level awareness. Now obviously here I'm talking only about the nerdiest of cocktail parties, but nonetheless this would be someone who could at least hold a conversation about basic data structures. They've heard of things like heaps and binary search trees, they're perhaps aware of some of the basic operations, but this person would be shaky using them in their own program or say in a technical interview context. Now with level 2 we're starting to get somewhere. So here I would put someone who has solid literacy about data structures. They're comfortable using them as a client in their own programs, and they have a good sense of which data structures are appropriate for which types of tasks. Now level 3, the final level, is the hardcore programmers and computer scientists. And these are people who are not content to just be a client of data structures and use them in their own programs, but they actually have an understanding of the guts of these data structures, how they are coded up, how they're implemented, not merely how they are used. Now my guess is that really a large number of you will wind up using data structures in your own programs, and therefore learning about what are the operations of different data structures and what are they good for will be a quite empowering skill for you as a programmer. On the other hand, I'll bet that very few of you will wind up having to implement your own data structures from scratch, as opposed to just using as a client the data structures that already come with the various standard programming libraries. So with this in mind, I'm going to focus my teaching on taking you up to level 2. My discussion is going to focus on the operations supported by various data structures and some of the canonical applications. So through this, I hope I'll develop your intuition for what kinds of data structures are suitable for what kinds of tasks. Time permitting, however, I'll also include some optional material for those of you wanting to take it to the next level and learn some about the guts of these data structures, the canonical implementations of how you'd code them up. So in this video, we'll start talking about the heap data structure. So in this video, I want to be very clear on what are the operations supported by a heap, what running time guarantees you can expect from canonical implementations, and I want you to get a feel for what kinds of problems they are useful for. In a separate video, we'll take a peek under the hood and talk a little bit about how heaps actually get implemented. But for now, let's just focus on how to use them as a client. So the number one thing you should remember about a given data structure is what operations it supports and what is the running time you can expect from those operations. So basically a heap supports two operations. There's some bells and whistles you can throw on, but the two things you got to know is insertion and extract min. All right, so the first thing I have to say about a heap is that it's a container for a bunch of objects, and each of these objects should have a key, like a number, so that for any given objects you can compare their keys and say one key is bigger than the other key. So for example, maybe the objects are employee records and the key is social security numbers. Maybe the objects are the edges of a network and the keys are something like the length or the weight of an edge. Maybe each object indicates an event and the key is the time at which that event is meant to occur. Now the number one thing you should remember about a given data structure is, first of all, what are the operations that it supports, and second of all, what is the running time you can expect from those operations. For a heap, essentially there's two basic operations: insert and extract the object that has the minimum key value. So in our discussion of heaps, we're going to allow ties. They're pretty much equally easy with or without ties. So when you extract min from a heap that may have duplicate key values, then there's no specification about which one you get. You just get one of the objects that has a tied for the minimum key value. Now, of course, there's no special reason that I chose to extract the minimum rather than the maximum. Either you can have a second notion of a heap, which is a max heap, which always returns the object with a maximum key value, or if all you have at your disposal is one of these extract min type heaps, you can just negate the sign of all of the key values before you insert them, and then extract min will actually extract the max key value. So just to be clear, I'm not proposing here a data structure that supports simultaneously an extract min operation and an extract max operation. If you wanted both of those operations, there'd be data structures that would give it to you. Probably a binary search tree is the first thing you'd want to consider. So I'm just saying you can have a heap of one of two flavors. Either the heap supports extract min and not extract max, or the heap will support extract max and not extract min. So I mentioned that you should remember not just the supported operations of a data structure, but what is the running time of those operations. Now for the heap, the way it's canonically implemented, the running time you should expect is logarithmic in the number of items in the heap. And it's log base 2 with quite good constants. So when you think about heaps, you should absolutely remember these two operations. Optionally, there's a couple other things about heaps that might be worth remembering. Some additional operations that they can support. So the first is an operation called heapify. Like a lot of the other stuff about heaps, it has a few other names as well, but I'm going to call it heapify, one standard name. And the point of heapify is to initialize a heap in linear time. Now, if you have n things and you want to put them all on a heap, obviously you could just invoke insert once per each object. If you have n objects, it seems like that would take n times log n time. Log n for each of the n inserts. But there's a slick way to do them in a batch, which takes only linear time. So that's the heapify operation. And another operation which can be implemented, although there are some subtleties, is you can delete not just the minimum, but you can delete an arbitrary element from the middle of a heap, again in logarithmic time. I mention this here primarily because we're going to use this operation when we use heaps to speed up Dijkstra's algorithm. So that's the gist of a heap. You maintain objects that have keys, you can insert in logarithmic time, and you can find the one with the minimum key in logarithmic time. So let's turn to applications. I'll give you several. But before I dive into any one application, let me just say, what's the general principle? What should trigger you to think that maybe you want to use a heap data structure in some task? So the most common reason to use a heap is if you notice that your program is doing repeated minimum computations, especially via exhaustive search. And most of the applications that we go through will have this flavor. There'll be a naive program which does a bunch of repeated minimums using just brute force search, and we'll see that a very simple application of a heap will allow us to speed it up tremendously. So let's start by returning to the mother of all computational problems, sorting an unsorted array. Now, a sorting algorithm which is sort of so obvious and suboptimal that I didn't even really bother to talk about it in any other point in the course is selection sort. What do you do in selection sort? You do a scan through the unsorted array, you find the minimum element, you put that in the first position, you scan through the other n-1 elements, you find the minimum among them, you put that in the second position, you scan through the remaining n-2 unsorted elements, you find the minimum, you put that in the third position, and so on. So evidently, this sorting algorithm does a linear number of linear scans through this array. So this is definitely a quadratic time algorithm. That's why I didn't bother to tell you about it earlier. So this certainly fits the bill as being a bunch of repeated minimum computations, or for each computation, we're doing exhaustive search. So this, a light bulb should go off and say, aha, can we do better using a heap data structure? And we can, and the sorting algorithm that we get is called heap sort. And given a heap data structure, the sorting algorithm is totally trivial. We just insert all of the elements from the array into the heap, then we extract the minimum one by one. From the first extraction, we get the minimum of all n elements. The second extraction gives us the minimum of the remaining n-1 elements, and so on. So when we extract min one by one, we can just populate a sorted array from left to right. Boom, we're done. What is the running time of heap sort? Well, we insert each element once and we extract each element once, so that's 2n heap operations. And what I promised you is that you can count on heaps being implemented so that every operation takes logarithmic time. So we have a linear number of logarithmic time operations for a running time of n log n. So let's take a step back and appreciate what just happened. We took the least imaginative sorting algorithm possible, selection sort, which is evidently quadratic time. We recognized the pattern of repeated minimum computations. We swapped in the heap data structure, and boom, we get an n log n sorting algorithm, which is just two trivial lines. And remember, n log n is a pretty good running time for a sorting algorithm. This is exactly the running time we had from merge sort. This was exactly the average running time we got from randomized quicksort. Moreover, heap sort is a comparison-based sorting algorithm. We don't use any data about the key elements. We just use it as a totally ordered set. And as some of you may have seen in an optional video, there does not exist a comparison-based sorting algorithm with running time better than n log n. So for the question, can we do better? The answer is no if we use a comparison-based sorting algorithm like heap sort. So that's pretty amazing. All we do is swap in a heap and the running time drops from the really quite unsatisfactory quadratic to the optimal n log n. Moreover, heap sort's a pretty practical sorting algorithm. You run this, it's going to go really fast. Is it as good as quicksort? Maybe not quite, but it's close. It's getting into the same ballpark. So let's look at another application, which frankly in some sense is almost trivial, but this is also a canonical way in which heaps are used. And in this application, it will be natural to call a heap by a synonymous name, a priority queue. So what I want you to think about for this example is that you've been tasked with writing software that performs a simulation of the physical world. So you might pretend, for example, that you're helping write a video game which is for basketball. Now, why would a heap come up in a simulation context? Well, the objects in this application are going to be events records. So an event might be, for example, that the ball will reach the hoop at a particular time, and that would be because a player shot it a couple seconds ago. When, if, for example, the ball hits the rim, that could trigger another event to be scheduled for the near future, which is that a couple players are going to vie for the rebound. That event, in turn, could trigger the scheduling of another event, which is one of these players commits an over-the-back foul on the other one and knocks him to the ground. That, in turn, could trigger another event, which is the player that got knocked on the ground gets up and argues the foul call, and so on. So when you have event records like this, there's a very natural key, which is just the timestamp, the time at which this event in the future is scheduled to occur. Now, clearly a problem which has to get solved over and over and over again in this kind of simulation is you have to figure out what's the next event that's going to occur. You have to know what other events to schedule, you have to know how to update the screen, and so on. So that's a minimum computation. So a very silly thing you could do is just maintain an unordered list of all of the events that have ever been scheduled and do a linear pass through them and compute the minimum. But you're going to be computing minimums over and over and over again. So again, that light bulb should go on and you could say, maybe a heap is just what I need for this problem. And indeed it is. So if you're storing these event records in a heap, with the key being the timestamps, then when you extract min, the heap hands for you on a silver platter using only logarithmic time exactly which event is going to occur next. So let's move on to a less obvious application of heaps, which is a problem I'm going to call median maintenance. The way that this is going to work is you and I are going to play a little game. So on my side, what I'm going to do is I'm going to pass you index cards one at a time when there's a number written on each index card. Your responsibility is to tell me at each time step the median of the numbers that I've passed you so far. So after I've given you the first 11 numbers, you should tell me as quickly as possible the 6th smallest. After I've given you 13 numbers, you should tell me the 7th smallest, and so on. Moreover, we know how to compute the median in linear time, but the last thing I want is for you to be doing a linear time computation every single time step. Right? I only give you one new number. Do you really have to do linear time just to recompute the median if I just gave you one new number? So to make sure that you don't run a linear time selection algorithm every time I give you one new number, I'm going to put a budget on the amount of time that you can use at each time step to tell me the median. And it's going to be logarithmic in the number of numbers I've passed you so far. So I encourage you to pause the video at this point and spend some time thinking about how you would solve this problem. Alright, so hopefully you've thought about this problem a little bit. So let me give you a hint. What if you use 2 heaps? Do you see a good way to solve this problem then? Alright, so let me show you a solution to this problem that makes use of 2 heaps. So the first heap we'll call h low. This heap will support extract max. Remember we discussed that a heap you could pick whether it supports extract min or extract max. You don't get both, but you can get either one. It doesn't matter. And then we'll have another heap h high, which supports extract min. And the key idea is to maintain the invariant that the smallest half of the numbers that you've seen so far are all in the low heap, and the largest half of the numbers that you've seen so far are all in the high heap. So for example, after you've seen the first 10 elements, the smallest 5 of them should reside in h low, and the biggest 5 of them should reside in h high. After you've seen 20 elements, then the bottom 10, the smallest 10 should reside in h low, and the largest 10 should reside in h high. If you've seen an odd number, either one can be bigger, it doesn't matter. So if you have 21, you have the smallest 10 in the one and the biggest 11 in the other, or vice versa. It's not important. Now, given this key idea of splitting the elements in half according to the 2 heaps, you need 2 realizations, which I'll leave for you to check. So first of all, you have to prove you can actually maintain this invariant with only O of log I work in step I. Second of all, you have to realize this invariant allows you to solve the desired problem. So let me just quickly talk through both of these points, and then you can think about it in more detail on your own time. So let's start with the first one. How can we maintain this invariant using only log I work at time step I? And this is a little tricky. So let's suppose we've already processed the first 20 numbers, and the smallest 10 of them we've all worked hard to put only in h low, and the biggest 10 of them we've worked hard to put only in h high. Now here's a preliminary observation. What's true? So what do we know about the maximum element in h low? Well, these are the 10th smallest overall, and the maximum then is the biggest of the 10th smallest. So that would be the 10th order statistic, so the 10th smallest overall. Now what about in the high heap? What is its minimum value? Well, those are the biggest 10 values, so the minimum of the 10 biggest values would be the 11th order statistic. Okay? So the maximum of h low is the 10th order statistic, the minimum of h high is the 11th order statistic. They're right next to each other. These are in fact the 2 medians right now. So when this new element comes in, this 21st element comes in, we need to know which heap to insert it into. And well, if it's smaller than the 10th order statistic, then it's still going to be in the bottom, then it's in the bottom half of the elements. It needs to go in the low heap. If it's bigger than the 11th order statistic, if it's bigger than the minimum value of the high heap, then that's where it belongs, in the high heap. If it's wedged in between the 10th and 11th order statistics, it doesn't matter. We can put it in either one. This is the new median anyways. Now, we're not done yet with this first point because there's a problem with potential imbalance. So imagine that the 21st element comes up and it's less than the maximum of the low heap. So we stick it in the low heap, and now that has a population of 11. And now imagine the 22nd number comes up, and that again is less than the maximum element in the low heap. So again, we have to insert it in the low heap. Now we have 12 elements in the low heap, but we only have 10 in the right heap. So we don't have a 50-50 split of the numbers. But we can easily rebalance. We just extract the max from the low heap and we insert it into the high heap. And boom, now they both have 11, and the low heap has the smallest 11 and the high heap has the biggest 11. So that's how you maintain the invariant, that you have this 50-50 split in terms of the small and the high between the two heaps. You check where it lies with respect to the max of the low heap and the min of the high heap. You put it in the appropriate place, and whenever you need to do some rebalancing, you do some rebalancing. And this uses only a constant number of heap operations when a new number shows up, so that's log I work. So now, given this discussion, it's easy to see the second point. Given that this invariant is true at each time step, how do we compute the median? Well, it's going to be either the maximum of the low heap and or the minimum of the high heap, depending on whether I is even or odd. If it's even, both of those are medians. If I is odd, then it's just whichever heap has one more element than the other one. So the final application we'll talk about in detail in a different video, a video concerned with the running time of Dijkstra's shortest path algorithm. But I do want to mention it here as well, just to reiterate the point of how careful use of data structures can speed up algorithms, especially when you're doing things like minimum computations in an inner loop. So Dijkstra's shortest path algorithm, hopefully many of you have watched that video at this point, but basically what it does is it has a central while loop, and so it operates once per vertex of the graph, and at least naively it seems like what each iteration of the while loop does is an exhaustive search through the edges of the graph, computing a minimum. So if we think about the work performed in this naive implementation, it's exactly in the wheelhouse of a heap, right? So what we do in each of these loop iterations is do an exhaustive search computing a minimum. You see repeated minimum computations, a light bulb should go off and you should think, maybe a heap can help. And a heap can help in Dijkstra's algorithm. The details are a bit subtle and they're discussed in a separate video, but the upshot is we get a tremendous improvement in the running time. So recalling that m denotes the number of edges and n denotes the number of vertices of a graph, with the careful deployment of heaps in Dijkstra's algorithm, the runtime drops from this really rather large polynomial, the product of the number of vertices and the number of edges, down to something which is almost linear time. Namely, O of m log n, where m is the number of edges and n is the number of vertices. So the linear time here would be O of m, linear the number of edges. We're picking up an extra log factor, but still this is basically as good as sorting. So this is a fantastically fast shortest path algorithm, certainly way, way better than what you get if you don't use heaps and just do repeated exhaustive searches for the minimum. So that wraps up our discussion of what I think you really want to know about heaps. Namely, what are the key operations that it supports? What is the running time you can expect from those operations? What are the types of problems that the data structure will yield speedups for? And a suite of applications. For those of you that want to take it to the next level and see a little bit about the guts of the implementation, there is a separate optional video that talks a bit about that. Today we're going to embark on the discussion of a new algorithm design paradigm, namely that of designing and analyzing greedy algorithms. So to put this study of greedy algorithms in a little bit of context, let's just zoom out. Let's both review some of the algorithm design paradigms that we've already seen, as well as look forward to some that we're going to learn later on in this course. So it's sort of a sad fact of life that in algorithm design there's no one silver bullet. There's no magic potion that's the cure for all your computational problems. So instead, the best we can do, and the focus of these courses, is to discuss general techniques that apply to lots of different problems that arise in lots of different domains. So that's what I mean by algorithm design paradigms, high-level problem-solving strategies that cut across multiple applications. So let's look at some examples. Back in part 1, we started with the divide and conquer algorithm design paradigm, a canonical example of that paradigm being the merge sort algorithm. So remember, in divide and conquer, what you do is you take your problem, you break it into smaller subproblems, you solve the subproblems recursively, and then you combine the results into a solution to the original problem. Like how in merge sort, you recursively sort two subarrays and then merge the results to get a sorted version of the original input array. Another paradigm that we touched on in part one, although we didn't discuss it anywhere near as thoroughly, is that of randomized algorithms. So the idea that you can have code flip coins, that is, make random choices inside the code itself. Often this leads to simpler, more practical, or more elegant algorithms. A canonical application here is the quicksort algorithm using a random pivot element, but we also saw applications, for example, to the design of hash functions. So the next major paradigm we're going to discuss is that of greedy algorithms. So these are algorithms that iteratively make myopic decisions. In fact, we've already seen an example of a greedy algorithm in part one, namely Dijkstra's shortest path algorithm. And then the final paradigm we're going to discuss in this class is that of dynamic programming, a very powerful paradigm which solves, in particular, two of the motivating questions we saw earlier, namely sequence alignment and distributed shortest paths. So what is a greedy algorithm anyways? Well, to be honest, I'm not going to offer you a formal definition. In fact, much blood and ink has been spilled over which algorithms precisely are greedy algorithms, but I'll give you an informal description, a sort of rule of thumb for what greedy algorithms usually look like. Generally speaking, what a greedy algorithm does is make a sequence of decisions, with each decision being made myopically. That is, it seems like a good idea at the time, and then you hope that everything works out at the end. The best way to get a feel for greedy algorithms is to see examples, and the upcoming lectures will give you a number of them. But I want to point out we've actually already seen an example of a greedy algorithm in part one of this course, namely Dijkstra's shortest path algorithm. So in what sense is Dijkstra's algorithm a greedy algorithm? Well, if you recall the pseudocode for Dijkstra's algorithm, you'll recall there's one main while loop. And the algorithm processes exactly one new destination vertex in each iteration of this while loop. So there's exactly n-1 iterations overall, where n is the number of vertices. So the algorithm only gets one shot to compute the shortest path to a given destination. It never goes back and revisits the decision. In that sense, the decisions are myopic, irrevocable, and that's the sense in which Dijkstra's algorithm is greedy. So let me pause for a moment to discuss the greedy algorithm design paradigm generally. Probably this discussion will seem a little abstract, so I recommend you revisit this discussion on this slide after we've seen a few examples. And at that point, I think it'll really hit home. So let me proceed by comparing it and contrasting it to the paradigm we've already studied in depth, that of divide and conquer algorithms. So you'll recall that in a divide and conquer algorithm, what you do is you break the problem into subproblems. So maybe you take an input array and you split it into two subarrays. Then you solve the smaller subproblems recursively, and then you combine the results of the subproblems into a solution to the original input. So the greedy paradigm is quite different in several respects. First, both a strength and a weakness of the greedy algorithm design paradigm is just how easy it is to apply. So it's often quite easy to come up with plausible greedy algorithms for a problem, even multiple different plausible greedy algorithms. I think that's a point of contrast with divide and conquer algorithms. Often it's tricky to come up with a plausible divide and conquer algorithm, and usually you have this eureka moment where you finally figure out how to decompose the problem in the right way, and once you have the eureka moment, you're good to go. So secondly, I'm happy to report that analyzing running time of greedy algorithms will generally be much easier than it was with divide and conquer algorithms. For divide and conquer algorithms, it was really unclear whether they were fast or slow because we had to understand the running time over multiple levels of recursion. On the one hand, problems size was getting smaller. On the other hand, the number of subproblems was proliferating. So we had to work hard. We developed these powerful tools like the master method and some other techniques for figuring out just how fast an algorithm like merge sort runs, or just how fast an algorithm like Strasson's fast matrix multiplication algorithm runs. In contrast, with greedy algorithms, it'll often be a one-liner. Often it'll be clear that the work is dominated by, say, a sorting subroutine. And of course, we all know that sorting takes n log n time if you use a sensible algorithm for it. Now, the catch, and this is the third point of comparison, is we're generally going to have to work much harder to understand correctness issues of greedy algorithms. For divide and conquer algorithms, we didn't talk much about correctness. It was generally a pretty straightforward induction proof. You can review the lectures on quicksort if you want an example of one of those canonical inductive correctness proofs. But the game totally changes with greedy algorithms. In fact, given a greedy algorithm, we often won't even have very good intuition for whether or not they are correct, let alone how to prove they're correct. So even with a correct algorithm, it's often hard to figure out why it's correct. And in fact, if you remember only one thing from all of this greedy algorithm discussion many years from now, I hope one key thing you remember is that they're often not correct. Often, especially if it's one that you proposed yourself, which you're very biased in favor of, you will think the greedy algorithm must be correct because it's so natural, but many of them are not. So keep that in mind. So to give you some immediate practice with the ubiquitous incorrectness of natural greedy algorithms, let's review a point that we already covered in part 1 of this class concerning Dijkstra's algorithm. Now in part 1 we made a big deal about what a justly famous algorithm Dijkstra's shortest path algorithm is. It runs blazingly fast and it computes all of the shortest paths. What else do you want? Well, remember there was an assumption when we proved that Dijkstra's algorithm is correct. We assumed that every edge of the given network has a non-negative length. We did not allow negative edge lengths. And as we discussed in part 1, for many applications you only care about non-negative edge lengths, but there are applications where you do want negative edge lengths. So let's review on this quiz why Dijkstra's is actually incorrect, despite being so natural. It's incorrect when edges can have negative lengths. So I've drawn in green a very simple shortest path network with 3 edges, and I've annotated the edges with their lengths. You'll notice one of those edges does have a negative length, the edge from V to W, with length -2. So the question is, consider the source vertex S and the destination vertex W. And the question is, what is the shortest path distance computed by Dijkstra's algorithm? And you may have to go and review just the pseudocode in part 1 or on the web to answer that part of the question. And then what is in fact the actual shortest path distance from S to W? Where as usual, the length of a path is just the sum of the lengths of the edges in the path. All right, so the correct answer is D. So let's start with the second part of the question. What is the actual length of a shortest path from S to W? Where there's only 2 paths at all in the graph, the one straight from S to W, that has length 2, and the one that goes via the intermediate point V, that has length 3 plus -2 equal to 1, which is shorter. So SVW is the shortest path that has length 1. Why is Dijkstra incorrect? Well, if you go back to the pseudocode of Dijkstra, you'll see that in the very first iteration, it will greedily find the closest vertex to S. In that case, this is W. W is closer than V. It'll greedily compute the shortest path distance to W, knowing the information it has right now, and all it knows is there's this one hop path from S to W. So it'll irrevocably compute the shortest path distance from S to W as 2. Never reconsidering that decision later. So Dijkstra will terminate with the incorrect output that the shortest path length from S to W is 2. This doesn't contradict anything we proved in part 1 because we established correctness of Dijkstra only under the assumption that all edge lengths are non-negative, an assumption which is violated in this particular example. But again, the takeaway point here is that it's easy to write down a greedy algorithm, especially if you came up with it yourself. You probably believe deep in your heart that it's got to be correct all the time, but more often than not, probably your greedy heuristic is nothing more than a heuristic, and there will be instances on which it does the wrong thing. So keep that in mind in greedy algorithm design. So now that my conscience is clear, having warned you about the perils of greedy algorithm design, let's turn to proofs of correctness. That is, if you have a greedy algorithm that actually is correct, and we'll see some notable examples in the coming lectures, how would you actually establish that fact? Or if you have a greedy algorithm and you don't know whether or not it's correct, how would you approach trying to understand which one it is, whether it's correct or not? So let me level with you. Proving greedy algorithms correct, frankly, is sort of more art than science. So unlike the divide and conquer paradigm, where everything was somewhat formulaic, we had these black box ways of evaluating recurrences, we had this sort of template for proving algorithms correct. Really, proving correctness of greedy algorithms takes a lot of creativity, and it has a bit of an ad hoc flavor. That said, as usual, to the extent that there are recurring themes, that is what I will spend our time together emphasizing. So let me tell you just again at a very high level how you might go about this. You again might want to revisit this content after you've seen some examples where I think it'll make a lot more sense. So method 1 is our old friend, or perhaps nemesis, depending on your disposition, namely proofs by induction. Now, for greedy algorithms, remember that they do is they sequentially make a bunch of irrevocable decisions. So here the induction is going to be on the decisions made by the algorithm. And if you go back to our proof of correctness of Dijkstra's algorithm, that in fact is exactly how we proved Dijkstra's algorithm correct. It was by induction on the number of iterations. In each iteration of the main while loop, we computed the shortest path to one new destination, and we always proved that assuming all of our previous computations were correct, that's the inductive hypothesis, then so is the computation in the current iteration. And so then by induction, everything the algorithm ever does is correct. So that's a proof by induction that a greedy algorithm can be correct, and we might see some more examples of those for other algorithms in the lectures to come. Some of the textbooks call this method of proof greedy stays ahead, meaning you always prove greedy's doing the right thing, iteration by iteration. So a second approach to proving the correctness of greedy algorithms, which works in a lot of cases, is what's called an exchange argument. So you haven't yet seen any examples of exchange arguments in this class, so I can't really tell you what they are, but that's where we're going to proceed next. I'm going to argue by an exchange argument that a couple of different famous greedy algorithms are in fact correct. It has a couple different flavors. One flavor is to approach it by contradiction. You assume for contradiction that a greedy algorithm is incorrect, and then you show that you can take an optimal solution and exchange two elements of that optimal solution and get something even better, which of course contradicts the assumption that you started with an optimal solution. A different flavor would be to gradually exchange an optimal solution into the one output by a greedy algorithm without making the solution any worse. That would show that the output of the greedy algorithm is in fact optimal. And then formally that's done by an induction on the number of exchanges required to transform an optimal solution into yours. And finally, I've already said it once, but let me say it again. There's not a whole lot of formula behind proving greedy algorithms correct. You often have to be quite creative. You might have to stitch together aspects of method 1 and method 2. You might have to do something completely different. Really, any rigorous proof is fair game. So what are greedy algorithms good for? Well, it turns out they're well suited for a number of fundamental problems across different domains of computer science. And to whet your appetite for the many examples that we're going to see, I want to begin by discussing the problem of optimal caching. The punchline of the lecture is going to be that a natural greedy algorithm in fact minimizes the number of cache misses over all possible ways of managing a small, fast cache. So what is the caching problem? Well, on the one hand, there's going to be a big but slow memory, which you can think of as holding everything you might be interested in. But then there's also going to be what we call a cache. And so this is a much smaller memory to which access is much faster. So this situation comes up all the time across different domains of computer science, architecture, operating systems, networking. Just to mention a couple of really obvious examples, you could imagine the small fast memory being something like an L2 cache and the big slow memory being main memory, or perhaps actually main memory is the fast memory and the big slow memory would be disk. Now your task in the caching problem is to process what we're going to call a sequence of page requests. So a page request just means that the client wants to access something in memory, and it's guaranteed to be in the big slow memory, but if it's not already in the small fast memory, then you got to bring it in. You got to put it there for the subsequent access. The algorithmic aspect of the problem enters the picture when there's a cache miss, or also known as a page fault. That is, when there's a request for some data which is not already in the cache. When that's the case, you have to bring it into the cache, and the design question then is, what do you evict from the cache in order to make room for this new piece of data which you have to bring in? So to illustrate the issues, let's look at an extremely simple example, a cache that just has 4 slots for pieces of data. Let's assume that initially the cache is seeded with the 4 pieces of data I'll call A, B, C, and D. Now remember, the input is a sequence of page requests. So these are requests for different pieces of data. Now when a new request comes in, you're basically sitting there crossing your fingers that what's been requested is already in the cache. So for example, if the first request comes in for the piece of data marked C, you said, good, we're good to go. It's already in the cache, go ahead and access it. Similarly, if the next request is for D, you don't have to do anything. The good times roll and D just gets accessed directly. The problem arises when something is requested that's not in the cache. So let's say the next request is for the data item E. Now remember, you have to bring E into the cache, and of course you have to evict one of these 4 pieces of data to make room for it. And your algorithm has to decide which. Can you get rid of A, or B, or C, or D? For this example, let's assume that we evict A to make room for E. Assume further that the next request that comes in is for a new piece of data, F. Again, it's not in the cache, so we have to evict something to make room for it. Let's assume we get rid of B in order to bring in F. And now an unhappy situation, but something that could certainly occur, is we get a request for something that used to be in the cache, but which we have since evicted. So for example, if the next request is for A, then we're stuck. It's going to be another page fault. We have to evict something to bring in A. And similarly, if there's a B, again, we're paying the price for evicting B to make room for F in the past. So in this example, with these particular choices for page evictions, we incur 4 page faults. Now, the first two, the E and the F, there's nothing we could have done about it. We were given a cache that initially did not have E and F, and then E and F showed up. Well, what are you going to do? You're going to miss no matter what. However, 2 were caused by our unfortunate eviction decisions earlier on to evict A and B, only to find them requested just after eviction. And with 20/20 hindsight, we can conclude we really should have evicted C and D, not A and B, to make room for E and F. So the point of this example is to illustrate, first of all, the caching problem, how it works. You have this small, fast memory. It can't contain everything at once, and so you have to sort of manage the cache and evict things to make room for stuff as it gets accessed. That's the first point of the example. The second point is to illustrate there's really 2 types of cache misses or page faults. There's the ones which, really you can't do anything about. No matter what algorithm you use, you're going to suffer those faults. But then, depending on the eviction algorithm, you may be able to avoid some of the cache misses that you would incur with an inferior algorithm. So now the obvious question is, how well can we do? What's the best algorithm? How do we minimize the number of cache misses, suffering only the ones that are inevitable? So this question was given a very elegant answer by Bellotti back in the 1960s, and I'm going to state the answer as a theorem. It's a theorem we're not going to prove for reasons I'll discuss in a second, but what the theorem says is that a natural greedy algorithm is an optimal algorithm for the caching problem. That is, it minimizes the number of cache misses over any way you might think about managing the cache. And the natural greedy algorithm that is optimal is called the furthest in the future algorithm. So what is the furthest in the future algorithm? Well, it's exactly what you'd think it would be. It's basically what seems like a good idea at the moment you have to perform a eviction from the cache. Basically, you want to put off judgment day. You want to put off the regret of evicting this particular piece of data as long as possible. When are you going to regret evicting a piece of data? Well, it's when it gets requested next. So if you have 4 things in the cache, one is requested next, one's requested in 7 time steps, and one's requested in 70 time steps. That's the one you want to evict now, because it'll take the longest until you actually regret that eviction. So for example, in the example on the previous slide, you can check that the furthest in the future algorithm, it would in fact evict the ones you want to evict, A and B, not the ones that we evicted in the example C and D. Now, at this point, many of you are probably justifiably scratching your heads. You're wondering, why is this useful? It doesn't seem like this is what we wanted. The objection to this result being that the furthest in the future algorithm is clairvoyant. Its very definition assumes that you know the future. It assumes that at the moment that you have to make an eviction, you're aware of when each of the pieces of data in the cache will be requested next. But if you think for a minute about the motivating applications for studying the optimal caching problem, this assumption just doesn't hold. You simply do not know the future. You simply do not know when each of the pieces of data in your cache will be requested next. So this algorithm is not defined. It is unimplementable. Despite that, this is still an extremely useful result to know. Why? Well, 2 reasons. First of all, this unimplementable algorithm can nevertheless serve as a guideline for practical implementable algorithms. For example, it naturally motivates the LRU, or least recently used, caching algorithm. So what you do in the LRU algorithm is, instead of looking forward in the future, which you can't do generally, you look in the past and you say, well, let me guess that whatever's been requested recently will be requested again soon. Whatever hasn't been requested for a long time will continue to not be requested for a long time. So that says, as a proxy for the piece of data that's going to be referenced the furthest out in the future, you look for the one that was most recently referenced the furthest back in the past. So that's the LRU algorithm, and as long as data exhibits what's called locality of reference, meaning whatever is being requested a lot in the recent past is also going to be what's requested in the near future, then LRU is going to approximate furthest in the future. And indeed, LRU is in many applications the gold standard amongst practical implementable caching algorithms. The second reason this theorem is useful in practice is because it serves as an idealized benchmark, a hypothetical perfect scenario against which you can compare your latest and greatest caching heuristic. So for example, maybe you have a caching application and you start by implementing the LRU, least recently used caching algorithm. Then as a sanity check, you probably want to go back later, once you have hindsight, you look at the last few days of traces of logs of page requests and you say, how well did we do? Let's look at how well our caching algorithm, LRU, did, and let's look at how well we would have done had we known the future. And hopefully you're just a few percent away, and then you can conclude that, yes, indeed, the data seems to have locality of reference. Yes, indeed, LRU is doing almost as well as if we know the future, and we can proceed. On the other hand, if you go back through the last few days of logs and you find that your caching algorithm is doing much worse than furthest in the future, then it's back to the drawing board with respect to your caching algorithm. You should work harder, understand the data better, and come up with a smarter heuristic. So for almost all of the greedy algorithms that we cover in this course, I'm going to explain to you why they are correct. I'm going to prove it rigorously. This algorithm is an exception. I'm actually not going to prove this theorem for you. The way it works is by what's called an exchange argument. Again, you may not have seen any examples, but you will soon. But the exchange argument to prove Bilatti's result, as far as I know, it's pretty tricky, believe it or not. Even though the algorithm's natural, you might think this result feels a little self-evident. Try to prove it rigorously. Not easy at all. Indeed, if you look at a textbook and say operating systems or a field like that, generally you'll see a description of this algorithm, you'll see the claim that it's optimal, but you won't find the proof. Some algorithms textbooks, for example, algorithm designed by Klein-Gritardos, do include a proof of this theorem. For those of you that are interested, I challenge you to prove it yourself without looking it up on the web or in a textbook. I think if you try to prove it, you'll appreciate the subtleties that come up in understanding whether greedy algorithms are correct or not. In the best case scenario, I would love to see a simple proof of this theorem, something that I could explain in a class like this in, say, 5 minutes or less. That would be amazing. For our next case study of how to use greedy algorithms, we're going to turn to the application domain of scheduling. That is, how do you schedule jobs on shared resources in order to accomplish some objective. So the domain of scheduling, there's lots of different applications of greedy algorithms. We'll see 2 in this course. We'll start for today just with the following simple scenario. So we'll assume for today that there's just one shared resource. This resource could represent any number of things. For concreteness, you can think of it as a computer processor. And then there's a lot of different things that got to get done. So for example, there's a lot of processes that have to be handled by this processor. And the algorithmic question we're going to study is, in what order should we sequence these jobs? Which one should we do first? Which one should we do second? And so on, all the way up to which one should we do last. So obviously, to answer this question, we need to pin down the mathematical model a little bit more precisely. And let's start with just, what are the characteristics of jobs? What information do we have that might lead us to prefer one job over another? Well, for this problem, we're going to assume that each job comes with 2 known parameters. So first of all, a job J has what we're going to call a weight W sub J. That's a non-negative real number. And you should think of the weight of a job as quantifying its importance. That is, jobs with a higher weight in some sense deserve to be processed earlier than those with a lower weight. And secondly, each job J is going to come with a non-negative length L sub J. Now, depending on the application, you may or may not have a good estimate of how long jobs are going to take, but for today, to keep things simple, let's assume that we know what the length of every job is, and that's L sub J. It's part of the input to our problem. So we've now defined the input to this computational problem. We get n jobs, each specified by a weight and a length, and we know that the output is going to be a sequence of these n jobs in some order. So what we have to understand now is, what criterion do we want to optimize? What are we trying to accomplish with this sequence? To explain that, I need to tell you about completion times of jobs. So the completion time of a job is defined hopefully in exactly the way you'd think. So for the job which is scheduled first, it's just the length of the job, because that's how long it takes to process that job. For whatever job gets scheduled second, its completion time is the length of the first job, and then the length of that job itself. So in other words, it's just the total time which elapses before that job gets completed. Okay, so in general, the completion time of a job is just the sum of the lengths of the jobs scheduled to before that job plus the length of that job itself. To make sure this is clear, let's go through a quick example. So suppose there are 3 jobs with lengths 1, 2, and 3. I'm not going to tell you the job weights because they're irrelevant for the purposes of computing the completion time. And let's suppose we do the schedule where we just schedule job 1 first, then job 2, then job 3. So pictorially, I'm going to represent that schedule just by stacking the jobs on top of each other with the interpretation that time starts at the bottom. So time 0 is where we schedule job 1, and then time increases as we go from the bottom to the top of the diagram. And the question then is, what are the completion times of these 3 jobs? Okay, so the correct answer is answer C. So for the first job, it gets scheduled first, so it's very happy, and it just takes 1 unit of time to complete, so its completion time is 1. The second job, well, it has to wait for the first job to complete, so 1 unit of time elapses, and then it itself has to complete, so that's 2 more units, so that gives it a completion time of 3. For the third job, it has to wait for the first 2 to complete, so that adds 3 to the clock, and then plus it takes 3 units of time for a total of 6. So that's the definition of job completion times. In some sense, we obviously want completion times to be as small as possible. But it's not so simple. In any given schedule, the jobs that are early on are going to have small completion times, and the jobs toward the end are going to have big completion times. So inevitably, we're going to have to trading off the completion times between different jobs. What is the optimal way to do that? Well, that depends on our objective function, and in scheduling there's many different objective functions you might want to use. Today I'm just going to tell you about one. It's not the only natural objective function, but it's one of several most natural objective functions. It's called minimizing the weighted sum of completion times. You translate this English phrase into mathematics in the obvious way. What you want to do is you want to minimize the sum over all n jobs of their completion time, but then multiplied by their weight wj. Okay, so the sum over j of wj times cj, where wj is the weight and cj is the completion time as defined on the previous slide. If you think about it for a second, you'll realize this is equivalent to minimizing the weighted average of the completion times with the weights given as in the input. So just to make sure this makes sense, let's go back to the example that we saw. In that example, we had jobs with lengths 1, 2, and 3, and we thought about the schedule where we scheduled them in that order. To evaluate this objective function, I have to tell you their weights. So let's suppose their weights are 3, 2, and 1, respectively. In this case, the weighted sum of completion times in the schedule in the previous slide, well, first we begin with the first job, which has weight 3. Its completion time, remember, was 1. Then we have the second job with weight 2. Its completion time was 3. Then we have the third job with weight 1. Its completion time was 6. So we sum up the weighted completion times, and we get a total of 15. And I'll let you verify that, in fact, of all of the 3 factorial or 6 schedules in that example, this is, in fact, the schedule that minimizes the weighted sum of completion times. And the algorithmic question we're going to study next is, how do we do this in general? Given arbitrary input, n jobs, weights, and lengths, what is the sequence that minimizes the sum over all n factorial sequences you might consider? So the plan for this video is to develop a greedy algorithm that always minimizes the weighted sum of completion times of a given set of n jobs. But more than this specific problem, more than this specific algorithm, I want you to focus on the process by which we arrive at this greedy algorithm. Because I think this process is really something which you can use yourself in your own applications. The process we're going to use is we're going to first look at just a special case of the problem where it's reasonably intuitive what should be the optimal thing to do. Looking at these special cases will then motivate a couple of natural greedy algorithms. Then we'll figure out how to narrow a couple greedy algorithms down to just a single candidate. And that, in fact, as we'll prove in the following lectures, will always be correct. So let's just briefly recall what is it we're trying to do. The computational problem, an instance, is specified by n jobs, which come along with weights and lengths. And amongst all n factorial ways that we can sequence the jobs, we want to somehow home in on the one that minimizes the sum of weighted completion times. Recall from the previous video that the completion time of a job is just the amount of time that elapses before it's done. So that's going to be the length of all of the previous jobs plus the length of job j itself. What we're hoping is going to work out is that we can devise a greedy algorithm that always solves this problem. So maybe I should take a step back and ask, why do greedy algorithms seem like a sensible way to approach the scheduling problem? Well, in general, greedy algorithms are not guaranteed to work. You may have to do something more complicated. But scheduling still seems like a good place to try them out. Remember what a greedy algorithm does. It iteratively makes myopic decisions, and then you hope you have a reasonably good result at the end. Now, what are we doing? We're studying a sequencing problem. The definition of the problem is to schedule a job, then another job, then another job, all the way up to the last job. And so this iterative nature of the solution suggests that, at least if you're lucky, if the problem's simple enough, maybe there's a greedy algorithm which simply schedules the jobs in the correct order one at a time. So we're going to see if that works for minimizing the sum of weighted completion times. So let's start by thinking positive, being optimistic. So let's posit that a greedy algorithm does exist for this problem. Given that we're in the greedy algorithm section of the course, probably you don't find this hard to believe. But suppose one existed, how would we discover what it is? Well, a useful technique, not just for this problem, but more generally in real life, first focus on some special cases of the problem where it's relatively clear how you should proceed. And the two special cases I want you to think about for this problem are, first of all, suppose I told you all of the jobs had exactly the same length, but they had different weights. Then, what order do you think it makes sense to schedule the jobs in? Secondly, suppose I told you that all of the jobs had exactly the same weight, but they had different lengths. Then, what order do you think you should schedule the jobs in? So first of all the jobs have the same length, you should prefer jobs with larger weights. Certainly, this intuitively jives with our semantics of weights. That says more importance, which suggests that higher weight jobs should go first. So if you look at the actual formula of minimizing the sum of weighted completion times, if the jobs all have the same length, then the completion times are going to be the same. You're going to see the same set of them. If all the jobs have length 1, the completion times of the jobs are going to be 1, 2, 3, 4, all the way up to n, no matter what sequence you use. So to make this as small as possible, you want the highest weights to be associated with the smallest completion times. That is, you want them up front as early as possible. The second special case, where jobs have equal weights but varying lengths, I think is a little more subtle. Here what you want to do is you always want to favor small jobs, jobs with the smallest lengths. Everything else being equal. The reason for that is that scheduling a job in a given position forces all the other jobs to wait for that job to complete. So whatever job you schedule first has a negative impact on all of the rest of the n-1 jobs. So all else being equal, you want the smallest job there that minimizes the consequences for the jobs that are to follow. If you find this a little unintuitive, I suggest just looking at a very simple example. 2 jobs, both have weight 1, one has length 1, one has length 2. If you schedule the small job first, you'll have completion times of 1 and 3 for a total of 4. But if you schedule the bigger job first, you get completion times of 2 and 3 for the bigger sum of completion times of 5. So the next step is to move beyond special cases, which we understand well, to the general case, which perhaps we don't understand. So suppose all of the weights are different and all of the lengths are different. Well, if we have 2 jobs and both of these rules of thumb give us the same advice, we're good. If there's one job which is both higher weight and smaller than another job, then clearly that job should go first. But what if our 2 rules of thumb, to prefer high weight jobs and to prefer small jobs, give us conflicting advice? What if we have a pair of jobs where one of them is, on the one hand, higher weight, higher priority, but on the other hand, bigger than the other one? Which one should go first? Well, let's again stay positive, and let's try to think about the simplest kind of algorithm that could conceivably work. There won't be a guarantee that it works, but it might work. So we have these 2 different parameters, lengths and weights. Maybe we can aggregate these 2 parameters into a single one, into a single sort of score for each of the jobs, so that if we schedule the jobs from high score to low score, will always be optimal. That would be great if we can just compile these 2 numbers into one for each job and then just sort and be done. There is, of course, the question of exactly how do we choose this aggregation function? How do we compile length and weight into a single number? Well, as guidelines, we should recall our special case and make sure we respect our 2 rules of thumb. So all else being equal, we should prefer jobs with higher weight. So that says higher weight should lead to higher scores if we're going to schedule the jobs from high score to low score. And then also, if a length is bigger, that should decrease the score. We should prefer jobs that have a small length. So this idea leaves open the question of exactly how do we aggregate the length and the weight of a job into a single number. So what I want you to do now is I want you to think for a minute about what kind of simplest possible functions you could use. So again, these are mathematical functions. They take as input two numbers, a length and a weight of a job, and they output a single number, a score. And the function should have the properties that it's increasing in the job's weight and it's decreasing in the job's length. So there's more than one answer to this question, but just sort of dream up some ideas of what this function might look like. All right, so there's certainly any number of functions which have these properties, but I'm just going to write down for concreteness two of what I think are of the simplest functions that have these properties. So one is going to be based on taking the difference of the two numbers, and one is going to be based on taking the ratio of the two numbers. So if you're going to use a function based on the difference, and you want it to be increasing in the weight and decreasing in the length, then of course the obvious difference to use is weight minus length. This can be negative sometimes, but that doesn't bother us. The algorithm is still well defined. And if you're going to use a ratio and you want it to be increasing in weight, decreasing in length, then the sensible ratio to use is the weight of a job divided by the length of a job. It is, of course, possible that you have ties for either one of these scoring functions, so let's just allow ties to be broken arbitrarily. Now, what we're seeing here is a concrete instantiation of something I promised you in our high-level discussion of greedy algorithms. Namely, it's both a strength and a weakness of them that they're really easy to come up with and propose. So here we have just, this one simple problem, and we now have two different competing greedy algorithms for the problem. Now, because these two algorithms don't do the same thing, only one of them, at most, can be always correct. At least one of them has to be wrong sometimes. So, as the algorithm designer, what the process now is, maybe we can rule out at least one of these two proposed greedy algorithms by showing an example where it doesn't do the right thing. So I want to emphasize, this is the type of scenario that's very likely to arise in your own algorithm design adventures. You might have some problem, you're not sure how to solve it yet, you've brainstormed up a couple of proposed algorithms, and a good thing to do, a good time saver, is to quickly rule out some of those algorithms as not the right way to go, as a poor approach to the problem. So in this context, we have these two greedy algorithms. Let's quickly break one of them, show that it's not always correct. How do we do that? Well, a smart way to go would be to come up with an input where the two algorithms do different things. If they do different things, at most one of them is going to be correct. At least one of them is going to be incorrect. So that's the plan. Now, to execute this goal, as usual, we want to keep things as simple as possible, but no simpler. So what's the simplest possible instance that could lead to different behavior by our two algorithms? Well, obviously one job is not enough because there's only one possible feasible solution. But already with two jobs, we might be able to have one algorithm flip them one way and the other algorithm schedule them in the opposite order. In fact, it is not difficult to come up with an instance with two jobs where they do different things. And let me just go ahead and write such an instance down for you now. So suppose I give you two jobs. The first one is both longer and more important than the other one. Specifically, its length is 5, its weight is 3. The second job, its length is merely 2, but its weight is merely 1. So what I want you to do is I want you to take our two proposed greedy algorithms, the first one which orders by difference, the second one which orders by ratio. I want you to execute them on this two-job input and compute the sum of weighted completion times, and then answer what is the sum of weighted completion times of the corresponding two schedules. All right, so the correct answer is answer B. Let's just briefly go through why. So first, let's just make sure we understand which algorithm produces which schedule. So the first job has the better ratio. Its ratio is 5/3, whereas the ratio of the second job is 1/2, which is smaller. Whereas the second job has the larger difference. It has a difference of -1, whereas the first job has the more negative difference of -2. So the first algorithm, which orders by difference, will schedule the second job first, then the first job. The second algorithm will schedule the first job first, then the second one. So it just remains to compute the objective function value of those two schedules. So for the first schedule with the second job first, well, the second job has weight of 1, it has a completion time of 2. The second job has a weight of 3 and a completion time of 7, so that gives us a total of 23. Whereas the schedule produced by the second algorithm, we have the weight 3 job first. Its completion time, now that it's first, is only 5. And then the second job with weight 1 gets the completion time of 7. for a total of 22. So ordering by difference gives us a value of 23. Ordering by ratio gives us a value of 22. So in this case, the ratio does better than the difference. So certainly the difference is not optimal for this specific example. So what have we accomplished? Well, what we've done is we've very quickly ruled out one of our natural proposed greedy algorithms. We know that ordering by difference is not always correct. Again, it's going to be correct in special cases, like when all the lengths are equal or all the weights are equal, but it is not correct in general. That said, please remember the warning I gave you in the high-level discussion of greedy algorithms, which is greedy algorithms are very often wrong. Just because we know algorithm number 1 is incorrect sometimes does not at all imply that algorithm number 2 is guaranteed to be correct. It's really easy to come up with multiple incorrect greedy algorithms for the same problem. It does, however, turn out in this case, for this greedy algorithm, algorithm number 2, ordering by ratio, it is happily always correct. But you certainly shouldn't believe this claim until I provide you with a proof, a rigorous argument explaining the correctness. Always maintain healthy skepticism about the performance of a greedy algorithm until you learn otherwise. So this fulfills another promise I gave you in the high-level discussion of greedy algorithms, namely, when they're correct, it's often quite difficult to prove it. So this will be the topic of the next couple videos, the correctness proof for this greedy heuristic. The third and final thing we discussed about greedy algorithms, typically, is that the running time is not difficult to analyze. So that's a break that we catch relative to divide and conquer algorithms. And again, that's certainly true here, right? So what does this algorithm do? All it does is compute these ratios and then sort the jobs by ratio. So essentially, the algorithm reduces to a single sorting computation. And of course, from part 1, we know very well how to sort in n log n time. So now let's turn our attention to proving the correctness of this greedy algorithm we've devised that purportedly minimizes the sum of the weighted completion chimes. Let me remind you of the formal correctness claim. The claim is that our second greedy algorithm, the one which looks at the ratio of each job, the ratio of the weight to the length, and sorts them in decreasing order, is always correct. For every possible input, it outputs the sequence of jobs which minimizes the weighted sum of completion times. And as promised, it wasn't hard to devise this greedy algorithm. It's certainly not hard to analyze its running time, which is just n log n, the same time as sorting, but it is quite tricky to prove it correct. The way we're going to do that is going to be our first example of what's called an exchange argument, which is one of the few recurring principles in the correctness proofs of greedy algorithms. So I'm actually going to give you proofs of 2 different versions of this claim. Both will make use of an exchange argument in slightly different ways. For starters, that's going to be in this video and the next one. I'm going to make a simplifying assumption that there are no ties amongst the ratios, that each job has its own distinct ratio of its weight versus its length. In this case, we'll be able to get away with a proof by contradiction. So on this slide, let me give you the high-level proof plan of how this is going to go. We'll start delving into the details on the next slide. So at a high level, we're going to begin by fixing an arbitrary instance, by which I mean, just the description of the weights and lengths of n jobs. Remember, we have to prove that our algorithm is always correct, so we just fix an arbitrary instance and prove correctness on this arbitrary instance. So as I said, for the case with no ties, we're going to proceed by contradictions. Remember, this means we assume what we're trying to prove is false, and from that we derive something which is obviously false, inconsistent. So what would it mean to assume that this claim is false? It means there exists an instance for which this greedy algorithm does not produce an optimal solution, for which there's some other solution not output by the greedy algorithm, which is better than that of the greedy algorithm. So let me just give you some notation to set this up. We're going to let sigma denote the greedy schedule. And if our claim is false, that means this is not an optimal schedule. There's some other one which is better, so call this better optimal schedule sigma star. So to complete a proof by contradiction, we need to derive something which is obviously false. And the way we're going to do that here might strike you initially as a little weird, but it turns out to work really well in this context. From this assumption that the greedy algorithm is not optimal and there's a better schedule sigma star, we're actually going to exhibit yet another schedule which is even better than sigma star, strictly smaller objective function value than sigma star has. Why is that a contradiction? Well, by assumption, sigma star is optimal. So if we show that there's something even better than sigma star is not optimal, and that completes the proof by contradiction. So now let's start filling the details of this proof plan and making it rigorous. So as I said, in this video and the next, we're going to be assuming that all of the ratios are distinct. In general, of course, that need not be true, and I'll give you a separate argument to handle the case of ties. I'm going to make a second assumption, but unlike the first assumption, the second assumption has no content. It's just an assumption about notation. I'm going to assume by renaming jobs that job 1, number 1, is the one with the highest ratio, job number 2 is the one with the second highest ratio, and so on, job n being the one with the smallest ratio. As a consequence of this switch in notation, the greedy schedule is very simple to describe. It just schedules job 1 first, then job 2 second, then job 3 third, and so on all the way up to job n. Okay, so we have one assumption which is not without loss of generality, and we'll have a separate argument for handling ties. We have a second assumption which is without loss of generality. It's just an agreement amongst friends who want to minimize notation. And now let's actually derive something with content. So given that the greedy schedule is just the jobs in order, 1, 2, 3, all the way up to n, and given our assumption that the greedy solution is not optimal, and instead there's some other distinct optimal schedule, sigma star, I claim that sigma star must contain consecutive jobs. That is, somewhere in the schedule, sigma star, I can isolate a pair of jobs, one executed after the other, such that the earlier of those two consecutive jobs has a larger index. I'm going to call these jobs I and j, with I being earlier. So again, by virtue of the optimal solution sigma star being something other than the schedule 1, 2, 3 up to n, there must be two jobs somewhere in the schedule executed in a row, one after the other, so that the earlier job I has a higher index than the subsequent job j. Why is this true? Well, the reasoning is that the only schedule that has the property that indices only go up as you go from the earliest job to the latest job, the only way the indices will always go up is if you schedule the jobs 1, 2, 3 all the way up to n. There is no other schedule with the property that indices always go up other than 1, 2, 3 all the way up to n. So this is an observation that's going to be important in the rest of the proof, so make sure you pause, give yourself enough time to stare at it and convince yourself it is in fact true. Any schedule other than 1, 2, 3 all the way through n has to have consecutive jobs, the earlier one having a higher index than the later one. So I'm now in a position to explain the exchange in the exchange argument. So let me just distill the two key points from the discussion so far. So first of all, we've changed notation so that ratios are decreasing with index, and this is exactly the same as the schedule that the greedy algorithm will output. And then assuming that the optimal schedule sigma star is something else, we know it has consecutive jobs with the earlier one having a higher index. Keep in mind our high-level proof plan from the first slide of this video. We're doing a proof by contradiction. We need to derive a contradiction, and what we're going to do is we're going to exhibit a schedule even better than sigma star, thereby contradicting its purported optimality. So how do we do that? We do that with an exchange. So this exchange is going to take the form of a thought experiment. We're going to take this purportedly optimal schedule sigma star, and we're going to switch the order just of the two jobs I and j, leaving all of the other jobs unchanged. So sigma star consists of various jobs. Let's call them stuff collectively. Then next is job I, and after that immediately is job j, and then there's possibly some more jobs that get executed after j. And remember, we've observed that we can choose I and j so that I has a higher index than j, despite being scheduled earlier. Then when we execute this exchange, the stuff before I and j is the same as before. The more stuff after j and I is the same as before, but we're going to have them occur in opposite order. And the key thing we have to understand next is what are the ramifications of this exchange? What are the costs? What are the benefits? That's how we'll begin the next video. Okay, let's continue the proof of correctness of our greedy algorithm for minimizing the sum of the weighted completion times, and let's move on to understanding the ramifications of the exchange of jobs suggested at the conclusion of the previous video. So recall the basic idea is to use this observation that the optimal schedule sigma star, by virtue of our assumption of being different than the greedy one, has to have this pair of consecutive jobs where the earlier one has the higher index. So my question for you involves thinking about how the completion times of all of the jobs change after we make this exchange of the two jobs, I and j. Which ones go up, which ones go down, which ones are unaffected, which ones can we not actually predict whether they go up or down. All right, so the answer to this quite key question is the third answer. Jobs other than I and J are unaffected. The completion time of job I goes up and the completion time of job J goes down. So let's review why. Consider a job K other than I or J. It's probably easiest to see if in sigma star, K completes before I and J. It's scheduled earlier than I and J. Don't remember what the completion time of a job is. It's just the time that needs to elapse before it gets done. So it's the sum of the job lengths up to and including that job itself. So if K was scheduled before I and J before, it's exactly the same after I and J are swapped. You don't know the difference. Exactly the same set of jobs precedes job K as before, so its completion time is the same. But if you think about it, this exact same argument is true for jobs K that succeed I and J. So before we do the swap, it has to wait for a bunch of jobs to complete, including I and J. And after we swap I and J, it still has to wait for I and J to complete. Yeah, they complete in opposite order, but who cares? The amount of time that elapses is exactly the same. So importantly, jobs other than I and J are completely agnostic to this swap. Their completion time is exactly the same as before. So that's the first part. So job I, its completion time goes up. It's easy to see why. It used to be before J, now it has to wait for J. In fact, we can say exactly how much completion time goes up by. It goes up by exactly the length of J. That is the extra time which now needs to elapse before I gets completed. By exactly the same reasoning, the completion time of job J actually drops. It has to wait for the same jobs to complete as before, except it no longer has to wait for job I. So not only can we say its completion time goes down, we can say that it goes down by precisely the length of job I. So now we're in a great position to finish off this proof. Let's summarize what we've got so far. So for our cost-benefit analysis of exchanging I and J, we discovered the cost is limited to an increase in the completion time of job I, and the benefit is limited to the decrease in the completion time of job J. Specifically, the cost, the new cost incurred by the exchange, is the weight of job I times the amount by which its completion time went up, namely the length of job J. Similarly, the benefit of the exchange is the drop of Li in J's completion time, and that gets multiplied by its weight of Wj. So now finally, we're at the point where we can use the fact that this purportedly optimal schedule sigma star schedules I and J in some sense incorrectly, with the higher index job first, despite it having a lower ratio, in contrast to the principles followed by our greedy algorithm. So why is it relevant that the earlier job I has a higher index? Well, a higher index corresponds to a lower ratio. Remember, we did this notation switch so that the first job has the highest ratio, the second job has the second highest ratio, and so on. So the bigger your index, the further you are down in the ordering, the lower your ratio. So because I is bigger than J, it means I's ratio is worse than J. The usefulness of this becomes even more apparent when we clear denominators. We multiply both sides by Li times Lj, and then we find that Wi times Lj is strictly less than Wj times Li. But what are these? These are just the cost and benefit terms, respectively, of our thought experiment exchange, of exchanging I and J. So what does it mean that the benefit of the swap outweighs the cost? It means that if we take sigma star, this purportedly optimal solution, and we invert the jobs I and J, we get a schedule with an even better weighted sum of completion times. But that is nuts. That's absurd. Sigma star was supposed to be optimal. So here's our contradiction. That completes the proof. So in this video, we're going to revisit our greedy algorithm for minimizing the weighted sum of completion times, and we're going to give a more robust, more general correctness proof that also accommodates ties amongst the ratios of the different jobs. The main reason I'm doing this is not because I think the result is so earth-shattering in its own right, but rather to give you further examples of exchange arguments in action, in particular outside of a proof by contradiction. So let's be formal about our new, more general correctness proof. So we're again talking about the greedy algorithm, which orders jobs by the ratio of weight to the length. We're no longer assuming these are distinct, so we can't really say decreasing order. We'll say non-increasing order. And ties can be broken any way you want. We'll prove the algorithm's correct no matter how the ties are resolved. So fortunately, we'll be able to reuse much of the work that we did for the previous correctness proof. But actually, our overall proof plan is going to change a little bit. We're no longer going to proceed by contradiction. So here's the high-level plan now. So as before, we're going to argue correctness on every separate instance, so fix an arbitrary one. So the notation will be similar to last time. So on this input, we'll let sigma denote the output of our greedy algorithm, and then we'll let sigma star denote an arbitrary other competitor, any other schedule of the jobs. So now what we're going to do is we're going to show that sigma, the output of our greedy algorithm, is at least as good as sigma star. Since sigma star was arbitrary, that means the greedy algorithm's output is at least as good as every other schedule, and therefore sigma has to be optimal. So let's now fill in the details. We're going to make a similar notational assumption as last time, and that we're going to assume that the greedy schedule is just 1, 2, 3, all the way up to n. And again, that's a content-free assumption. We can get away with it just by changing the names of the jobs, changing notation. So recall the proof plan. We have to take any other competing schedule sigma star and show that it's no better than sigma, show that sigma is at least as good as it. So fix any such schedule sigma star. Obviously, if sigma star is sigma, then they're the same. They're just as good as each other, so there's nothing to do. Now, if sigma star is not the same thing as sigma, if it's not just the sequence 1, 2, 3, all the way up to n, we're going to reuse a key observation from our previous proof. Namely, any schedule other than just 1 through n has to contain in it a consecutive pair of jobs, I and j, where j is executed immediately after I, where I has the higher index. So now we argue similarly to last time. What does it matter that one job has a higher index than another? Well, that means it's further along in the ordering, which means its ratio can only be smaller. Remember, the ratios are non-increasing. They can only go down in the ordering. So higher index means lower ratio. But there may be ties, so we can't claim a strict inequality, just a weak inequality. And so again, by clearing denominators, this boils down to the weight of job I times the length of job j is at most the weight of job j times the length of job I. Now, the next thing I want you to recall from our previous proof is that there are nice semantics for WILJ and WJLI, namely as the cost and the benefit of exchanging jobs I and j in the schedule sigma star. So arguing as in the previous videos, we can claim that exchanging I and j from the schedule sigma star has a net benefit, that is a benefit minus cost, of WJLI. That's because job j's completion time drops by Li, minus WILJ. That's because job i's completion time increases by Lj with this exchange. And so this is non-negative. So in comparison with our previous proof, what the assumption of no ties bought us, it bought us the stronger fact that when we exchange I and j, in fact, sigma star gets strictly better. We get a better schedule than what we started with. Here with ties, that need not be true. If I and j have exactly the same ratio and we exchange them, then the cost equals the benefit, so the net change in the objective function is 0. So we can only claim that by inverting I and j, we don't make sigma star worse. It can only get better. It might stay the same. So let's see why that's good enough to nonetheless complete the proof. So what the previous slide gives us, it gives us a method of changing a schedule, massaging a schedule, so that it doesn't get any worse. It can only get better. Specifically, if we take any schedule sigma star, we take any adjacent inversion, by which I just mean 2 consecutive jobs with the higher one having a higher index. We exchange the jobs in any adjacent inversion, we get a new schedule, which can only be better. Sum of weighted completion times might be the same, but if it's different, it has to be smaller. So in our previous proof, we knew it was strictly better because we had no ties, and then our proof by contradiction said we were done. So what are we going to do now? What we're going to do is we're going to take this operation, which massages a schedule without making it worse, and we're just going to repeat it over and over and over again. Because actually, this operation has a second property. Not only can it not make a schedule worse, but it also decreases the number of inverted job pairs. And here by an inversion, I mean the same thing as when we counted inversions with the divide and conquer algorithm back in part 1. I just mean the job pairs somewhere in a schedule where the higher indexed one occurs earlier in the ordering. When we exchange adjacent inversion, we uninvert that inversion, and because they're adjacent, we don't create any new inversions. So the number of inverted job pairs drops by exactly 1 each time we do one of these exchanges. So what does that mean? So here's the proof in a nutshell. We take an arbitrary competitor, some schedule sigma star, and we find either it's the same as the greedy schedule. If it's not, there's an adjacent inversion, in which case we exchange it. We get a schedule that's at least as good, and fewer inversions. Either this new schedule is sigma, in which case we're done, or it's not, and then we find an adjacent inversion, and we exchange it. It only gets better, and we keep going. Why can this not continue forever? Well, the number of inversions can only be n choose 2 initially. That's if you start with the schedule n, n-1, n-2, all the way 1, if the jobs are initially backward. So we can only do this exchange n choose 2 times before we necessarily terminate with the greedy schedule 1 through n. At that point, what have we done? We've taken an arbitrary schedule sigma star, we've massaged it, making it only better and better and better and better, terminating with our greedy schedule sigma. What does that say? That says our greedy schedule sigma is at least as good as what we started with sigma star. So our greedy schedule is at least as good as this arbitrary schedule sigma star. So it's optimal. It's better than everything. So one final note before I write down the QED. For those of you familiar with the bubble sort algorithm, and it's totally fine if you're not familiar with bubble sort, but if you are familiar with bubble sort, you will recognize that essentially what we're doing here inside the proof, not in our algorithm, but inside our proof, we're applying bubble sort in effect to this arbitrary competing schedule sigma star. And by uninverting the inversions, we transform it into the greedy schedule, making it only better, thereby justifying as optimal our greedy algorithm schedule sigma. So in this sequence of videos, we're going to apply the greedy algorithm design paradigm to a fundamental graph problem, the problem of computing minimum spanning trees. The MST problem is a really fun playground for greedy algorithm design because it's this singular problem in which pretty much any greedy algorithm you come up with seems to work. So we'll talk about a couple of the famous ones, show why they're correct, and show how they can be implemented using suitable data structures to be blazingly fast. So I'll give you the formal problem definition on the next slide, but first let me just say informally what it is we're trying to accomplish. Essentially what we want to do is connect a bunch of points together as cheaply as possible. And as usual with an abstract problem, the objects could mean something very literal, so maybe the points we're trying to connect are servers in some computer network, or it could represent something more abstract, like maybe we have a model of documents, like web pages, where we represent them as points in space, and we want to somehow connect those together. Now, the main reason I'm going to spend time on the minimum spanning tree problem is pedagogical. It's just a great problem for sharpening your skills with greedy algorithm design and proofs of correctness. It'll also give us another opportunity to see the beautiful interplay between data structures and fast implementation of graph algorithms. That said, the minimum spanning tree problem does have applications. One very cool one is in clustering, and that I'll talk about in detail in a later video. It also comes up in networking. So if you do a web search on spanning tree protocol, you'll find some information about that. So as I said at the beginning, the minimum spanning tree problem is remarkable in that it doesn't just admit one greedy algorithm that's correct, but in fact it admits multiple greedy algorithms that are correct. We're going to talk about two of them, the two most well-known ones, but there are even some others, believe it or not. So the first one we're going to discuss, beginning in the next video, is Prim's MST algorithm. This dates back over 50 years to 1957. In fact, as you'll see, Prim's algorithm shares a remarkable number of similarities with Dijkstra's shortest path algorithm, so you might not be surprised to know that Dijkstra also independently discovered this algorithm a couple years later. But in fact, it was only noticed much later that this exact same algorithm had been first discovered over 25 years earlier by a mathematician named Jarnik. For that reason, you'll sometimes hear this called Jarnik's algorithm or the Prim-Jarnik algorithm. For brevity and to be consistent with some of the main textbooks in the area, I'm going to just call this Prim's algorithm throughout the lectures. The other algorithm we're going to cover, which is also rightfully famous, is Kruskal's MST algorithm. As far as I know, this was indeed first discovered by Kruskal, roughly the same time as Prim was doing his algorithm in the mid-50s. And in what sense do I say these algorithms are blazingly fast? Well, they run in almost linear time, linear in the number of edges of the graph. Specifically, we'll see how using appropriate data structures, we'll get each of them to run in time big O of m log n, where m is the number of edges in the graph and n is the number of vertices in the graph. We'll employ data structures to speed up Prim's algorithm in exactly the same way we did for Dijkstra's algorithm. That is, we'll be using the heap data structure. One thing that's cool about Kruskal's algorithm is it'll give us an opportunity to study a new data structure, namely the union find data structure. And that's a lot of fun to think about in its own right, as you'll see. So to put this amazing running time in perspective, I want to emphasize that not only is it awesome in the sense it's almost linear. It takes barely more time to compute the spanning tree than it does to read the input graph. Reading the input graph alone, remember, would take linear time, O of m time. But moreover, graphs can have an enormous number of different spanning trees, an exponential number. So somehow these algorithms are homing in really quickly on a needle in a haystack. There's no way they have time to look at all of the spanning trees, and yet they find the one which is the best, which is optimal amongst all of them. How do these seemingly magical algorithms do it? Well, to discuss the details, let's start by formalizing the minimum spanning tree, or MST, problem on the next slide. So in the MST problem, this is a graph problem, so the main part of the input is a graph comprising vertices and edges. I do want to emphasize for the MST problem, we will be considering only undirected graphs. This is different, notice, than when we discussed shortest path problems in part 1 of the course. There we worked with directed graphs. There is an analogous problem to the minimum spanning tree problem for directed graphs. It's often called the optimal branching problem. And there are fast algorithms for it, but those algorithms are just slightly beyond the scope of this course, so we're not going to cover it. We're going to discuss only undirected graphs and minimum spanning trees for them. Now, whenever you talk about graph problems, you need to talk about how is the graph actually represented. So that's something we discussed at length in part 1. If you don't remember, I suggest going back and reviewing the video on graph representations. For the MST problem, we're going to assume that the graph is given as an adjacency list. That means we're given an array of vertices, an array of edges, and we have pointers wiring vertices to their incident edges and wiring edges back to their two endpoints. In addition to the graph itself, the input includes a cost for each of the edges. We're going to use the notation C sub e to denote the cost of an edge E. And in another contrast to our discussion of shortest path problems, we're actually not going to care if the edge costs are positive or negative. They can be any number whatsoever. So no prizes for guessing what the output's supposed to be. It's right there in the problem definition. The output is supposed to be a minimum cost spanning tree of the graph. But let's drill down and explain exactly what we mean by that. So first of all, what do we mean by the cost of a tree, or more generally the cost of a subgraph as a subset of the edges? Well, we're just going to be looking at summing up the edges in the tree that we output. Now the other question is, what do I mean by a tree that spans all vertices? So let me tell you exactly what this means. This subgraph T should have two properties. First of all, there cannot be any cycles. There cannot be any loops in this tree. And by spanning all vertices, what I mean is that this subgraph is what's called connected. That is, there's a path using the edges in T from any vertex of the graph to any other vertex. That's what it means to span all of the vertices. So for example, consider the following graph with 4 vertices and 5 edges. I've labeled each of the 5 edges with a cost, which in this case is just an integer between 1 and 5. So let's look at some example subgraphs. Let's start with the 3 edges, AB, BD, and CD. This subgraph satisfies properties 1 and 2. That is, it has no cycles, there's no loops, and it spans all of the vertices. If you start at any one of these 4 vertices, you can get to any of the other 4 vertices by using only red edges. So in that sense, this red subgraph is a spanning tree. However, it is not the minimum cost spanning tree. There is another spanning tree which is even cheaper, has a smaller sum of edge costs, namely the edges AC, AB, and BD. This also has no cycles. It is also connected, but the sum of the edge cost is only 7, smaller than the 8 of the previous spanning tree. In fact, this pink subgraph is the unique minimum spanning tree of this graph. There is a subgraph that has 3 edges, which has an even smaller sum of edge costs, namely the triangle AB, BD, and AD. But this light blue subgraph, this triangle, is not a spanning tree. In fact, it fails on both counts. It does obviously have a cycle. It has a loop. That's what it is by definition. It's also not connected. So there's no way to get from C, the vertex, to any of the other 3 vertices by following only light blue edges. It's disconnected, and so it fails property 1 as well. So the MST problem in general is you're given an undirected graph, like, for example, this 4-node 5-edge graph, or presumably something much larger in an interesting problem, and you're supposed to quickly identify the minimum spanning tree, like in this example, the pink subgraph. So what I want to do next is something you're probably quite accustomed to me doing by this point, is I want to make a couple of mild simplifying assumptions just among friends. So these assumptions are not important in the sense that all of the conclusions of these lectures will remain true, will remain valid, even if these assumptions are violated, but it'll make the lectures a little bit easier. It'll allow us to focus on the main points and not get distracted by less relevant details. So here are the two assumptions that we're going to make throughout all of the lectures on minimum spanning trees. The first assumption we're going to make is that the input graph G is itself connected. That is, G contains a path from any vertex to any other vertex. So why am I making this assumption? Well, if this assumption is violated, then the problem isn't even well defined. If the graph isn't connected, then certainly none of its subgraphs are connected, so it has no spanning trees, and it's not clear what we're trying to do. So those of you who still remember the stuff we covered in part 1, in particular graph search, should recognize that this condition is easy to check in a pre-processing step. Just run something like breadth first search or depth first search. Remember, we know how to implement those in linear time, and those will in particular tell you whether or not the input graph is connected. Now, another thing you might be wondering is, well, suppose it was disconnected. Then what? Should we really just sort of throw up our hands and give up? You can define a version of the minimum spanning tree problem, a more general one, called minimum spanning forest, where basically you want the minimum cost subgraph that spans as much stuff as possible. Essentially, it's responsible for computing a spanning tree within each of the connected components of the original graph. And using the algorithms I'll show you here, Prim's algorithm, Kruskal's algorithm, they're easily modified to solve the more general problem with disconnected input graphs as well. But again, for simplicity, among friends, let's just focus on the connected graph case. It contains all of the main ideas. Our second standing assumption throughout all of the minimum spanning tree lectures will be that in the input graph, the edge costs are distinct. So you're already used to this sort of no ties kinds of assumption from our foray into scheduling algorithms, and we're going to do something similar here. Now, again, this assumption is not important in the sense that the algorithms we cover, Prim's algorithm, Kruskal's algorithm, they remain correct even if the input has equal cost edges, irrespective of how ties are broken. So the algorithms are correct as widely as you would want. That said, I'm not going to actually prove for you that they're correct with ties. Remember, in our scheduling application, it was a little bit easier to give a proof of correctness without ties. I gave you that. And then optionally, there was a slightly more complicated argument that handled ties. You can do the same thing here, but I'm just not going to give it to you. I'll leave that for the keen viewer to work out for themselves. Okay, so it's time to discuss our first minimum spanning tree algorithm, namely Prim's algorithm. Definitely a candidate for the greatest hits compilation. And again, remember, even though it's called Prim's algorithm, it was actually discovered earlier by Yarnik. So how's it work? Well, before showing you any pseudocode, let's first illustrate it on an example. As we go through the example, I hope that the similarities to Dijkstra's shortest path algorithm will be evident. I'm going to work with the same example graph from the previous video with 4 vertices and 5 edges. The plan is to grow a tree one edge at a time, and we're going to keep growing this tree like a mold. We're going to start from just a seed vertex, and then we're going to suck up one new vertex with each iteration of the algorithm. So this is similar to Dijkstra's algorithm. In Dijkstra's algorithm, it was clear where we should grow the initial mold from because we were given a source vertex that they're trying to compute shortest paths out of. We have no source vertex in the minimum spanning tree problem, but it turns out we can just pick an arbitrary vertex to start. Doesn't matter which one, which is cool. So the plan is in each iteration we're going to add one edge and span one new vertex adjacent to the ones that we're already spanning. Now, as a greedy algorithm, Prim is simply going to select the cheapest edge that allows it to span one additional new vertex. Now, at the start of the algorithm here, we're not really spanning anything. We're sort of thinking of ourselves as growing from and currently spanning just the vertex in the upper right. So what are the edges by which we can span an adjacent vertex? Well, there's 2 edges. There's the top edge with cost 1, then we'll span in addition the upper left vertex, or there's the edge with cost 2 on the right. If we include that, we'll be able to span the vertex in the bottom right. So we're going to be greedy. We're just going to choose the cheaper edge, the edge of cost 1. Now the vertices that our tree thus far spans are the top 2 vertices. So in the next iteration, we want to add one more edge to span one additional new vertex. And now we see that there are 3 edges sticking out of what we're spanning thus far that will allow us to span a new edge. There's the edges that have cost 2, 3, and 4. The 2 and the 3 will allow us to span the vertex in the bottom right. If we pick the 4, that'll allow us to span the vertex in the bottom left. Again, we're going to be greedy, so of these 3 candidate edges, we're going to pick the cheapest one, which is the edge of cost 2. So now the mold that we've been growing, in effect, covers all of the vertices except for the one in the bottom left. So now in the final iteration, we want to include one more edge so that we span that final remaining vertex, the one in the bottom left. Note that there was this edge of cost 3 that we never added, but it got sucked up into the tree that we grew anyways. So we're going to go ahead and ignore that. Adding the 3 wouldn't allow us to span any more vertices. In fact, it would create a loop, which we don't want. So we're going to say, okay, we'll have the 2 edges that would allow us to span an extra vertex. There's the 4 and there's the 5. We're going to be greedy. We're going to pick the 4. And once we have the edges that cost 1 and 2 and 4, we have a spanning tree. There's no loops. There's a path from any vertex to any other vertex along pink edges. The cost is 7. You might recall from the previous video, this is indeed the minimum cost spanning tree of this graph. Of course, the fact that we have this simple procedure that works correctly in this toy example with just 4 vertices and 5 edges really means nothing. I mean, you shouldn't draw any immediate conclusions that this is a good algorithm in general, even though that is going to be the case. So let's next go and actually define the algorithm generally. So if you have a general graph, what does it mean to start somewhere and grow a mold, span one more vertex each iteration, always proceeding greedily until you're done? So let's spell out the pseudocode on the next slide. So here is Prim's minimum spanning tree algorithm. We're going to start with just 2 lines of initialization. We're going to maintain a set of vertices capital X. This is meant to be the vertices that we span so far. Again, we need some seed vertex from which to start the process. It doesn't matter which one we pick. We're going to get the same tree at the end no matter what. So just call it little s. That's an arbitrary vertex from which we start growth. The other thing we're maintaining is, of course, the tree. So that's initially going to be empty. We're going to add 1 edge to it in each iteration. An invariant that we're going to maintain throughout the algorithm is that the edges that currently reside in the set capital T span the vertices that currently reside in the set capital X. Then we're going to have our main while loop. This is the workhorse of the algorithm, and it's very similar to the one in Dijkstra's algorithm. Namely, each iteration is responsible for picking 1 edge, crossing the current frontier, advancing to include 1 new vertex. And again, it's going to be greedy. The criterion is going to be different, in fact, simpler than with Dijkstra's algorithm. Instead of looking at length, we're just going to say, what's the cheapest edge that allows us to span a new vertex? So the loop's going to keep going as long as there are vertices that we don't yet span. And then what we do is we search through the edges that allow us to span a new vertex. So which edges are those? Well, we want there to be 1 endpoint in the set capital X of vertices we already have our tree spanning. And we want the other endpoint to be non-redundant. So we want it to be outside of capital X. So if we have an edge that crosses the frontier in this sense, 1 endpoint in capital X, 1 endpoint outside, that's how we increase the number of spanned vertices by 1 in an iteration. So if E is the cheapest edge amongst all of those that cross the frontier with 1 endpoint on either side, that's the one we're going to add to our tree so far capital T in this iteration. Its endpoint that's not already in capital X, that's going to be the vertex that we add to X in this iteration. And again, the semantics of an iteration is that we're trying to increase the number of spanned vertices while paying as little as possible. That's the sense in which Prim's algorithm is a greedy algorithm. So as usual with a greedy algorithm, this seems natural enough, but it's not at all clear that it's correct, that it always computes a minimum spanning tree. In fact, if you think about it, it's not even obvious it actually computes a spanning tree at all, minimum or otherwise. But it is correct. Let's make that statement precise on the next slide. So the key claim is that Prim's algorithm is correct. Given any connected input graph, it is guaranteed to output a spanning tree with minimum possible cost. So before we delve into any details, let me just finish this video by telling you about the proof plan. We're going to prove this theorem in 2 parts. First, we're going to establish that it outputs some spanning tree, maybe not minimum. Even that's not trivial. Then we'll worry about arguing that the spanning tree output actually is one of minimum cost. Both parts of the proof are interesting. For part 1, to argue that we output some spanning tree, we're going to review some preliminaries about graphs and about cuts and about spanning trees in graphs. For part 2, to argue optimality, we're going to rely on a very neat property of spanning trees, minimum spanning trees, called the cut property. I'm happy to report that the work that we do here in both parts will bear further fruit later. We're going to reuse these ingredients when we prove the correctness of another MST algorithm, namely Kruskal's algorithm. For those of you who would much rather talk about running time than correctness, don't worry, your time will come. After we wrap up this correctness proof, I'll address how do you implement Prim's algorithm quickly. In particular, using heaps, we'll get the running time down to the near linear bound of O of m log n. Okay, so in this video, we're going to begin our discussion about why Prim's algorithm is correct, why it always, for every connected graph, outputs a minimum spanning tree of that graph. For this video, we're going to content ourselves with a much more modest goal. We're only going to prove, for now, that Prim's algorithm outputs a spanning tree. We're not going to make any claims yet about optimality. Even just this fact is non-trivial, and proving it will give us a good opportunity to get our hands dirty with some basic properties of graphs, and specifically graph cuts. Graduates of part 1 of this online class, of course, are already familiar with graph cuts. We studied them at length via Karger's randomized algorithm for computing the minimum cut of a graph. So the concept is the same here. Let me state it again to jog your memory. So a cut of a graph is simply a partition of its vertex set into two groups, and each of those two groups should be non-empty. So pictorially, we envision some of the vertices of G, this blob A, being in one group, and the rest of the vertices, this blob B, being in a different group. Now, what's up with the edges? How can they be distributed in this picture? Well, the two endpoints of an edge, there's three cases. Either both of the endpoints can be in the set A, so there's various edges internal to A. Similarly, an edge might have both of its endpoints inside of B. But we're going to be most interested in the third case, edges that have one point exactly in each of A and B. So these are edges that we say cross the cut AB. So hopefully the definition of a cut seems simple enough, but cuts, and in particular their relationship to edges, can be quite interesting and quite useful. So as shown here in the picture, of course, for a given cut there can be many edges crossing it. By the same token, for a given edge of a graph, in general there will be many cuts of the graph that edge crosses. So to understand this a little bit better, let's just review a simple property about cuts in the graph. Let me ask you how many there are. Specifically, for a graph that has n vertices, roughly how many cuts does it have? Roughly n squared, roughly 2 to the n, or roughly n to the n. Now, none of these four answers is exactly right, but one of the four is a lot closer to the exact expression than the other three, and I'm asking you, which of them is it? All right, so the correct answer is the third one, 2 to the n. A graph of n vertices has essentially 2 to the n cuts. So there's an exponential number of cuts. There's a lot of them. So why is this true? Well, in effect, you can imagine making a binary decision for each of the n vertices. They either go into A or they go into B. So n binary decisions results in 2 to the n different outcomes. Now, why is this slightly incorrect? Well, in fact, a cut has to have two non-empty sets. A is not allowed to be empty. B is not allowed to be empty, so that rules out two of the possibilities. So actually, strictly speaking, it's 2 to the n minus 1 different cuts of a graph. So what we're going to do next is we're going to state and prove 3 easy facts about cuts in graphs. Once we have these 3 easy facts, we will be able to prove the claim at the beginning of this video, namely that Prim's algorithm always outputs a spanning tree. The first of these 3 properties about cuts I'm going to call the empty cut lemma. The point of the empty cut lemma is to give us a characterization that is a new way of saying when a graph is connected. So in particular, I'm going to phrase it in terms of a graph being not connected. And the claim is that a graph is not connected if and only if we can find a cut of the graph that has no edges crossing it. So remember how we defined a graph being connected? That means for any 2 vertices in the graph, we can find a path in the graph from one vertex to the other. So what we're saying is that being not connected, that is, there existing a pair of vertices with no path between them, is equivalent to there being a cut with no crossing edges. So let's go ahead and prove this real quick. So as an if and only if statement, really this proof we have to do in two parts. First, we have to prove that assuming the first statement, we can derive the second. Then we have to show that assuming the second statement, we can derive the first. I think the easier direction is to assume the right-hand side and then derive the left-hand side. So let's start with that one. That is, consider a graph G so that there's a cut AB with no edges of G crossing this cut. The plan is to exhibit a pair of vertices that do not have a path between them, thereby certifying that the graph is not connected. So it's pretty easy to figure out which pair of vertices we should look at. Just take one vertex from each side of the cut, which has no crossing edges. So why is it that there's no path from U to V in the graph G? Well, the path from U to V would surely have to cross the cut, A comma B. But there's no edges available for crossing the cut. So therefore, this path from U to V cannot exist. So that completes the first part of the proof. We assume the right-hand side, we derive the left-hand side. Now we start all over again, but we assume the left-hand side, and we have to prove the right-hand side. So by the assumption that the graph is not connected, there has to exist a pair of vertices U and V that have no path between them. We are now responsible for exhibiting some cut A comma B such that no edges of the graph G cross it. So where are we going to get these sets capital A and capital B from? Well, here's the trick, which is going to make the proof go really nicely. We define the set of vertices capital A to be those reachable from U in the graph G. Another way to think about this is that capital A is simply U's connected component in the sense that we discussed in part 1 of the course. Now, because we want a cut and a cut is our partition, we better well put in the group capital B all of the vertices that are not in A. If you like, this is all of the connected components other than the one that contains U. Note that by definition, U is in capital A, certainly U is reachable from itself, and by assumption, V and U are not reachable from each other, so V is going to be in capital B. So neither of these sets is non-empty. This is indeed a bona fide cut of the graph G. All that remains is to notice that there are no crossing edges across this cut. And why is that true? Well, if there was an edge crossing the cut AB with one endpoint in A, one endpoint in B. Well, by definition, there are paths from U to everything else in A. So if there was any edge sticking out of A, that would give us a path to some vertex in B. But B, by definition, are vertices not reachable from capital A. So that's a contradiction. So again, the point is that if there were edges crossing this cut, then we can expand A and make it even bigger. So therefore, there aren't any edges crossing the cut. The cut is empty. That's what we needed to prove. Assuming the graph was disconnected, we have exhibited a cut, A comma B, with no crossing edges. So that wraps up of the first of our three facts, and in fact the most difficult of our three facts about cuts in graphs. And again, what does the empty cut lemma say? It gives us a new way of talking about whether or not a graph is connected. So it's disconnected if and only if there's an empty cut. It's connected if and only if there are no empty cuts. So that's the key point from this slide. Let's now knock off the other two facts we're going to need. The first one I'm going to call the double crossing lemma. In essence, what the double crossing lemma says is that if a cycle in a graph crosses a cut, then it has to cross it twice. It cannot cross it only once. So pictorially, we look at a cut of a graph. So there's the two vertex groups A and B. By hypothesis, there's some edge E with one endpoint in each side. And by assumption, this edge E participates in some cycle that we're calling capital C. And if you look at the picture, you realize that the claim in this lemma is obvious, that because the cycle has to loop back on itself, if it has an edge with one endpoint on either side, there has to be a path connecting the two dots, connecting those two endpoints back to each other, and that path has to cross back over this cut AB. Indeed, the double crossing lemma is a special case of a stronger statement, which is equally easy to see, which is that if you take any cut of a graph and you take any cycle, it starts and ends at the same point, then it has to cross this cut an even number of times. It might cross it 0 times, but it's not going to cross it once. It could cross it twice. It could cross it 4 times if it crisscrosses back and forth. It could cross it 6 times and so on. But if it crosses it strictly more than 0 times, then it has to cross it at least twice. That's the point of the double crossing lemma. So we'll use this in its own right later on, but I'm also, for the moment, interested in an easy corollary of the double crossing lemma. I will call this the lonely cut corollary. Let me tell you the point of the lonely cut corollary. In general, in these spanning tree algorithms, to ensure that we output a spanning tree, we have to, in particular, make sure we don't create any cycles. The point of this corollary is it's a tool to argue that we don't create cycles. So how can we be sure that an edge doesn't create cycles? Well, here's a way. Suppose there's a cut, so we're looking at an edge E. Suppose we can identify a cut A comma B so that edge E is the only cut crossing it. It's the lonely edge crossing this cut. Well, then by the double crossing lemma, there's no way this thing is in any cycle. If it were in a cycle and it crossed a cut, that cycle would have to cross it again, and this edge wouldn't be lonely. It would have company. So if you're lonely on a cut, it means you cannot be in a cycle. So now we've got all of our ducks lined up in a row, and we're ready to prove the first part of the correctness of prim. That is, we're ready to argue that prim's algorithm, given a connected graph, outputs a spanning tree. Again, for the moment, we're making no claims about optimality. That'll be in the next video. So we're going to make this argument in 3 steps. And for the first step, you might want to go look again at the pseudocode of prim's algorithm, just to remember what the notation was. The first step, we're just going to notice that the semantics of the algorithm are respected. So the algorithm maintains 2 different sets throughout its evolution. On the one hand, it maintains a set capital X, intended to be the vertices spanned so far. On the other hand, it maintains a set of edges, capital T, the edges that have been picked so far. And the intent was that the current edges, capital T, always spans the current vertex set, capital X. So the first thing is just to verify that that is in fact true. This I'm not going to prove formally. In my experience, students find this kind of obvious and the intuition is correct. If you want a rigorous proof, I would go ahead and fill in the details yourself. It's a straightforward induction with no nasty surprises. Now, we're trying to argue the output of this algorithm is a spanning tree. So let's recall what that means. What is it that we have to check? So there's 2 properties. First of all, there can't be any cycles. There can't be any loops. Second of all, it has to span all of the vertices. There has to be a path inside the tree edges from any vertex to any other vertex. So let's go ahead and prove both those things in reverse order. So the second step of the proof is going to be to argue that the algorithm outputs something which does span all of the vertices. So at the end of the day, we'll have a path from any vertex to any other vertex using only the edges in our chosen set, capital T. Now, by part 1 of this proof, all we need to prove is that the algorithm halts with capital X equal to capital V. Then we know that capital T spans everything in V. So how could that not happen? How could prim's algorithm somehow halt with the spanned vertices capital X not being all of capital V? We'll go back and check out the pseudocode and look at the main while loop. So every while loop, every iteration, we add 1 new vertex to capital X. What could go wrong? The only thing that could go wrong would be if it's some iteration, before we're spanning everything, when we scan the frontier around capital X, there aren't any edges. That's the only way we could fail to increase the vertices in capital X in a given iteration. But what would that mean? What would it mean if it's some iteration we couldn't find edges with one endpoint in capital X and the other endpoint in V minus X? Well, then we would have exhibited an empty cut. The cut X, comma, V minus X would have no crossing edges. And now we can use the empty cut lemma, which says if there's an empty cut, then the graph is disconnected. But by assumption, we're working with a connected input graph, so that can't happen. Okay, so the algorithm never gets stuck. We always increase capital X by 1 vertex because the original graph was connected. That means it halts with something spanning all of the vertices. For the final step, we need to argue that prim's algorithm never creates any cycles in the edges that it's choosing, capital T. So why are there no cycles? Well, what we're going to do is we're going to talk about each edge in turn that prim's algorithm adds and argue that whenever a new edge gets added, there's no way that edge creates any cycles in the set capital T. And to see why, take a snapshot of the algorithm at some given iteration. So there's some current set capital T, and there's some set vertices capital X that the edges in T span. V minus X are the vertices not yet spanned by T, and of course we can think of X comma V minus X as a cut of the graph. And at this moment in time, at this snapshot, the edges of capital T, they're all of one type. They all have both of their endpoints inside capital X. None of them have any endpoints inside v minus x. So in particular, none of the edges chosen thus far cross the cut x comma v minus x. That's by construction. They only span the vertices of x. Now, what type of edge is going to get added in this iteration? Well, Prim's algorithm searches only over edges that have one endpoint inside x and one endpoint outside. That is, it searches only over edges that cross the cut x v minus x. So the edge that gets added in this iteration is going to be a trailblazer for this cut. None of the edges yet chosen cross the cut, but the edge chosen in this iteration will definitely cross the cut. So at the moment edge E gets added to the tree capital T, it is going to be lonely across the cut x comma v minus x. So by the lonely cut corollary, as the sole member crossing this cut in capital T, it cannot possibly participate in any cycles. Remember, if it participated in a cycle in capital T, that cycle would have to cross this cut somewhere else. But there aren't any other edges crossing this cut. This is the only one. So that's why when we add a new edge, there's no way it can create any cycles. It's the sole member crossing this particular cut. All right, so now that we've completed our warm-up by showing that at the very least Prim's algorithm outputs a spanning tree, let's move on and actually show it outputs a minimum cost spanning tree. And to prove this theorem, we're going to have to tackle head-on the kind of crisis which you always face when designing a greedy algorithm. So in a greedy algorithm, you're making an irrevocable decision. Like in Prim's algorithm, we're including an edge in our tree and never revisiting it later. And how can you be sure that you're not making a mistake? How can you have a guarantee that the decision you're making seemingly myopically right now is actually a good decision, won't come back to bite you later? So it turns out for minimum spanning trees, there's a beautiful condition which tells you when you're guaranteed to not regret including an edge in a spanning tree. That guarantees when an edge has to belong to the minimum spanning tree. So that's called the cut property. It's the subject of the next slide. So this is a cool enough property that we're going to bestow it not just with all caps, but even with a box. Now, that's a pretty good property. So what does it state? Well, consider an edge of a graph, an edge that we are wondering if it's safe to include it in a tree so far. So here's the sufficient condition guaranteeing that you won't regret including this edge in the tree so far. The condition is stated in terms of a cut. So suppose you can find a cut A comma B with the property that amongst all edges in the graph G that happen to cross this cut, the edge E is the cheapest edge crossing this cut. Okay, so not only should our edge E cross this cut AB, but it should be the cheapest such edge. If this condition is met, then we definitely want to include the edge E in our solution. Indeed, the edge E has to be a member of any minimum spanning tree of the graph. So in this video, we're going to assume that the cut property is true. It is by no means obvious, definitely requires a proof. I'll give you the proof in a separate video. It's a little bit tricky. It's based on a subtle exchange argument. For this video, we're going to assume that it's true, however, and we just want to be clients of it. We want to figure out what it's good for. Now, I will soon show you that it actually implies correctness of Prim's algorithm, but just to get a feel for it, let's look at it in a much simpler graph. Let's just look at a 4 cycle, 4 nodes, 4 edges with edge costs 1, 2, 3, and 4. So let's look at a few cuts. So let's look at the cut where on one side of the cut I put the upper right vertex, and on the other side of the cut I put the other 3 vertices. So there are 2 edges crossing this cut, the edge that has cost 1, the edge that has cost 2. So the edge with cost 1 is the cheapest edge crossing this cut. So by the cut property, the edge of cost 1 has to be in the MST. Okay, so we looked at one cut, invoked the cut property. It told us an edge to stick in the MST. That was pretty cool. Let's look at another cut. Let's look at a cut where on one side we just put the bottom right vertex, and on the other side we put the other 3 vertices. Now this cut has 2 edges crossing it, the edges that have costs 2 and cost 3. The edge of cost 2 is the cheapest edge crossing this cut. So by the cut property, it has to be in the MST. So that's cool. So we know the 2's got to be there. Now let me point out something interesting that's happened, which is that it is not the case that this edge of cost 2 is the cheapest crossing. Every single cut that it crosses. Remember when we looked at cut number 1, this edge of cost 2 is actually the most expensive edge crossing that cut. But we found a different cut that is the cheapest crossing, and that's enough to justify the cut property. So in other words, all that's important for the cut property, I just got to find you one cut for which an edge is the cheapest. That's enough to conclude its presence in the MST. So similarly, we can look at a third cut, just consisting of the bottom left vertex and the other 3 vertices. And it's the same story. There are 2 edges crossing this cut, the edge of cost 3, the edge of cost 4. The edge of cost 3 is the cheapest edge crossing this cut, so we know it's got to be in the MST. And again, when we looked at cut number 2, it didn't tell us whether or not the edge of cost 3 is in the MST, but when we looked at cut number 3, that was enough to conclude that the edge of cost 3 has to be in the MST. So there we go. So we could use the cut property to construct an entire MST. On the other hand, there's no way to use the cut property to try to justify the edge of cost 4. Any cut that you pick for which the edge of cost 4 crosses, there'll be some other cheaper edge crossing it. So you can never use the cut property, as one would hope, to justify the inclusion of the edge of cost 4. And you better not be able to, because 4 is not in the MST. Now, a quick side note. Some of you might be wondering what I wrote in the conclusion of the cut property. I said the MST of G. So that would seem to indicate that the minimum spanning tree is unique. So that deserves a quick comment. So first of all, if the edge costs are not distinct, if you have ties between edges, then you can certainly have multiple different minimum spanning trees, and you have to state the cut property a little bit differently. But again, in the lectures, we're just going to assume distinct edge costs, so that's not a problem. And in fact, something that'll be a consequence of the next slide, we'll notice that the minimum spanning tree is unique with distinct edge costs. It's not obvious, but we'll prove it shortly. All right, so what I want to do to finish up this video is I want to assume that the cut property is true. And then from that, I want to argue that Prim's algorithm is correct. Always outputs an MST. The proof of the cut property is non-trivial and deserves its own video, which you can see separately. All right, so given the tools that we've developed, this argument's actually going to be quite short. So let's assume that the cut property is a true statement. And let's begin by building on the previous video. The previous video argued that Prim's algorithm outputs a spanning tree. It didn't argue it was a minimum one, but it argued that it's a spanning tree. It spans all the vertices and it has no cycles. Let's call the output of Prim's algorithm at the end of the algorithm T star. Now, stare at the cut property. Stare at the pseudocode of Prim's algorithm. What happens in each iteration of Prim's algorithm? Well, we have our set capital X. That's what we span so far. There's the rest of the stuff, v minus x, so that's a cut, x, v minus x. What does Prim choose to include next? Well, it brute force searches through the edges that cross this cut, and it adds the cheapest one of them. Well, that is right in the wheelhouse of the cut property. What does the cut property says? It says cheapest edges crossing cuts have to be in the MST. So they just fit together beautifully. Prim's algorithm explicitly picks an edge at each iteration, which satisfies the hypothesis of the cut property and therefore has to be in the MST. So remember, the conclusion of the cut property says edges so justified must belong to the MST. So if everything in T star is justified by the cut property, then everything in T star is in the MST. So T star is a subset of the MST. But T star, of course, as we've argued, is already a spanning tree in and of itself. And if you add more edges to T star, it's no longer going to be a spanning tree because you're going to pick up cycles, right? If you ever have something that's connected, there's a path from each pair of vertices, and you add a new edge, you're going to close a path, you're going to get a loop. Okay, so T star is already a spanning tree, and you can't have anything bigger and still be a spanning tree. So therefore, this has to be the minimum spanning tree. There cannot be anything else. So for this reason, T star must, in fact, be the minimum cost spanning tree of the graph. Since the input graph was arbitrary, assuming only it was connected, this completes, assuming the cut property, the proof of correctness of Prim's minimum spanning tree algorithm. Okay, so to this point, we've proven the correctness of Prim's minimum spanning tree algorithm under an assumption that the cut property is true. So the purpose of this video is to supply the missing proof to convince you of this cut property. Let me remind you where we stand. So through all the minimum spanning tree videos, we're assuming distinct edge costs. All of this can be extended to edge costs with ties. In particular, there's a version of the cut property when edges have ties. But we're just going to focus on the main ideas which were exposed already with distinct edge costs. So what does the cut property say? Well, it's meant to be a guarantee that an edge is safe to include in your tree so far. So it justifies an iteration of a greedy algorithm like Prim's algorithm. Specifically, consider an edge of a graph, and suppose you can find some cut, a comma b, so that amongst all the edges that are crossing this cut, e is the cheapest. So the edge e has to not just cross this cut, but it has to be cheaper than any edge that crosses this cut. If you can find just one cut of this form, so that e is the cheapest crossing edge, then it's definitely not a mistake to include e in your tree. You definitely want it. It is in the MST. So this is a non-trivial claim, and let's turn to the proof. At a high level, the plan will be not that different than the correctness of our greedy scheduling algorithm for minimizing the weighted sum of completion times. That is, we're going to use an exchange argument embedded in a proof by contradiction. And the type of contradiction will be of the same form. We'll start with an optimal solution. Suppose it doesn't have the property that we want it to have, and then we do an exchange to make it even better, contradicting the assumption that this solution is optimal. So specifically, if we argue by contradiction, we assume that the cut property is false. So let's just make sure we understand what that means. If the cut property is false, then there's a graph, and there's an edge, which actually is the cheapest crossing some cut, and yet that edge does not belong to the minimum cost spanning tree T star. The plan then is to exchange this missing edge E with some edge that is in the tree T star, which is more expensive, thereby getting a better spanning tree providing the contradiction. So this idea currently is a little bit hand-wavy. To really execute it, we have to specify which edge we're going to exchange the edge E with. That's a subtle point, and we'll develop it over the next couple of slides. So let's begin with a sort of first cut attempt at an exchange argument. So what's the world look like? Well, we have some cut of a graph. So we have one blob of vertices A, and then the rest of the vertices are in this blob B. This is the cut for which edge E is the cheapest. And by our assumption in this proof by contradiction, this cheapest edge E does not belong to the minimum spanning tree T star. That said, I claim, while T star may not have this edge E that crosses this cut, it better possess some other edge crossing this cut AB. So why is that true? Well, suppose the opposite. Suppose, in fact, T star did not have any edge crossing this cut AB. Well, then T star wouldn't be connected. It wouldn't span all the vertices, right? Remember our proof of the empty cut lemma. So if you had this empty cut, then there's no way to have a path from one side to the other side. Okay, but that's spanning trees have to have paths between each pair of vertices. So T star as a spanning tree has to contain something from this cut. By assumption, it doesn't contain edge E, so it contains some other edge, let's call it F, that crosses this cut. Now, of course, since E is the cheapest edge crossing this cut and F is some other edge crossing this cut, F is strictly more expensive than E. And at this point, we seem beautifully set up to execute the desired exchange argument. We have the edge that the optimal solution is missing. We have a candidate replacement, edge F, which is more expensive. So if we swap E and F, hopefully we get a new spanning tree that has strictly smaller cost, providing the desired contradiction. But things are more settled than they were with the scheduling application. The reason being is that schedules are simply sequences of jobs. So whenever you do an exchange of two jobs, it's clear you get another schedule. But spanning trees and graphs are subtle objects. And there's a question, if we take a spanning tree and we add one new edge and delete an edge, do we get another spanning tree of the graph or not? So the following quiz is going to ask you to think about that question carefully. Okay, so what we wish that the answer to this quiz was either answer A or answer C. So A would be the cleanest solution if it were always true that when you take a spanning tree, you take an edge outside of the spanning tree, and then you swap those two edges, you get a new spanning tree, then in fact our proof of the cut property would be done, right? We would just go on that previous slide, we would rip out the edge F from the spanning tree, we'd plug in the edge E, because E costs less than F, we'd get a spanning tree which was cheaper, and we'd be done. That would be our contradiction. Now if A wasn't true, we'd still be okay if C was true. If maybe not every swap yields a new spanning tree, but at least if you're swapping in the edge that's the cheapest crossing some cut, you get a spanning tree, then we'd also be golden, because in fact we only are trying to execute the swap, the exchange, using an edge which is the cheapest crossing some cut. If you go back to the previous slide, you'll see that was the only case we needed this fact to be true. Unfortunately, the correct answer to this quiz is D. You need not get a new spanning tree when you execute an exchange, even if you're plugging an edge which is the cheapest edge crossing some cut. So to understand this better, let me redraw the picture that we had on the previous slide. We had our cut AB, we had our cheapest edge E, which by assumption does not belong to the spanning tree T star, but we observed that T star has to contain at least one other edge crossing this cut because it's connected, and we called that F. And we're wondering if swapping E and F yields a new spanning tree or not. So to reason about this, let me just draw you what the rest of the spanning tree might look like. So in this picture, the spanning tree T star is given by the pink edges, and it's just this path of 5 edges on the 6 vertices. So what happens if we exchange E and F? Well, unfortunately, something bad happens. So we certainly get a new subgraph with 5 edges. After all, we just subtracted one and added one. But this new subgraph fails to be a spanning tree. It fails on both counts. First of all, it obviously has a cycle. It has a 4 cycle. And secondly, it's not connected. The upper right vertex is just totally disconnected from the rest of the vertices. So that's no good. That's an exchange which just does not produce a feasible solution, and it is not therefore useful in our proof by contradiction. Now, if we wanted to salvage some hope from this seemingly promising proof plan, we could take solace from the fact that there's not just one pink edge crossing the cut AB. F isn't the only one. There's actually this other one on the bottom. So let me call that E prime. Now, E being the cheapest edge crossing this cut overall, not only is E cheaper than F, it's cheaper than E prime also. So in some sense, with our motivation, we could care less which edge we exchange E from crossing this cut, because it's cheaper than all of them. And we see that at least in this example, swapping with E prime yields a good solution. It yields a feasible spanning tree. So what have we learned? What we've learned is that if we want to execute this exchange argument, we cannot blithely exchange with any edge of T star that crosses this cut. So the best case scenario, so what we're hoping is true, that we can always find some suitable edge, like E prime on the previous slide, so that when we execute this swap, we do in fact get a spanning tree. And I'm happy to report that we can indeed always do this. So what I need to explain is the procedure by which we exhibit this edge E prime, which doesn't get us into trouble when we swap, which still gives us a spanning tree after the swap. So let me explain the procedure by which we identify this magical edge E prime that we can swap with and still be a spanning tree. So here's the way to think about it. So we've got this spanning tree T star. We've got this edge, which is not yet in T star. Now, if we just plug E into T star, we're going to get a cycle. Why? Well, a spanning tree, remember, it has a path between each pair of vertices. So if this new edge, maybe its endpoints are U and V, T star already has a path between U and V. So when you plug in this new direct edge between U and V, it closes the loop. It gives you a cycle. So let's go ahead and call that cycle capital C. Let me also redraw the picture from the example on the previous slide so you can see what that cycle was in that special case. Now here's the pattern to notice about this cycle capital C, at least in this example, which is that the lousy edge, the edge F, for which when we swapped we didn't get a spanning tree, that's off of this cycle capital C. Whereas the good edge, the edge where we could do a swap and get a spanning tree, E prime, that's on this same cycle capital C. And that turns out to be true in general. So when you add the edge to the spanning tree and you get a new cycle, that cycle is what furnishes the candidates for swaps that will give you a new spanning tree. So the one lingering concern then, we have this cycle. All edges of this cycle are going to be good candidates for swapping. We just need to make sure that there is some edge that actually crosses this cut AB, like the edge E prime does in the picture. But here we're going to rely on a fact from a previous video, the double crossing lemma. Remember, the double crossing lemma says that if you have a cycle that crosses a cut at least once, then it has to cross it twice. Right? So if you cross once, then it has to loop back around, and then looping back around, it's going to cross it a second time. So this cycle capital C, we know it crosses the cut AB once. That's because it includes the original cheapest edge across the cut E. So it's got to cross it a second time. There's got to be an E prime in the cycle crossing the cut, and that's going to allow us to do the swap and get a new, cheaper spanning tree completing the contradiction. So just to spell things out in a little more detail, so what we do is we first say we use the double crossing lemma. So we have this purported minimum spanning tree T star. We have this cheap edge E not in it. We plug E into the spanning tree. We get the cycle. We call the cycle capital C. The cycle crosses the cut AB once through the edge E. It crosses it a second time by the double crossing lemma. We're going to call that edge E prime. Since E prime crosses the same cut as E, we know E prime is strictly more expensive than E. Remember, E is the cheapest one crossing this cut, AB. So now what we do is we execute the swap with this new edge E prime. So E prime's in T star. The cheapest edge E is not in T star, so we can swap them. We can rip E prime out, we can stick E in. Now something I want you to think through carefully at home, convince yourself this is true, is that because we plucked E prime from this cycle, this new tree, which I'm going to call capital T, this is a spanning tree, necessarily. You know, intuitively the reason being, you plug in E, you get this one cycle involving E, and then when you rip out E prime, you destroy the cycle. And because it's on a cycle, you don't destroy connectivity between any pair of vertices. There's still one path between each pair. But make sure you believe that, convince yourself at home. And once you're so convinced, you will also realize that we've finished the proof. We've executed our proof by contradiction. Since E was the cheapest edge crossing the cut, and E prime is another edge crossing the cut, E's got to be cheaper. Since T differs from T star only in the swap of these two edges, its aggregate cost has gone down, and that contradicts the purported optimality of T star, completing the proof of the cut property. So at this point, we understand Prim's algorithm, and we also know why it's correct. That is, why it always computes the minimum cost spanning tree of a graph. So in this video, we're going to turn to implementation issues and running time analysis. We'll begin by just analyzing the straightforward implementation of Prim's algorithm. That's already reasonable. It's polynomial running time, but not especially close to linear. Then we'll see how a suitable deployment of heaps, very much in the way that we did for Dijkstra's algorithm, leads to a blazingly fast near linear running time. So let's briefly review the pseudocode for Prim's algorithm. Recall that Prim grows a tree one edge at a time, spanning one new vertex in each iteration. So it maintains two sets, capital X, a set of vertices that have spanned so far, and capital T, these are the edges we've committed to thus far. They start out by just being some arbitrary vertex little s and the empty set, and in each iteration of this main while loop, we add one new edge to the tree, and whatever new vertex that edge spans, we add that to capital X. The algorithm terminates when we're spanning all of the vertices, and as we've seen, it halts not just with a spanning tree, but with a minimum cost spanning tree. So suppose we just literally implemented this algorithm as is. What would be the running time? Well, the initialization step takes only constant time, so let's ignore that. So then we just have this one loop. So let's just ask how many iterations does the loop take, and how much time is needed to execute each iteration. Well, the number of loop iterations is going to be exactly n minus 1. So where n is the number of vertices, x starts out with one vertex, it terminates when it has all n vertices. How much work do we need to implement each iteration? Well, essentially what each iteration is doing is a brute force search through the edges. It's looking for the edges that have one endpoint inside x and one endpoint outside, and amongst those it just remembers the cheapest. And it's easy to see that you can implement each iteration in O of m time, where m is the number of edges. For example, you can just, with each vertex, associate a Boolean variable that keeps track of whether or not it's in the set capital X. That way, when you see an edge, you know whether it's crossing the frontier or not in constant time. So putting it together, O of n iterations with O of m work for each gives us a running time of O of m times n. So this running time is already nothing to sneeze at. As we discussed, graphs can have an exponential number of spanning trees. So this algorithm is doing far less work than examining each of these spanning trees. It's homing in polynomial time to the minimum cost one. So that's pretty cool. But remember the mantra of any algorithm designer worth their salt. Confronted with a solution, you should always ask, but can we do better? And can we do better than running time O of m times n? We can, as we'll see in the rest of this video. The big idea for speeding up Prim's algorithm is exactly the big idea we used in part 1 to speed up Dijkstra's algorithm. Namely, we're going to deploy a suitable data structure. So what data structure seems like it might be a good idea for making Prim run faster? Well, what's happening in the main workhorse while loop of Prim's algorithm? Over and over again, we keep needing to do a minimum computation. Amongst all edges crossing the frontier, we need to find the cheapest one. So the question we should ask ourselves is, what kind of data structure would facilitate, would speed up repeated minimum computations? And if you recall from part 1, we have a data structure where that's exactly what its raison d'etre is, the heap. The meaning of life for a heap is to speed up repeated minimum computations, just like in Prim's algorithm. So let me just remind you briefly, what are the operations exported by a heap data structure and what is the running time? So first, recall that a heap contains a bunch of objects, and each of those objects should have some key value from some totally ordered set, like a number, like for example an edge cost. So what can you do with a heap? Well, the salient operations for our purposes today are, first of all, you can insert new stuff into the heap with their whatever their key value is. You can extract the object with the minimum key value, and you can also delete stuff from the middle of the heap. And all of these can be done in logarithmic time, logarithmic in the number of objects stored by the heap. So it's not going to be important for us today to know how heaps are implemented, what they look like under the hood. We're just going to be clients of them. We're just going to make use of these operations and the fact that they run in logarithmic time. But, just for those of you who are curious and or want to have your memory jogged, under the hood, heaps are implemented logically as a complete binary tree. They're actually laid out in an array, but you sort of think of them conceptually as being in a complete binary tree. And they satisfy what's called the heap property. And the heap property is to make sure that you know where the object with the minimum key value is. So the actual definition is every parent should have a key value which is less than that of its children. So as you go up the tree, the key value can only drop. And that means you know where the minimum's got to be. It's got to be at the root of this tree, or the front of the array. So that's great. That's how you locate the minimum so quickly in a heap. Now, what do you do when you want to extract the minimum? So you rip off the root of this tree, and now you have to rearrange the tree to restore the heap property. So you swap the last leaf up to where the root was. You bubble down as needed to restore the heap property. How do you insert? You put the new object as the new last leaf, and you bubble it up as needed to restore the heap property. To delete from the middle of a heap, you just sort of rip it out and then bubble things up or down as necessary to restore the heap property. Again, that's not supposed to, if you're hearing this for the first time, I know this is too fast. This is just to jog your memory for those of you who already learned this in part 1 of the course. For more details, you can go review the appropriate videos there. So now that I've reminded you about the salient properties of heaps, let's return to the question of how do we deploy them cleverly to speed up Prim's algorithm. So our intuition is that because we're doing repeated minimum computations in Prim's algorithm each time in this while loop to compute the cheapest edge crossing a frontier, that's sort of in the wheelhouse of heaps. So how should we use heaps? Well, the first idea, which is a pretty good idea, is to use the heap to store edges, right? Because our minimum computation should result in us choosing an edge. So when we extract min from a heap, we want it to hand us an edge on a silver platter. So it would seem, this would be your first thought, that the heap should store edges, and that the key value that you use should just be the edge cost, because you want to find the cheapest edge. So this is already a quite good idea. Using heaps in this manner will already definitely speed up Prim's algorithm relative to the naive implementation. And in fact, and I'll leave this as an exercise for you to work out, using heaps in this way results in an implementation that runs in time big O of m log n. What I'm going to show you instead is not that implementation, but an even cleverer implementation of Prim using heaps. We're not going to see a benefit in the asymptotic running time. This more sophisticated version will also give us m log n running time, but it would give you better constants, and it is the version you would want to implement in practice. So the one slightly tricky point in this exercise is, remember in Prim's algorithm, you don't just want the cheapest edge overall in each iteration. You want the cheapest edge which crosses the current cut, that has one endpoint in each of x and v minus x. And when you use heaps in this way, it might hand you on a silver platter an edge which is cheap, but isn't necessarily crossing the frontier. So you need some extra checks to ensure that you're always finding the minimum edge and that that edge crosses the frontier between x and v minus x. So I'll leave it to you to work out the details of this implementation in the privacy of your own home. What I want to spend our time together on instead is this somewhat more sophisticated, more practical way to use heaps. And for those of you who remember our fast implementation of Dijkstra, this will be very familiar to you. It'll be the same kinds of ideas that we used for Dijkstra. And the key point is instead of using the heap to store edges, we're going to use it to store vertices. So in a bit more detail, our plan is going to be to maintain two invariants. The first invariant is going to describe what the heap contains. The second invariant is going to be what the key values of those heap objects are. So as I said, we're now going to be storing vertices in the heap, not edges. Which vertices? Exactly the vertices that we don't yet span, the vertices of v minus x. The motivation here is that rather than getting on a silver platter the edge in which to add next to the tree, we're going to get from the heap on a silver platter the vertex that we're next going to add to capital X. So the second invariant tells us what the key values of these vertices in v minus x are supposed to be, and we're going to define them to be the cheapest cost of an edge incident to this vertex that crosses the current frontier. So I think a picture will make this definition clear. So consider some snapshot of Prim's algorithm at some iteration. We have our vertices x that we're already spanning. We have our vertices v minus x that we're not spanning. And remember, the elements of the heap by invariant 1 are exactly the vertices on the right-hand side, the vertices of v minus x. So we're trying to define the key value for some vertex in the heap. So some vertex v, which is on the right side, which is not in x. And so what we do is we look at the edges incident on this vertex v that go back to the left-hand side. So edges incident to v that are crossing the frontier. And there may be, of course, be many such edges. And the invariant we want to maintain is that the key value for this vertex v is the cheapest of all the incident edges crossing the frontier, or in this picture, the key should be equal to 2. There is the niggling issue of how do you define the key if there are no incident edges at all that are crossing the frontier. So maybe you have a vertex w which is buried deep inside of v minus x, and actually none of the incident edges go back to the left blob at all. So in that case, we just define the key to be plus infinity. So given this high-level approach to implementing Prim's algorithm using heaps, we now have a few things to think through. So first of all, we have to think about how to initialize the heap so that these invariants are satisfied at the beginning of Prim's algorithm. Second of all, we have to check that if these invariants are satisfied, then we can faithfully simulate each iteration of the while loop in Prim's algorithm, hopefully very quickly. And then third, we have to think about how do we make sure these invariants are maintained throughout the course of Prim's algorithm. So let's do those in turn. So the first thing is, how do we set up the heap at the beginning of Prim's algorithm in a pre-processing step so that both of these invariants are satisfied? Well, at the beginning, x consists just of this single arbitrary start vertex s. V minus x contains the other n minus 1 vertices. The key value of a vertex other than s at the beginning of Prim's algorithm is just the cheapest edge between that vertex and s, if there is one, or plus infinity otherwise. So the thing to think through, and make sure you believe this, is that first of all, with a single scan through the edges, so an O of m time, we can compute the key value for each vertex that needs to go in the heap, and then we just have to insert those n minus 1 vertices into the heap. So that's going to cost us O of m time for an edge scan. And then n log n for the inserts. In fact, for those of you that really know heaps very well, you might know about a heapify operation, which allows you to do a batch of n inserts in O of n time. Okay, so you can do this even faster in linear time, but we're not going to need that in this lecture. And also, I claim that this expression m plus n log n is bounded above by the expression m log n, at least in asymptotic notation. To see that, remember two things. First of all, we're assuming that the input graph is connected. Otherwise, there's no spanning trees, and it's not interesting to talk about minimum spanning trees. Second of all, in any connected graph, the number of edges m is at least n minus 1. So asymptotically, m is always at least as big as n, and it can be bigger. So you can always replace an n by an m and get a valid upper bound. So that's what we're doing here. The second issue we need to think through is how do we faithfully simulate each iteration of the while loop in Prim's algorithm given that these two invariants hold. So this issue is going to work out beautifully really by construction. We set up our heap and we set up our definition of keys so that extracting min from the heap in an iteration is a faithful simulation of the brute force search in the naive implementation of Prim's algorithm. So specifically, assuming that these two invariants hold, when we invoke extract min from this heap, what it provides to us on a silver platter is the next vertex, not yet an x, the next vertex that we should add to x in this iteration, and moreover, the cheapest edge incident to that vertex crossing the frontier is the one that we should be adding to the set T in this iteration. And the way to think about this fact is to think of us as essentially simulating the brute force search in the naive implementation using a 2-round knockout tournament. So in the straightforward implementation of Prim, the way we think of it is we just do a scan through all the edges crossing the frontier, and we remember the winner. We remember the smallest cost of them all. Here with a heap, we're doing it in 2 steps. So first of all, for each vertex on the right-hand side of the cut, for each vertex in v minus x, it locally remembers what is its best candidate. So what is the cheapest edge incident on that vertex crossing the frontier? So that's kind of round 1. So for an edge to be chosen as the winner, at the very least, it better be a local winner. It better be the cheapest edge crossing the cut that ends at this particular vertex on the right-hand side of the cut. So that's just in the definition of the key of each vertex. It encodes the value of the winner local to that vertex. And then this extract min is invoking the second round of this two-round elimination tournament. It's saying, well, amongst all the proposals from the first round, amongst all the crossing edges that are locally minimum, given its endpoint, which of them is the cheapest overall? And that's going to be the cheapest edge crossing this cut, the result of this extract min computation. So the third and final issue to think through is we need to make sure that we pay the piper, that we keep these invariants maintained. We know that if they're satisfied, then we have this great way of finding the best edge in each iteration. We just do an extract min. But how do we make sure that these invariants stay maintained throughout the algorithm? So to get a feel for the issues that arise in maintaining the invariant, specifically invariant number 2, and also just to make sure we're all on the same page with respect to this definition of the key value of the vertices in the heap, let's go through an example. So in this example, I've drawn in the picture a graph that has 6 vertices. In effect, we've already run 3 iterations of Prim's algorithm. So 4 of the 6 vertices are already in capital X. The remaining 2 vertices, V and W, are not yet in X. They're in V minus X. So for 5 of the edges, I've given them costs labeled in blue. For the other edges, it's not relevant for this question what their edge costs are, so you don't have to worry about it. So the question is the following. So given our semantics of how we define keys for vertices that are not in X, so in this case the vertices V and W, what are their current key values supposed to be? So those are the first 2 numbers I want you to tell me. What's the current key value of V and W? And then secondly, after we run one more iteration of Prim's algorithm, then what is the new key value of the vertex W supposed to be? So the correct answer is the 4th one. Let's see why. So first, let's remember the semantics of keys. What's the key supposed to be? It's supposed to be amongst all the edges that on the one hand are incident to the vertex, and on the other hand are crossing the cut. It's the cheapest cost of any of those edges. So for the node V, there's 4 incident edges with cost 1, 2, 4, and 5. The 1 is not crossing the cut. The 2, 4, and 5 are crossing the cut. The cheapest of those is 2. So that's why V's current key value is 2. For the node W, it has 2 incident edges, a 1 and a 10. The 1 is not crossing the cut. The 10 is. It's the only candidate crossing the cut, so its key value is 10. So the third part of the question says, what about when we execute one more iteration of Prim's algorithm? So what is Prim's algorithm going to do? Well, it's going to move the edge with the smallest key from the right-hand side to the left-hand side. V has a key value of 2, W has a key value of 10, so V is going to be the one that gets moved from the right-hand side to the left-hand side. So once that happens, we now have a new set, capital X, with a 5th vertex. V is now a member. So the new value of X is everything except for the vertex W. Now, the key point is that as we've changed the set capital X, the frontier has changed, the current cut has changed. So of course it's a different set of edges that are crossing this new cut. Some have disappeared and some are newly crossing it. The ones that have disappeared are the 2 and the 4 and the 5. Anything between the vertex that got moved, that was already spanning going to the left-hand side, has now been sucked inside of capital X. On the other hand, the edge VW, which was previously buried internal to V minus X, with one of its endpoints being pulled to the left-hand side, it is now crossing the cut. So why do we care? Well, the point is W's key value has now changed. It used to have only one incident edge crossing the cut, the edge of cost 10. Now with a new cut, it has 2 incident edges, both the 1 and the 10 are crossing the cut. The cheapest of those 2 edges is, of course, the edge of cost 1, and that now determines its key value. It's dropped from 10 to 1. So the takeaway from this quiz is that, well, on the one hand, having our heap set up to maintain these 2 invariants is great because a simple extract min allows us to implement the previous brute force search in Prim's algorithm. On the other hand, the extraction screws things up. So it messes up the semantics of our key values. We may need to recompute keys for the vertices. So in this next slide, I'm going to show you the piece of pseudocode you'd use to recompute keys in the light of an evolving frontier. Fortunately, restoring invariant number 2 after an extract min is not so painful. The reason being is that the damages done by an extract min are local. More specifically, let's think about what are the edges that might be crossing the cut now that were not previously crossing the cut. Well, the only vertex whose membership in these sets has changed is V, so they have to be edges that are incident to V. If the other endpoint was already in X, then we don't care. This edge has just been sucked into X. We never have to worry about it. But if the other endpoint, so of this edge incident to V, if the other endpoint W is not in X, then with V being pulled over to the left-hand side, now this edge spans the frontier when previously it did not. So the edges we care about are incident to V with the other endpoint outside of X. And so our plan is just the obvious one, which is for each dangerous vertex, each vertex incident to V where the other endpoint W is not an X, we just follow to the other endpoint W and we just recompute its key. And we just do that for all of the relevant W's. So the recomputation necessary is not difficult. There's basically 2 cases. So this other endpoint W, now it has one extra candidate edge crossing the cut, namely the one that's also incident on V, the vertex that just moved. So either this new edge VW is the cheapest local candidate for W, or it's not. And we just take the smaller of those 2 options. So that completes the high-level description of how you maintain invariants 1 and 2 throughout this heap-based implementation of Prim's algorithm. So each iteration you do an extract min. Following the extract min, you run this pseudocode to restore invariant number 2, and you're good to go for the next iteration. So for those of you who want not just a conceptual understanding of this implementation, but really want to get down to the nitty-gritty, want to dot all the I's and cross all the T's, a subtle point you might want to think through is how it is you implement this deletion from a heap. The issue is deletion from a heap is generally from a given position. And so here I'm only talking about deleting a vertex from a heap. That doesn't quite type check. Really what you want to say is delete the vertex at position I from a heap. So really pulling this off, the natural way to do it is have some additional bookkeeping to remember which vertex is at which position in the heap. So again, for the detail-oriented amongst you, that's something to think through, but this is the complete conceptual description of the algorithm. Let's now move on to the final running time analysis. So the first claim is that the non-trivial work of this algorithm all takes place via heap operations. That is, it suffices to just count the number of heap operations, each of which we know is done in logarithmic time. Okay, so let's count up all of the heap operations. One thing we already talked about, but I'll mention it here again for completeness, is we do a bunch of inserts just to initialize the heap in a pre-processing step. So after we initialize, we move on to the main while loop. Remember, there's exactly n-1 iterations of that while loop. And in each one, we extract min exactly once. So these were the easy steps. What you should be concerned about are the heap operations, the deletions and reinsertions that are triggered by needing to decrease the key of vertices that are not in X. Indeed, in a single iteration of Prim's algorithm, in a single move of a vertex inside of capital X, can necessitate a large number of heap operations. So it's important to count these operations in the right way, namely in an edge-centric manner. And the claim is that a single edge of the graph is only going to trigger a single decrease key pair of operations, a single insertion-deletion combo. We can even pinpoint the moment in time at which we're going to have this deletion and reinsertion. It's going to be when the first of the endpoints, so either V or W, the first iteration at which one of those gets sucked into the left-hand side capital X, that's going to trigger the insert-delete potentially for the other endpoint. When the second endpoint gets sucked into the left-hand side, you don't care because the other endpoint has already been taken out of the heap. There's no need to maintain its key. So that means that the number of heap operations is most twice the number of vertices, plus at most twice the number of edges. We're again going to use this fact that the input graph is connected, and therefore the number of edges is asymptotically at least the number of vertices. So we can say that the number of heap operations is at most a constant factor times the number of edges m. As we've discussed, every heap operation runs in time logarithmic in the number of objects in the heap, so that's going to be log n in this case. So we get an overall running time of O of m times log n. So this is now a quite impressive running time for the really quite non-trivial minimum cost spanning tree problem. Of course, we'd love to do even better. If we could shave off the log n factor and be linear in the input, that would be even more awesome. But we got to feel pretty good about this running time, right? This is only a log n factor slower than what it takes to read the input. This is the same kind of running time we're getting for sorting. So this actually puts the minimum spanning tree problem into the class of 4 free primitives. If you have a graph and it fits in the main memory of your computer, this algorithm is so fast, maybe you don't even know why you care about the minimum spanning tree of a graph. Why not do it? It's basically costless. That's how fast this algorithm is. So in these next few videos, we're going to continue our discussion of the minimum cost spanning tree problem, and I'm going to focus on a second good algorithm, good greedy algorithm for the problem, namely Kruskall's algorithm. Now, we already have an excellent algorithm for computing the minimum cost spanning tree in Prim's algorithm, so you might wonder, why bother spending the time learning a second one? Well, let me give you 3 reasons. So the first reason is this is just it's a cool algorithm. It's definitely a candidate for the greatest hits. It's something I think you should know. It's competitive with Prim's algorithm both in theory and practice. So it's another great greedy solution for the minimum cost spanning tree problem. The second reason is it'll give us an opportunity to learn a new data structure, one we haven't discussed yet in this course. It's called the union find data structure. So in exactly the same way, or in a similar way to how we used heaps to get a super fast implementation of Prim's algorithm, we'll use a union find data structure to get a super fast implementation of Kruskall's algorithm. So that'll be a fun topic just in its own right. The third reason is there's some very cool connections between Kruskall's algorithm and certain types of clustering algorithms. So that's a nice application that I'll spend some time talking about. I'll discuss how natural greedy algorithms in a clustering context are best understood as variants of Kruskall's minimum spanning tree algorithm. So let me just briefly review some of the things I expect you to remember about the minimum cost spanning tree problem. So the input, of course, is an undirected graph G, and each edge has a cost. And what we're trying to output, the responsibility of the algorithm, is a spanning tree that is a subgraph which has no cycles and is connected. There's a path between each pair of vertices, and amongst all potentially exponentially many spanning trees, the algorithm is supposed to output the one with the smallest cost, smallest sum of edge costs. So let me reiterate the standing assumptions that we've got through the minimum spanning tree lectures. So first of all, I'm assuming the input graph is connected. That's obviously necessary for it to have any spanning trees. That said, Kruskall's algorithm actually extends in a really just easy, elegant way to the case where G is disconnected, but I'm not going to talk about that here. Secondly, remember we're going to assume that all of the edge costs are distinct. That is, there are no ties. Now, don't worry, Kruskall's algorithm is just as correct if there are ties amongst the edge costs. I'm just not going to give you a proof that covers that case, but don't worry, a proof does indeed exist. Finally, of the various machinery that we developed to prove the correctness of Prim's algorithm, perhaps the most important and most subtle point was what's called the cut property. So this is a condition which guarantees you're not making a mistake in a greedy algorithm. It guarantees that a given edge is indeed in the minimum spanning tree. And remember, the cut property says if you have an edge of a graph and you can find just a single cut for which this edge is the cheapest one crossing it. Okay, so the edge E crosses this cut, and every other edge that crosses it is more expensive. That certifies the presence of this edge in the minimum spanning tree. It guarantees that it's a safe edge to include. So we'll definitely be using that again in Kruskal's algorithm when we prove it's correct. So as with Prim's algorithm, before I hit you with the pseudocode, let me just show you how the algorithm works in an example. I think you'll find it very natural. So let's look at the following graph with 5 vertices. So the graph has 7 edges, and I've annotated them with their edge costs in blue. So here's the big difference in philosophy between Prim's algorithm and Kruskal's algorithm. In Prim's algorithm, you insisted on growing like a mold from a starting point, always maintaining connectivity and spanning one new vertex in each iteration. Kruskal is going to just throw out the desire to have a connected subgraph at each step of the iteration. Kruskal's algorithm will be totally content to grow a tree in parallel with lots of simultaneous little pieces, only having them coalesce at the very end of the algorithm. So in Prim's algorithm, while we were only allowed to pick the cheapest edge subject to this constraint of spanning some new vertex, in Kruskal's algorithm we're just going to pick the cheapest edge that we haven't looked at yet. Now there is an issue, of course. We want to construct a spanning tree at the ends. We certainly don't want to create any cycles, so we'll skip over edges that would create cycles. But other than that constraint, we'll just look at the cheapest edge next in Kruskal's algorithm and pick it if there's no cycles. So let's look at this 5 vertex example. Again, there's no starting point. We're just going to look at the cheapest edge overall, so that's obviously this unit cost edge. And we're going to include that in our tree, right? Why not? Why not pick the cheapest edge? It's a greedy algorithm. So what do we do next? Well, now we have this edge of cost 2. That looks good, so let's go ahead and pick that one. Cool. Notice these 2 edges are totally disjoint. Okay, so we are not maintaining a connectivity of our subgraph at each iteration of Kruskal's algorithm. Now, it just so happens that when we look at the next edge, the edge of cost 3, we will fuse together the 2 disjoint pieces that we had previously. Now we happen to have one connected piece. Now, here's where it gets interesting. When we look at the next edge, the edge of cost 4, we notice that we're not allowed to pick the edge of cost 4. Why? Well, that would create a triangle with the edges of cost 2 and 3, and that, of course, is a no-no. We want a spanning tree at the end of the day, so we can't have any cycles. So we skip over the 4 because we have no choice. We can't pick it. We move on to the 5, and the 5 is fine. So when we pick the edge of cost 5, there's no cycles, we go ahead and include it, and now we have a spanning tree and we stop. Or if you prefer, you could think of it that we do consider the edge of cost 6. That would create a triangle with the edges of cost 3 and 5, so we skip the 6. And then for completeness, we think about considering the 7, but that would form a triangle with the edges of cost 1 and 5, so we skip that. So after this single scan through the edges in sorted order, we find ourselves with these 4 pinked edges. In this case, it's a spanning tree, and as we'll see, not just in this graph, but in every graph, it's actually the minimum cost spanning tree. So with the intuition hopefully solidly in place, I don't think the following pseudocode will surprise you. We want to get away with a single scan through the edges in sorted order. So obviously in the pre-processing step, we want to take the unsorted array of edges and sort them by edge cost. To keep the notation in the pseudocode simple, let me just, for the purposes of the algorithm description only, rename the edges 1, 2, 3, 4, all the way up to m, conforming to this sorted order. Right? So the algorithm is just going to scan through the edges in this newly found sorted order. So we're going to call the tree in progress capital T, like we did in Prim's algorithm. And now we're just going to zip through the edges once in sorted order. And we take an edge unless it's obviously a bad idea. And here a bad idea means it creates a cycle. That's a no-no. But as long as there's no cycle, we go ahead and include the edge. And that's it. After you finish up the for loop, you just return the tree capital T. It's easy to imagine various optimizations that you could do. So for example, once you've added enough edges to have a spanning tree, so n-1 edges, where n is the number of vertices, you can go ahead and abort this for loop and terminate the algorithm. But let's just keep things simple and analyze this 3-line version of Kruskal's algorithm in this lecture. So just like in our discussion of Prim's algorithm, what I want to do is first just focus on why is Kruskal's algorithm correct. Why does it output a spanning tree at all? And then the spanning tree that it outputs, why on earth should it have the minimum cost amongst all spanning trees? Then once we're convinced of correctness, we'll move on to a naive running time implementation, and then finally a fast implementation using suitable data structures. So in this algorithm, we'll prove the correctness of Kruskal's minimum cost spanning tree algorithm. So to prove this correctness theorem, let's fix an arbitrary connected input graph G, and let's let T star denote the output of Kruskal's algorithm when we invoke it on this input graph. So just like with our high-level proof plan for Prim's algorithm, we're going to proceed in 3 steps. We're first going to just establish the more modest goal that Kruskal's algorithm outputs a spanning tree. We're not going to make any initial claims about optimality. So those are the first 2 steps, one to argue there's no cycles, one to argue that the output's connected. And then in the 3rd step, relying on the cut property, we'll say it's not just a spanning tree, it's actually the minimum cost spanning tree. For this proof, I am going to assume you're familiar with the machinery we developed to prove that Prim's algorithm is correct. So the first step of the proof is going to be very easy. So one important property of a spanning tree is that there's no cycles, and it's quite obvious looking at the pseudocode of Kruskal's algorithm that it's not going to produce any cycles. Every edge that creates a cycle is explicitly excluded from the output. What's a little less obvious is that as long as the input graph is connected, then Kruskal's algorithm will output a connected subgraph, and therefore a spanning tree. So to argue the output's connected, we're going to have 2 subparts of the proof. The first thing I want you to do is recall what we call the empty cut lemma. So this was a way of talking about when a graph is disconnected, or equivalently when a graph is connected. And you'll recall that a graph is connected if and only if, for every cut, there's at least one crossing edge. So to prove this second step of this proof, that T star is connected, we just have to prove that for every single cut, it has at least one edge crossing that cut. So that's what we're going to show. To get started, let's fix an arbitrary cut A comma B. Using the assumption that the input graph is connected, it certainly contains at least one edge that crosses this cut. The question is whether or not T star contains a crossing edge, but certainly the original graph G contains a crossing edge. So here's the key point of the argument. Kruskal's algorithm, by definition, it makes a single scan through all of the edges. That is, it considers every edge of the original input graph exactly once. So what I want you to do is I want you to think about this cut AB, which has at least one edge of G crossing, and I want you to fast forward Kruskal's algorithm until the moment that it first considers an edge crossing this cut AB. The key claim is that this first edge seen by Kruskal's algorithm is definitely going to be included in the final output T star. So why is this true? Well, let me remind you of the lonely cut corollary. The lonely cut corollary says that if an edge is the sole edge crossing a cut, if it's lonely in a cut, then it cannot participate in any cycle, right? If it was in a cycle, that cycle would loop back around and cross the cut a second time. Now, what does that have to do with the picture here? Well, if this is the first edge that Kruskal sees crossing this cut, then certainly the tree so far T star contains nothing crossing this cut, right? It hasn't even seen anything crossing this cut yet. So at the moment it encounters the first edge, there's no way including that first edge will create a cycle because that first edge is going to be lonely in this cut AB. So again, summarizing, the first edge crossing a cut is guaranteed to be chosen by Kruskal's algorithm. It cannot create a cycle. That's why there's at least one edge of Kruskal's output crossing this particular cut AB. Since AB was arbitrary, all edges, all cuts have some edge of T star crossing them. That's why T star is connected. So this completes the part of the proof where we argue that Kruskal's algorithm outputs a spanning tree. Now we have to move on and argue that it's actually a minimum cost spanning tree. We're going to argue this in the same way as we did for Prim's algorithm. We're going to argue that every edge ever selected by Kruskal's algorithm is justified by the cut property, satisfies the hypotheses of the cut property. Recall from our correctness proof for Prim's algorithm, this is enough to argue correctness, that the output is a minimum cost spanning tree. Right? An edge justified by the cut property is not a mistake. It's got to belong to the minimum cost spanning tree. If you have an algorithm, it outputs a spanning tree, and it never made a mistake, that's got to be the minimum cost spanning tree. And that's going to be the case for Kruskal. Now, this statement was easy to prove for Prim's algorithm, and that's because the definition of Prim's algorithm, it selects edges based on being the cheapest in some cut. So it's tailor-made for the application of the cut property. Not so for Kruskal's algorithm. If you look at the pseudocode, nowhere does the pseudocode discuss picking cheap edges across cuts. So we have to show that Kruskal's algorithm, in effect, is inadvertently at every edge picking the cheapest edge crossing some cut. And we actually have to exhibit what that cut is in our proof of correctness. So that's what we have to do here. So to argue that, let's just sort of freeze Kruskal's algorithm at some arbitrary iteration where it adds a new edge. We need to show that this edge is justified by the cut property. So maybe this edge has endpoints u and v, and let's let capital T denote the current value of the edges selected by the algorithm so far. So let's think about what the state of the world looks like at a sort of intermediate iteration of Kruskal's algorithm. So Kruskal's algorithm maintains the invariant that there's no cycles, but remember it doesn't maintain any invariant of the current edges forming a connected set. So in general, in an intermediate iteration of Kruskal's algorithm, you got a bunch of pieces, a bunch of little mini trees floating around the graph. Connected components, if you like, with respect to the current edge set, capital T. And there can be some, isolated vertices floating around as well. What more can we say? Well, if the current edge has endpoints u and v, and Kruskal is deciding to add this edge uv to the current set capital T, we certainly know that capital T has no path between u and v. Right? If it did have a path, then this new edge would create a cycle, and Kruskal would skip the edge. So since it isn't skipping the edge, u and v are currently in different pieces. They're in different connected components with respect to the current edge set. Now remember, ultimately, if we're going to apply the cut property, we have to somehow exhibit some cut from somewhere, justifying this particular edge. So here's where we get the cut from, and it's going to be a very similar argument to when we proved the empty cut lemma, characterizing disconnectedness in terms of empty cuts. We're going to say, look, with respect to the tree edges we have so far, with respect to the green edges, there's no path from u to v. That means we can find a cut such that u's on one side, v's on the other side, and there's no edges crossing the cut. So here's the cool part of the proof, and this is also the part where we actually use the fact that Kruskal is a greedy algorithm, that it considers the edges from cheapest to most expensive. Notice we haven't actually used that fact up to this point, and we better use that fact. So the claim is that not only is this edge we're adding uv, not only does it cross this cut AB, but actually it's the cheapest edge crossing the cut. Nothing from the original input graph G that crosses it can be cheaper. So why is that true? Well, let's remember how we wrapped up the previous slide when we were arguing that the output of Kruskal's algorithm is connected. What did we argue? We said, well, fix any cut you like, any cut of the graph, and freeze Kruskal's algorithm the very first time it considers some edge crossing that cut. We noticed that Kruskal's algorithm is guaranteed to include that first edge crossing the cut in its final solution. There's no way that that first edge considered can create a cycle with respect to the edges already chosen. So it's not going to trigger the exclusion criterion in Kruskal's algorithm, and that edge is going to get picked. So what's the significance about being the first edge crossing a cut? Well, because of the greedy criterion, because Kruskal considers edges from cheapest to most expensive, the first edge it encounters crossing a cut is also necessarily the cheapest edge that's crossing the cut. So here's how we weave these different strands together to complete the correctness proof. All right, so let's remember where we are. We're focusing on a single iteration of Kruskal's algorithm. It's about to add this edge u comma v to the edges capital T that it's chosen in the past. We've exhibited a cut a comma b with a property that no previously chosen edges, no edges of capital T, cross this cut. Edge uv is going to be the first chosen edge crossing this cut. We just argued that Kruskal's algorithm is guaranteed to pick the first edge crossing a cut. So by virtue of there not yet being any chosen edges crossing the cut AB, it must be the case that this current edge UV is the first one that's ever been seen by Kruskal's algorithm that crosses this cut AB. Now, in being the first edge it's ever seen crossing this cut, it must also be the cheapest edge of the input graph that crosses this cut. That is the hypothesis of the cut property. That is why this edge uv in this current arbitrary iteration is justified by the cut property. So now we understand why Kruskal's algorithm is correct, why it always computes a minimum cost spanning tree. In this video, we'll turn our attention to implementation issues. We'll begin with a straightforward implementation of Kruskal's algorithm. That'll give us a polynomial runtime bound, which is good, but we'd like to do better. So then we'll show how deploying a suitable data structure, something you haven't seen before, the union find data structure, allows us to speed up Kruskal's algorithm to be competitive with Prim's algorithm. That is, we'll get a near linear running time bound of O of m log n. So let's just briefly review the very elegant pseudocode for Kruskal's algorithm. So it's a greedy algorithm. It considers the cheapest edges first, all the way up to the most expensive. So we begin with a sorting pre-processing step to put the edges in sorted order. For notational convenience, let's just rename the edges so that 1 is the cheapest edge and all the way up to m being the most expensive edge. We then have our single linear scan in this for loop, and we just grab edges whenever we can. Okay, so we maintain this evolving set capital T, which at the end of the algorithm will be our spanning tree. Now, what forces us to exclude an edge from this set capital T? Well, if it creates a cycle with the edges we've already chosen, obviously that's a no-go. We can't have cycles in our final output. But as long as we don't have a cycle from including an edge, we go ahead and optimistically include it. And as we've seen, this is a correct algorithm. It always outputs the minimum cost spanning tree. So, what would be the running time of this algorithm if we just straightforwardly implement the pseudocode on this slide? Well, so let's just consider the algorithm step by step. In the first step, we sort the edges. So that's going to take m log n time. Now, don't forget, whenever we're speaking about graphs, we have the convention that m denotes the number of edges and n denotes the number of vertices. So you might justifiably wonder why I wrote m log n for the running time of the sorting step instead of m log m, since after all what it is we're sorting are the edges and there's m of them. Well, what I'm using here is that in this context we can switch log n and log m interchangeably with each other inside of big O notation. Why is that true? Well, recall when we first discussed graphs in part 1, we noticed that there can't be too many edges. So the number of edges m is at most quadratic in the number of vertices. It's the most big O of n squared. So if m is at most n squared, then log m is at most 2 log n, and the 2 is suppressed in the big O notation. So log m and log n are interchangeable in this context. Notice that for the minimum cost spanning tree problem, you may as well assume that there's no parallel edges. You may as well assume that the graphs are simple. If you have a bunch of parallel edges between a given pair of vertices, you can just throw out all but the cheapest one. That's the only one you'll ever need. So moving on to the main loop, pretty obvious how many iterations we have there. We have m iterations. So all we need to figure out is how much work do we have to do in each iteration. So what is it that each iteration needs to accomplish? It needs to check whether or not adding the current edge to the edges we've already chosen creates a cycle or not. So I claim that can be done in time linear in the number of vertices. That is, it can be done in big O of n time. So how do we accomplish this? Well, we need 2 quick observations. First of all, and this is something we've seen in arguments in previous videos, checking whether or not this new edge is going to create a cycle. Say the edge has endpoints u and v. Checking for a cycle boils down to checking whether or not there's already a path between the endpoints u and v and the edges capital T that we've chosen so far. If there is a uv path already, adding this edge will close the loop and create a cycle. If there currently is no uv path, then adding this edge will not create a cycle. So the second observation is, well, how do we check if there's a path from u to v in the edges we've already chosen? Well, we know how to do that just using graph search. So you can use breadth first search, you can use depth first search, it doesn't matter. You just start at the vertex u and you see if you ever reach v or not. If you reach it, there's a path. If you don't reach it, there's not a path. Breadth first search, depth first search, whatever, it takes time linear in the graph that you're searching. And since we only need to search through the edges that are in capital T, and there's going to be at most n minus 1 of them, linear time in this context means O of n, O of the number of vertices, because that also bounds the number of edges that might be in capital T, the edges that we're searching for a path in. So adding up all of this work, what do we have? We have the sorting pre-processing step. That takes time big O of m log n. Then we have these m iterations of the for loop, each of which takes O of n time. So that gives us an m times n factor. The latter term dominates, so the overall running time is big O of m times n. So this coincidentally is the same running time we got from the straightforward implementation of Prim's algorithm, and I'll make the same comments here. This is a reasonable running time. It's polynomial in the input size. It's way better than checking all exponentially many spanning trees that the graph might have, but we certainly would like to do better. We'd certainly love to have an implementation of Kruskal's algorithm that gets us to a near linear running time bound. And that's the plan. How are we going to do it? Well, really the work that we're doing here over and over again, which is kind of a bummer, is these cycle checks. In every single iteration, we're spending time linear in the number of vertices to check for a cycle. And the question is, can we speed that up? And the union find data structure will actually, believe it or not, allow us to check for a cycle in constant time. So if we actually had a data structure that could implement constant time cycle checks, then we'd have to spend only constant time for each iteration of this while loop. So the loop overall would take only linear time in the number of edges, O of m edges. If we got that, then believe it or not, the sorting pre-processing step would become the bottleneck in the running time of Kruskal's algorithm. Our running time would drop from m times n down to near linear, down to O of m log n. So let me now tell you a little bit about this magical data structure that's going to give us constant time cycle checks. I'm just going to give you the high-level picture and how it connects to Kruskal's algorithm on this slide. We'll look at the details of the data structure in the next video. I also want to warn you that I'm not going to discuss in this pair of videos the state-of-the-art for union-find data structures. I'm going to give you a fairly primitive version, but that is nevertheless sufficient to give us our desired m log n running time of Kruskal's algorithm. So if you're interested, there is some optional material about different implementations of union-find that use some super cool ideas like union by rank and path compression that give you different and in some senses better operation times. But the quick and dirty version of union-find that I'm going to discuss here is sufficient for our present needs. So the raison d'etre of a union-find data structure is to maintain a partition of a set of objects. So in this picture, the overall rectangle is meant to denote a set of objects, and then C1, C2, C3, and C4 are disjoint subsets that together form the union of the entire set. So that's what I mean by a partition of a group of objects. We're not going to ask too much of this data structure. We're only going to ask it to support two operations. No prizes to guess what those two operations are called. So the find operation, we give it an object from this universe, and we ask the data structure to return to us the name of the group to which that object belongs. So for example, if we handed it something in the middle of this rectangle, an object, we'd expect it to return to us the name C3. The union operation, by contrast, takes as input the names of two groups, and what we want the data structure to do is to fuse those two groups together. That is, the objects in the first group and the objects in the second group should all coalesce and be now in one sole group. So why might such a data structure be useful for speeding up Kruskal's algorithm? To see the connection, think of Kruskal's algorithm as working conceptually in the following way. So initially, when the algorithm starts and the set capital T is empty, each of the vertices is by its own. It's on its own isolated component. And then each time Kruskal adds a new edge to the set capital T, what that does is it takes two current connected components and fuses them into a single connected component. So for example, toward the end of Kruskal's algorithm, maybe it's included enough edges that now the tree capital T that is constructed so far has only 4 different connected components. And maybe it's about to add a new edge, u comma v, where of course u and v should be in different connected components with respect to the edges chosen so far. So this new edge addition at this iteration of Kruskal is going to fuse the connected components of u and v into a single one. So that corresponds to taking the union of the groups to which u and v respectively belong. So to be a little more precise about it, so what are going to be the objects contained by the union-find data structure in Kruskal's algorithm? Well, they're going to correspond to vertices. It's the vertices coalescing that we want to keep track of. So what are going to be the groups in the partition that we maintain? They're just going to correspond to connected components with respect to the edges that Kruskal's algorithm has already committed to. And with these semantics, it's clear that every time Kruskal adds a new edge to its set capital T, we have to invoke the union operation to fuse two connected components into one. So let me now introduce you to the union-find data structure. Let's not lose sight of our goal. Our goal is to be able to check for cycles in Kruskal's algorithm in constant time. So the first and most basic idea behind this union-find data structure implementation is we're going to maintain a linked structure for each group, that is, for each connected component with respect to the edges Kruskal has chosen thus far. By a linked structure, I just mean each vertex of the graph is going to have an extra pointer field. In addition, with each group, with each connected component, we're going to designate one vertex, and we don't care which one, just some vertex from this connected component, as the leader vertex of that component. All right, so what is the point of these extra pointers at each vertex, and what is the point of having these leaders? Well, a key invariant that we're going to maintain is that a given vertex with its extra pointer points to the leader vertex of its connected component. So for example, maybe we have two different connected components with three vertices each, one containing the vertices u, v, and w, another containing the vertices x, y, and z. Any of these three vertices could be the leader of each of these two components. So perhaps u happens to be the leader vertex of the first component, and x happens to be the leader vertex of the second component. And then the invariant just says every vertex should be pointing to the leader of its component. So v and w should be pointing to u. U has its own pointer. It should be pointing to itself. Similarly, in the second component, x is pointing to itself. Y points to x, and z also points to x. So in blue here are the actual edges of the graph, and in green there are these sort of extra edge pointers that we've invented where everybody's pointing back to the leader of their component. And so one very simple thing in this setup, which turns out to be a good idea, is each component is in effect inheriting the name of its leader vertex. So we refer to a group, we refer to a component via the object, via the vertex, who happens to be the representative, who happens to be the leader. And what's kind of amazing is even just this very simple scaffolding on the connected components is enough to have constant time cycle checks, provided the invariant is satisfied. Well, how do we do that? So remember that checking if adding the edge u, v is going to create a cycle boils down to checking whether there's already a path between u and v. Well, there's already a path between u and v if and only if they're in the same connected component. Given two vertices u and v, how do we know if they're in the same connected component? We just follow the respective leader pointers and we see if we get to the same place. If they're in the same component, we get the same leader. If they're in different components, we get different leaders. So checking for a cycle just involves, for each of u and v, comparing a quality of leader pointers. That is clearly constant time. More generally, the way you implement the find operation for this flavor of disjoint union data structure is you simply return the leader pointer of the object that you were handed. So if you're given a vertex, you just follow the leader pointer of that vertex and you return wherever you wind up. So that's pretty excellent. As long as in this simple data structure the invariant is satisfied, we have our desired implementation of constant time cycle checks. But, and certainly this is a recurring theme in our data structure discussions, whenever you have a data structure and it needs to maintain an invariant, whenever you do an operation that changes the data structure, so like in this case when you do a union, fusing two groups together, you have to worry, well, does the invariant get destroyed when you do that operation? And if it does, how are you going to restore the invariant without doing undue work? So in the present context of Kruskall's algorithm, here's how this plays out. So we're happily doing our constant time cycle checks. Whenever an edge creates a cycle, we don't do anything, we skip the edge, we don't change our data structure, and we move on. The issue is when we have a new edge and it doesn't create a cycle, our cycle check fails. Now Kruskall's algorithm dictates that we add this edge into the set capital T that we're building. And that fuses two connected components together. But remember, we have this invariant. Every vertex should point to the leader of its component. Well, if we had component A and we had component B, they're both pointing to the leader vertex of their respective components. Now, when these components fuse into one, we've got to do some updating of leader pointers. In particular, there used to be two leaders, now there has to be just one, and we have to rewire the leader pointers to restore the invariant. So to make sure you're clear on this important problem, let me ask you the following question. So consider the case when at some point in Kruskall's algorithm a new edge is added and two connected components fuse into one. Now to restore the invariant, you have to do some leader pointer updates. In the worst case, asymptotically, how many leader pointer updates might be required in order to restore the invariant? So the answer to this question, somewhat alarmingly, is the third answer. So it might require a linear number in the number of vertices n pointer updates to restore the invariant. Maybe one easy way to see that is just imagine the very last edge that Kruskal is going to add in the set T, the one which fuses the final two connected components down into one. For all you know, those two components have exactly the same size. They have n over 2 vertices each. You're going down from 2 leader pointers to 1. One of those sets of n over 2 vertices are going to have to inherit the leader pointers from the other side. So one of the two sets is going to have n over 2 vertices get their leader pointer updated. So that's a bummer. We're sort of hoping for a near linear time bound, but if each one of our linear number of edge additions might trigger a linear number of leader pointer updates, that seems to be giving rise to a quadratic time bound. But remember when I introduced the union find data structure, I only said that first idea was idea number 1. Presumably there's an idea number 2, and here it is. And it's very natural. If you were coding up an implementation of union find data structure, you would probably very naturally do this optimization yourself. All right, so consider the moment in time in which some component A merges with some component B. Each of these two components currently has their own respective leader vertex, and all vertices from that group are pointing to that leader vertex. Now, when they fuse, what are you going to do? The first obvious thing to do is say, well, let's not bother computing some totally new leader. Let's either reuse the leader from group A or the leader from group B. That way, if, for example, we retain the leader from group A, the only leader pointers that need to be rewired are the ones who come from component B. The vertices in component A can keep their same leader vertex and their same leader pointers as before. So that's the first point. Let's just have a new union of two components inherit the leader of one of the constituent parts. Now, if you're going to retain one of the two leaders, which one are you going to retain? Maybe one of the components has 1,000 vertices, the other component only has 100 vertices. Well, given the choice, you're certainly going to keep the leader from the first component. That way you only have to rewire the 100 leader pointers of the second group. Right? If you kept the leader of the second group, you'd have to rewire the 1,000 pointers from the first group, and that seems silly and wasteful. So the obvious way to implement a merge is you just keep the leader of the bigger group and rewire everybody from the second group, the smaller group. So you should notice that in order to actually implement this optimization where you always retain the leader of the larger group, you have to be able to quickly determine which of the two groups is larger. But you can augment the data structure we've discussed to facilitate that. So just with each group, you just keep a count of how many vertices are in that group. So you maintain a size field for each group. That allows you to check in constant time what's the population of two different groups and figure out, again, in constant time, which one's bigger. And notice that when you fuse two groups together, it's easy to maintain the size field. It's just the sum of the sizes of the two constituent parts. So let me now revisit the question from the previous slide. In the worst case, given this optimization, how many leader pointers asymptotically might you have to rewire when you merge two components together? Well, unfortunately, the song remains the same. The answer is still the third one. And it's because for exactly the same reason as on the previous slide. It still might be the case that, say, in the final iteration of Kruskal, you're merging two components that both have size n/2. So it doesn't matter. I mean, no matter which leader you choose, you're going to be stuck updating the leader pointers of n/2 or theta of n vertices. So, while this is clearly a smart practical optimization, it doesn't seem to be buying us anything in our asymptotic analysis of the running time. However, what if we think about the work done in all of these leader pointer updates in the following different way? Rather than asking how many updates might a merging of two components trigger, let's adopt a vertex-centric view. Let's suppose you're one of the vertices of this graph. So initially at the beginning of Kruskal's algorithm, you're in your own isolated connected component, you just point to yourself, you're your own leader. And then as Kruskal's algorithm runs its course, your leader pointer will periodically get updated. At some point you're no longer pointing to yourself, you're pointing to some other vertex. Then at some point your pointer gets updated again, you're pointing to yet some other vertex, and so on. How many times over the entire trajectory of Kruskal's algorithm, in light of our new optimization, might you, as some vertex of this graph, have your leader pointer updated? Well, here's the very cool answer. The answer is the second one. So while it remains true that if you always have the union of two groups inherit the leader pointer of the larger one, it's still true that a given fusion might trigger a linear number of leader pointer updates. Each vertex will only see its leader pointer updated a logarithmic number of times over the course of Kruskal's algorithm. What is the reason for this? Well, suppose you're a vertex and you're in some group and it has maybe 20 vertices, so you're one of 20. Now, suppose at some point your leader pointer gets updated. Why did that happen? Well, it meant that your group of 20 vertices merged with some other group that has to be bigger. Remember, your leader pointer only gets rewired in a fusion if you were in the smaller group. So you're joining a group at least as big as yours. So the size of the union, the size of your new community, your new connected component, is at least double the size of your previous one. So the bottom line is every time you as a vertex has your leader pointer updated, the population in the component to which you belong is at least twice as large as before. Now, you start in a connected component of size 1. The connected component is not going to have more than n vertices, so the number of doublings you might have to endure is at most log base 2 of n. So that bounds how many leader pointers you will see as a vertex in this graph. So in light of that very cool operation, we can now give a good running time analysis of Kruskall's algorithm using the union find data structure, using the scaffolding on the connected component structure to do cycle checks. We, of course, have not changed the preprocessing step. We're still sorting the edges from cheapest to most expensive at the beginning of the algorithm, and that still takes big O of m log n time. So what work do we have to do beyond this sorting preprocessing step? Well, fundamentally, Kruskall's algorithm is just about these cycle checks. In each iteration of the for loop, we have to check if adding a given edge would create a cycle with those edges we've already added. And the whole point of the union find scaffolding, these linked structures, is that we can check cycles in constant time. Just given an edge, we look at the leader pointers of its endpoints, and a cycle will be created if and only if their leader pointers are identical. So for the cycle checking, we only do constant time for each of the O of m iterations. But the final source of work is maintaining this union find data structure, restoring the invariant each time we add a new edge to the set capital T. And here the good idea is we're not going to just bound the worst case running time of these leader pointers for each iteration, because that could be too expensive. That could be up to linear in just a single iteration. Rather, we're going to do a global analysis, thinking about the total number of leader pointers that ever occur. On the previous slide, we observed that for a single vertex, it's only going to endure a logarithmic number of leader pointer updates. So summing over all of the n vertices, the total work done for leader pointer updates is only n log n. So even though we might do a linear amount of pointer updates in just one iteration of this for loop, we still have this global upper bound of n log n on the total number of leader pointer updates. Very cool. So looking over this tally, we observe the stunning fact that the bottleneck for this implementation of Kruskall's algorithm is actually sorting. So we do more work in the preprocessing step, m log n, than we do in the entire for loop, which is only m plus n log n. So that gives us an overall running time bound of big O of m log n, matching the theoretical performance that we achieved in Prim's algorithm implemented with heaps. So just like with our heap-based implementation of Prim's algorithm, we get a running time which is almost linear, only a logarithmic factor slower than reading the input. And just like with Prim's algorithm, you should find Kruskall's algorithm to be very competitive in practice. In this optional video, I'm going to give you a glimpse of the research frontier on the problem of computing minimum cost spanning trees. We've now seen two excellent algorithms for this problem, Prim's algorithm and Kruskall's algorithm, and with suitable data structures both run in near linear time, big O of m log n, where m is the number of edges, n is the number of vertices. Now on the one hand, we should be pretty happy with those algorithms. We're only a log factor slower than what it takes to read the input. But again, the good algorithm designer should never be content, never be complacent. We should always ask, can we do better? Maybe we can do even better than m log n. Well, believe it or not, you can do better than these implementations, at least in principle, at least in theory. You have to work pretty hard, and I'm definitely not going to discuss the algorithms or the analysis that prove this fact, but let me just mention a couple references that give MST algorithms with asymptotic runtime even better than m log n. So quite shockingly, if you're happy with randomized algorithms, as we were with, say, the quicksort sorting algorithm, then the minimum cost spanning tree problem can be solved in linear time. That's obviously an optimal algorithm. You have to look at the whole graph to compute the minimum cost spanning tree, but you can solve the problem in time a constant factor larger than what it takes to read the input. This algorithm is much, much newer than Prim and Kruskall's algorithm, as you might expect. It does date back to the 20th century, but definitely the latter stages of last century. So the names of a couple of the inventors of this algorithm will already be familiar to those of you that paid close attention in part 1. So the Karger here is the same as the author of the randomized min cut algorithm we studied in part 1. Tarjan's name is coming up a couple times in these courses, but for example, when we discuss strongly connected component algorithms. So what if you're not happy with a bound just on the expected running time, with the expectation over the coin flips of the algorithm? What if you want a deterministic algorithm? So if we think of this randomized algorithm as being analogous to quicksort in the sorting problem, what would be the analog of merge sort? Well, it turns out we do not know whether or not there's a linear time deterministic algorithm for minimum spanning trees. That's an open question. You might think here at this late date, 2012, 2013, we'd know everything there is to know about minimum cost spanning trees. We do not know if there exists a linear time deterministic algorithm. We do know that there's a deterministic algorithm with a running time absurdly close to linear. Specifically, there's an algorithm with running time m, the number of edges, times alpha of n. So what, you ask, is alpha of n? What is this function? Well, it's something called the inverse Ackermann function. So defining the Ackermann function and its inverse actually takes a little bit of work, so I'm not going to do it right now. For those of you that are curious, you should check out the optional material on the union find data structure, which is yet another context where sort of unbelievably this inverse Ackermann function arises. But for the present context, what you should know is that this is a crazy slow-growing function. It's not constant. For any number c, I can exhibit a large enough value of n so that this function values is at least c, so that alpha of n is at least c. So it's not bounded by a constant, but it's mind-boggling how slow-growing this function is. Let me actually just give you an incredibly slow-growing function which actually grows much faster than the inverse Ackermann, just to prove the point. Specifically, the inverse Ackermann function grows quite a bit slower than log star n. Log star n I can define for you easily. Recall our definition of log base 2 way back when we first demystified logarithms at the beginning of part 1. If you type n into your calculator and you keep dividing by 2, you count the number of times you divide by 2 until you drop below 1. That's log base 2 of n. For log star, instead of dividing by 2, you're going to hit the log button on your calculator. And you count how many times you hit log until the result drops below 1. That number, the number of times you hit log, is defined to be log star of n. The log star function is the inverse of the function which is a tower of 2's. The function which takes as input, an integer, say t, and raises 2 to itself t times. So to appreciate just how slow growing the log star function is, let alone the inverse Ackermann function, what you should do is type in the biggest number you can into your nearest calculator or computer. Just keep typing in 9s as long as you can. Then go ahead and evaluate log star. Keep applying the log function until it drops below 1. Probably the result's going to be something in the neighborhood of 5. So log star of the biggest number in your calculator or computer is going to be 5. That's how slow growing this function is. So the upshot is that the algorithms community has the time complexity of the MST problem almost nailed, but not quite in the deterministic case. The right answer is somewhere between m and m times inverse Ackermann function, and we don't know where. But you know what? It gets weirder. So check out the following result of Petty and Ramachandran. They, in a sense, solved the deterministic minimum cost spanning tree problem by exhibiting an algorithm whose time complexity is optimal. So they gave an algorithm and they gave a proof, just in the spirit of what we did for sorting, they gave a proof that no algorithm could have running time asymptotically better than theirs. But what they didn't do is explicitly evaluate what the time complexity of their algorithm is. So they managed to prove optimality without actually evaluating exactly what's its running time. So it's certainly somewhere between linear and linear times inverse Ackermann. We know that's the true time complexity of the problem. We know an algorithm that achieves that optimal complexity, but to this day, we do not know what that optimal time complexity actually is as a function of the graph size. So those are some of the most advanced things that we do know about the minimum cost spanning tree problem. Let me just mention a couple of things that we still, to this day, do not know. So let me start with the randomized algorithms. Now, maybe your reaction is there's no open questions in the randomized algorithms world because we know you need linear time to solve the problem, and I've told you that there is a randomized algorithm with expected running time that is linear. So what more could you want? Well, what I want is I want an algorithm that's not just linear time, but also simple enough that I can teach it to other people. So ideally, it would be in an undergraduate course like this, but I would actually be very happy to have a randomized algorithm, linear time, simple enough to cover in a graduate course. The current linear time algorithms do not have that property. They're more complicated than I can even cover in a graduate course. To accomplish this task, it turns out to be enough to solve a seemingly simpler task, namely to get a simple randomized linear time algorithm for the MST verification problem. So let me tell you what that means. So in the MST problem, you're supposed to optimize. Amongst all exponentially many spanning trees, you got to find me the one with the smallest sum of edge costs. In MST verification, the job seems simpler. I'm actually going to hand you a candidate MST, or I'm going to hand you a spanning tree. It may or may not be the best one, and you just need to check, is it the optimal one or not? Furthermore, in the event that it's not optimal, you should tell me edges that are not in the minimum spanning tree, edges that are too expensive that I should throw out. The reason it's enough to design a linear time algorithm for this seemingly simpler problem is that the content of the Karger-Klein-Tarjan paper is a reduction, a randomized reduction from optimizing over spanning trees to the seemingly simpler problem of MST verification. Moreover, all of the novel content in the Karger-Klein-Tarjan algorithm, it's linear time, it's randomized, and it is really simple. I teach this stuff in that paper in my graduate classes. But it needs this MST verification subroutine as a black box, and the only known implementations that are linear time for MST verification are quite complicated. So find a simple way to do MST verification that runs in linear time, and you're good to go with your simple optimal MST algorithm. For deterministic algorithms, the holy grail is obvious. We'd love to have a deterministic algorithm for MST that runs in linear time, or at the very least, we just need to figure out, what is the best possible time complexity of any deterministic MST algorithm. So one of the takeaways of this discussion is that, for all the amazing advances by computer scientists on the design and analysis of algorithms over the past 50 years or so, there are still totally fundamental things that we do not understand. So there's still great ideas to come in the future. So if you've been intrigued by some of the things I've said in this video and you want to learn more about these advanced minimum cost spanning tree algorithms, for further reading, I'd recommend a survey by Jason Eisner called State-of-the-Art Minimum Spanning Tree Algorithms. It's about 15 years old now, but it's still an amazing resource for learning about this advanced material. So by now we've spent quite a bit of time talking about the minimum cost spanning tree problem. There's a number of motivations why we do that. The first, it's just a uniquely great problem for the study of greedy algorithms. You can propose a bunch of different greedy algorithms, and quite unusually, all of them seem to work. So you get correct greedy algorithms, but it's quite subtle what's driving their correctness. You also get a lot of practice arguing about graphs and arguing about exchange arguments and so on. The second reason it's been worthwhile spending time on these algorithms is it's given us some more practice with data structures and how to use them to speed up algorithms, namely heaps to speed up Prim's algorithm, the union find data structure to speed up Kruskall's algorithm. The third reason that we're talking about them is they have applications in their own right. That's the subject of this video and the next, and we're going to focus on applications to clustering problems. So let me begin by just talking about the goal of clustering informally, and then I'll let you pin me down to a precise objective function on the next slide. So in a clustering problem, the input is n points that we think of as being embedded in space. And it's actually quite rare that in the underlying problem that we care about, is it actually intrinsically geometric? Is it actually intrinsically points in space? Usually we're representing something we care about. Maybe it's web pages, maybe it's images, maybe it's a database, as points in space. And given a bunch of objects, we want to cluster them into, in some sense, coherent groups. For those of you coming from a machine learning background, you'll often hear this problem referred to as unsupervised learning, meaning the data is unlabeled. We're looking for just patterns in data when the data is not annotated. This obviously is a fairly wishy-washy description of a problem, so let's be a little bit more precise. We're going to assume that part of the input is what we're going to call a similarity measure, meaning for any two objects, we're going to have a function giving us a number indicating how similar, or really rather how dissimilar they are to each other. In keeping with the geometric metaphor, we're going to refer to this function as a distance function. One thing that's cool is we don't need to impose many assumptions on this distance function. The one thing we're going to assume is that it's symmetric, meaning the distance from P to Q is the same as the distance from Q to P. So what are some examples? Well, if you want to really go with the geometric metaphor, if you're representing these points as in a space Rm for some dimension m, you can just use the Euclidean distance, or if you prefer some other norm like, say, L1 or L infinity. In many application domains, there are widely accepted similarity or distance measures. One example would be for sequences, as we discussed in an introductory lecture, the penalty of the best alignment between two genome fragments. So now that we have this distance function, what would it mean to have coherent groups? Well, things which have small distance from each other, which are similar, they should generally be in the same group, and things that are very dissimilar, that have large distance between them, you would expect to mostly be in different groups. So how can we evaluate how good a clustering is, how well it's doing with the job of putting nearby points together and dissimilar points in different groups? Well, to be honest, there's many ways of approaching formalizing that problem. The approach we're going to take is an optimization-based approach. We're going to posit an objective function on clusterings and then seek out the clustering that optimizes that objective function. I want to warn you, that's not the only way to approach the problem. There are other interesting approaches, but optimization is a natural one. Furthermore, just like in our scheduling application, there's more than one objective function that people study, and that is well motivated. So one very popular objective function would be, say, the k-means objective, which I encourage you to look up and read more about. For this lecture, I'm just going to adopt one specific objective function. It's natural enough, but it's by no means the only one or even the primary one, but it'll serve the purpose of studying a natural greedy algorithm related to minimum spanning tree algorithms, which is optimal in a precise sense. So let me develop the terminology needed to state the objective function and the optimization problem precisely. One issue that always comes up in clustering problems is how many clusters are you going to use? So to keep things simple in this video, we're going to assume that part of the input, k, indicates how many clusters you're supposed to use. So we're going to assume that you know a priori how many clusters you want. So in some application domains, this is a totally reasonable assumption. You might know, for example, that you want exactly 2 clusters, the k equals 2. In some domains, you may have good domain knowledge from past experience that you know how many clusters you expect to need. That's all fine and good. Also, in practice, if you don't really know what k is supposed to be, you can go ahead and run the algorithm we're going to talk about for a bunch of different values of k, and then use some metric or just eyeball it to figure out which is the best solution. So the objective function we're going to look at is defined in terms of separated pairs of points, that is, points that are assigned to distinct clusters. Now, if you have more than one cluster, inevitably there's going to be some separated pairs of points. Some points are going to be in one group, other points are going to be in a different group. So separated points are inevitable, and the most alarming separated points are the ones that are the most similar, the ones that have the smallest distance. If points are separated, we want them to be far apart, so we're particularly concerned with nearby points that are separated. So that's going to be our objective function value called the spacing of a clustering. It's the distance between the closest together pair of separated points. Now, what do we want from the spacing of a clustering? Well, we want all of the separated points to be as far apart as possible. That is, we want the spacing to be big. The bigger, the better. So that naturally motivates the formal problem statement. You're given as input the distance measure. You're told the distance between each pair of points. You're also told the desired number of clusters. Amongst all ways of clustering the points into k clusters, find the clustering which makes the spacing as big as possible. So let's develop a greedy algorithm that seeks to make the spacing as big as possible. And to facilitate the discussion, I'll use an example point set with just 6 black points up here in the upper right part of the slide. Now, the good idea behind this greedy algorithm is to not worry about the constraints that at the end of the day we can only output k different clusters. We're actually going to be infeasible. We'll have too many clusters throughout the algorithm. Only at the conclusion of the algorithm will we be down to k clusters, which will be our final and feasible solution. So that frees us up to initialize the procedure where the degenerate solution, where each point is in its own cluster. So in our example point set, we have these 6 pink isolated clusters. In general, you're going to have n clusters, and we've got to get down to k. Now, let's remember what the spacing objective is. In the spacing objective, you go over all of the separated pairs of points. So for this degenerated solution, it's all pairs of points. And you look at the most alarming separated pair, that is those that are the closest to each other. So the spacing is the distance between the closest pair of separated points. Now, in a greedy algorithm, you want to increase your objective function as much as possible. But actually, things are pretty cut and dried in this scenario. Suppose I give you a clustering, and you want to make the spacing bigger. The only way you can do that is by taking the currently closest pair of separated points and making them not separated anymore. That is, putting them in the same cluster. So it's in some sense obvious what you want to do to make the objective function go up at all. You got to look at the pair of points that is defining the objective, the closest pair of separated points, and you have to fuse them. You have to fuse their clusters so that they're no longer separated. In this example, it looks to me like the closest pair of points, which of course are separated, is this pair in the upper right. So if we want to make the spacing bigger, then we fuse them into a common cluster. So we started with 6 clusters, now we're down to 5. So now we reevaluate the spacing again of this new clustering. We ask, what is the closest pair of separated points? So that would seem to me to be this pair in the bottom right. And again, the only way we can increase the spacing by merging clusterings is to merge these two isolated clusters into one. Now we do it again. We say which pair of points determines the current spacing, which the currently separated pair of points that are nearest to each other. That to me would look like this pair that's on the rightmost part of the picture. The only way to merge two clusters and make the spacing actually go up is to merge the clusters containing the pairs of points determining the current spacing. So in this case, 2 different clusters with 2 points each would collapse into a single cluster with 4 points. Let's assume that we wanted 3 clusters anyways, which is where we are. So at this point, the greedy algorithm is going to halt. So let me now spell out the pseudocode of the greedy algorithm more generally, but it's exactly what you'd expect given the discussion so far. All right, so I'd like you to stare at this pseudocode for 10 seconds or however long you need and try to relate this to an algorithm that we've seen in the course, in particular an algorithm that we've seen quite recently. I hope it reminds you strongly of an algorithm we've already covered. Specifically, I hope you see a strong resemblance between this greedy algorithm and Kruskall's algorithm for computing a minimum cost spanning tree. Indeed, we can think of this greedy clustering algorithm as being exactly the same as Kruskall's minimum cost spanning tree algorithm, except aborted early, stopped when there's k components remaining, that is, before the final k-1 edge additions. So just to make sure the correspondence is clear, what is the graph, what are the edges, what are the edge costs? Well, the objects in the clustering problem, that is the points, those correspond to vertices in a graph. The other part of the input of the clustering problem are distances, which are given for every pair of points. So those play the role that edge costs were playing in the minimum spanning tree problem. Since we have a distance or an edge cost for every single pair of points, we can think of the edge set in the clustering problem as being the complete graph, because we have an edge cost or a distance for every single pair. So this type of agglomerative clustering has a name, this idea of fusing components one at a time using MST-like criterion. It's called single-link clustering. So single-link clustering is a good idea. If you work at all with clustering problems or unsupervised learning problems, it definitely should be a tool in your toolbox. We're going to justify its existence in one particular way in the next video when we show that it does indeed maximize the spacing over all possible K clusterings. But even if you don't care about the spacing objective function per se, you want to be familiar with single-link clustering. It has many other nice properties as well. This video will prove the correctness of our greedy algorithm for clustering. We'll show that it maximizes the spacing over all possible K clusterings. You might have hoped that we could deduce the correctness of this greedy algorithm for clustering immediately from our correctness proofs for various greedy minimum spanning tree algorithms. Unfortunately, that doesn't seem to be the case. In the minimum cost spanning tree problem, we were focusing on minimizing the sum of the edge costs. Here we're looking at a different objective, maximizing the spacing. So we do need to do a proof from scratch. That said, the arguments we'll use should look familiar to you, not just from the sort of exchange type arguments when we prove the cut property, but also it might remind you even more, going back further, to our greedy algorithms for scheduling. So let's now set up the notation for the proof. As usual, we're going to look at the output of our algorithm. It achieves some objective function values, some spacing. We're going to look at an arbitrary competitor, some other proposed scheduling, and we're going to show that we're at least as good. Our spacing is at least as large. So specifically, we'll denote the clusters in the output of our algorithm by C1 up to CK. Our clustering has some spacing, some distance between the near closest pair of separated points. Call it capital S. We're going to denote our competitor, some alternative K clustering, by C hat 1 up to C hat K. What is it that we're trying to show? We want to show that this arbitrary other clustering has spacing no larger than ours. If we can show that, then because this clustering was arbitrary, it means the greedy clustering has spacing as large as any other, so it's maximizing the spacing. And that's what we want to prove. Put differently, we want to exhibit a pair of points separated by this clustering C1 hat up to C hat K, such that the distance between those separated points is S or smaller. So let me just quickly dispose of a trivial case. If the C hats are the same as the C's, possibly up to a renaming, then of course exactly the same pairs of points are separated in each of the clusterings, so the spacing is exactly the same. So that's not a case we have to worry about. The interesting case then is when the C hats differ fundamentally from the C's, when they're not merely a permutation of the clusters in the greedy clustering. And the maneuver we're going to do here is similar in spirit to what we did in our scheduling correctness proof. Way back in our scheduling correctness proof, we argued that any schedule that differs from the greedy one suffers from, in some sense, a local flaw. We identified an adjacent pair of jobs that was in some sense out of order with respect to the greedy ordering. The analog here is we're going to argue that for any clustering which is not merely a permutation of the greedy clustering, there has to be a pair of points which is classified differently in the C hats relative to the C's. By differently, I mean they're clustered together in the greedy clustering. These points P and Q belong to the same cluster C sub I. Yet, in this alternative clustering, which is not just the permutation of the greedy clustering, they're placed in different clusters. One maybe P in C hat I, and Q in some other C hat J. So I want to now split the proof into an easy case and a tricky case. To explain why the easy case is easy, let's observe a property that this greedy clustering algorithm has. Now, the algorithm's philosophy is that the squeaky wheel should get the grease. That is, the separated pair of points that are closest to each other are the ones that should get merged. So for this reason, because it's always the closest separated pair that gets merged, if you look at the sequence of point pairs that get merged together, that determine the spacing in each subsequent iteration, the distances between these sort of worst separated points is only going up over time. At the beginning of the algorithm, the closest pair of points in the entire point set are the ones that get directly merged. Then those are out of the picture. Now some further away pair of points are separated and determines the spacing. Then they get merged. Once they've been coalesced, then there's still some further away pair of points, which is now the smallest one separated. They get merged, and so on. So if you look at the sequence of distances between the pairs of points that are directly merged by the greedy algorithm, that is only going up over time. And this sequence culminates with the final spacing, capital S, of the greedy algorithm. In some sense, the spacing of the output of the greedy algorithm is the distance between the point pair that would get merged if we ran the greedy algorithm one more iteration. But unfortunately, we're not allowed to do that. Okay, so the point is, for every pair of points directly merged by the greedy algorithm, they're always a distance at most, capital S, away from each other. So the easy case then is when this pair of points PQ, which on the one hand lie in a common greedy cluster, but on the other hand in different clusters of the C hats, if they were at some point not merely in the same cluster, but actually directly merged by the greedy algorithm, if at some iteration they determine the spacing and were picked by the greedy algorithm to have their clusters merged, then we just argued that the distance between P and Q is no more than the spacing capital S of the greedy clustering, and since P and Q lie in different clusters of the C hats, it's separated by the C hats, and therefore they upper bound the spacing of the C hats. Maybe there's some even closer separated pair by the C hats, but at the very least P and Q are separated, so they upper bound the spacing of the C hat clustering. So remember, that's what we wanted to prove. We wanted to show that this alternative spacing couldn't have better spacing than our greedy spacing. It had to be at most as big. It had to be at most capital S. So in this easy case, when P and Q are directly merged by the greedy algorithm, we're done. So the tricky case is when P and Q are only indirectly merged. And you may be wondering at the moment, what does that mean? How do two people wind up in the same cluster if they weren't at some point directly merged? So let's draw a picture and see how that can happen. So the issue is that 2 points P and Q might wind up in a common greedy cluster, not because the greedy algorithm ever explicitly considered that point pair, but rather because of a path or a cascade of direct mergers of other point pairs. Imagine, for example, that at some iteration of the greedy algorithm, the point P was considered explicitly along with the point A1, where here A1 is meant to be different than Q. So that's a direct merger, and P and A1 wind up in the same cluster. Their clusters are merged. Maybe the same thing happens with a point Q and some point A sub L, which is different than P. Similarly, maybe at some other time, some totally unrelated pair of points A2 and A3 are directly merged. And then at some point, A1 and A2 are considered by the greedy algorithm because they're the closest pair of separated points, and they get merged, and so on. So the edges in this picture are meant to indicate direct mergers, pairs of points that are explicitly fused because they determine the spacing at some point of the greedy iteration. But at the end of the day, the greedy clustering is going to have the results of all of these mergings. So in case you're feeling confused, let me just point out that we really saw this exact same thing going on when we were talking about minimum spanning trees in Kruskal's algorithm. So at an intermediate point in Kruskal's algorithm, after it's added some edges but before it's constructed a spanning tree, as we discussed, the intermediate state is a bunch of different kinetic components. And there are vertices that have an edge chosen between them. They, of course, are going to be in the same kinetic component. But then a kinetic component could have long paths in it. So you could have vertices that are in the same kinetic component in an intermediate state of Kruskal's algorithm, despite the fact that we haven't chosen an edge directly between them. There's rather a path of chosen edges between them. It's exactly the same thing going on here. Now, what we have going for us is that if a pair of points, as discussed, was directly merged, we know they're close. The distance between them is at most the spacing, capital S. We really don't know anything, frankly, about the distance between pairs of vertices that were not directly merged. They just sort of accidentally wound up in a common cluster. But this turns out to be good enough. This is actually sufficient to argue that this competitor clustering with the C hats has spacing no more than S, no better than ours. Let's see why. So given that P and Q are in a common greedy cluster, it must be that there is a path of direct mergers that force them to be in the same cluster. So let's let the intermediate points involved in that path denoted A1 up to AL. So here's the part of the proof where we basically reduce the tricky case to the easy case. So we've got this pair of points PQ. Now remember, not only are they in a common greedy cluster, but they're in different clusters in our competitor, in the C hats. So the point P is in some cluster, call it C hat I, and Q is in something else. In particular, it's not in C hat I. Now imagine you go on a hike. You start at the point P, and you hike along this path. You traverse these direct mergers toward Q. Now, you're starting inside C hat I, and you end up outside. So on some point on your hike, you will traverse the boundary. You will, for the first time, escape from C hat I and wind up in some other cluster. So that has to happen, and let's call AI and AI plus 1 the consecutive pair of points at which you go from inside this cluster to outside this cluster. And now we're back in the easy case. Now we're dealing with a separated pair that were directly merged by the greedy algorithm. Remember that we set up this path to be a path of direct mergers. So in particular, AJ and AJ plus 1 were direct mergers. Therefore, their distance is at most S. And again, by virtue of being direct merges, the distance is at most the spacing of the greedy clustering, and yet as a separated point by the C hats, it's also an upper bound on the spacing of the C hats. This means the spacing S of our greedy clustering is as good as the competitor. Since the competitor was arbitrary, we're optimal. That completes the proof. So welcome to this optional sequence of videos on state-of-the-art implementations of the union-defined data structure. Now, as advanced and optional material, let me make a few comments before we get started. So the first comment is, I'm going to assume that you're in a particularly motivated mood. Now, no one's forcing you to take these algorithms courses, so I'm always assuming that you're a very motivated individual, but that's going to hold even more true than usual in these advanced videos. And the way that plays out is, well, I'm going to hold myself to the same exacting standards of clarity that I usually do. I'm going to ask a little bit more of you of the viewer. I'm going to perhaps dot a few less I's, cross a few less T's than I usually do, and so you may find yourself periodically needing to pause and think through some of the details that I'm glossing over. The second comment is I'm going to give sort of short shrift to applications of the union-find data structure. That's not because there aren't any. There are plenty of applications of this data structure, but for these videos we're really just going to immerse ourselves in the beauty and the depth of the ideas behind the design of the data structures and especially the analysis of their performance. The final comment is to keep in mind that this is some seriously next level material. It is totally normal that the first time you see this stuff, you find it confusing, you find it difficult to understand. So confusion should not discourage you. It does not represent any intellectual failing on your part. Rather, keep in mind, it represents an opportunity to get even smarter. So with those comments in mind, let's go ahead and proceed to a different approach to the union-find data structure via lazy unions. So let's have one slide with a quick review of what we already know about the union-find data structure. Recall we discussed this in the context of a fast implementation of Kruskal's minimum spanning tree algorithm. The raison d'etre of a union-find data structure is to maintain a partition of a universe of objects. So in the context of Kruskal's algorithm, the objects were the vertices, and the groups we wanted to maintain were the connected components with respect to the edges we committed ourselves to so far. The data structure should support two operations, no prizes for guessing the names of those two operations. First is the find operation. This is given an object from the universe, return the name of that object's group. So for example, if X was in the middle of this square that I've put on the right, representing the universe capital X, we would return C3, the name of the group that contains X. So in the context of Kruskal's algorithm, we use the find operation to check for cycles. How did we know whether adding a new edge would create a cycle with respect to the edges we've already chosen? Well, it would be if and only if the endpoints of that edge were already in the same connected component. That is, if and only if the two find operations return the same answer. In the union operation, you're given not one object but two, call them X and Y, and then the responsibility of the operation is to merge the groups that contain X and Y. So for example, in the picture, if Y was in C4, X was as before in C3, then your job is to fuse the groups C3 and C4 into a single group. In the context of Kruskal's algorithm, we needed this operation when we added a new edge. This fused together two of the existing connected components into one. So that was exactly the union operation. So we already went through one implementation of union-find. That was in order to get a blazingly fast implementation of Kruskal's algorithm. So let's just review how that worked. With each group, we associated a linked structure. So each object had one pointer associated with it. And the invariant was, in a given group, there was some representative leader object, and everybody in that group pointed to the leader of that group. So for example, on the right, I'm showing you a group with three objects, X, Y, and Z, and X would be the leader of this group. All three of the objects point directly to X, and that would just be the output of the find operation, the leader of the group. We use that as the group name. Now, the part which is cool and obvious about this approach is our find operations take constant time. All you do is return the leader of the given object. Now, the tricky part was analyzing the cost of union operations. So the problem here is that to maintain the invariant that every object of a group points to its leader, when you fuse two groups, you have to update a bunch of the object's leaders. You can only have one leader for the one new group. The simple but totally crucial optimization that we discussed was when two groups merge, you update the leader pointers of all objects in the smaller group to point to the leader of the bigger group. That is, the new fused group inherits the leader from the bigger of its constituent parts. If we do that optimization, it's still the case that a single union might take linear time, theta of n time, but a sequence of n unions takes only big O of n log n time. And that's because each object endures at most a logarithmic number of leader updates, because every time its leader pointer gets updated, the population of the group that it inhabits doubles. So in this sequence of videos, we are going to discuss a different approach to implementing the union-find data structure. And let's just go all in and try to get away with updating only a single pointer in each union. All right, well, how are we going to do that? Well, I think if we look at a picture, it'll be clear what the approach is going to be. So let's look at a simple example. There's just 6 objects in the world, and currently they're in 2 groups. 1, 2, and 3 are in one group with leader 1. 4, 5, and 6 are in the second group with leader 4. So with our previous implementation of union find, the 2 groups have equal size, so we pick one arbitrarily to represent the new leader. Let's say 4 is going to be the new leader, and now we update objects 1, 2, and 3 so that they point directly to their new leader 4. And so the new idea is very simple. Let's just sort of as a shorthand for rewiring all of 1, 2, and 3 to point to 4, let's just, rewire 1's pointer to point to 4. And then it's understood that 2 and 3 as descendants of 1 also now have the new leader 4 as well. So as a result, we do again get a directed tree afterwards, but we don't get one with just depth 1. We don't get as shallow, bushy a tree. We get a deeper one that has 2 levels below the root. So let me give you another way of thinking about this in terms of an array representation. And here I also want to make the point that, while conceptually it's going to be very useful to think of these union find data structure in terms of these directed trees, if you're actually implementing this data structure, this is not how you do it. You wouldn't bother with actual pointers between the different objects. You just have a simple array indexed by the nodes, and in the entry corresponding to a node I, you would just store the name of I's parent. For instance, if we reframe this exact same example in array representation, before we do the union, what do we got? Well, objects 1, 2, and 3 all have parent 1. Objects 4, 5, and 6 all have parent 4. So in the array, we'd have a 1 in the first 3 entries and a 4 in the second 3 entries. So in the old solution, we have to update the parent pointers of objects 1, 2, and 3. They're all going to point directly to 4, so that gives us an array entirely of 4s. Whereas in the new solution, the only node whose parent pointer gets updated is that of object 1. It gets updated from itself to 4. And in particular, objects 2 and 3 still point to object 1, not directly to object 4. So that's how union works in a simple example. How does it work in general? Well, in general, you're given 2 objects. Each belongs to some group. You can think of these 2 groups conceptually as directed trees. If you follow all the parent pointers, all parent pointers lead to the root vertex, and we identify those root vertices with the leaders of these 2 groups. Now, when you have to merge the 2 trees together, how do you do it? Well, you pick one of the groups and you look at its root. Currently it points to itself. You change its parent pointer to point to the other group's leader. That is, you install one of the 2 roots as a new child of the other tree's root. So I hope the pros and cons of this alternative approach to the union find data structure are intuitively clear. The win, the pro, comes in the union operation, which is now very simple. Now you might be tempted to just say union takes constant time because all you do is update one pointer, but it's actually not so simple, right? Because remember, you're given 2 objects x and y, and in general you're not linking x and y together. They might be somewhere deep in a tree. You're linking roots together. So what is true is that the union operation reduces to 2 indications of find. You have to find x's root, r sub 1, you have to find y's root, r sub 2, and then you just do constant time linking either r1 to r2 or vice versa. Now the issue with this lazy union approach is that it's not at all obvious, and in fact it's not going to be true, that the find operation takes constant time. Remember, previously when we actually did all this hard work of updating all of these leader pointers every time we had a union, it guaranteed that whenever there was a find, boom, we just look in the field, we return the leader pointer, we're done. Here, parent pointers do not point directly to roots. Rather, you have to traverse, in general, a sequence of parent pointers from a given object x to go all the way up to the root of the corresponding tree. So because of these trade-offs, these pros and cons, it's really not obvious at all whether this lazy union approach to the union find data structure is a good idea, whether it's going to have any payoffs. So that's going to take some really quite subtle analysis, which is the main point of the lectures to come. It's also going to take a couple of optimizations, and the next video will start with the first one. You might be wondering, okay, so when you do a union and you have to install one root under the other, how do you make that choice? So the right answer is something called union by rank. That's coming up next. So let's start thinking about this alternative lazy union-based approach to the union-find data structure in some detail. To get this to work as quickly as we want to, we're going to need two optimizations. This video will introduce the first of those optimizations, union by rank. So let's have a quick slide making precise what we learned in the previous video. So in our new implementation, it's still the case that each object has one extra field. You can think of it logically as a pointer to some other object. Really, it's just recording the name of some other object. But the semantics have changed. In our first implementation of union find with eager unions, this field, we called it a leader pointer. And the invariant was that every object's pointer points directly to the leader of its group. In this lazy union implementation, we are relaxing that invariant. So I'm going to change the name. I'm not going to call it a leader pointer. I'm just going to call it a parent pointer. And the new relaxed invariant is that the collection of everybody's parent pointers induces a collection of directed trees. Each tree in this collection represents one of the groups in the partition that we're maintaining. Each of these trees has a root vertex, that is a vertex which points back to itself. It is these root vertices, these root objects, that we think of as the leaders of these components. So as before, we're going to refer to a group by the name of its leader vertex, and that leader is, by definition, the root of the corresponding directed tree. One way to think about things is that when we had eager unions, we again associated a directed tree with each of the groups, but we also insisted that it was a super shallow, bushy tree, that it had depth only 1. That is, all you had was a root, the leader, and then everybody else who pointed directly to the leader. In this lazy union implementation, we're allowing the trees to grow deeper. We don't insist that they have only one level below the root. So as far as the initialization, at birth in a union find data structure just consists of n degenerate trees. Each object just initially points to itself and is a root at the beginning. In general, how do you implement find from some object? Well, you just have to return the leader of its group, and we know you can get to the leader just by traversing parent pointers from X until you get to a root, until you get to some object that points back to itself. That's what you return at the end of the find call. How do you do union? Well, given two objects X and Y, you have to find their respective roots. So you just invoke the find operation twice, once for X to get its root S1, once from Y to get its root S2, and then you install either S1 or S2 as a child of the other. So you do one pointer update after the two finds. So for now, I'm going to leave union underdetermined. I'm not going to give you a rule to decide which of S1 and S2 becomes the child of the other. And the next quiz, I want you to think through, what would be the worst case running time of these operations if we make that choice arbitrarily, if we just pick S1 or S2 arbitrarily to become the child of the other. All right, so the correct answer, unfortunately, is the last one. Both find and union can actually blow up to linear time operations if you're not careful about how you implement the union. So why is this true? Well, first let me just point out that B is definitely not the correct answer. Whatever find and union's worst case running time is, it's definitely the same for both of them. Remember, union reduces to 2 calls to find plus constant work. So that's going to tell you that they're both going to have the same operation time in the worst case. Now, why is it linear? The reason you're stuck with linear time is because the trees that you build through a sequence of unions can, in the worst case, become very scraggly. And to see what I mean, imagine you just do a sequence of unions, and at each time you're unioning a group with just one object into the group that you've built up so far. So if you union together a group of size 2 and a group of size 1, well, if you choose arbitrarily, maybe you make the group of size 1 the new root. So now you've just got a chain of the 3 objects. Maybe you union in another singleton group, and arbitrarily you choose the singleton group to be the new leader. That gives you a chain of 4 objects, and so on. So if you do a linear number of unions and you're not careful about who you make a child of the other, you might well end up with a chain of linear length, and then if you do finds for the objects toward the bottom of that chain, they're going to require linear work. And again, union has a subroutine of find, so it's going to then take linear work as well. So when you see this example, I hope your immediate reaction is, well, geez, we can certainly do better than that. We can just be somewhat intelligent with, when we do a union, which of the old roots do we install as the child of the other one? There's a rough analogy with how we made a natural optimization with our eager union implementation of union find. There we had to make some kind of choice between which of the two old leaders do we retain. We retained the one from the bigger group to minimize the number of leader updates. So here the natural thing to do is, well, look at which of the two trees is already deeper, and we want to keep the root of that deeper tree. That's to avoid it from getting deeper still. So we install the root of the shallower tree as a child of the deeper one. Let's make that precise on the next slide with the notion of the rank of an object. So the rank is just going to be a second field along with the parent pointer that we maintain for each object. It's just going to be some integer. Let me tell you how I want you to think about the ranks, at least for now. Okay, so I'm going to give you some semantics, very natural semantics, but I want to warn you, they're only going to hold valid for the next couple of videos. When we introduce something else called path compression, these semantics are going to break down. But initially, this is how I want you to think about ranks. It's going to be the maximum number of hops required to get from a leaf of X's tree up to X itself. So for example, if X is a root, this is going to be the worst case length, the maximum length of any leaf to root path in the tree. So just to make sure this is clear, let me draw a quick example. So here in blue, I've shown you one particular union find data structure that has two groups. Now, it's very easy to compute the rank of leafs. That's 0 because the only path from a leaf to that node is the empty path. There are two nodes that have rank 1. Then the root of the bigger tree has rank 2. And if you think about it, in general, the rank of a node is going to be 1 plus the largest rank of any of its children. For example, if you're a node X, you have a child Y, and there's some path from a leaf Z up to Y that requires 5 pointer traversals, while going from Z all the way up to U at X is going to require 6 pointer traversals. And of course, when you initialize the data structure, you want to set everybody's rank to 0, because everybody's just in a tree by themselves at the beginning. This notion of rank is going to be a super crucial concept throughout this entire sequence of lectures on union find. So make sure you understand this definition. I encourage you to draw out some of your own examples, do some computations to get a better feel for the concept. For the moment, we're just going to use rank to avoid creating scraggly trees. So let's go back to the bad example in the quiz. Let's remember what the intuition was. We wound up with this long chain and therefore really bad worst case running time for our operations because we were stupidly taking a tree that was already pretty deep and installing it as a child under a single node, under a super shallow tree, thereby producing a tree which is even deeper. So the obvious way to avoid that is when faced with merging together a deep tree and a shallow tree, you install the shallow tree as a child under the deep one. That's going to slow down this deepening process as much as possible. So we can make that precise just using this rank notion. Notice that the rank is exactly quantifying the depth of a tree. So the rank of the root of a tree by this invariant is equal to the depth of the tree. So if you want to make the shallower tree the child of the other one, that means you want to make the smaller rank tree the child of the bigger rank tree. This optimization is what is meant by union by rank. There still remains the case where the two roots have equal rank, that is, where the two trees that we're fusing have exactly the same maximum path length, and in that case we do just arbitrarily choose one of them. So in the pseudocode I've written here, I've arbitrarily chosen Y's root to be the one that remains the root. X's root, S1, is going to be installed as a child of S2. But again, you can do it either way, it's not going to matter. Now, we're not off the hook yet. Remember, this is a data structure where we're intending for an invariant to hold. These semantics for the ranks is quantifying worst-case path length to the node. And we made a modification to the data structure. We rewired somebody's parent pointer. So now it's our responsibility to check, does the invariant still hold? And if it doesn't still hold, then we have to restore it, hopefully using minimal extra work. So in this quiz, we're going to think through how ranks change when we do a union. So remember the notation, we're in the middle of a union of the objects X and Y. S1 and S2 refer to the ranks, that is the leaders of the groups of the trees that contain X and Y respectively. The first thing I want you to think through and convince yourself of is that for objects other than S1 and S2, other than the pair of objects that are involved in the actual pointer rewiring, nobody's rank changes. So make sure you think that through and convince yourself. Ranks are invariant, except possibly for the objects S1 and S2. In this quiz, we're going to drill down on how do the ranks of S1 and S2 change, given that we took one of them and rewired its parent pointer to point to the other. Okay, so the correct answer to this quiz is the fourth one. So remarkably, in many cases, there's no change at all to anybody's ranks, including S1 or S2. If the ranks were different before the union, both of the ranks stay the same. The one exception is when you take the union of two ranks which are equal, then whichever one is the new root, and in the pseudocode that I showed you, S2 is chosen to be the new root, its rank gets incremented. It goes up by 1. I think the easiest way to see this is just with a couple pictures, a couple examples. So let me just draw two directed trees and the corresponding ranks. And in this one, S1 has strictly bigger rank. Its rank is 2, so we install S2 as a child under S1. So recomputing the ranks in the fused together tree, we see that again, the rank at the root at S1 is 2, the same thing as it was before, it didn't go up. So what's the general principle here? Well, in general, suppose you have these two trees, and suppose the first one's root S1 has a bigger rank, say rank R. What does that mean? So that means that there exists a path from a leaf to the root S1 that requires a full R hops. And in the second tree, by virtue of its rank being less than R, at most R minus 1, it says that every single path from a leaf to the root S2 of that tree uses only R minus 1 hops. So when you install S2 as a child under S1, well, you know, the length of every leaf to root path, now the root is S1, it's only gone up by 1. You just have to get to S2 and then one more hop, you make it all the way to S1. So if all those paths took at most R minus 1 before, all the paths all the way up to S minus 1 to S1 take at most R hops now. So the worst case path length has not gone up. That's exactly what happens in this example. So it's true that when we install S2 under S1, we have yet another path that requires 2 hops that goes through S2, but we had one previously, so the rank doesn't go up. The worst case path length is exactly the same as before. And this is the same kind of reasoning explains why the rank has to get bumped up by 1 when you fuse together two trees that had the same rank. So suppose S1 and S2 both have rank R. Well, then both of them have a leaf to root path that requires a full R hops. And now when you install S1 as a child under S2, that path where you needed R hops to get from the leaf to S1, now to get all the way up to S2, you need one more hop. So now suddenly there exists a path from a leaf to the new root S2 that requires a full R plus 1 hops. That's why the rank's got to go up. In this video, we'll provide, for the first time, concrete evidence that the lazy union approach to the union-find data structure is viable. Specifically, we'll prove that the worst-case running time of both the find and the union operation is logarithmic in n, the number of objects stored in the data structure. We're going to do even better later once we introduce a second optimization known as path compression, but an important stepping stone is to understand why just union by rank already gets us to a reasonable logarithmic runtime bound. So a quick review of the lazy union approach to implementing the union find data structure. So with each node, we're going to maintain a parent pointer, and it's no longer the case that we insist that the parent pointer point directly to the leader of a group. Rather, we just insist that the collection of parent pointers induces a collection of directed trees. The root of each tree, that is the node which is its own parent, we're going to define as the leader of that group. So given any old object X, how do you implement find? How do you figure out what the leader vertex is? Well, you just traverse parent pointers up until you get to the root of that particular group. So for this implementation of the find operation, the worst case running time is just going to be the longest path of parent pointers that you ever have to traverse to get from an object to some root. So the way we're going to quantify that is using these ranks. So this is again a field that we maintain for each object. And for now, this will break down later, but for now, before we have path compression, we're going to maintain the invariant that the rank of an object X is exactly the largest number of pointers you have to traverse from some leaf to get to X. As a consequence, the biggest rank of any object is the longest path from any leaf to any root, and that's going to be an upper bound on the worst case running time of the find operation. So let's move on to the union operation. So here, given two objects X and Y, you need to fuse their two trees, their two groups. So you find the roots of the two trees. So you call a find on X, you call a find on Y. That gives you their two respective roots. And now you install one as a new child of the other. And we saw in a quiz in the last video that if you're not careful about which root you install as a child under the other, you can wind up with these long chains and be stuck with a linear worst case time for both find and union. So instead we have this union by rank optimization, which says, well, we want to keep our trees from getting scraggly, and the way we're going to do that is when we have a shallow tree and a deep tree, we make the shallow tree a child under the root of the deep one. That prevents the tree from getting even deeper. Now, there is a situation where the two trees have exactly the same depth, that is, where the two roots have exactly the same rank. In that case, we just proceed arbitrarily. Now, when we merge two trees that both had a common rank r, it's important that in the new tree, the rank has gone up to r plus 1. So we need to update, we need to increment the rank of the new root to reflect that increase. So that's where we've already been. Where are we going to next? Well, the plan for this video is to show that with the union by rank optimization, the maximum rank of any node is always bounded above by log base 2 of n, where n is the number of objects in the data structure. Now, we just said the worst case running time of find is governed by the maximum rank. So logarithmic maximum rank means logarithmic running time of find. That also carries over to the union operation. Remember, union is just two finds plus constant work to rewire one pointer. So that's going to give us a logarithmic time bound on both operations. So let's see why that's true. So let's begin the analysis with a few simple but useful properties that follow immediately from our invariant, from the way that we change the ranks of objects as we do finds and as we do unions. So the first simple property is focus on your favorite object x and watch this object's rank change over the course of the data structure as we do finds and unions. How can it change? Well, when we do a find, we don't change anything. All the ranks stay the same. When we do a union, all the ranks stay the same. Well, except there is one case in the union where the rank of a single node gets bumped up by 1, gets increased. So ranks only go up over time for all of the objects. That's property 1. So the second property is, again, pretty much trivial, but really, really useful. So what is the situation in which somebody's rank gets bumped up by 1? Well, it's when we take the union of two trees that have a common rank, and then whichever of the two roots that we pick to be the root of the new bigger tree, that's the object whose rank gets bumped up by 1. It's the new root of this fused tree. So in particular, the only type of object that can ever get a rank increase is a root. If you're not a root, your rank will not go up. Furthermore, once you're not a root in this data structure, you will never be a root again in the future. There is no process by which you shed your parent. Once you have a parent other than yourself, you will always have exactly that parent. Putting those two observations together, we find that as soon as an object x becomes a non-root, as soon as it has a parent other than itself, its rank is frozen for the rest of time, forevermore. The third and final simple property follows from a formula we mentioned in the last video about computing ranks. So remember, the rank of a node in general is going to be 1 more than the maximum rank of any of its children. So if you have a child and there's some path from a leaf to that child that takes 5 hops, the path to you from that child is actually going to take 6 hops. As a consequence, as you go from the leaf up to the root, you will see a strictly increasing sequence of ranks. The rank of a parent is always strictly more than the rank of all of its children. So that's it for the immediate properties. Let's go to a property which is a little less immediate. But still, this next lemma, which I'm going to call the rank lemma, it's the best kind of lemma. So on the one hand, it's just not that hard to prove. I'll give you a full proof in the following 2 slides. On the other hand, it's really powerful. It's going to play a crucial role in the analysis we're doing right now, a logarithmic runtime bound with the union by rank optimization. And we'll keep using it again as a workhorse once we introduce path compression and prove better bounds on the operations. So what's the rank lemma say? Well, it controls the population size of objects that have a given rank. So we wanted to apply at all intermediate stages of our data structure. So we're going to consider an arbitrary sequence of unions. You can throw in some finds as well. I don't care. Finds don't change the data structure, so they're totally irrelevant. So think about a sequence of unions, a sequence of mergers. The claim is for every non-negative integer r, the number of objects that have rank exactly r at this time is at most n, the total number of objects divided by 2 to the r. So for example, if r equals 0, it says at most n objects have rank 0. So that's a trivial statement. There's only n objects. But at any given time, the number of objects that have rank 1 is at most n over 2. The number of objects that have rank 2 is at most n over 4, and so on. And if you think about it, if we succeed in proving the rank lemma, we're pretty much done showing the efficacy of the union by rank optimization. So in particular, once you take r in this key lemma to be log base 2 of n, it says that there's at most one object that has rank log base 2 of n. And there can't be any objects that have rank strictly larger. That is, this lemma implies that the maximum rank at all times is bounded above by log base 2 of n. And remember, the maximum rank is the longest path of pointers traversals you ever need to get from a leaf to a root, and that means the most amount of work we'll ever do in a find, and therefore in a union, is big O of log n. Okay, so I've now teased you with the consequences of the rank lemma, assuming that it's true, but why is it true? Let's turn to the proof. I'm going to break the proof down into two claims, claim 1 and claim 2. We'll see that the two claims easily imply the rank lemma. So claim 1 asks you to consider two objects x and y that have exactly the same rank r. And the claim asserts that these subtrees of these two objects have to be disjoint. They have no objects in common. And here by the subtree of an object, I just mean the other objects that can reach this one by following a sequence of parent pointers. So that is, the subtree at x is the objects from which you can reach x. The subtree at y is the objects from which you can reach y. The second claim is that if you look at any object that has rank r and you look at its subtree, that is, if you look at the number of objects that can reach this object x by following pointers, there have to be a lot of them. There have to be at least 2 raised to that object's rank r objects in its subtree. Notice that if we prove claim 1 and claim 2, then the rank lemma follows easily. Why? Well, fix a value for r. 2, 10, I don't care what. Look at all the nodes that have this rank r. By claim 2, each of them has at least 2 to the r objects that can reach them, and by claim 1, these have to be disjoint sets of objects. Well, there's only n objects to go around, and if each of these disjoint sets has at least 2 to the r of them, there can be at most n over 2 to the r such groups. That is, at most n over 2 to the r nodes, objects, with this rank r. So we've reduced the proof of the rank lemma to proving claims 1 and 2. I will do them in turn. So for claim 1, let me go via the contrapositive. That is, I will assume that the conclusion is false, and I will show that the hypothesis must then also be false. So let's assume that we have two objects x and y, and their subtrees are not disjoint. That is, there exists an object z from which you can reach x, and from the same object z, you can also reach y via a sequence of parent pointers. Well, now let's use the fact that we're dealing with a directed tree, right? So if you started an object z, there's only a unique parent pointer to follow each time. So that is, all of the objects reachable from z, they form a directed path leading up to the root of z's group. So the only way for both x and y to be reachable from z, they have to both be on this path. If they're both on this path, then one has to be an ancestor of the other. So now we're going to use the third of our simple properties that we observed, that is, on every path to the root, ranks strictly go up each time. So whichever of x or y is an ancestor of the other, that has strictly higher rank. Therefore, x and y do not have the same rank. That completes the proof of claim 1. So let's move on to claim 2. Remember, claim 2 asserts that an object of rank r necessarily has 2 to the r objects or more in its subtree. That's how many objects can actually reach this object x by following parent pointers. So for this proof, we're going to proceed by induction on the number of operations. And again, remember, find operations have no effect on the data structure, so we can ignore them. So it's just by induction on the number of union operations that happen. So for the base case, before we've done any unions whatsoever, we're doing just fine. Every object has a rank of 0, and the subtree size of every object is equal to 1, that object itself, also known as 2 to the 0. Now for the inductive step, there's an easy case and a hard case. The easy case is where nobody's rank changes, where we do a union and everybody's rank stays exactly the same. In this case, we're golden. Why? Well, when you do a union, subtree sizes only go up. There's only more pointers, so there's only more objects that can reach any given other object. So subtree sizes go up, ranks stay the same. If we had this inequality of subtree sizes being at least 2 to the r before, we have it equally well now. So the interesting case is when somebody's rank actually changes. How can that happen? Well, it happens in only one particular way that we understand well. We're looking at a union operation between objects x and y. Suppose the roots of these objects are s1 and s2 respectively. It's only when these two roots have the same rank, let's call that common rank r, that somebody's rank gets changed. In particular, we're going to break ties as we did in the previous video. S2 will be the root of the fuse tree. S1 will become a child of it. And in that case, S2's rank gets bumped up by 1. It goes from R to R plus 1. Now notice, in this case, we do have something to prove. What are we trying to establish? We're trying to establish that every subtree size is big as a function of the rank. So S2's rank has gone up, and therefore the lower bound, the bar that we have to meet for the subtree size, has also gone up. It's doubled. So in this case, we actually have to scrutinize S2's new subtree. So what is its new subtree? Well, it's really just composed from its old subtree, and it inherits S1 and all of its subtrees. Well, in that case, we know that S2's new subtree size, the number of objects that can reach it, is just its old subtree size plus the old subtree size of S1. But then we're in good shape because we have the inductive hypothesis to rescue us. So remember, before this union, by the inductive hypothesis, for every object with a given rank, say R, it had at least 2 to the R objects in its subtree. So S1 and S2 both had rank R before this union. So before this union, both of their subtree sizes were at least 2 to the R. So S2's new subtree size is bounded below by 2 to the r plus 2 to the r, a quantity also known as 2 raised to the r plus 1. Quite conveniently, r plus 1 is S2's new rank. So even with S2's new bigger rank, its subtree size is still meeting the lower bound, meeting the target of 2 raised to that new rank, 2 raised to the r plus 1. So that completes the inductive step. Therefore, it completes the proof of claim 2, that objects of rank r have subtree sizes at least 2 to the r. Therefore, it completes the proof of the rank lemma, that for every rank r, there's at most n over 2 to the r nodes of rank r. And remember, the rank lemma implies that the maximum rank at all times is bounded by log base 2 of n, as long as you're using union by rank. And that implies that with this first optimization, the worst case running time of union and find are both big O of log n, where n is the number of objects in the data structure. So I don't blame you if you're feeling a little bit restless. You've now watched 3 videos about this alternative approach to the union find data structure based on lazy unions, and frankly, we don't have many tangible things to show for it. We already had a perfectly fine implementation of this data structure based on eager unions. That gave us constant time finds, and yeah, union could be linear in the worst case, but it was logarithmic on average over a sequence of unions. And so now we have this other implementation. Both of our operations are requiring logarithmic time. It's true, it's a worst case bound, and it's true union by rank is pretty cool, but still the bottom line up to this point is not that compelling. But I've still got another trick up my sleeve, and just watch what happens once we employ a second optimization known as path compression. So the optimization is very natural. I suspect many a serious programmer would come up with this on their own if they were tasked with implementing union find with union by rank. So to motivate this optimization, let's think about what would be our worst nightmare as someone maintaining such a data structure and hoping for good performance. Well, remember, the running time of a find is proportional to the number of parent pointers you have to traverse. That is, it's proportional to the depth of the object at which it's invoked. So what's the worst case find look like? Well, it's going to be at a leaf, and moreover, it's going to be at a leaf which is furthest away from its corresponding root. Now, on the one hand, we're using union by rank, so we know that this depth can't be too bad. We know it's going to be at most big O of log n. However, there will be examples, there will in general be leafs that are theta of log n hops away from their root. And for all we know, we're just going to get this endless sequence of find operations where every single one is invoked on a leaf that's a log n number of hops away from its root. So for example, in the pink tree that I've shown in the upper right of the slide, maybe someone just keeps searching for the object, keeps invoking find from the object 1 over and over and over again. And then we're going to be suffering a log number of steps every single operation. But if you think about it, it's totally pointless to keep redoing the work of previous finds, to keep retraversing the same parent pointers over and over again. So for example, in the pink tree that I've shown in the upper right, imagine that find is invoked from object 1. So then we traverse the 3 parent pointers, we discover the ancestors 4 and 6 before terminating at 7, and we discover that 7 is the leader or the root corresponding to the object 1. Now remember, we do not care that 4 and 6 are ancestors of 1. That is uninteresting. We only visited them to discover what we actually cared about, that 7 is the leader, the root corresponding to 1. Well, but let's just cache that information now that we've computed it. So this is now basically reconstructing the eager union find implementation. Let's just rewire 1's parent pointer to point straight to 7. We don't need to recompute 4 and 6 in some later find operation. And more generally, after we've invoked find from object 1, we may as well rewire 4's parent pointer as well to point directly to its leader 7. So that then is path compression. When find is invoked from some node x and you traverse parent pointers from x up to its root, call it r. For every object that you visit along this path from x to r, you rewire the parent pointer to point directly to r. So r doesn't have its parent pointer changed, it still points to itself. The penultimate object on this path doesn't have its parent pointer changed. It already was pointing to the root r, but anything below the root and its immediate descendant on this path from x will have its parent point updated, and it will be updated to point directly to r. Now, we couldn't get away with this if the tree had to be binary, but it doesn't have to be binary. We couldn't get away with this if we had to satisfy some other constraint like a search tree property, but we don't. So nothing's stopping us from just caching this information about whose everyone's leaders are, because that's really the only information we're responsible from exporting from this union find data structure. So pictorially, if you like thinking about the trees, in effect what path compression does is make the trees shallower and more bushy. So in our example on the upper right, it rips out 1 and 4 and makes them immediate descendants of the root 7. Prefer to think in terms of the array representation, and remember in the array representation, the array index for I is recording the parent of the object I. So in our pink tree, 5, 6, and 7 all point to 7. They all have parent 7. Whereas 2 and 3 have parent 5. 4 has the parent 6, and 1 has the parent 4. And after applying path compression following a find invoked at the object 1, 1 and 4 are redirected to have parent 7. So what are the pros and cons of the path compression optimization? Well, the con side is quite minor. Really, we're just doing a little multitasking on find, and that introduces a small constant factor overhead. We are already doing work proportional to the number of hops on the path from x to its root, and we're still just doing constant work for each node on that path. We're doing an extra constant work for each node after the fact to rewire the parent pointer to point to the root. The pro should be obvious. This is going to speed up all subsequent find operations. You're really making sure you don't redo redundant work. You don't traverse parent pointers over and over and over again. So what's clear is that finds will speed up. What's really not clear is whether they'll speed up by a lot. So is this only going to affect the performance of the find operation by, say, a factor of 2? Or will we get something fundamentally better than the logarithmic performance we were stuck with without path compression? So let me spend a slide on the subtle point of how ranks interact with the path compression optimization. So the plan is we're going to manipulate rank fields with path compression in exactly the same way as we did when we didn't have path compression. So how did we manipulate them previously? Well, at the birth of the union find data structure, everybody has rank 0. Ranks never change except possibly when you do a union. When you do a union, you look at the roots of the two objects whose groups you have to union. You look at their ranks. If one of them has strictly bigger rank, that becomes the root of your new merged tree. The root with a smaller rank is installed as a child underneath. If you union two roots that have exactly the same rank, you pick arbitrarily which of them is the new root, and you bump up its rank by 1. That is how we manipulated ranks before. That is exactly how we're going to manipulate them now. So in particular, when we apply path compression, when we rewire parent pointers following a find, we do not touch anybody's ranks. We leave them all exactly the same. So again, ranks only change in one specific case in a very specific way. Namely, during a union, when we merge two trees that have exactly the same rank, and when we do that kind of union, that kind of merge, whichever of the old roots winds up being the new root, we bump up its rank by 1. That is the only modification we ever make to any ranks. Now, it might bother you that we don't recompute the ranks when we apply path compression. In a way, I sort of hope it does bother you, because by not recomputing ranks, by just manipulating them exactly as before, we're actually losing the semantics of what ranks meant in the previous video. So the key invariant we had, that ranks exactly represented worst case search time to that object, is now lost. The easiest way to see what I'm talking about is probably through an example. So let me redraw the same tree we had on the previous slide, both before and after we apply path compression following a find invoked at the object 1. So what I've done here is in the top tree, before the path compression's been applied, I've labeled ranks just as they were in the previous video. So for each node in the top tree, its rank is equal to the longest path from a leaf to that node. Then I applied path compression from the object 1, resulting in the bushier, more shallow tree on the bottom. And as I said, I did not touch anybody's ranks when I applied this path compression. I didn't do any recomputations. And you'll see now we've lost the semantics for the ranks. Just to give a simple example, there are now leaves that don't have rank 0, that have rank strictly bigger than 0. So what we can say is that for every node, the rank is an upper bound, not necessarily exactly the same as, but at least as big as the longest path from a leaf to that node. But because of the shortcuts that we've installed, we no longer have the equality that we had before. There is good news, however. We can definitely salvage a lot of the technology that we developed in the last video for the union by rank analysis and apply it fruitfully here to the case with path compression. In particular, any statement that we made last video that talks only about the ranks of objects and not about their parent pointers per se, that will be as true with path compression as without. Why? Well, think about making two copies of a union find data structure. Exactly the same set of objects, and now run them in parallel on exactly the same sequence of union and find operations. So by definition, we manipulate the ranks of objects in exactly the same way in the two copies. It doesn't matter if there's path compression or not. So at all moments in time, every object will have exactly the same rank in one copy as it does in the other copy. Path compression or no, doesn't matter. Exactly the same ranks. What's going to be different in the two copies are the parent pointers. They're in some sense going to be further along. They're going to point further up into the tree in the copy with path compression. But no matter, any statement that's purely about ranks, it's going to be equally well true with or without path compression. So in particular, remember the rank lemma that we proved in the last video. That says there's at most n over 2 to the r objects of rank r. That was true without path compression. It's going to be true with path compression, and we're going to use it in the forthcoming analysis. Another fact which is still true with path compression, in fact in some sense it's only more true with path compression, is that whenever you traverse a parent pointer you will get to a node with strictly larger rank. Remember in the last video we said as you go up toward the root you're going to see a strictly increasing sequence of ranks. Here each pointer with path compression represents a sequence of pointers without path compression, so certainly you will still only be increasing in rank every time you traverse a pointer. Let's now quantify the benefit of path compression by proving new performance guarantees on the operations in this union find data structure, and finding the running time bounds are going to blow away the logarithmic bound that we had when we were only doing union by rank without path compression. We're going to do the analysis in two steps, and it's going to be historically accurate in the sense that I'm first going to show you a theorem by Hopcroft and Ullman, which gives an excellent but not quite optimal bound on the performance of this union find data structure, and then we're going to build on the Hopcroft-Ullman ideas to prove Tarjan's even better bound on the performance of this data structure. So here is the performance guarantee that Hopcroft and Ullman proved back in 1973, about 40 years ago. They said, consider a union find data structure implemented as we've been discussing. Lazy unions, union by rank, path compression. Consider an arbitrary sequence of m find and union operations, and suppose the data structure contains n objects. Then the total work that the data structure does to process this entire sequence of m operations is m times log star of n. What is log star of n, you ask? Well, it's the iterated logarithm operator. So by analogy, remember when we first demystified the logarithm, way back at the beginning of part 1, we noticed that log base 2 of a number is just, well, you type that number into your calculator, you count the number of times you divide by 2 until the result drops below 1. So log star, you type the number n into your calculator, you count the number of times you need to hit log before the result drops below 1. So it totally boggles the mind just how slowly this log star function grows. In fact, let me give you a quick quiz just to make sure that you appreciate the glacial growth of the log star function. So the correct answer is B. It is 5. And you should probably spend a couple seconds just reflecting on how absurd this is, right? So you take this ridiculous number, 2 to the 65,000. Remember, the number of atoms in the known universe estimated is way smaller than this. It's just 10 to the 80. So you take this ridiculous number, you apply the log star function, you get back 5. Why do you get back 5? Well, take logarithm once. What do you get back? 65,536, also known as 2 to the 16. So you take log again, you get back 16, also known as 2 to the 4. You take log again, you get back 4, also known as 2 to the 2. You take log again, you get back a 2, and then one more time gets you down to 1. So you can think of log star as the inverse of the tower function, where the tower function takes, think of it as a positive integer t, and it just raises 2 to the 2 to the 2 to the 2 to the 2 t times. And this in particular shows that log star, despite its glacial growth, is not bounded by a constant. This function is not big O of 1. For any constant c you can think of, I can in principle exhibit a large enough n so that log star of my n is bigger than your c. Namely, I can just set n to be 2 to the 2 to the 2 to the so on c times. Log star of that will be at least c. So that's the Hopcroft-Ullman performance guarantee that on average over a sequence of m union and find operations you spend only this ridiculously small log star n amount per operation. We're going to prove it in the next video. In this video we're going to prove our first performance guarantee on the union find data structure with path compression. This is the bound first established by Hopcroft and Ullman. Let me briefly remind you about the guarantee. Consider a union find data structure where you're using lazy unions, you're doing union by rank, and you're using the path compression optimization. Consider an arbitrary sequence, say of m union and find operations. The guarantee is that over the course of this sequence of operations, the total work that you do is at most m, the number of operations, times the glacially growing function log star of n. Remember, log star of n is defined as the number of times you have to apply the logarithm function to n before you get a result which is below 1. Remember, 2 raised to the 65,536, a totally absurd number. Log star of that number is merely 5. So the theorem is true no matter what m is, no matter how many operations you do, whether you do very few, whether you do a whole lot of them. I'm going to focus on the interesting case where m is at least asymptotically as big as n, where m is omega of n. I'll let you think through in the privacy of your own home why the arguments that we're about to see imply the theorem no matter what m is. So one final comment about this guarantee before we turn to its proof. Notice what the theorem is not saying. The theorem is not saying that every single one of these find and union operations runs in big O of log star n time. And that's because that statement in general, which would be stronger, that statement is false. There are going to be operations in general that take more than log star n time. Now, on the one hand, we know no operation is going to be slower than logarithmic time. Even when we didn't have path compression, no operation was worse than log n time, and we're not going to do any worse with path compression. So the worst case time bound is log n, but some operations may indeed run that slowly. But over a sequence of m operations, the average amount of work we do on a per operation basis is only log star of n. This is exactly the sort of so-called amortized analysis that we did in our very first union find implementation with eager unions. We agreed that particular unions might take linear time, but over a sequence of unions we spend only logarithmic time. So the same thing is here, with the exception that we're getting a radically better on average running time bound of log star n over a sequence. So before I launch into the proof details, let's just spend one slide talking a little bit about the proof plan, and in particular, what is the intuition behind the performance that we're trying to make precise, that we're trying to encode in a mathematical way in the proof that's about to follow. Well, if we're hoping to prove a bound better than log n, what we were stuck with without path compression, it better be the case that installing all these shortcuts really qualitatively speeds up finds and unions. And on some level, it's sort of clear that things have to be sped up. We're replacing an old chain of pointers with a single pointer, so you can only go faster. But how do we keep track of this progress? How do we compile this intuition and make it into a rigorous guarantee? So here's the idea. Let's focus on an object x, which is no longer a root. At this point, its parent is somebody other than itself. And one thing I want you to remember from our union by rank analysis is that once an object is not a root, its rank is frozen forevermore. Now, we proved that in the context when there was no path compression, but again, remember, we manipulate ranks in exactly the same way when there is path compression. So that's still true. If you're an object and you're no longer a root, there is no way your rank will ever change again. Now, what we're certainly hoping is true is that finds that originate at, say, this object x are running fast. Not only that, but they should even be getting faster and faster as time goes on because we're doing more and more path compression. So here's the big idea. The way we're going to reason about the worst case running time of the find operation, or equivalently, the longest sequence of parent pointers we might have to traverse to get to a root, is we're going to think about the sequence of ranks that we observe as we traverse these parent pointers from an object x up to the root. Let me give you an example. So what would be the worst case situation? Well, the worst case would be if we have a data structure, and let's say the maximum rank is something like 100, the worst case sequence of ranks, the longest sequence we'd ever see, would be if we start a find operation at an object with rank 0, we traverse a parent pointer, we get to its parent, it has rank 1, we traverse its parent, it has rank 2, then 3, then 4, and so on all the way up to 100. Now remember, ranks have to strictly increase whenever we traverse a parent pointer. As we discussed, that was true with or without path compression. So in the worst case situation, to go from 0 to 100, you have to traverse 100 pointers. So that would be a bummer. Wouldn't it be nice if every time we traversed a parent pointer, the rank increased not just by 1, but by a much bigger number? So for example, if we went from 0 to 10 to 20 to 30 to 40 and so on, that would guarantee that we get to the max rank node 100 in only 10 steps. So again, the bottom line is, if we can have a larger, lower bound on the gap in ranks between an object and its parent, that implies more rapid progress through the possible ranks of the nodes that we could see, and it translates to faster finds, to fewer parent pointer traversals. So with that idea in mind, that big gaps between ranks imply rapid progress, I want to propose as a progress measure for a given non-root object x, the gap between x's rank, which again remember is frozen forevermore, and the rank of its current parent. So this progress measure is a good one for two reasons. First, as we just discussed, if you have a handle on this gap, if you can lower bound it, then that gives you an upper bound on the search time. Secondly, this gap allows us to quantify the benefit of path compression, of installing these shortcuts. Specifically, whenever you install a new shortcut, you rewire an object's parent pointer to point higher up in the tree. Its new parent is going to have rank strictly bigger than its old one. That means this gap is only going to get bigger. Summarizing, path compression improves this progress measure. That is, if an object x previously had a parent p and then has its parent pointer rewired to a different node p prime, the rank of p prime is bigger than the rank of p. And just to make sure this is crystal clear, let's just draw a couple of cartoon examples. So first, just in the abstract, if you think about an object x, suppose it has some parent p, and suppose the root of the tree is some p prime, so some ancestor strictly further up in the tree. Remember, ranks always increase as you go up the tree, as you follow the parent pointers. So that means P's rank is strictly bigger than X. P prime's rank, this is the important thing, is strictly bigger than P. So when you rewire X's parent pointer to point from P no longer, but rather to P prime, it acquires a new parent, and its new parent is an ancestor of its old one, ergo it must have strictly bigger rank. For that reason, the gap between X's rank, which is fixed forevermore, and the rank of its new parent, that gap is bigger than the gap between its rank and the rank of its old parent. You can also see this effect in action with the running 7-object example we were using in the last video. So I've shown that example, that tree in pink, both before and after path compression. And again, before path compression, I just define the ranks as with union by rank, so that the rank of each node is equal to the longest path from a leaf to that node. And then, of course, we don't change the ranks when we apply path compression. And what do we observe? Where exactly 2 of the objects had their parent pointer rewired, namely objects 1 and 4 had their parent pointer rewired to point directly to 7. And as a consequence, the gap in rank between object 1 and its parent has leaped from merely 1, the difference between each rank and the rank of 4, up to 3, the difference between its rank and that of its new parent, 7. Similarly, object 4, its rank gap has jumped from 1 to 2. Its rank is only 1 less than its old parent, 6, but it's 2 less than that of its new parent, 7. So believe it or not, we actually have the 2 crucial building blocks for the Hopcroft-Ullman analysis. Building block number 1 is the rank lemma that we discussed a couple of videos ago. The fact that with or without path compression, you can't have too many objects with a given rank r, namely at most n over 2 to the r. The second building block is the one we just covered, that every time you update a parent pointer under path compression, the gap has to grow between the rank of that object and the rank of its new parent. The rest of the proof is just an optimal exploitation of those 2 building blocks. Let me now show you the details. I need to begin by setting up some notation and definitions. The first one is that of rank blocks. So for a given value of n, the number of objects in the data structure, we define the rank blocks as follows. 0 gets its own block, as does 1. The next block is 2, 3, 4. The next block starts at 5, obviously, and the last entry is going to be 2 raised to the 4th, so 2 raised to the final rank of the previous block, also known as 16. The next block then starts at 17 and goes up to 2 raised to the last rank of the previous block, so 2 raised to the 16, also known as 65,536. And so on until we have enough rank blocks that we capture n. Actually, if you think about it, because ranks can only be log n, we only have to go up to log n, but that actually doesn't affect anything by more than a constant. So let's just go ahead all the way up to n. So how many rank blocks are there? Well, focus just on the largest member of each of the rank blocks. The largest member of a given rank block is 2 raised to the largest member of the previous rank block. So for the tth rank block, roughly what you have as this largest entry is 2 to the 2 to the 2 raised t times. How many times you need to do that before you get n? By definition, you need log star of n. So that's how many rank blocks there are. That's where log star n enters the analysis. So I realize this must be a very inscrutable definition, these weird rank blocks. So let me tell you how you should think about them. They're meant to encode an intuition that we had on the previous slide, where we said, well, we should be happy if the rank of an object's parent is a lot bigger than the rank of that object itself. Why? Well, when we traverse that object's parent pointer, we make a ton of progress through the rank space, and you can only make a ton of progress through the rank space a limited number of times. So that means a small number of parent traversals. That means fast finds. So these rank blocks are just a very clever way of defining sufficient progress, when we're going to be happy with the gap between the rank of an object and the rank of its parent. Specifically, we're happy whenever these 2 ranks lie in different rank blocks. We're not happy if they lie in the same rank block. So for example, if you're at an object and it has rank 8, and you go to its parent and it has rank 18, then we're happy, because 18 is in the rank block after the one that contains 8. On the other hand, if you go from rank 8 to rank 15, then we're not happy. Okay, we're going to call that not a big gap between the rank of the object and the rank of the object's parent. So let's build on that idea to make another definition. So consider a given snapshot in time. That is, we've done some sequence of finds, we've done some sequence of unions. So we're going to call some objects at this point in time good and some of them bad. Here are the criteria by which you are good. So first of all, if you're the root of your tree, you're going to be good. If you're a direct descendant of the root, that is, if your parent is the root of your tree, then you're also good. If not, though, if you're deeper in the tree, then you're going to be good if and only if your parent's rank is in a strictly larger rank block than your own rank. So that is, in the previous example, if your rank is 8 and your parent's is 18, then you're good. If your rank is 8 and your parent's is 15 and your parent's not a root, then you're going to be bad. The role of this definition is to split the work that we do into two parts. First of all, we do some work visiting good nodes. Second of all, we do some work visiting bad nodes. The work we do visiting good nodes will be very easy to bound, no problem. We'll have to do a separate global analysis to bound the total work that we do visiting bad nodes. This dichotomy is exactly the same as something we faced when analyzing Kruskall's algorithm when we implemented it using the union find data structure with eager unions. There, you'll recall, there were some parts of the work in Kruskall's algorithm that were easy to bound just iteration by iteration. For example, every cycle check cost only constant time. But then there was this more complicated type of work, namely all of the leader pointer updates, that we had to bound globally via a separate argument. The exact same thing is going to happen here. Good nodes will be able to bound operation by operation, whereas the bad nodes will have a global analysis controlling the total work done over all of the operations. So more precisely, I've set up the definitions so that the work done visiting good nodes is bounded by big O of log star n every single operation. Indeed, how many good nodes could you possibly visit during a find operation, say from some object x? So you start at x and you traverse these parent pointers going all the way up to the root. Well, there's the root, there's the descendant of the root, so that's 2. So let's set those aside. What about the other good nodes that you encounter on your path? Well, by definition, when you visit a good node, the rank of its parent is in a bigger rank block than the rank of that node itself. That is, every time you traverse a parent pointer from a good node, you will progress to a subsequent rank block. Well, there's only log star n rank blocks, so you can only progress through subsequent ones log star n times, so the total number of good nodes you're going to see is big O of log star n. So now let's go ahead and express the total amount of work that we do over all of the find and union operations and these two quantities. Work done to good nodes, which we now know is just log star n each operation, plus the visits to the bad nodes, which at the moment we have no idea how big it is. So now let's proceed to the global bound on the total amount of work that we perform on bad nodes. And this is really the crux of the whole theorem. So let's just review the definitions real quick. What does it mean that you're a bad node? So first of all, you're not the root. Second of all, you're not a direct descendant of the root. That is, you have a grandparent. And third, it is not the case that your parent's rank is in a later rank block. It's in exactly the same rank block as your own rank. That's what it means that you're bad. So how much work do we spend on bad nodes? Well, let's analyze it one rank block at a time. So fix an arbitrary rank block. Let's say for some integer k, its smallest rank is k plus 1, and its biggest rank is 2 to the k. Now, I told you what our two main building blocks were. The first one is the rank lemma. I'm going to ask you to remember that in a second. But first, I want to put to use our other building block, which is that path compression increases the rank gap between objects and their parents. That's what we're going to use right now. Specifically, consider a find operation and a bad object x that it visits. By virtue of being bad, x is not the root, and it's not a direct descendant of the root. So a root is a higher up ancestor than its parent. Therefore, x's parent pointer will be changed in the subsequent path compression. It will be rewired to point directly to the root, a strict ancestor of its previous parent. Therefore, the rank of its new parent will be strictly bigger than the rank of its previous parent. That's going to keep happening every time that x is visited while it's bad. It keeps getting new parents, and those new parents keep having ranks strictly bigger than the previous one. Well, how many times can this happen before the rank of x's parent has grown so big that it lies in a subsequent rank block? The biggest value in x's rank block, and remember, x is a non-root, its rank is frozen forever, so it's always stuck in this rank block. Once its parent's rank gets updated, let's say at least 2 to the k times, then the rank has to be so big that it lies in the next rank block. At that point, x is no longer bad. Its parent pointer makes so much progress, it goes to another rank block. Now we got to call it good. And of course, once x becomes good in this fashion, it will be good forevermore. It is not a root. It will never be a root again. Its rank is frozen forever, and its parent's rank can only go up. So once you're good, once your parent's rank is sufficiently large, it'll be sufficiently large for the rest of time. All right, so we're almost there. Let's just make sure we don't forget anything that we've done. So the total work, we're bounding in these 2 ways. So first of all, we visit log star n good nodes for each operation. So overall, m operations at O of m log star n for the good nodes. Plus, there's the number of visits over the m operations to the bad nodes. We're going to bound that work globally, but we're going to proceed rank block by rank block. So we're fixing one, ranks k plus 1 up to 2 to the k. What we showed on the last slide is that for every object x whose final frozen rank lies somewhere in this rank block, the number of times it gets visited while it's bad, the number of times it can be visited before it becomes good forevermore, is bounded above by 2 to the k. So we've now used one of our key building blocks, that path compression increases the ranks of parents. Now let's use the other building block, the rank lemma. The rank lemma, you'll recall, says that at any given moment in time and for any possible rank r, the number of objects that currently have rank r cannot be any bigger than n over 2 to the r. So let's use the rank lemma and apply it to upper bound how many nodes could possibly have their final frozen ranks lying somewhere in this rank block. Could have their final frozen rank somewhere between k plus 1 and 2 to the k. So let's just sum over all of the ranks in the rank block. So starting at k plus 1, going up to 2 to the k. By the rank lemma, for a given value of I, we know there's a most n divided by 2 to the I objects that eventually wind up with rank I. And by the usual geometric sum, this whole thing can be upper bounded by n divided by 2 to the k. So this is now starting to look like a magical coincidence, though of course we made a number of definitions in the analysis. Specifically, we structured the rank blocks so that this magic would happen. Specifically, the number of inhabitants of a rank block, n over 2 to the k, times the maximum number of visits to an inhabitant in the rank block while they're bad, times 2 to the k, that's actually independent of the rank block. We multiply these two things together, the number of visits per object 2 to the k, the number of objects n over 2 to the k. What do we get? We get n. Now this was only counting the number of visits to bad objects in a given rank block, but there aren't that many rank blocks. Remember, there's only log star n of them. So that means the total amount of work spent visiting the bad nodes, summed over all of the rank blocks, is big O of n times log star of n. Combining the bounds for the good nodes and the bad nodes, we get quantity m plus n times log star of n. At the beginning, I mentioned that the interesting case is when m is big omega of n. In that case, this bound is just big O of m times log star n. Essentially, if you have a very sparse set of union operations, you can just apply this analysis to each of the directed trees separately. So that's it. That's the full story, a complete analysis of the brilliant Hopcroft-Ullman analysis, log star n on average operation time under path compression. Brilliant as it is, you can do even better. That's the subject of the next couple videos. The Hopcroft-Ullman guarantee states that if you implement a union-find data structure using lazy unions, union by rank, and path compression, then you get a pretty amazing guarantee. Do any sequence you want of m union and find operations. The total amount of work done by this data structure is bounded above by big O of m times log star of n, where n is the number of objects in the data structure. So on the one hand, I hope you're suitably impressed by this result. So the proof of it that we gave in the last video is, frankly, totally brilliant. And secondly, the guarantee itself is excellent, what with log star of n being bounded above by 5 for any imaginable value of n. On the other hand, I do hope there's sort of a little voice inside you wondering if this log star bound could really be optimal. Can we do better, maybe by a sharper analysis of the data structure we've been discussing, or perhaps by adding further ingenuity, further optimizations to the data structure? For all we know, you might be able to get away with a linear amount of work, so O of m work to process an arbitrary sequence of finds and unions. It turns out you can do better than the Hopcroft-Ullman guarantee. There is a sharper analysis of the exact same data structure. That analysis was given by Tarjan, and here is the statement of his guarantee. So the improved bound states that for an arbitrary sequence of m union and find operations, the total work done by this data structure, union by rank and path compression, is big O of m times alpha of n. Now, what, you may ask, is alpha of n? That's a function known as the inverse Ackermann function. So what, then, is the inverse Ackermann function? Well, the short answer is that it's a function that, incredibly, grows still more slowly, in fact, much, much, much more slowly, than the log star function we discussed in the Hopcroft-Ullman bound. The precise definition is non-trivial, and that is the subject of this video. In the next video, we'll prove this theorem and explain how the inverse Ackermann function arises in an optimal analysis of union by rank with path compression. So I'll first define the Ackermann function, and then I'll describe its inverse. One thing I should warn you is you will see slight variations on these two definitions out there in the literature. Different authors define them in ways convenient for their own purposes. That's also what I'm going to do here. I'm going to take one particular definition, convenient for the union find data structure analysis. All of the variants that you'll see out there in the literature exhibit roughly the same ridiculous growth, so the details aren't really important for the asymptotic analysis of data structures and algorithms. So you can think of the Ackermann function as having two arguments, which I'm going to denote by k and r. Both of these are integers. K should be at least 0, r should be at least 1. The Ackermann function is defined recursively. The base case is when k equals 0. For all r, we define a sub 0 of r as the successor function. That is, it takes as input r and it outputs r plus 1. In general, when k is strictly positive, the argument r tells you how many times to apply the operator, the function, ak minus 1, starting from the input r. That is, it's the r-fold composition of a sub k minus 1, and again applied to the argument r. So in some sense, describing the Ackermann function isn't that hard, right? I didn't really need, that much of a slide to actually write down its description. But getting a feel for what on earth this function is takes some work. So the first thing, maybe just as a sanity check, is note that it is a well-defined function. So, you're all programmers, so you could easily imagine writing a program which took as input k and r, and, at least in principle, given enough time, computed this number. It would be a very simple recursive algorithm with a pseudocode just following the mathematical definition. So it is some function, given k and r, there is some number that's the result of this definition. Now, in the next sequence of quizzes, let's get a feel for exactly how this function behaves. And so let's start on the first quiz just by fixing k to be 1, and now viewing the Ackermann function with k fixed at 1 as a function purely of r. So what function does a1 of r correspond to? All right, so the correct answer is B. At least A1 is quite simple to understand. All it does is double the argument. So if you give it R, it's going to spit out 2R. So why is that? Well, A1 of R, by definition, is just the function A0 applied to R, R times. A0, by definition, is the successor function. It adds 1. So if you apply the successor function R times starting from R, you get 2R as a result. So let's now move from A1 to A2. So let's think about exactly the same question, fixing k at 2 and regarding it as a function of r only. What function is it? So the answer here is C. For every positive integer r, a2 of r is equal to r times 2 to the r. And the reasoning is the same as before, so remember a2 of r just means you apply a1 r times. In the last quiz we discovered that a1 was doubling, so if you double r times, that has the effect of multiplying by a 2 to the r factor. So let's take it up a notch yet again. Let's bump up k to 3, and let's think about a sub 3. But let's not yet think about exactly what a sub 3 is as a function of r. Let's keep things simple. What is just a sub 3 evaluated when r equals 2? So k equals 3, r equals 2. That's a number. What number is it? Okay, so the correct answer is the third one. It's 2048, also known as 2 to the 11th. Let's see why. Well, a sub 3 of 2, that just means we apply a sub 2 twice to 2. Now, in the last quiz, we evaluated not only a sub 2 of 2, but a sub 2 of all integers r. We discovered it was r times 2 to the r. So that means it's a simple matter to evaluate this application of a sub 2 twice. First, a sub 2 of 2, that's just 2 times 2 to the 2, also known as 8. And then a sub 2 of 8 is going to be 8 times 2 to the 8, also known as 2 to the 11, or 2048. So what about in general? How does the function a sub 3 behave as a function of a general parameter r? Well, when we answer this question, we're going to see for the first time the ridiculously explosive growth that the Ackermann function exhibits. And this will just be the tip of the iceberg, right? This is just when k equals 3. So by definition, a sub 3 of r, you start from r and you apply the function a sub 2 r times. So let's remind ourselves what the function a sub 2 is. We computed that exactly. That's r times 2 to the r. So to make our life simple, let's just think about the 2 to the r part. So in the real function a sub 2, you also multiply by r. But let's just think about the 2 to the r part. So imagine you applied that function over and over and over again. What would you get? Well, now you get a tower of 2's, where the height of the tower is the number of times that you apply that function. Right? If you apply it once, you get 2 to the r. If you apply it twice, you're going to get 2 raised to the 2 to the r. 3 times 2 to the 2 to the 2 to the r, and so on. So r applications of a sub 2 gives you something that's even bigger than a tower of r2's. So let's move on to A4, and this is the point at which, personally, my brain begins to hurt. But let's just push it a little bit further so that we appreciate the ridiculous growth of the Ackermann function. And as with A3, let's punt for the moment on understanding the dependence for a general r. Let's just figure out what a sub 4 of 2 is. So k equals 4, r equals 2. Well, so this by definition, you just take 2 and you apply a sub 3 twice. We computed a sub 3 of 2 in the previous quiz. We discovered that was 2048, so that's the result of the first application of A3. And now we find ourselves applying A3 to 2048. So in effect, R now is 2048. And remember, we concluded the last slide by saying, well, A sub 3, whatever it is, it's at least as big as a tower of R2's. And here R is 2048. So this, of course, is now the land of truly ridiculous numbers that we're dealing with. I encourage you to take a calculator or a computer and see how big a tower of 2's you can even compute. And it's not going to be anywhere close to 2000. I can promise you that. And hey, that's just a4 of 2. What about the function a4 for a general value of r? Well, of course, in general, a4 of r is going to be r applications of a3 starting at r. Now, in the last slide, we argued that a sub 3, this function is bounded below by a tower function. So a sub 3 takes in some input, some integer, and it spits out some tower with height equal to that integer. So what happens when you apply that tower function a3 over and over again? Now you get what's called an iterated tower function. So when you apply the function a sub 3 for the first time to r, it's going to spit out a number which is bounded below by a tower of height r, a tower of 2's, r of them. Now when you apply a sub 3 a second time, its output is going to be a tower of 2's whose height is lower bounded by a tower of 2's of height r, and so on. Every time you apply a sub 3, you're just going to iterate this tower function. You will sometimes see the iterated tower function referred to as a wowzer function. You probably think I'm pulling your leg, but I'm not kidding. You can look it up. So that is the Ackermann function and a bunch of examples to appreciate just how ridiculously quickly it is growing. So now let's move on to define its inverse. Now the Ackermann function has two parameters, k and r, excuse me. So to define an inverse, I'm going to fix one of them. Specifically, I'm going to fix r equal to 2. So the inverse Ackermann function is going to be denoted by alpha. For simplicity, I'll define it only for values of n that are at least 4. And it's defined for a given value of n as the smallest k, so that if you apply a sub k to 2, to r equals 2, then the result is at least n. So again, it's simple enough to kind of write down a definition like this, but you really have to plug in some concrete numbers to get a feel for what's going on. So let's just write out, what are the values of n that will give you alpha of n equal 1, that'll give you alpha of n equal 2, alpha of n equal 3, and so on. Okay, so for starters, alpha of 4 is going to be equal to 1, right? So if you applied a 0 to 2, that's the successor function, so you only get 3. So that's not at least as big as 4. On the other hand, if you apply a sub 1 to 2, that's the doubling function, so if you apply it to 2, you get 4. So a sub 1 does give you a number which is at least as big as n when n is 4. So next, I claim that the values of n for which alpha of n equals 2 are the values 5, 6, 7, and 8. Why is that true? Well, if you start from 2 and you apply the function a sub 1, the doubling function, you only get 4. So a sub 1 is not sufficient to achieve these values of n's. On the other hand, if you apply a sub 2 to 2, remember that's the function which given an r outputs r times 2 to the r. So when you apply it to 2, you get 2 times 2 to the 2, also known as 8. So a sub 2 is sufficient to map 2 to a number at least as big as 8. By the same reasoning, recall that we computed a sub 3 of 2, and we computed that to be 2048. So therefore, for all of the bigger values of n, starting at 9 and going all the way up to 2048, their alpha value is going to be equal to 3, because that is the smallest value of k, such that a sub k of 2 is at least those values of n. And then things start getting a little bit ridiculous. So remember, we also lower bounded a sub 4 of 2. We said that's at least a tower of 2's of height 2048. So for any n up to that value, up to a tower of 2's of height 2048, alpha of those n's is going to be equal to 4. This, of course, implies that the inverse Ackermann function value of any imaginable number is at most 4. And I don't know about you, but my brain is already hurting too much to think about which are the values of n such that alpha is equal to 5. So as a point of contrast, let's do the same experiment for the log star function so that we get some appreciation about how, as glacially growing as log star may be, the inverse Ackermann function is growing still qualitatively slower. So the log star function, remember, is the iterated logarithm. So it's starting from n, how many times you need to hit log on your calculator, let's say base 2, before the result drops below 1. So when is log star of n going to be equal to 1? Well, that's when n is going to be equal to 2. Then you hit log once and you drop from 2 to 1 and you're done. If n equals 3 or 4, then you need more than one application of logarithm to drop below 1, but you only need 2 applications. So log star of n is going to be 2 for n equals 3 and 4. Similarly, for n anywhere between 5 and 16, log star n is going to be equal to 3, right? If you start from 16, that's 2 to the 4. So if you apply log once, you get 4. A second time, you get 2. A third time, you get 1. By analogy, the values of n for which log star of n equals 4 are going to be starting at 17 and going up to 2 to the 16, also known as 65,536. So let's just go one more step for which n is log star of n equal to 5. Well, obviously we start at 65,537 and we end at 2 raised to the largest number of the previous block. So 2 raised to the 65,536. So these numbers are impressive enough on the right-hand side. There is no imaginable number of importance for which log star is going to be bigger than 5. Looking at the left and the right-hand sides, though, we see that there really is a qualitative difference between the rate of growth of these two functions, with the inverse Ackermann function in fact growing much, much slower than the log star function. So perhaps the easiest way to see that is to look at the right-hand side, and on each of the lines on the right-hand side, look at the largest value of n so that log star is a given number. So for example, in the third line, the largest n such that log star of n equals 3 is a tower of 2's of height 3, 2 to the 2 to the 2, also known as 16. Similarly, on the fourth and fifth lines, the largest n that give values of log star equal to 4 and 5 are a tower of 2's of height 4 and a tower of 2's of height 5. On the other hand, look at the fourth line on the left-hand side. So already when we ask about the largest values of n that have inverse Ackermann value 4, we're talking about towers of 2s, in fact of height 2048. So that is, the n's, which give us alpha of n equal to 4, we would have to write down 2048 lines on the right-hand side before we had values of n that were equally big. This indicates how the log star function, while growing glacially indeed, is nevertheless moving at light speed compared to the inverse Ackermann function. So in this video, we're going to prove Tarjan's inverse Ackermann bound and the performance of the union find data structure with union by rank and path compression. Frankly, I hope you're kind of excited. This is one of the crown jewels in the entire history of algorithms and data structures. Let me remind you what the bound says. You've got a union find data structure. We're doing lazy unions. We're doing union by rank. We're doing path compression. And for an arbitrary sequence of m, find, and union operations, the total amount of work you do over the sequence of operations is bounded above by m times alpha of n, where n is the number of objects in the data structure, and alpha is the inverse Ackermann function that we defined in the previous video. I want to give a shout out here to Dexter Cozen's beautiful book, The Design and Analysis of Algorithms. It is his analysis that I will be following closely here. So it's true that merely stating Tarjan's bound is non-trivial. We had this entire video defining the Ackermann function and its inverse so we could make sense of the statement. That said, we're well positioned to prove Tarjan's bound. In fact, the template of the proof is going to very much mirror what we already did for the log star analysis by Hopcroft and Ullman. So in that spirit, let's review what were the two basic workhorses, the two building blocks that drove forward the Hopcroft-Ullman analysis. So the first building block is the rank lemma, which dates back all the way to the video's pre-path compression. And remember, the rank lemma gives us control on how many objects can exist with a given rank. And in particular, that upper bound is decreasing exponentially with the rank. It's n over 2 to the r objects at most with a given rank r. But of course, we needed a second building block to exploit the fact that we were using the path compression optimization. So how did we quantify the progress made by path compression? Well, we argue that every time a node has its parent pointer updated in path compression, it acquires a new parent with strictly larger rank. So you can think of the Hopcroft-Ullman analysis as a clever and essentially optimal exploitation of these two building blocks. How did we use them? Well, we defined a notion of rank blocks, and each rank block had size 2 raised to the size of the previous rank block. Why were rank blocks useful? Well, they allowed us to measure progress as we followed parent pointers. We defined an object to be good if following its parent catapulted you into a subsequent rank block. Because there's only a log star number of rank blocks, you can only visit log star good nodes on any given find operation. So that gave us a per operation bound of a log star for visits to good nodes. And then for visits to bad nodes, we used the second building block to argue that every time you visit a bad node, the rank of its parent increases. And that can only happen so many times before the rank of this object's parent is so much bigger than this object's rank itself that the node has to be good. You have to make a lot of progress by following its parent pointer. And the point is, if we want to do better than the Hopcroft-Ullman analysis, we're not going to do better by taking these same two building blocks and exploiting them in a better way. That can't be done. So what we need to do is have a better version of one of the two building blocks. So the key idea in Tarjan's analysis is to have a stronger version of the second building block. We're going to argue that path compression doesn't merely increase the rank of nodes' parents by 1, but in fact, it increases typically the rank of objects' parents by a lot. And what's kind of amazing is the length of the proof we're about to do is really basically the same as that in the Hopcroft-Ullman analysis, and the steps match up almost perfectly. So the bound is even better, the argument is even more ingenious, it's even harder to imagine how one would come up with this idea oneself. But as far as checking it, as far as understanding it, the complexity level is roughly the same as what we've already done in the log star analysis. So here we go. So in this slide, I'm going to give you a definition, and the point of the definition is to measure how much progress we make in terms of ranks when we follow a node's parent pointer. So the definition here is going to play exactly the same role that the definition of rank blocks played in the Hopcroft-Ullman analysis. So what I'm going to define is a number, a statistic, measuring the difference, the gap, between the rank of an object and the rank of its parent. So this definition is only going to make sense for non-root objects X. One thing I want you to remember from previous videos is that once an object is not a root, it will never again be a root, and its rank will never again change. So non-root objects have rank fixed forevermore. So we're going to use the notation delta of x for the statistic, and the definition of delta of x is the largest value of k, such that a sub k, this is the Ackermann function, remember, such that a sub k applied to the rank of this object x is bounded above by the rank of x's parent. So the bigger the gap between the rank of x's parent and x's rank, the bigger the value of delta of x. So let me talk through some simple examples just to make sure this makes sense and also review the Ackermann function a little bit. So first of all, let me just point out that delta of x is always non-negative for any non-root object x. So why is this true? Well, remember, and this goes all the way back to our union by rank discussion, the rank of an object's parent is always at least one more than the rank of that object. And the function a sub 0, recall, we define just as the successor function. So for every object that's not a root, it's always true that its parent has rank at least one more than it, and that means we can always at least take k to be 0 and have this inequality be satisfied. Now, when is it going to be true that an object x has a delta value at least equal to 1? Well, that is equivalent to stating we can take k to be 1 in this inequality, and the inequality holds. So let's remember, what is the function a sub 1? In the previous video, we discovered that was just the doubling function. So we can take k equal to 1 and have this inequality satisfied if and only if the rank of the node's parent is at least double the rank of that object. Similarly, an object x has a delta value equal to at least 2 if and only if we can take k equal to 2 on this right-hand side of the definition and have this inequality be satisfied. So let's recall what the function a sub 2 is. A sub 2 of r is just r times 2 to the r. So an object x has delta value equal to 2 if and only if its parent's rank is substantially bigger than its own rank, in the sense that if it has rank r, its parent's rank has to be at least r times 2 to the r. And in general, the bigger the value of delta, the bigger the gap between the rank of the object x and the rank of its parent. And of course, because the Ackermann function grows so ridiculously quickly, the gap between this object's rank and its parent's rank is growing massively as you take delta to be larger and larger. So now that we understand this better, one thing that should be clear is that the delta value of an object x can only go up over time. Right, so remember, we're talking only about non-root objects x, so the x's rank itself is frozen forevermore. The only thing that's changing is it's acquiring potentially new parents through path compression, and each new parent's rank is bigger than the previous one, so the gap in the ranks is only going up, and therefore the delta value of this object x can only go up over time. So one final comment, you'll recall in the Hopcroft-Ullman analysis, the way we defined rank blocks ensured that there weren't too many of them, there were only log star. Similarly here, the way we're defining the statistic delta guarantees that there are not too many distinct delta values that objects can take on. So we've already argued that delta is an integer that's at least 0, and we can also bound it from above, at least for any object x that has a rank at least 2, which will be good enough for our purposes. If an object x has rank at least 2, its value of delta cannot be any larger than the inverse Ackermann of n, than alpha of n. And this is really just by the way we define the inverse Ackermann function alpha. We defined it as the smallest value of k, such that if you apply a sub k to 2, that catapults you beyond n. And since ranks of objects are bounded above by n, actually they're even bounded above by log n, but in particular by n, that means you'll never see a delta value bigger than alpha of n for any object x that has a rank at least 2. So that completes the definition of the statistic delta of x, and once again the point of this statistic is to quantify progress through rank space as we traverse a parent pointer from an object. So in the Hopcroft-Ullman analysis, we used rank blocks for that purpose. Here we're using the statistic delta of x, and now we have to redefine good and bad objects to reflect this different measurement for progress, for gaps between ranks of objects and ranks of their parents. So that's what I'm going to provide for you on this slide, a definition of good and bad nodes. And this definition will play exactly the same role as it did in the Hopcroft-Ullman analysis. For the good nodes, we'll be able to just get a per operation bound for how many visits we make to them. And then we'll be stuck with, and this will be the main part of the proof, a global analysis arguing that the total number of visits to bad nodes over a sequence of operations cannot be too big. So the bad objects will be those that meet the following set of 4 criteria. If an object fails to meet any of these 4 criteria, it will be called good. So the first 2 criteria will be familiar from the Hopcroft-Ullman analysis. So first of all, roots get a pass, and direct descendants of roots also get a pass. So to be bad, it must be the case you're neither a root nor are you the child of a root. So what's the motivation for these 2 criteria? Well, it's exactly the same as it was in the Hopcroft-Ullman analysis. It's just to ensure that bad nodes, after they're visited on a find, get their parent pointer updated. So remember, when you do path compression, after you've done a find from an object x all the way up to its corresponding root, everybody's parent pointer gets updated except for the root and except for the child of the root. Those 2 nodes keep the same parent pointer. So to make sure we have progress, we want to exclude the root and the direct descendants of the root from being bad. We'll account for them separately. The third criterion is not conceptually important, it's just for technical convenience, sort of an artifact of the way I've defined the inverse Ackermann function. We're going to give nodes that have rank 0 or 1 also a free pass. So in order to be bad, we're only going to worry about the case where the rank is at least 2. So the final criterion is really the ingenious one, and it's the one that ensures that when you do path compression, typically objects' parents' ranks will increase extremely rapidly, not just by 1. And this criterion says for an object x to be bad, it has to be the case that it has some ancestor y. So an object you get to by traversing parent pointers from x that has exactly the same value of delta. So if an object x has delta of x equal to 2, for it to be bad, there has to be some ancestor object y that also has a delta value equal to 2. And again, if x fails to meet any of these 4 conditions, then x gets a pass. X is called a good object. Now, I said that the role of this definition is going to be to split the work done into 2 groups, and that we're going to be able to easily bound, even on a per operation basis, the number of visits to a good node. So the next quiz asks you to think about that carefully. All right, so the correct answer is B. It's theta of the inverse Ackermann function of n. And this is really one of the points of how we define good and bad nodes. We guarantee that there cannot be too many good nodes whenever we do a find operation. So to see why this is true, let's just count up the number of nodes along a path that can fail to meet each of the 4 criteria. Well, so the first criterion was we give roots a free pass. So there's at most 1 node that's good because it's a root. Similarly, on a given path, there's at most 1 object on that path that's a direct descendant of the root. Because ranks always strictly go up when you follow parent pointers, there can be at most 1 object of rank 0 and at most 1 object of rank 1. So at most 2 objects get a free pass because of the third criterion. Well, so let's think about the interesting case, nodes that are good because they fail to meet the 4th criterion. How many can there be? Well, let's focus on a particular value of delta. So let's say, think about all of the objects along a path that have delta of x equal to 3. There may well be lots of objects on this path with delta of x equal to 3. Maybe there's like 17 of them. Call the highest, the closest to the root, such object z. Of these 17 objects with delta of x equal to 3, z is going to be the only one that is good. The other 16 objects with delta of x equal to 3 are going to be bad. Why? Well, any object other than z has an ancestor, namely z, with exactly the same delta value. So those 16 objects do meet the 4th criterion. They will be classified as bad. Summarizing, for each of the alpha of n possible values of delta, only the uppermost object, the object closest to the root with that particular delta value, can possibly be classified as good. So that bounds at alpha of n the number of objects that fail to meet this 4th criterion. That gives us the total bound on the number of good nodes on any path. So just like in the Hopcroft-Ullman analysis, we're going to think about the total amount of work done by our union find data structure as constituting two pieces, work done visiting good nodes and work done visiting bad nodes. The previous quiz says that we have a bound on visits to good nodes even on a per operation basis. At most, inverse Ackermann of n good nodes are visited every single operation. What remains is to have a global bound on the number of visits to bad nodes. The argument will be to show that over an arbitrary sequence of M find and union operations, the total number of visits to bad nodes is bounded above by big O of n times alpha of n. So here is the crux of the argument. Here is why, when you do a visit to a bad node, the subsequent path compression massively increases the gap between that object's rank and the rank of its parent. So let's freeze the data structure at the moment where a find operation makes a visit to a bad object. Call that bad object X. Let's think about what the data structure must look like in this scenario. So we've got our bad object X. It may or may not have nodes pointing to it. We're not going to care. By virtue of it being bad and meeting the third criterion, we know the rank of X is at least 2. Its delta value could be anything. Whatever it is, let's call it K. So because X is not a root, it has some parent. Call that parent P. And not only does X have ancestors, but because it meets the fourth criterion, we actually know it has an ancestor Y who has the same delta value as X. That is, it has an ancestor Y with delta of Y equal to K. It is possible that P and Y are the same object, or they could be different. It's not going to matter in the analysis. So recalling that the statistic delta is only defined for non-roots, we can conclude that Y is also not the root. It must then have some parent, call it P prime. P prime might be a root, or it might not. We don't care. So now let's understand the effect of the path compression, which is going to happen subsequent to this find operation. X's parent pointer is going to be rewired to the root of this tree. The root of this tree is either at P prime or even higher than that. Given that fact, let's understand how much bigger the rank of X's new parent, P prime or higher, is compared to the rank of its old parent, P. So the rank of X's new parent is at least the rank of P prime. So if P prime is in fact the root, then the rank of X's new parent is just the rank of P prime. Otherwise, its new parent is even higher than P prime. And since ranks only increase going up the tree, that means it would be only higher than the rank of P prime. How does the rank of P prime compare to its child, that of its child Y? Well, and here's a key point, because delta of Y is equal to K, remember what the definition of delta is. It quantifies the gap between the rank of an object and that of its parent. We're going to use that here for Y and its parent P prime. It means the rank of P prime is so big, it's at least the function A sub K applied to Y's rank. So our third and final inequality is the same as the first one. So it could be the case that Y actually is the same as P. It actually is X's old parent. In that case, the rank of X's old parent is precisely the rank of Y. Otherwise, Y is even higher up than X's old parent P, and therefore, by the monotonicity of rank, the rank of Y is even bigger than the rank of X's old parent. So now in this chain of inequalities, I want you to focus on the leftmost quantity and the rightmost quantity. What does this say at the end of the day? It says when you apply path compression to X, it acquires a new parent, and the rank of that new parent is at least the A sub K function applied to the rank of its old parent. Again, path compression at the very least applies the A sub K function to the rank of X's parent. So now let's suppose you visit some bad object X, not just once, but the same object X while it's bad over and over and over again. This argument says that every such visit to the object X while it's bad applies the function A sub K to the rank of its parent. So in particular, let's use R to denote the rank of this bad object X. And again, by virtue of it being bad, R has to be at least 2. Imagine we do a sequence of R visits to this object X while it's bad. Each of those visits will result in it acquiring a new parent, and that new parent's rank is much bigger than the rank of the previous parent. It's at least a sub k applied to the rank of the previous parent. So after r visits, that's applying the function a sub k r times to the rank of x's original parent, which of course has rank at least that of x, at least r. Well, we have another name for applying the function a sub k r times to r. Remember, this is just by definition of the Ackermann function, a sub k plus 1 applied to r. So what does this mean? Well, this means that after r visits to a bad object x that has rank r, the rank of x's parent has to have grown so much that that growth is reflected in our statistic delta that measures the gap in the rank between an object and the object's parent. So remember how we define delta of x? It's the largest value of k so that the rank of x's parent is even bigger than a sub k applied to the rank of x. So what this inequality shows is that every r parent pointer updates to x allow you to take k to be even bigger than before. You can bump up k by 1 and still have this inequality be satisfied. That is, every r visits to a bad object of rank r, delta has to increase by at least 1. But there's only so many distinct values that the statistic delta of x can take on. It's always non-negative, it's always an integer, it can only increase, and it's never bigger than the inverse Ackermann function alpha of n. So therefore, the total number of visits to an object x while it's bad over an arbitrary sequence cannot be more than r, the number of visits needed to increment delta of x, times the number of distinct values, which is alpha of n, the inverse Ackermann function. So now we've done all the hard work. We're almost there. We just need one final slide putting it all together. All right, so to see how all of this comes together, let's first recall that all that we need to do is bound the total number of visits to bad objects over this entire sequence of union and find operations. So in the previous slide, we showed that for a bad object x with rank r, the total number of times it's visited while it's bad is bounded above by r times the inverse Ackermann function of n. So let's sum that over all of the objects to get our initial bound on the total number of visits to bad objects. So now we have to be a little careful here because there are n objects x, and ranks can be as large as log n. So a naive bound would give us something like n times log n times alpha of n. And that's not what we want. We really want n times alpha of n. So we need to use the fact that not all nodes can have big rank. And that's exactly what the rank lemma says. So to rewrite this in a way that we can apply the rank lemma, bounding the number of objects with a given rank, let's bucket the objects according to their rank. So rather than summing over the objects, we're going to sum over possible ranks r, and then we're going to multiply times the number of objects that have that rank r. While I'm at it, let me pull the alpha of n factor, which doesn't depend on the object, out in front of the sum. For every value of r, the rank lemma tells us there are at most n over 2 to the r objects with that rank. So this factor of n is independent of the rank r, so let me pull that out in front of the sum. And when the dust settles, we get n times the inverse Ackermann function of n times the sum over non-negative integers r of r divided by 2 to the r. So we've seen this kind of sum without the r in the numerator, just a geometric sum 1 over 2 to the r. We know that's bounded by a constant. And more generally, throwing an r in the numerator, well, that's no match for this exponentially decreasing denominator. So this sum still evaluates to a universal constant. I'll let you check that in the privacy of your own home. And so that gives us a bound of big O of n times the inverse Ackermann function of n on the total number of visits to bad objects. Since we also have a per operation bound of alpha of n on the number of visits to good nodes, combining the work of the two cases, we get O of m plus n times inverse Ackermann function of n. And again, the interesting case here is when m is big omega of n. Otherwise, you can just do this analysis separately for each tree in the data structure. And there you have it. You now understand in full detail one of the most amazing results in the history of algorithms and data structures. So Tarjan's bound is unimaginably close to being linear without actually being linear. It's off by this inverse Ackermann function factor. Now, from a practical perspective, for any imaginable value of n, alpha of n is at most 4. So this gives you a linear time bound for imaginable values of n. In fact, even the Hopcroft-Ullman log star bound, log star is at most 5 for any imaginable value of n. So that also is, in essence, linear time bound for all practical purposes. But theoretically speaking, we have not proven a linear time bound on the amount of work done by the union-find data structure. So the Pavlovian response of any algorithms researcher worth their salt would be to ask, can we do better? And we could ask that question in a couple different senses. The first sense would be, well, maybe we can have a sharper analysis of this exact data structure. Maybe union by rank and path compression is sufficient to guarantee a linear amount of work. After all, we didn't need to change the data structure. We only needed to change the analysis to sharpen the log star bound to an alpha of n bound. So this question, remarkably, Tarjan answered in the negative in his original paper. He showed that if you use this exact data structure, union by rank and path compression, then there are arbitrarily large sequences of unions and finds on arbitrarily large collections of objects, so that this data structure actually performs asymptotically m, the number of operations, times the inverse Ackermann function of n, the number of objects, amount of work. That is, keeping the data structure fixed, this analysis cannot be asymptotically improved. This data structure fundamentally has worst case performance governed by this insane inverse Ackermann function. So this is already a mind-boggling fact, and indeed Tarjan, in the conclusion of his paper, notes that it's remarkable to have such a simple algorithm with such a complicated running time. But you can also ask the question, could we do better perhaps by improving or changing the data structure? After all, by adding path compression, we got a qualitative improvement in the average operation time. It dropped from log to alpha of n. Perhaps there's yet another optimization out there waiting to be discovered that would drop the amount of work per operation over a sequence down to constant time per operation, linear work overall. Tarjan, in his paper, made the bold conjecture that there is no linear time method, no matter how clever you are, and remarkably, that conjecture has since been proved. It was proved for certain classes of data structures, both in Tarjan in his original paper and in a follow-up paper in '79, but the final version of this conjecture was proven by Friedman and Sachs back in 1989. No matter how clever you are, no matter what union-find data structure you come up with, there will be arbitrarily long sequences of operations so that the average amount of work you do per operation is the inverse Ackermann function of the number of objects in the data structure. Pretty unbelievable. So let me just wrap up with a historical comment. So full disclosure, I wasn't quite alive when this result came out, but in reading about it and talking to senior researchers about it, my sense is that it was really sort of a watershed moment for the field of data structures and algorithms. Specifically, it confirmed the belief of people working in algorithms and data structures that the field possessed surprising depth and beauty. There had, of course, been earlier glimpses of this. We mentioned in the optional material in Part 1, Knuth's analysis of linear probing back in the early 1960s, but this was really something for the worst-case analysis of algorithms and data structures. So the fact that such a practical and naturally arising problem in algorithms and data structures requires, necessarily, the understanding of the Ackermann function and its inverse. A function, mind you, which was first proposed and defined back in the 1920s in the service of recursion theory, almost 10 years before Turing was doing his work on models of computation, was a real eye-opener, and it showed that this field is something that would keep many generations of scientists quite busy for many years to come. So this set of lectures will be our final application of the greedy algorithm design paradigm. It's going to be to an application in compression. Specifically, I'll show you a greedy algorithm for constructing a certain kind of prefix-free binary codes known as Huffman codes. So we're going to spend this video just sort of setting the stage. So let's begin by just defining a binary code. So a binary code is just a way to write down symbols from some general alphabet in a manner that computers can understand. That is, it's just a function mapping each symbol from an alphabet capital sigma to a binary string, a sequence of zeros and ones. So this alphabet capital sigma could be any number of things, but as a simple example, you could imagine it's the letters A through Z, say in lowercase, plus maybe the space character and some punctuation. So maybe for a set of size 32 overall. And if you have 32 symbols you need to encode in binary, well, an obvious way to do it is there happens to be 32 different binary strings of length 5, so why not just use one of each of those for your symbols? So this would be a fixed length code in the sense we're using exactly the same number of bits, namely 5, to encode each of the symbols of our alphabet. This is pretty similar to what's going on with ASCII codes. And of course, it's a mantra of this class to ask when can we do better than the obvious solution. So in this context, when can we do better than fixed length codes? Sometimes we can, in the important case when some symbols are much more likely to appear than others. In that case, we can encode information using fewer bits by deploying variable length codes. And this is, in fact, a very practical idea. The variable length codes are used all the time in practice. One example is in encoding MP3 audio files. So if you look up the standard for MP3 encoding, there's this initial phase in which you do analog to digital conversion, but then once you're in the digital domain, you do apply Huffman codes, what I'm going to teach you in these videos, to compress the length of the files even further. And of course, as you know, compression, especially lossless compression, like Huffman codes, is a good thing. You want to download a file, you want it to happen as fast as possible, or you want to make the file as small as possible. So a new issue arises when you pass from fixed length codes to variable length codes. So let me illustrate that with a simple example. Suppose our alphabet sigma is just 4 characters, A, B, C, D. So the obvious fixed length encoding of these characters would just be 00, 01, 10, and 11. Well, suppose we wanted to use fewer bits and we wanted to use a variable length encoding. An obvious idea would be to try to get away with only 1 bit for a couple of these characters. So suppose instead of using a double 0 for A, we just use a single 0, and instead of using a double 1 for D, we just use a single 1. So that's only fewer bits, so that seems like that can only be better. But now here's the question. Suppose someone handed you an encoded transmission consisting of the digits 0, 0, 1. What would have been the original sequence of symbols that led to that encoded version? All right, so the answer is D. There is not enough information to know what 001 was supposed to be an encoding of. The reason is that having passed to a variable length encoding, there is now ambiguity. There is more than one sequence of original symbols that could have led under this encoding to the output 001. Specifically, answers A and C would both lead to 001. The letter A would give you a 0, the letter B would give you a 01, so that would give you 001. On the other hand, AAD would also give you 001, so there's no way to know. Contrast this with fixed length encoding. If you're given a sequence of bits with a fixed length code, of course you know where one letter ends and the next one begins. For example, if every symbol was encoded with 5 bits, you would just read 5 bits, you'd know which symbol it was, you'd read the next 5 bits, and so on. With variable length codes, without further precautions, it's unclear where one symbol starts and the next one begins. So that's an additional issue we have to make sure to take care of with variable length codes. So to solve this problem, that with variable length codes and without further precautions, it's unclear where one symbol ends and where the next one begins, we're going to insist that our variable length codes are prefix free. So what this means is when we encode a bunch of symbols, we're going to make sure that for each pair of symbols I and J from the original alphabet sigma, the corresponding encodings will have the property that neither one is a prefix of the other. So going back to the previous slide, you'll see that that example was not prefix free. For example, we used 0 was a prefix of 01. That led to ambiguity. Similarly, 1, the encoding for D, was a prefix of 10, the encoding for C, and that also leads to an ambiguity. So if you don't have prefixes for each other, and we'll develop this more shortly, then there's no ambiguity. Then there's a unique way to decode, to reconstruct what the original sequence of symbols was, given just the 0s and 1s. So lest you think this is too strong a property, certainly interesting and useful variable length codes exist that satisfy the prefix free property. So one simple example, again, just to encode the letters A, B, C, D, we can get away with encoding the symbol A just using a single bit, just using a 0. Now, of course, to be prefix free, it better be the case that our encodings of B and C and D all start with the bit 1. Otherwise, we're not prefix free. But we can get away with that. So let's encode a B with a 1 and then a 0. And now both C and D better have the property that they start neither with 0 nor with 10. That is, they better start with 11. But let's just encode C using 110 and D using 111. So that would be a variable length code. The number of bits varies between 1 and 3, but it is prefix free. And again, the reason we might want to do this, the reason we might want to use a variable length encoding is to take advantage of non-uniform frequencies of symbols from a given alphabet. So let me show you a concrete example of the benefits you can get from these kinds of codes on the next slide. So let's continue with just our 4-symbol alphabet, A, B, C, and D. And let's suppose we have good statistics in our application domain about exactly how frequent each of these symbols are. So in particular, let's assume we know that A is by far the most likely symbol. Let's say 60% of the symbols are going to be A's, whereas 25% are B's, 10% are C's, and 5% are D's. So why would you know these statistics? Well, in some domains, you're just going to have a lot of expertise. In genomics, you're going to know the usual frequencies of A's, C's, G's, and T's. For something like an MP3 file, well, you can literally just take an intermediate version of the file after you've done the analog to digital transformation and just count the number of occurrences of each of the symbols. And then you know exact frequencies, and you're good to go. So let's compare the performance of the just sort of obvious fixed length code where we use 2 bits for each of the 4 characters with that of the variable length code that's also prefix free that we mentioned on the previous slide. And we're going to measure the performance of these codes by looking on average how many bits do you need to encode a character, where the average is over the frequencies of the 4 different symbols. So for the fixed length encoding, of course, it's 2 bits per symbol. We don't even need the average, just whatever the symbol is, it uses exactly 2 bits. So what about the variable length encoding that's shown on the right in pink? How many bits on average for an average character, given these frequencies of the different symbols, are needed to encode a character of the alphabet sigma? Okay, so the correct answer is the second one. It's on average 1.55 bits per character. So what's the computation? Well, 60% of the time it's going to use only 1 bit, and that's where the big savings comes from. 1 bit is all that's needed whenever we see an A, and most of the characters are A's. We don't do too bad when we see a B either, which is 25% of the time. We're only using 2 bits for each B. Now, it is true that C's and D's we're paying a price. We're having to use 3 bits for each of those, but there aren't very many. Only 10% of the time is it a C, and 5% of the time is it a D. And if you add up the result, that's taking the average over the symbol frequencies, we get the result of 1.55. So this example draws our attention to a very neat algorithmic opportunity. So namely, given an alphabet and frequencies of the symbols, which in general are not uniform, we now know that the obvious solution, fixed length codes, need not be optimal. We can improve upon them using variable length prefix-free codes. So the computational problem we want to solve is which one is the best? How do we get optimal compression? Which variable length code gives us the minimum average encoding length of a symbol from this alphabet? So Huffman codes are the solution to that problem. We'll start developing them in the next video. So we clearly have something to be excited about. There's clearly this opportunity to design binary prefix-free codes which improve over the obvious fixed-length solution. So we'd like to have a, in some sense, optimal algorithm for this problem, and for that we of course need a crisp problem definition. So to do that, it turns out to be useful to think of codes as binary trees. So this video will develop that connection, concluding with the final formal problem statement. So the last video introduced us to this very interesting computational problem, namely, given characters from an alphabet with frequencies, find the best binary prefix-free encoding. Find the code which minimizes the average number of bits needed to encode a character. Crucial to reasoning about this problem is thinking of binary codes as binary trees. So to give you an idea of this correspondence, let's just revisit 3 of the binary codes we saw in the previous video and see what kind of trees they correspond to. So let's just continue with the 4-symbol alphabet, A, B, C, D. The obvious fixed-length code, where we encode ABCD with 0, 0, 0, 1, 1, 0, and 1, 1, is just going to correspond to the complete binary tree with 4 leaves. So let me label this complete binary tree as follows. I'm going to label the leaves A through D from left to right, and I'm going to label each edge of the tree with a 0 if it corresponds to a left-child relationship, and with a 1 if it corresponds to a right-child relationship. And now what you see is there's a correspondence between the bits along root to leaf paths and the fixed length encoding. So for example, for the symbol C, if we follow the path from the root to the leaf labeled C, we first encounter a 1 because it's a right child, then we encounter a 0 because it's a left child. That gives us a 1 and a 0. That's the same as our encoding of the symbol C in this fixed length encoding. And the same, of course, is true for the other 3 leaves. Next, when we first started playing around with variable length encodings to motivate the prefix free property, we studied a code where we replaced the double 0 for an A with a single 0 and the double 1 for a D with a single 1. Now this code was not prefix free. But we can still represent it as a binary tree. It's just not going to be a complete one. So I'm going to label the edges of this tree the same way as before. Left child edges will be given a label of 0. Right child edges will be given a label of 1. I'm going to label the left and right children of the root A and D respectively, and the 2 leaves will be given the labels B and C. The reason I labeled the nodes in this way is because then we have the same kind of correspondence between the encodings that we proposed for the various symbols and the bits that you see along a path from the root to nodes with those symbols. So for example, if you look at the node labeled D, the path from the root only has a single bit 1, and that coincides with the proposed encoding of the symbol D. Now remember, this code is not prefix free, and so therefore, as we saw, it had ambiguity. So if you're wondering what some encoded message means and you see a 0, you're not sure. That 0 might be representing the symbol A, or alternatively, it might be the first half of an encoding of the symbol B. So this ambiguity is also noticeable in the tree, and the property in the tree that tips you off to the ambiguity is that there are symbols at internal nodes of the tree. The symbols are not merely at the leaves, as they were with the first tree, with the fixed length encoding, but there are also 2 internal nodes that have symbols. So let's draw the tree for our final example, which was the variable length but prefix free code that we looked at in the previous video. So this is going to correspond to a tree which is not perfectly balanced, but it will have labels only at the leaves of the tree. So if you label the edges of this tree the way we've been doing, all the left child edges get a 0, all the right child edges get a 1, and we label the leaves of the tree from A to D going from left to right, you'll see we have the same correspondence as in the previous 2 trees. The sequence of bits from the root to a leaf coincide with the proposed encoding for it. So for example, if we look at the leaf labeled C, because you traverse a right child, another right child, and then a left child to get to it, that's the sequence 1, 1, 0, and that is precisely the proposed encoding for the symbol C. So in general, any binary code can be expressed as a tree in this way, with the left child pointers being labeled with 0s, the right child pointers being labeled with 1s, and the various nodes being labeled with the symbols of the given alphabet, and the bits from the root down to the node labeled with a given symbol corresponding to the proposed encoding for that symbol. And what's cool about thinking about codes as trees is that the really important prefix-free condition, which seems like a nuisance to check in the abstract, shows up in a really clean way in these trees. Namely, the prefix-free condition is the same as leaves being the only nodes that have labels. No internal nodes are allowed to have a label in a prefix-free code. The reason for this is that we've set it up so that the encodings correspond to the bits along paths from the root to the labeled node. So being a prefix of another corresponds to one node being an ancestor of the other. And so if all the labels are at the leaves, then of course nobody's an ancestor of the other, and we have no prefixes. The other thing that's really cool about this tree representation of codes is it becomes pictorially obvious how you do decoding, given a sequence of 0s and 1s from a prefix-free binary code. Namely, you start at the beginning, and you start at the root of your tree. Whenever you see a 0, you go left. Whenever you see a 1, you go right. At some point, you'll hit a leaf. That leaf will have some label, and that's the symbol that's being encoded. After you hit a leaf, you just start all over again back to the root. So for example, if you were using our variable length prefix-free code for the 4-letter alphabet, as in our running example, and you were given the sequence of 0s and 1s, 0, 1, 1, 0, 1, 1, 1, what would you do? Well, you'd start at the root, and you see a 0. So you follow the left child pointer, and you immediately get to a leaf. It's labeled A, so you're going to output an A as the first symbol. Now you start all over, you return to the root, Now what do you see? You see a 1, so you go right. You see another 1, so you go right. And now you see a 0, so you go left. And that gets you to the leaf labeled C. Now you start all over again. You see a 1, you go right. You see a 1, you go right again. And then finally you see yet one more 1, and you wind up at the leaf labeled D. So by repeated traversals through the tree, you decode this sequence of 0s and 1s as a CD. There's never any ambiguity because when you hit a label, you know you're at a leaf, there's nowhere to go. At every internal node, it's unlabeled. You know to expect another bit, another traversal further down in the tree. So a final important point about this correspondence is that the encoding lengths of the symbols, the number of bits needed to encode the various symbols, are just the depths of the corresponding leaves in the tree that corresponds to the code. So for example, in our running example, the symbol A is the only one that needs only 1 bit to encode, and it's also the only leaf in level 1 of the tree. And similarly, B needs 2 bits, it shows up in the next level. The C and the D, which need 3 bits, show up in the 3rd level. So this correspondence is really just by construction. So how do you encode a given symbol? Well, it's just the bits on the path from the root, and that the number of such bits is just the number of pointer traversals you need to get from the root down to that leaf, and that's just the depth of that leaf in the tree. So we're now in a great position to really have a crisp definition of the problem. The input, of course, is just the frequencies for a bunch of different symbols I from some alphabet capital sigma. I'm going to use P sub I as notation for the frequency of symbol I. So we know what it is we want to optimize. We want to minimize the expected number of bits needed to encode a symbol, where the average, the expectation, is taken over the provided frequencies of the various symbols. But let's express this objective function using our newfound correspondence with binary trees. In particular, the fact that we can think about encoding lengths as depths of leaves in trees. So given a tree T, which corresponds to a prefix-free binary code, that is, it should be a binary tree, and the leaves of this tree should be in one-to-one correspondence with the symbols of sigma, we're going to define capital L of T as the average encoding length. It's an average in the sense that we sum over all of the symbols of the alphabet, we weight each symbol by the frequency, and remember this is part of the input, so by the provided frequency P sub I of that symbol I, and then how many bits do we need to encode that symbol I? Well, it's just the depth of the leaf which is labeled I in the given tree, capital T. So this is what we want to make as small as possible. So for instance, using the data from the previous video, the letters A, B, C, D with frequencies 60, 25, 10, and 5%. Then if we use the complete binary tree, that is the fixed length encoding, we just get 2 bits per character. While if we use the lopsided tree optimized so that each A only takes 1 bit while suffering 3 bits for C and D, then the average encoding length drops to 1.55, as we saw in the last video. So what then is the goal? What's the responsibility of our algorithm? Well, amongst all binary trees which have leaves in correspondence to the symbols of sigma, we want to compute the one which makes this average encoding length as small as possible, which minimizes our objective function, capital L. Turns out Huffman's greedy algorithm does it. More details to come. So in this video, we'll finally discuss Huffman's algorithm, which is a greedy algorithm that constructs the prefix-free binary code minimizing the average encoding length. So let me just briefly remind you the formal statement of the computational problem that I left you with last time. So the input is just a frequency for each symbol I coming from some alphabet sigma. So the responsibility of the algorithm is to get optimal compression, so to compute an optimal code. So the code has to be binary, we have to use only 0s and 1s. It has to be prefix-free, meaning the encodings of any 2 characters, neither one can be a prefix of the other. That's to facilitate unambiguous decoding. And finally, the average number of bits needed to encode a character, where the average is with respect to the input frequencies, should be as small as possible. Now remember, these kinds of codes correspond to binary trees. The prefix-free condition just says that the symbols of sigma should be in one-to-one correspondence with the leaves of the tree. And finally, remember the encoding lengths of the various symbols just correspond to depths of the corresponding leaves. So we can formally express the average encoding length, which given a a legal tree capital T. I'm using the notation capital L of T. So what do? We just take the average over the symbols of the alphabet weighted by the provided frequencies, and we just look at the number of bits used to encode that symbol, equivalently the depth of the corresponding leaf in the tree T. So we want the tree that makes this number as small as possible. So this task is a little bit different than any that we've seen so far in this course, right? All we're given as an input is an array of numbers, and yet we have to produce this actual full-blown tree. So how can we just take a bunch of numbers and produce them in a sensible, principled way, some kind of tree whose leaves correspond to the symbols of the alphabet? So let's spin a slide just thinking about, at a high level, where would this tree come from? How would you build it up given this unstructured input? So there's certainly no unique answer to this question. And one idea which is very natural, but that turns out to be suboptimal, is to build a tree using a top-down approach, which you can also think of as an instantiation of the divide and conquer algorithm design paradigm. The divide and conquer paradigm, you'll recall, involves breaking the given subproblem into usually multiple, smaller subproblems. They're solved recursively, and the solutions are then combined into one for the original problem. Because trees, the desired output here, have a recursive substructure, it's natural to think about applying this paradigm to this problem. Specifically, you'd love to just lean on a recursive call to construct for you the left subtree, another subcall constructing the right subtree, and then you can fuse the results together under a common root vertex. So it's not clear how to do this partitioning of the symbols into two groups, but one idea, to get the most bang for your buck, the most information out of the first bit of your encoding, you might want to split them in the symbols into groups that have roughly, as close to as possible, a 50% of the overall frequency. So this top-down approach is sometimes called Fano-Shannon coding. Fano was Huffman's graduate advisor. Shannon is the Claude Shannon, inventor of information theory. But Huffman, in a term paper, believe it or not, realized that the top-down approach is not the way to go. The way to go is to build the tree bottom-up. Not only are we going to get optimal codes, but we're going to get a blazingly fast, greedy algorithm that constructs them. So what do I mean by bottom-up? I mean, we're going to start with just a bunch of nodes, each one labeled with one symbol of the alphabet. So in effect, we're starting with the leaves of our tree. And then we're going to do successive mergers. We're going to take at each step two subtrees thus far and link them together as subtrees under a common internal node. So I think you'll see what I mean in a picture. So imagine we want to build a tree where the leaves are supposed to be just A, B, C, and D. So one merger would be, let's just take the leaves C and D and link them as siblings under a common ancestor. Now in the second step, let's merge the leaf B with the subtree we got from the previous merge, the subtree comprising the nodes C, D, and their common ancestor. So now, of course, we have no choice but to merge the only two subtrees we have left, and then that gives us a single tree, which is in fact exactly the same lopsided tree we were using in the previous video as a running example. So let me explain what I hope is clear and what is maybe unclear at this juncture. I hope what's intuitively clear is that the bottom-up approach is a systematic way to build trees that have a prescribed set of leaves. So what do we want? We want trees whose leaves are labeled with the symbols of the alphabet sigma. So if we have an alphabet with n symbols, we're going to start with just the n leaves. What does a merger do? Well, it does two things. First of all, it introduces a new internal node, an unlabeled node. And secondly, it takes two of our old subtrees and fuses them into one, merges them into one. We take two subtrees, we make one the left child of this new internal node, the other the right child of this new internal node. So that drops the number of subtrees we're working with by one. So if we start with the n leaves and we do n-1 successive mergers, what happens? Well, on the one hand, we introduce n-1 new unlabeled internal nodes. And on the other hand, we construct a single tree. And the leaves of this tree that we get are in one-to-one correspondence with the alphabet letters as desired. Now, what I don't expect you to have any intuition for is what should we be merging with what and why. Forget about, how do we get an optimal tree at the end of the day. I mean, even just if we wanted to design a greedy algorithm, if we just wanted to make a myopic decision that looks good right now, how would we even do that? What's our greedy criterion that's going to guide us to merge a particular pair of trees together? So we can reframe this quandary in the same kind of question we ask for minimum cost spanning trees, and really more generally with greedy algorithms. When you're making irrevocable decisions, what strikes fear in your heart is that this decision will come back and haunt you later on. You'll only realize at the end of the algorithm that you made some horrible mistake early on in the algorithm. So just as for MSTs, we ask, when can we be sure that including an edge irrevocably is not a mistake, is safe in the tree that we're building? Here we want to ask, we have to do a merger. We want to do successive mergers. And how do we know that a merger is safe, that it doesn't prevent us from eventually computing an optimal solution? Well, here's the way to look at things that will at least give us an intuitive conjecture for this question. We'll save the proof for the next video. So what are the ramifications when we merge two subtrees, each containing a collection of symbols? Well, when we merge two subtrees, we introduce a new internal node which unites these two subtrees under them. And if you think about it, at the end of the day in the final tree, this is yet another internal node that's going to be on the root to leaf path for all of the leaves in these two subtrees. That is, if you're a symbol and you're watching your subtree get merged with somebody else, you're bummed out. You're like, man, that's another bit in my encoding. That's yet one more node I have to pass through to get back to the root. I think this will become even more clear if we look at an example. So naturally, we'll use our 4-symbol alphabet A, B, C, D. And initially, before we've merged anything, each of these is just its own leaf, A, B, C, D. So there's no internal nodes above them. In a sense, everybody's encoding length at the beginning is 0 bits. So now imagine we merge C and D. We introduce a new internal node, which is the common ancestor of these two leaves. And as a result, C and D are bummed out. They say, well, there's one bit that we're going to have to incur in our encoding length. There's one new internal node we're always going to have to pass through en route back to the root of the eventual tree. Now suppose next we merge B with a subtree containing both C and D. Well, everybody but A is bummed out about this merger because we introduce another internal node and it contributes 1 bit to the encoding of each of B, C, and D. It contributes an extra 1 to the encoding of C and D, and it contributes a 0 to the encoding of B. So all of their encodings in some sense get incremented, go up by 1 compared to how things were before. Now in the final iteration, we have to merge everything together. We have no choice. There's only 2 subtrees left. So here everybody's encoding length gets bumped up by 1. So A finally picks up a bit, namely 0 to encode it, and B, C, and D each pick up an additional bit of 1, which is prepended to their encodings thus far. And in general, what you'll notice is that the final encoding length of a symbol is precisely the number of mergers that its subtree has to endure. Every time your subtree gets merged with somebody else, you pick up another bit in your encoding. And that's because there's one more internal node that you're going to have to traverse en route to the root of the final tree. In this example, the symbols C and D, well, they got merged with somebody else in each of the 3 iterations. So they're the 2 symbols that wind up with an encoding length of 3. The symbol B, it didn't get merged with anybody in the first iteration, only in the second 2. That's why it has an encoding length of 2. So this is really helpful. So this lets us relate the operations that our algorithm actually does, namely mergers, back to the objective function that we care about, namely the average encoding length. Mergers increase the encoding lengths of the participating symbols by 1. So this allows us to segue into the design of a greedy heuristic for how to do mergers. Let's just think about the very first iteration. So we have our n original symbols, and we have to pick 2 to merge. And remember, the consequences of a merge is going to be an increase in the encoding length by 1 bit of whichever 2 symbols we're going to pick. Now what we want to do is minimize the average encoding length with respect to the frequencies that we were given. So which pair of symbols are we the least unhappy to suffer an increment to their encoding length? Well, it's going to be the symbols that are the least frequent. That's going to increase our average encoding length by the least. So that's the greedy merging heuristic. Something's got to increase. Pick the ones that are the least frequent to be the ones that get incremented. So that seems like a really good idea of how to proceed in the first iteration. The next question is, how are we going to recurse? So I'll let you think about that in the following quiz. So let's agree that the first iteration of our greedy heuristic is going to merge together the 2 symbols that possess the lowest frequencies. Let's call those 2 symbols little a and little b. The question is then, how do we make further progress? What do we do next? Well, one thing that would be really nice is if we could somehow recurse on a smaller subproblem. Well, which smaller subproblem? Well, what does it mean that we merge together the symbols A and B? Well, if you think about it, in the tree that we finally construct, by virtue of us merging A and B, we're forcing the algorithm to output a tree in which A and B are siblings, in which they have exactly the same parent. So what does it mean for the encoding that we compute that A and B are going to be siblings with the same parent? It means their encodings are going to be identical, save for the lowest order bit. So A will get encoded with a bunch of bits followed by a 0. B will be encoded by exactly the same prefix of bits followed by a 1. So they're going to have almost the same encoding. So for our recursion, let's just treat them as the same symbol. So let's introduce a new meta symbol, let's call it AB, which represents the conjunction of A and B. So it's meant to represent all of the frequencies of either one, all of the occurrences of either one of them. But remember, the input to the computational problem that we're studying is not just an alphabet, but also frequencies of each of these symbols of that alphabet. So my question for you is, when we introduce this new meta symbol AB, what should be the frequency that we define for this meta symbol? All right, so hopefully your intuition suggested answer C, that for this recursion to make sense, for it to conform to our semantics of what this merging does, we should define the frequency of this new meta symbol to be the sum of the frequencies of the two symbols that it's replacing. That's because, remember, this meta symbol AB is meant to represent all occurrences of both A and B. So it should be the sum of their frequencies. So I'm now ready to formally describe Huffman's greedy algorithm. Let me first describe it on an example, and then I think the general code will be self-evident. So let's just use our usual example. So we're going to have letters A, B, C, D with frequencies 60, 25, 10, and 5. So we're going to use the bottom-up approach. So we begin with each symbol just as its own node, A, B, C, D. I'm annotating in red the frequencies, 60, 25, 10, 5. The greedy heuristic says initially we should merge together the two nodes that have the smallest frequencies. So that would be the C and the D with their frequencies of 10 and 5. Now, based on the idea of the last slide, when we merge C and D, we replace them with a meta symbol CD, whose frequency is the sum of the frequencies of C and D, namely 15. Now we just run another iteration of the greedy algorithm, meaning we merge together the two nodes, the two symbols that have the smallest frequencies. So this is now B, 25, and CD, 15. So now we're down to just two symbols, the original symbol A, which still has frequency 60, and the, in some sense, meta symbol BCD, whose now cumulative frequency is 40. So when we're down to two nodes, that's going to be the point in Huffman's algorithm where we hit the base case and the recursion begins to unwind. So if you just have two symbols to encode, there's pretty much only one sensible way to do it. One is a 0 and one is a 1. So at this point, the final recursive call just returns now a tree with two leaves corresponding to the symbols A and BCD. And now as the recursion unwinds, we in effect undo the mergers. So for each merge, we do a corresponding split of the meta node, and we replace that with an internal node and then two children corresponding to the symbols that were merged to make that meta node. So for example, when we want to undo the merge of the B and the CD, we take the node labeled BCD and we split it into two, the left child being B, the right child being CD. So the original outermost call, what it gets from its recursive call is this tree with three nodes, and it has to undo its merger. It merged C and D, so it takes the leaf labeled with the symbol CD and splits it into two. It replaces it with a new unlabeled internal node, left child C, right child D. So how does the algorithm work in general? Well, just as you'd expect given the discussion on this concrete example. I'm going to take as the base case when the alphabet has just two symbols. In that case, the only thing to do is encode one with a 0, the other with a 1. Otherwise, we take the two symbols of the alphabet that have the smallest frequencies. You can break ties arbitrarily. It's not going to matter. It's going to be optimal either way. We then replace these two low-frequency symbols A and B with a meta symbol AB intended to represent both of them in some sense. As we just discussed with those semantics, we should be defining the frequency of the meta symbol AB as the sum of the frequencies of the symbols that it comprises. We now have a well-defined smaller subproblem. It has one fewer symbol than the one we were given, so we can recursively compute a solution for it. So what the recursive call returns is a tree whose leaves are in one-to-one correspondence with sigma prime. That is, it does not have a leaf labeled A, it does not have a leaf labeled B, it does have a leaf labeled AB. So we want to extend this tree T prime to be one whose leaves correspond to all of sigma. And the obvious way to do that is to split the leaf labeled AB, replace that with a new internal unlabeled node with two children, which are labeled A and B. The resulting tree capital T with leaves in correspondence to the original alphabet sigma is then the final output of Huffman's algorithm. As always with a greedy algorithm, we may have intuition. It may seem like a good idea, but we can't be sure without a rigorous argument. That is the subject of the next video. In this video, we'll establish the correctness of Huffman's algorithm, meaning that greedy algorithm always computes the prefix-free binary code that minimizes the average encoding length. Let me also remind you of our expression for the average encoding length in terms of a tree capital T. We'll be working with this expression quite a bit in this proof. So we average over the symbols, so we sum over the symbols I and the alphabet capital sigma. We weight the various terms by the frequencies which are given as part of the input. And remember that the encoding length that we're producing for a given symbol I is exactly the same as the depth of the corresponding leaf in the tree capital T. So I quite like the proof of Huffman's theorem. It's a cool proof, and will give us an opportunity to revisit the themes that we've been studying in proving the correctness of various greedy algorithms. At a high level, we're going to proceed by induction on the size n of the alphabet sigma. So there's a vague parallel you could draw with how we proved, say, Dijkstra's algorithm correct back in part 1, where by induction we show that each successive iteration of the algorithm is correct, assuming that the previous ones were. But in the inductive step, we're going to use an exchange argument. So to justify each of our mergers, we're going to argue that any optimal solution can be massaged into one that looks more like ours without making it any worse. And that's how we argue that each of our individual mergers is in fact a reasonable idea, a good idea. So more precisely, we're going to go by induction on the size n of the alphabet. I'm going to assume, to make the problem non-trivial, that the alphabet size is at least 2. So as in any proof by induction, we begin with the base case, and then we do the inductive step, wherein we can assume the inductive hypothesis. So the base case is when we just have a 2-letter alphabet. If you go back to Huffman's algorithm, you'll see that it does the obvious thing. In the base case, it just outputs a tree that encodes one of the symbols with the letter 0, and one of the symbols just with the bit 1. And that's the best you can do. You need a bit to encode every symbol, and that tree uses exactly 1 bit for each symbol. So Huffman's algorithm is optimal in that trivial special case. So for the inductive step, we focus on an arbitrary problem instance where the alphabet size is at least 3. Now, of course, whenever you're doing a proof by induction, the thing you've really got going for you is the inductive hypothesis. You assume that the assertion that you're trying to prove, in this case correctness of Huffman's algorithm, is true for all smaller values of n. That is, we're going to assume that if we invoke the algorithm on any smaller input, as of course we do in this recursive algorithm, we get to assume that the algorithm returns the correct solution to that smaller subproblem. So to understand how we're going to pass from the inductive hypothesis, so this assumption that we're correct on all smaller inputs, to the inductive step, the assertion that we're correct on the current input, we need to take a closer look at how the original input with its alphabet sigma relates to the smaller subproblem with the smaller alphabet sigma prime with the 2 letters fused into 1, which is the one that we solve correctly by assumption recursively. So recall our notation from the pseudocode for Huffman's algorithm. What the algorithm does is take the 2 symbols with the smallest frequencies, and let's call those 2 symbols A and B, and it replaces those 2 symbols with a single symbol AB, a sort of meta symbol representing the presence of either A or B. We also, in the quiz, discussed how the sensible frequency for this new meta symbol AB is the sum of the frequencies of A and B. Last video, when we were developing our intuition for what a greedy algorithm for successive bottom-up mergers might look like, we noticed that when you merge 2 symbols A and B, what you're really doing is committing to outputting a tree at the end of the day, at the end of your algorithm, in which the symbols A and B appear as siblings, in which they have exactly the same parent. Therefore, there's an exact correspondence, one-to-one correspondence, between, on the one hand, trees whose leaves are labeled with the symbols in sigma prime. So that is, there's no leaf labeled A, there's no leaf labeled B, there's instead one labeled AB. So there's a correspondence between those kinds of trees, labels of the leaves corresponding to sigma prime, and trees for the original alphabet sigma in which the symbols A and B are siblings, in which they have exactly the same parent. Given a tree as shown in the left picture, that is, given a tree for T prime, the leaves labeled according to sigma prime, you can, and this is in fact exactly what we do in Huffman's algorithm, split the leaf with the meta symbol AB, make it an internal node, and give it two leaves with labels A and B. That produces a tree of the form on the right. Conversely, given a tree of the form on the right, that is, its leaves are labeled according to sigma, and it just so happens that A and B show up as leaves of that tree, you can produce a tree for sigma prime just by contracting A and B together. So sucking up A and B into their parent and labeling the parent AB. So you can go back and forth between these two types of trees. One, arbitrary trees for sigma prime, and trees of a special kind for sigma, trees in which A and B happen to be siblings. This subset of trees for sigma are important enough to be given its own notation. So let me denote by capital X sub AB the trees with leaves labeled according to sigma in which it just so happens that A and B appear as siblings. So that'll be some trees for sigma, but not all of them, only the ones in which A and B are siblings. So this correspondence between solutions to the smaller subproblem and solutions of a particular form for the original problem has an important property. Namely, it preserves the objective function value. It preserves the average encoding length. Okay, that's not quite true, but it's almost true. It's good enough for our purposes. It preserves the average encoding length up to a fixed constant. So let me show you the computation which demonstrates that point. So consider any pair of matched trees T prime and T. And by matched, I just mean T prime is any old tree whose leaves are labeled according to sigma prime, and T is the tree you would obtain if you split the leaf with meta label AB in the usual way. You replace it with an internal node and children with labels A and B. So that's going to be the corresponding tree capital T. So take any such matched pair, and let's look at the difference between their average encoding lengths. Now remember, the average encoding length of a tree is just a sum over the symbols of the relevant alphabet, and what we got going for us here is that sigma and sigma prime are almost exactly the same, right? So the only difference is sigma prime has the meta symbol AB, whereas sigma has the individual symbols A and B. Furthermore, the two trees, T and T prime, are almost exactly the same. The only difference being that T prime has this leaf with the meta label AB, whereas T has two corresponding nodes, one level down, with the labels A and B. So when we take the difference of these two sums, everything cancels out, except that the tree T contributes two summands, one for the leaf with label A, one for the leaf with label B, and the tree T prime contributes with a minus sign, one summand that corresponding to the leaf with label AB. So when the dust clears and we cancel out all the terms, what we're left with is the term for the leaf A, namely the frequency of A times the depth of the leaf A in the tree T, a similar term for the leaf with label B in the tree T, and then with a minus sign, the frequency of the meta label AB in the tree times its depth in the tree T prime. But we are certainly not done with our simplifications. There is a strong relationship between the frequencies that we're staring at and a strong relationship between these various depths. Let's begin with the frequencies. How did we define the frequency of the meta symbol AB? Well, remember our quiz. It made sense to define it as the sum of the frequencies of A and B. What about the depths? Well, this symbol AB is at whatever depth it is in the tree T prime. Say it's a depth 10, something like that. Remember, T is obtained from T prime simply by splitting this leaf AB and giving it two new children with symbols A and B. So if the meta symbol AB was a depth 10 in T prime, then the leaves A and B are going to be a depth 11 in T. So the depth is simply one more than whatever it was previously in the tree T prime. So these relationships are going to result in a second wave of cancellations. So just to make that crystal clear, let's call the depth of AB in T prime D. So D is what I was calling 10 earlier. So A and B are both at depth D plus 1 in the tree T. So the first term becomes the frequency of A times the depth D plus 1. The second term becomes the frequency of b plus the depth d plus 1. And then the third term becomes the sum of the frequencies of a and b times the depth d. And when the dust settles yet again, we are left with a constant, PA plus PB. So the sums of two frequencies. And one thing I want you to really understand is that the difference between these two average encoding lengths is just some constant. It does not depend on which trees we started with. So if we choose a perfectly balanced tree and we do this difference, we get some constant like 0.1. If we choose some totally different pair of trees that are really lopsided and we take this difference, we still get 0.1. Exactly the same thing. So this fulfills the promise I gave you earlier that not only do we have this natural correspondence between, on the one hand, trees labeled with sigma prime and trees of a certain type labeled according to sigma, namely those in which A and B appear as siblings, but the correspondence preserves average encoding length. Okay, it doesn't quite preserve the average encoding length, but it preserves it up to a universal constant, and that's going to be good enough for our purposes, as we'll see in a sec. So I know you're probably catching your breath from that last computation, so let's zoom out. Let's make sure we don't lose the forest for the trees and see that we're actually mostly there. We're just one lemma away from finishing the proof of the theorem, the proof of correctness of Huffman's algorithm. So what do we have going for us? Well, first of all, we got the inductive hypothesis. Remember, in any proof by induction, you better rely very heavily on the inductive hypothesis. What does it say? It says when Huffman's algorithm recurses on the smaller subproblem with the smaller alphabet sigma prime, it solves it optimally. It returns a tree which minimizes the average encoding length with respect to the alphabet sigma prime and the corresponding frequencies. So we're going to call that tree the output of the recursive call t prime hat. So let me amplify the power of this inductive hypothesis by combining it with the computation we did in the last slide. So what do we know so far? We know for this smaller subproblem, which frankly we don't care about in its own right, but nevertheless, for the smaller subproblem with alphabet sigma prime, the recursive call solves it optimally. It returns to us this tree t hat prime, and among all trees with leaves labeled according to sigma prime, this tree is as good as it gets. It minimizes the average encoding length. But what did we learn on the last slide? We learned that there's a one-to-one correspondence between feasible solutions, between trees for the smaller subproblem with the alphabet sigma prime, and feasible solutions to the original problem, the one we care about, that have a certain form, in which it just so happens that A and B are siblings, that they share a common parent. Moreover, this correspondence preserves the objective function value, the average encoding length, or at least it preserves it up to a constant, which is good enough for our purposes. So the upshot is, in minimizing average encoding length over all feasible solutions for the smaller subproblem, our recursive call is actually doing more for us. It's actually minimizing the average encoding length for the original problem with the original alphabet sigma over a subset of the feasible solutions in which A and B are siblings. Now, does this do us any good? Well, it depends. What was our original goal? Our goal was to get the smallest average encoding length possible over all feasible solutions in the world. And so what have we just figured out? We figured out, well, we're getting the best possible scenario amongst some solutions, those in which A and B happen to be siblings. So we're in trouble if there is no optimal solution in which A and B are siblings. Then it doesn't do us any good to optimize only over these crappy solutions. On the other hand, if there is an optimal solution lying in this set XAB in which A and B are siblings, then we're golden. Then there's an optimal solution in this set. Our recursive call is finding the best solution in this set, so we're going to find an optimal solution. So that's really the big question. Can we guarantee that it was safe to merge A and B in the very first iteration? Can we guarantee there is an optimal solution, a best possible tree, that also has that property, that also has A and B as siblings? So the key lemma, which I'll prove on the next slide, and which will complete the proof of the correctness of Huffman's theorem, is indeed there is always an optimal solution in the set XAB, an optimal solution in which A and B, the two lowest frequency symbols, are indeed siblings. So I'll give you a full-blown proof of this key lemma on the next slide, but let me first just orient you and develop your intuition about why you'd hope this key lemma would be true. The intuition is really the same as that when we developed the greedy algorithm in the first place. Namely, when you have which symbols do you want to incur the longest encoding lengths? Well, you want them to be the lowest frequency symbols since you want to minimize the average. So if you look at any old tree, there's going to be, some bottommost layer. There's going to be some deepest possible leaves. And you really hope that A and B, the lowest frequency leaves, are going to be in that lowest level. Now, they might both be in the lowest level and might not be siblings, but if you think about it, amongst symbols at the same level, they're all suffering exactly the same encoding length anyways, so you can permute them in any way you want, and it's not going to affect your average encoding length. So once you put A and B at the bottommost level, you may as well put them as siblings, and it's not going to make any difference. So the final punchline being, you can take any tree, like say an optimal tree, and by exchanging the lowest frequency elements A and B to the bottom and to be common siblings, you can't make the tree worse. You can only make it better, and that's going to show that there is an optimal tree with the desired property, where A and B are in fact siblings. All right, so that's reasonably accurate intuition, but it's not a proof. Here is the proof. So we're going to use an exchange argument. We're going to take an arbitrary optimal tree, a tree minimizing the average encoding length. Let's call it T star. There may be many such trees. Just pick any one. I don't care which. And the plan is to show an even better tree, or at least as good tree, which satisfies the properties that we want, where A and B show up as siblings. So let's figure out where we're going to swap the symbols A and B to. So we've got our tree T star, and let's look at the deepest level of T star, and let's find our, any pair of siblings at this deepest level. Call them X and Y. So in this green tree on the right, we have two choices of pairs of siblings at the lowest level. It doesn't matter which one we pick. So let's just say pick the leftmost pair, call them X and Y. So A and B have to be somewhere in this tree. Let me just pick a couple of the leaves to be examples for where A and B might actually be in T star. And so now we're going to execute the exchange. We're going to obtain a new tree T hat from T star merely by swapping the labels of the leaves X and A, and similarly swapping the labels of the leaves Y and B. So after this exchange, we get a new valid tree. So once again, the leaves are labeled with the various symbols of sigma. And moreover, by our choice of X and Y, we've now, via this exchange, forced the tree to conform to the property. We've forced A and B to be siblings. They take the original positions of X and Y, which were chosen to be siblings. So to finish the proof, we're going to show that the average encoding length of T hat can only be less than T star. Since T star was optimal, that means that T hat has to be optimal as well. Since it also satisfies the desired property that A and B are siblings, that's going to complete the proof of the key lemma, and therefore the proof of the correctness of Huffman's algorithm. The reason, intuitively, is that when we do the swap, A and B inherit the previous depths of X and Y, because conversely, X and Y inherit the old depths of A and B. So A and B can only get worse, and X and Y can only get better, and X and Y are the ones with the higher frequencies. So the overall cost-benefit analysis is a net win, and the tree only improves. But to make that precise, let me just show you the exact computation. So let's look at the difference between the average encoding length given by the tree T star and that after the swap given by the tree T hat. So analogously to our computation on the previous slide, most of the stuff cancels because the trees T star and T hat, frankly, just aren't all that different. The only things that are different are the positions of the symbols A, B, X, and Y. So we're going to have 4 positive terms contributed by T star for these 4 symbols, and we're going to have 4 negative terms contributed by the tree T hat, again for these exact same 4 symbols. So let me just show you what happens after the dust settles and after you take away all the cancellation. You can write the 8 terms that remain in a slightly sneaky but clarifying way as follows. So we're going to have one product representing the 4 terms involving the symbols A and X, and then an analogous term for the 4 terms involving B and Y. So in the first one, we look at the product of 2 differences. On the one hand, we look at the difference between the frequencies of X and A. Remember, those are the 2 things that got swapped with each other. And then we also look at the difference between their depths in the original tree T star. And then because B and Y got swapped, we have an entirely analogous term involving them. The reason I rewrote this difference in this slightly sneaky way is it now becomes completely obvious what role the various hypotheses play. Specifically, why is it important that A and B have the lowest possible frequencies? We actually haven't used that yet in our proof, but it's fundamental to our greedy algorithm. Secondly, why did we choose X and Y to be in the deepest level of the original tree T star? Well, let's start with the first pair of products, the differences between frequencies. So the frequency of x minus the frequency of a, and similarly between y and b. Well, because a and b have the smallest frequencies of them all, these differences have to be non-negative. The frequencies of x and y can only be more. The second pair of differences also must be non-negative, and this is simply because we chose x and y to be at the deepest level. Their depths have to be at least as large as that of a and b in the original tree t star. Since all four differences are non-negative, that means the sum of their products is also non-negative. That means the average encoding length of t star is at least as big as t hat. So that's where t hat has to also be optimal. It in addition satisfies the desired property that a and b are siblings. And so that means our recursive call, even though we've committed to merging a and b, we've committed to returning a tree in which they're siblings. That was without loss. That was a safe merge. That's why Huffman's algorithm, at the end of the day, can return an optimal tree, one that minimizes the average encoding length over all possible binary prefix-free codes. So let me just wrap up with a few notes about how to implement Huffman's algorithm and what kind of running time you should be able to achieve. So if you just naively implement the pseudocode that I showed you, you're going to get a not particularly great quadratic time algorithm that moreover uses a lot of recursion. So why is it going to be quadratic time? Well, you have one recursive call each time, and you always reduce the number of symbols by one. So the total number of recursive calls is going to be linear in the number of symbols in your alphabet, n. And how much work do you do in each recursive call, not counting the work done by later calls? Well, you have to search to figure out the lowest frequency symbols A and B. So that's basically some minimum computation. So that's going to take linear time for each of the linear recursive calls. Now, the fact that we keep doing these repeated minimum computations in each recursive call, I hope, triggers a light bulb that maybe a data structure would be helpful. Which data structure's raison d'etre is to speed up repeated minimum computations? Well, as we've seen, for example, in Dijkstra's and Prim's algorithms, that would be the heap. So of course, when you define a heap, you have to say what the keys are, but since we always want to know what the symbols with the smallest frequencies are, the obvious thing to do is to use frequencies as keys. So the only question then is what happens when you do a merge? Well, the obvious thing is just to add the frequencies of those two symbols and reinsert into the heap the new meta symbol with its key equal to the sum of the keys of the two elements that you just extracted from the heap. So not only is that going to work great, it's going to be n log n time. It's very easy to implement in an iterative manner. So that's starting to be a really blazingly fast implementation of Huffman's algorithm. In fact, you can do even better. You can boil down an implementation of Huffman's algorithm to a single invocation of a sorting subroutine followed by a merely linear amount of work. Now, in the worst case, you're still going to be stuck asymptotically with an n log n implementation because you can't sort better than n log n if you know nothing about what you're sorting. But in this implementation, the constants are going to be even better, and as we discussed in part 1, there are sometimes special cases where you can beat n log n for sorting. So for example, if all of your data is representable with a small number of bits, then you can do better than n log n. So I'm going to leave this even faster implementation as a somewhat non-trivial exercise. I'll give you a hint though, which is if you do sorting as a pre-processing step, you actually don't even need to use a heap data structure for this implementation. You can get away with an even more primitive data structure of a queue. You might, however, want to use two queues. So next time you find yourself in line for coffee, that's a nice thing to think about. How do you implement Huffman's algorithm merely with one invocation to sorting so that the symbols are sorted by frequency, followed by linear work using two queues? So the time has arrived to begin our study of dynamic programming. So this is a general algorithm design paradigm. As I mentioned at the beginning of the course, it has a number of justly famous applications. However, I'm not going to tell you just yet what it is that makes an algorithm dynamic programming. Rather, our plan is, over the next few videos, to develop from scratch an algorithm for a non-trivial, concrete computational problem. The problem is finding the maximum weight independence set in a path graph. This concrete problem is going to force us to develop a number of new ideas, and once we've finished solving the problem, at that point we'll zoom out and I'll point out what are the characteristics of our solution which make it a dynamic programming algorithm. Then, armed with both a sort of formula for developing dynamic programming algorithms, as well as a concrete instantiation, we'll move on to a number of further and, in general, harder applications of the paradigm. Indeed, even more than usual, the dynamic programming paradigm takes practice to perfect. In my experience, students find it counterintuitive at first, and they often struggle to apply the paradigm to problems that they haven't seen before. But here's the good news. Dynamic programming is relatively formulaic, certainly more so than our recent study of greedy algorithms, and it's something you can get the hang of. So with sufficient practice, and that's exactly what I'll be giving you over the next couple of weeks, you should find yourself with a powerful and quite widely applicable new tool in your programmer toolbox. So let me introduce you to the concrete problem we're going to study over the next few videos. It's a graph problem, but a very simple graph problem. In fact, we're going to restrict our attention merely to path graphs. That's graphs that consist solely of a path on some number n of vertices. The only other part of the input is a single non-negative number per vertex. We're going to call these weights. For example, here's a path graph on 4 vertices, and let's give the vertices the weights 1, 4, 5, and 4. The responsibility of the algorithm is going to be to output an independent set. What that means is a subset of the graph's vertices so that no 2 vertices are adjacent. So in the context of a simple path graph, it just means you got to return some of the vertices and always avoiding consecutive pairs of vertices. So when you have a path of 4 vertices, examples of independent sets include the empty set, any single vertex, vertices 1 and 3, vertices 2 and 4, and vertices 1 and 4. You could not, for example, return vertices 2 and 3 because those are adjacent. That is forbidden. Now, to make this interesting, we're going to want just not any old independent set, but the one whose sum of vertex weights is as large as possible. That's the max weight independent set problem. So what I'm going to do next is use this concrete problem as an opportunity to review the various algorithm design paradigms that we've seen so far. Along the way, we'll see that none of them actually work very well for this problem, and that's going to motivate us to devise a new approach, and that approach is going to turn out to be dynamic programming. So there's always our standard punching bag, brute force search. This would entail iterating through all of the independent sets and remembering the one with maximum total weight. Of course, it's correct, no question about that, but as usual, this would require exponential time. Even in just a path graph, the number of independent sets is exponential in the number of vertices n. So what other algorithm design paradigms do we know? Well, we just finished a big segment on greedy algorithms. We could certainly think about that. You know, pretty much most problems, it's easy to propose greedy algorithms, and this one's no exception. I think the most natural greedy algorithm you might try to use to compute a maximum weight independent set would be, well, what's the myopic decision? Well, you want to get as much weight overall, so at each step, you want to just pick the vertex with the highest weight that you haven't already chosen. Now, of course, you have to worry about feasibility. Remember, we're not allowed to output adjacent or consecutive vertices, so if any vertex is ruled out by adjacency, we ignore it. And amongst those that preserve feasibility, we include the highest weight one in our set so far. Well, let me redraw the 4-node path graph we had on the last slide, and let me ask you, what would this greedy algorithm compute on this 4-node path, and how does that compare to the optimal solution, the independent set with the maximum total weight? So the correct answer is the second one. Let's see why. So let's start with the optimal solution, the max weight independent set. Remember, independent sets are forbidden from choosing adjacent or consecutive vertices. So in this case, the only sensible solutions to consider are the first and third vertex, the second and fourth, or the first and fourth. Of these, the best is the second and fourth for a total of 8. So what about the greedy algorithm? Well, we just had this period of time where we got really spoiled with the success of greedy algorithms, especially in the minimum spanning tree problem. But let me remind you, greedy algorithms, they're often good heuristics. They're often not guaranteed to be correct. And so I'm happy to have this opportunity to quickly remind you again of that drawback of greedy algorithms. They're quite frequently not correct. So this is another such case. So what would the greedy algorithm do? Well, it begins by picking the max weight vertex overall. So that would be this vertex with weight 5. That unfortunately blocks the algorithm from picking either of the 2 vertices that has weight 4. The only remaining option that preserves feasibility is to pick the vertex of weight 1. So that gives us an independent set of weight 6. So this greedy algorithm is not correct. You could, of course, try to devise other types of greedy algorithms, but I don't know of any greedy approach that will actually solve this problem optimally. So that's a bummer, but we still haven't exhausted our algorithm design paradigms. Remember, we learned this quite powerful divide and conquer approach early on in part 1 of this class. And, it seems like it could work here. We had all these successful applications where the input was an array. We broke it into 2 halves. We recursed on both sides and combined the results. And here, path graphs don't look so different than an array of numbers. So the obvious approach for divide and conquer is to break the path into 2 paths, each of half the length of the original, recursively compute a maximum weight independent set in each, and then somehow combine the results. But the issues with the divide and conquer approach are already apparent just in our simple 4-vertex example. So if we recurse on the left half, that is the first 2 vertices, and we compute a max weight independent set, that's just going to be the second vertex by itself. And if we independently recurse on the right-hand side, on the vertices 3 and 4, the maximum weight independent set on the right half is going to be the vertex of weight 5. And now when the recursion's complete and we get our subsolutions back, we have the second vertex and we have the third vertex, but the problem is the union of those 2 solutions conflicts, right? We cannot simultaneously output the second and third vertices. Those are consecutive. Those are adjacent, and that's not allowed. Moreover, in a 4-node graph, it's sort of easy to see how to repair this conflict. But in a big graph with, say, thousands of nodes, if you have a conflict right where the 2 subproblems meet, it is not at all obvious how you would quickly fix that and get a feasible and optimal solution to the original problem. Now, in some sense, the divide and conquer paradigm is more powerful or better suited for this problem than the greedy approach, in that I do know of divide and conquer algorithms that could solve this problem optimally, that run in quadratic time. But doing better than that in a divide and conquer matter seems quite challenging. And in the dynamic programming-based algorithm we'll develop, we'll solve the problem in linear time. That's coming up next. So having now iterated through all of our algorithm design paradigms and noticing that none of them seem to work very well for computing the maximum weight independent set of a path graph, we're going to develop some ideas for a new paradigm. And the key approach in this new paradigm is to first reason about the structure of an optimal solution. And what I mean by this is we're going to seek out statements of the following form. The optimal solution, whatever it may be, has to possess a certain form. It has to have been built up from an optimal solution to a subproblem in a prescribed way. So in fact, in much of our discussion of both divide and conquer and greedy algorithms, this kind of reasoning was implicit. With dynamic programming, we're going to make it systematic. For example, implicit in the correctness of many a divide and conquer algorithm is the fact that an optimal solution to the whole problem has to be expressible, has to be constructible in a prescribed way from solutions to smaller subproblems. So what's the motivation for doing this thought experiment, trying to understand what the optimal solution could possibly look like? Well, the plan is we're going to narrow the possible candidates for the optimal solution down to a relatively small set of candidates. With a small set, we can get away with brute force search to pick the best one. So one lesson you learn once you get good at dynamic programming is that it's not at all circular to reason about the very object that you're trying to compute. Remember, the goal here is to devise an algorithm to compute an optimal solution. And now I'm telling you to do a thought experiment as if you had already computed it, as if I had handed it to you on a silver platter. But that kind of daydreaming can be very productive in thinking, hey, what if I did have an optimal solution? What could I say about it? What would it look like? Observations of that form can actually light up a trail to the computation of that exact object. And we'll see that in the next couple of videos. All right, so that's enough lofty philosophy for now. Let's get concrete. Okay, so we've got this path graph. The vertices have weights. We want the max weight independent set. Let's again do this thought experiment. What if someone handed to us, what can we say about its structure? We'll be using the following notation when we reason about this maximum weight independent set. S denotes the vertices in that optimal solution, in that max weight independent set. And we're going to let V sub n denote the rightmost, the final vertex of the input graph. So here's a content-free statement. This last vertex of the path, V sub n, either it's an S or it isn't. So that's going to give us two cases when we reason about the optimal solution. Let's start with a case where Vn is excluded from the optimal solution, capital S. So let's let G prime denote the path graph you get by plucking off Vn, plucking off the rightmost vertex from the original graph G. So let's make a couple of trivial observations. So first of all, this set capital S, it's an independent set in G. It doesn't include the last vertex. So we can regard this set S equally well as an independent set of the smaller graph G prime. If it didn't contain consecutive vertices in G, nor does it in G prime. But actually we can say more. Not only is S any old independent set in G prime, it has to be an optimal, that is maximum weight independent set in G prime. Why? Well, if there was something better than S in G prime, we could take that exact same independent set S star, regard it as an independent set in G, and of course it would still be better than S in G. But that contradicts our assumption that S was a max weight independent set in G. So summarizing, if the max weight independent set S of the original path graph G does not include the rightmost vertex, it can be very simply described in terms of an optimal solution to a smaller subproblem. It literally is a max weight independent set of G prime, the path graph with one fewer vertex. All right, so case 1 is a warm-up for case 2, which is similar but slightly more complicated. Now let's assume that the max weight independent set S does in fact use the rightmost vertex Vn. Now, by the definition of an independent set, no two consecutive, no two adjacent vertices can be chosen. So by virtue of choosing V sub n, the rightmost vertex, S in this case absolutely cannot include the penultimate vertex V sub n minus 1. So we're going to note by G double prime the path you get from G by plucking off both of the rightmost two vertices. So now let's do our best to mimic the argument in case 1. In case 1 we said, well, S has to also be an independent set of G prime. Now here that doesn't make sense, right? Here S contains the last vertex, so we can't talk about it even being a subset of any smaller graph. However, if we think about S except for the last vertex V sub n, S with Vn removed is an independent set, in fact, of G double prime, because remember S can't contain the second to last vertex. And once again, just like in case 1, we can say something stronger. S with Vn removed is not any old independent set of G double prime. It actually must be an optimal one. It must have maximum possible weight. The reasoning is similar. Suppose S with Vn removed was not the best possible independent set in G double prime. Then there is something else, call it S star, which is even better, has even bigger weight. How do we get a contradiction? Well, if we just add Vn to this even bigger independent set S star that lies in G double prime, we get a bona fide independent set of the entire graph G with overall weight even bigger than that of S. But that contradicts the optimality of S. So, for example, you could imagine that this purported optimal solution, capital S, had total weight 1100 in two parts. It had 1000 weights coming from vertices in G double prime, but it also had V sub n, which had weight 100 on its own. And so now in the contradiction, you say, well, suppose there was an independent set that had even more than 1000 weight just in G double prime, say 1050. Well, then we just add this last vertex V sub n to that. We get an independent set with weight 1150 in the original graph G. But that contradicts the fact that S was supposed to be optimal with weight merely 1100. So notice that the reason we're using the graph G double prime in this argument, it's to make sure that no matter what S star is, no matter what this independent set of G double prime is, we can just add Vn to it blithely and not worry about feasibility. Right? So the rightmost vertex S star could possibly possess is the third to last vertex Vn minus 2. So there's no worries about feasibility when we extend it by adding in the rightmost vertex V sub n. So to make sure you don't lose the forest for the trees, let me remind you what our high-level plan was, and let me point out that we actually just executed that plan quite successfully in this problem. The plan was to narrow down the candidates for what the optimal solution could be, to reason about the form of the optimal solution and argue that it has to look in a particular way. What did we just prove on the previous slide? We said that the optimal solution actually can only be one of two things. Either it excludes the final vertex and it is nothing more than the max weight independent set from G prime, or if it includes the rightmost vertex, then it must be a maximum weight independent set from G double prime augmented with this last vertex V sub n. There's only two possibilities for what the optimal solution could possibly look like in terms of optimal solutions of smaller subproblems. So a corollary of this is that if a little birdie told us which case we were in, whether or not V sub n was in the optimal solution, we could just complete this by recursing on the appropriate subproblem. If the little birdie tells us the optimal solution doesn't have Vn, we just recurse on G prime. If the little birdie tells us V sub n is in the optimal solution, we recurse on G double prime and then add V sub n to the result. Now, of course, there is no little birdie, and we have no idea whether this rightmost vertex is in the optimal solution or not. But hey, there's only two possibilities, right? Here's an idea. Maybe it seems crazy, but why not try both possibilities and just return whichever one is better? Why do I suggest that maybe this is crazy? Well, if you stare at this and you think about it and you think about the ramifications of trying both possibilities as you recurse down the graph, this may start feeling a little bit like brute force search. And in fact it is. This is just a recursive organization of a brute force search. Nevertheless, as we'll see in the next video, if we're smart about eliminating redundancy, we can actually implement this idea in a linear time. So now that we've done some work with our thought experiment, understanding exactly what the optimal solution, the maximum weight independent set, has to look like in a path graph, let's turn that work into a linear time algorithm. Let me quickly remind you the bottom line from the previous video. So we argued two things. First of all, if the max weight independent set of a path graph happens to exclude the rightmost vertex, then it has to in fact be a max weight independent set of the smaller graph G prime, obtained from G by plucking off the rightmost vertex. If, on the other hand, a max weight independent set does include the rightmost vertex V sub n, then if you take out V sub n and look at the remaining part of the independent set, that has to be max weight among the smaller graph G double prime, defined by plucking their two rightmost vertices off of the original graph G. Ergo, if we happen to know, if a little birdie told us which of these two cases we were in, we could recursively compute the optimal solution of either G prime or G double prime as appropriate and be done. If we recurse on G prime, we just return the result. If we recurse on G double prime, we augment it by V sub n and return the result. Now, there is no little birdie. We don't know which of the two cases we're in, so we concluded the previous video by proposing just trying both cases. So let's write down what that proposed algorithm would look like before we take a step back and critique it. So the good news about this algorithm is it is correct. It's guaranteed to return the maximum weight independent set. So how would you prove this formally? Well, it would be by induction in exactly the same way we proceeded with divide and conquer algorithms. And for the same reason, I'm not going to talk about the details here. If you're interested, I'll leave it as an optional exercise to write this out formally. But intuitively, the inductive hypothesis guarantees correctness of our recursive calls, so computing the maximum weight solution in either G prime or G double prime. And then the previous video, the whole point of that, in effect, was arguing the correctness of our inductive step. Given the correct solution to the subproblem, we argued what has to be the optimal way to extend it to a solution to the original graph G. The bad news, on the other hand, is that this algorithm takes exponential time. It's essentially no better than brute force search. So while the correctness of this kind of recursive algorithm follows the template of divide and conquer pretty much exactly, the running time has blown up to exponential. And the reason for that difference is, in our divide and conquer algorithms, think of merge sort as a canonical example, we made a ton of progress before we recursed, right? We threw out half of the array, 50% of the stuff, before we bothered with any recursion. How much progress are we making in this algorithm? Well, very little. It's positive progress, but very small. We throw out either one or two vertices out of maybe this graph with, say, 1 million vertices before recursing. So we're branching by a factor 2 and making very little progress before each branch. That's why we get this exponential running time rather than something more in the neighborhood of n log n. So this brings us to the following question. This is an important question. I want you to think about it carefully before you respond. So we have this exponential time algorithm. It makes an exponential number of recursive calls. Each recursive call is handed some graph for which it's responsible for computing the maximum weight independence set. The question is this. Over all of these exponentially many different subproblems, each of which is passed some graph as a subproblem, how many fundamentally different subproblems are ever considered across these exponentially many recursive calls? So the answer to this question and the key to unlock the crazy efficiency of our dynamic programming implementation is B. So despite the fact that there's an exponential number of recursive calls, we only ever solve a linear number of distinct subproblems. In fact, we can explicitly say what are the different subproblems that get solved throughout the recursion. What happens before you recurse? Well, you pluck vertices from the graph you were given off from the right. Maybe you pluck off one vertex, that's in the first recursive call, or in the second recursive call you pluck off two vertices, but both from the right. So an invariant maintained throughout the recursion is that the subproblem you're handed was obtained by successive plucking off of vertices from the right part of the graph, from the end of the graph. So, however you got to where you are, whatever the sequence of recursive calls led to where you are now, you are guaranteed to be handed a prefix of the graph induced by the first I vertices, where I is some number between 0 and n. So therefore, there's only a linear number of subproblems you ever have to worry about, the prefixes of the original input graph. From this, we conclude that the exponential running time of the previous algorithm arises solely from the spectacular redundancy of solving exactly the same subproblem from scratch over and over and over and over again. So this observation offers up the promise of a linear time implementation of this algorithm. After all, there's no need to solve a subproblem more than once. Once you've solved it once, you know the answer. So an obvious way to speed up this algorithm, speed it up dramatically, is to simply cache the results of a subproblem the first time you see it. Then you can look it up in some array, constant time, at any point later on in the algorithm. So there's a word for this. I won't really use it in this class, but just so that you know what it is, it's called memoization. So in case this is a little vague, what I mean is you would have some array, some global array, indexed 1 to n or maybe 0 to n, with the semantics that the ith entry of this array is the value of the solution of the ith subproblem. Now, when you do a recursive call and you're handed the first I vertices of the graph, and again, remember, we know that the subproblem has to look like the first I vertices of the graph for some I. You check the array. If it's already been filled in, if you already know the answer, great. You just return it in constant time. You don't bother to resolve. If this is the first time you've ever seen this subproblem, then you recurse and you solve it as we suggested in the previous slide. So with this simple memoization fix, this algorithm is linear time. The easiest way to see that, and actually in fact a better implementation, is to go away from this recursive top-down paradigm and instead implement the solution in a bottom-up way. So solving subproblems in a principled way from the smallest to the original one, the biggest. So a little bit more precisely, let me use the notation G sub I to denote the subgraph of the original graph consisting of the first I vertices. So we're going to have an array with the same semantics as in the recursive version. The ith entry denotes the solution to the ith subproblem, that is the max weight independent set of G sub I, and the plan is to populate that bottom up, that is from left to right. So we'll handle the edge cases of the first two entries of this array specially. G sub 0 would be the empty graph, so there's no independent set. So let's define the max weight independent set in that graph to be 0. And if you graph in G1, where the only vertex is V1, the max weight independent set is obviously that one vertex. Remember, weights are non-negative. So our main for loop just builds up solutions to all of the subproblems in a systematic way, going from the smallest graph, G sub 2, up to the biggest graph, the original one, G sub n. And when we consider the graph G sub I, how do we figure out what the max weight independent set is of that graph? Well, now we use completely directly the work that we put in the previous video. The previous video told us what an optimal solution has to look like, and it has to have one of two forms. We proved either the max weight independent set of G sub I excludes the last vertex V sub I, and then is merely an optimal solution of the graph G sub I minus 1. If it's not that, there's nothing else that can be other than including the last vertex V sub I and being an optimal max weight independent set for the graph G sub I minus 2. We know it's one of those two things. We don't know which. We do brute force search among the two possibilities, and that gives us the optimal solution for the ith subproblem. Crucially, when we need to do this brute force search for the ith subproblem, we already know, we've already computed the optimal solutions to the smaller subproblems that are relevant. Those can be looked up in constant time, and that's what makes each iteration of this for loop run in constant time. So we've done a fair amount of work to get to this point, but after seeing that the greedy algorithm design paradigm failed us, the divide and conquer algorithm design paradigm was inadequate, brute force search is too slow, with this, as we'll see, dynamic programming algorithm, we now have a one-line solution, effectively, to the max weight independent set problem in path graphs. Pretty cool. What's the runtime? Well, this is probably the easiest algorithm whose runtime we've ever had to analyze. Obviously, it's linear time, constant time for each iteration of the for loop. Why is the algorithm correct? Well, it's just the same as our recursive algorithm. It makes exactly the same decisions. The only difference is it doesn't bother with the spectacular redundancy of resolving subproblems it's already solved. Again, if you wanted to prove it from scratch, it would just be a straightforward induction, like in our divide and conquer algorithms. The recursive calls are correct by the inductive hypothesis. The inductive step is justified by the case analysis of the previous video. So we now have an algorithm, a very elegant one, that solves the weighted independent set problem in path graphs. Moreover, the algorithm runs in linear O of n time, clearly the best possible. But before we do a victory lap, I want to point out that there's something this algorithm doesn't do that you might want it to do, namely hand you the actual optimal solution, not merely the value of that optimal solution. So the point of this video is to show you how we can reconstruct an optimal solution given the table filling algorithm from the previous video. So let me just write that algorithm back down. It's so short it won't take me too long. Now when this algorithm completes, what do we have in our hands? We have an array, and this array is filled with numbers. So in particular, in the last entry of the array is a number like 184. So that's great. That tells us that the maximum weight that any independent set possesses is 184. But in many applications, we're going to want to know not just that information, but actually which vertices constitute that independent set with total weight 184. So perhaps the first hack that comes to mind to address this issue is to augment the array so that each entry stores not just the value of an optimal solution to the subproblem induced by the graph G sub I, but also an actual set of vertices achieving that value. And I'll leave it for you to, if you want, rework the previous pseudocode so that when you fill in a new entry, you fill in not just the value of an optimal solution, given solutions to the previous subproblems, but in fact also the solution itself. This hack, however, is not generally how things are done in dynamic programming. It unnecessarily wastes both time and space, and a much smarter approach is to reconstruct from the filled-in table an optimal solution as needed. So if you think about it, it's kind of cool that this is even possible, that our one-line algorithm doesn't cover its tracks, that it leaves us clues for us as detectives to go back and examine and reconstruct what the optimal solution is. The following key point articulates exactly why this is indeed possible. So the starting point of this observation is the correctness of our algorithm, our one-line algorithm, which, of course, we established in the previous video. And by correctness, I mean it's guaranteed that this algorithm will populate each entry of the array correctly. The number in the ith entry is indeed the maximum weight of an independent set in the graph GI. So remember our thought experiment about what the optimal solution could possibly look like. We concluded it could only be one of two things, and we really wound up wishing we had a little birdie that could tell us whether or not the rightmost vertex v sub n was in the optimal solution or not. If we knew which case we were in, we could just recursively compute the remainder of the solution from a graph that has either one or two fewer vertices. So here's the point. This filled-in table, that's our little birdie. Here's what I mean. Well, what's the reasoning that our algorithm goes through to fill in this last entry of this array? And don't forget, we've already proven that our algorithm is correct. We did that in our last video. Well, it does a comparison between the two possible candidates vying for the optimal one. On the one hand, it computes the case 1 solution. It looks up the optimal value of a solution from the graph with one fewer vertex, and it compares that to the case 2 solution, including Vn, the last vertex, and adding that to an optimal solution with 2 fewer vertices. And in this max operator in the line of code, it's explicitly comparing which is better. Case 1, the solution which excludes v sub n, or case 2, the solution which includes v sub n. So whichever one of those was the winner, whichever one of those cases was used to fill in that last entry, that exactly tells us whether or not v sub n is in the optimal solution. If we use the first case, that means v sub n is not in the optimal solution. It gets excluded. If the second case was the winner, then we know v sub n is in the optimal solution because that was the winner. If we have a tie, then there's an optimal solution either way. There's one that includes vn and there's one that excludes vn. So those are the tracks in the mud left for us by the forward direction of the for loop. We can just go back and look which case was used to fill in each entry of the array. Again, for the ones that used case 1, that corresponds to excluding the current vertex. For those that used case 2 to fill in the entry, that corresponds to including that vertex in the solution. So the reconstruction algorithm will take as input the filled-in array that was generated by our one-line algorithm on the previous slide. And what it's going to do is it's going to trace through this array from right to left. And at each step of the main loop, it's going to look at the current entry, and it's just going to compute explicitly which of the two candidates were used to fill in this array entry. If you want, you could also cache the results of these comparisons on the forward pass. That's an optimization that will be useful later for harder problems. But for now, if you want, you can just think about redoing the comparison, saying, hey, there were two possible ways that we could have filled in this entry. Let's just check which of the two were used. So if, in fact, the preceding array entry is at least as large as the one from 2 back plus the weight of the current vertex, that corresponds to case 1 winning, to the subsolution that excludes the current vertex being better than the one that includes it. So in that case, we just skip the current vertex v sub I, and we decrease the array index by 1 in our scan. If the other case wins, that is, if we fill in the current entry, if an optimal solution to the current graph g sub I comprises the current vertex v sub I plus the optimal solution to the graph with 2 fewer vertices, in this case, we know we better include v sub I. That's part of an optimal solution to the current subproblem. Moreover, that's the case where we need to look up the optimal solution with 2 fewer vertices. So we include the current vertex and we decrease the array index by 2. So formally, we have a correctness claim, which is that the final output capital S returned by the reconstruction algorithm is as desired a maximum weight independent set of the original graph G. We've already talked about all the ingredients necessary for a formal proof for those of you who are interested. Of course, it proceeds by induction, and in the inductive step, you use the same case analysis we've been using over and over again. The optimal solution at any given point, it has only 2 possible candidates. The algorithm explicitly figures out which of the 2 that it is, and that is what triggers whether or not to include or exclude the current vertex. The running time, it's even easier. We have a while loop. It runs at most n iterations. We do constant work in each of the iterations. So just like the forward pass, this backwards pass is really just a single scan through the array. It's going to be lightning fast linear time. Hey, so guess what? We just designed our first dynamic programming algorithm. That linear time algorithm for computing the max weight independent set in a path graph is indeed an instantiation of the general dynamic programming paradigm. Now, I've deferred articulating the general principles of that paradigm until now because I think they're best understood through concrete examples. Now that we have one to relate them to, let me tell you about these guiding principles. We will, in the coming lectures, see many more examples. So the key that unlocks the potential of the dynamic programming paradigm for solving a problem is to identify a suitable collection of subproblems. And these subproblems have to satisfy a number of properties. In our algorithm for computing max weight independent sets in path graphs, we had n plus 1 subproblems, one for each prefix of the graph. So formally, our ith subproblem in our algorithm, it was to compute the max weight independent set of G sub I, of the path graph consisting only of the first I vertices. So the first property that you want your collection of subproblems to possess is it shouldn't be too big. You shouldn't have too many different subproblems. The reason being is, in the best case scenario, you're going to be spending constant time solving each of those subproblems. So the number of subproblems is a lower bound on the running time of your algorithm. Now, in the max weight independent set example, we did great. We had merely a linear number of subproblems, and we did indeed get away with mere constant work for each of those subproblems, giving us our linear running time bound overall. The second property you want, and this one's really the kicker, is there should be a notion of smaller subproblems and larger subproblems. In the context of independent sets of path graphs, this was really easy to understand. The subproblems were prefixes of the original graph, and the more vertices you had, the bigger the subproblem. So in general, in dynamic programming, you systematically solve all of the subproblems, beginning with the smallest ones and moving on to larger and larger subproblems. And for this to work, it better be the case that at a given subproblem, given the solutions to all of the smaller subproblems, it's easy to infer what the solution to the current subproblem is. That is, solutions to previous subproblems are sufficient to quickly and correctly compute the solution to the current subproblem. The way this relationship between larger and smaller subproblems is usually expressed is via recurrence, and it states what the optimal solution to a given subproblem is as a function of the optimal solutions to smaller subproblems. And this is exactly how things played out in our independent set algorithm. We did indeed have a recurrence. It just said that the optimal value, the max weight independent set value for g sub I, was the better of two candidates. And we justified this using our thought experiment. Either you just inherit the max weight independent set value from the preceding subproblem, from the I-1 subproblem, or you take the optimal solution from two subproblems back, from gi-2, and you extend it by the current vertex v sub I. That is, you add the ith vertices weight to the weight of the optimal solution from two subproblems back. So this is a pattern we're going to see over and over again. We'll define subproblems for various computational problems, and we'll use recurrence to express how the optimal solution of a given subproblem depends only on the solutions to smaller subproblems. So just like in our independent set example, once you have such a recurrence, it naturally leads to a table filling algorithm where each entry in your table corresponds to the optimal solution to one subproblem, and you use your recurrence to just fill it in, moving from the smaller subproblems to the larger ones. So the third property you probably won't have to worry about much. Usually this just takes care of itself. But needless to say, after you've done the work of solving all of your subproblems, you better be able to answer the original question. This property is usually automatically satisfied because in most cases, not all, but in most cases, the original problem is simply the biggest of all of your subproblems. Notice this is exactly how things worked in independent sets. Our biggest subproblem, g sub n, was just the original graph. So once we fill up the whole table, boom, waiting for us in the final entry was the desired solution to the original problem. So I realize, this is a little abstract at the moment. We only have one concrete example to relate to these abstract concepts. I encourage you to revisit these again after we see more examples, and we will see many more examples. Something that all of the forthcoming examples should make clear is the power and flexibility of the dynamic programming paradigm. This is really just a technique that you have got to know. Now, when you're trying to devise your own dynamic programming algorithms, the key at the heart of the matter is to figure out what the right subproblems are. If you nail the subproblems, usually everything else falls into place in a fairly formulaic way. Now, if you've got a black belt in dynamic programming, you might be able to just stare at a problem and intuitively know what the right collection of subproblems are, and then boom, you're off to the races. But of course, for white belts in dynamic programming, there's still a lot of training to be done. So rather, in the forthcoming examples, rather than just plucking the subproblems from the sky, we're going to go through the same kind of process we did from independent sets and try to figure out how you would ever come up with these subproblems in the first place by reasoning about the structure of optimal solutions. That's a process you should be able to mimic in your own attempts at applying this paradigm to problems that come up in your own projects. So perhaps you were hoping that once you saw the ingredients of dynamic programming, all would become clear why on earth it's called dynamic programming. And probably it's not. So this is an anachronistic use of the word programming. It doesn't mean coding in the way I'm sure almost all of you think of it. It's the same anachronism in phrases like mathematical or linear programming. It more refers to a planning process. But for the full story, let's go ahead and turn to Richard Bellman himself. He's more or less the inventor of dynamic programming. We'll see his Bellman-Ford algorithm a little bit later in the course. So he answers this question in his autobiography. And he talks about when he invented it in the 1950s. And he says those were not good years for mathematical research. He was working at a place called RAND. He says, we had a very interesting gentleman in Washington named Wilson, who was the Secretary of Defense. And he actually had a pathological fear and hatred of the word research. I'm not using the term lightly. I'm using it precisely. His face would suffuse. He would turn red. And he would get violent if people used the term research in his presence. You can imagine how he felt then about the term mathematical. So the RAND Corporation was employed by the Air Force, and the Air Force had Wilson as its boss, essentially. Hence, I felt I had to do something to shield Wilson and the Air Force from the fact that I was really doing mathematics inside the RAND Corporation. What title, what name could I choose? In the first place, I was interested in planning and decision making, but planning, it's not a good word for various reasons. I decided, therefore, to use the word programming. Dynamic has a very interesting property as an adjective in that it's impossible to use the word dynamic in a pejorative sense. Try thinking of some combination that will possibly give it a pejorative meaning. It's impossible. Thus, I thought dynamic programming was a good name. It was something not even a congressman could object to, so I used it as an umbrella for my activities. So in these next two videos, we'll give our second application of the dynamic programming paradigm. It's to a quite well-known problem. It's called the knapsack problem. And we'll show how following the exact same recipe that we used for computing independent sets in path graphs leads to the very well-known dynamic programming solution to this problem. So let's jump right into the definition of a knapsack problem. So the input is given by n items. So each item comes with a value, v sub I, the more the better for us, and also a size, w sub I. We're going to assume that both of these are non-negative. For the sizes, we're going to make an additional assumption that they're integral. In addition to these two n numbers, we're given one more, which is called a capacity, capital W. Again, we'll assume this is both non-negative and an integer. The role of these integrality assumptions will become clear in due time. In the knapsack problem, the responsibility of an algorithm is to select a subset of the items. What do we want? Well, we want as much value as possible, so we want to maximize the sum of the values of the items that we select. So what prevents us from picking everything? Well, the sum of the sizes of the items that we pick have to total to at most the capacity, capital W. Now, I could tell you some cheesy story about a burglar breaking into a house with a knapsack with a certain size, capital W, and wants to make away with sort of the best loot possible. But that would really be doing a disservice to this problem, which is actually quite fundamental. This problem comes up quite a bit, especially as a subroutine in some larger task. Really, just whenever you have sort of a budget of a resource that you can use and you want to use it in the smartest way possible, that's basically the knapsack problem. So you can imagine how it would come up in a lot of contexts. So let's now execute a recipe for developing a dynamic programming algorithm. Remember, the key to any dynamic programming solution is to figure out what is the right set of subproblems, and we're going to arrive at the subproblems for the knapsack problem, just as we did for max-weight independent sets, by doing a thought experiment about the optimal solution and understanding what it has to look like in terms of solutions to smaller subproblems. The bottom line of this thought experiment, the deliverable, will be a recurrence. It'll be a formula which tells us how the optimal value of one subproblem depends on the value of smaller subproblems. So to begin the thought experiment, fix an instance of knapsack and let capital S denote an optimal solution, a max value solution. We began our previous thought experiment with the content-free statement that the final vertex of a path is either in the optimal solution or it's not. Now, what is the analog of the rightmost vertex in this knapsack problem? Well, unlike a path graph, there's no intrinsic sequentiality to the items that we're given. They're just an ordered set. But it's actually useful to think of the items as sort of literally ordered 1, 2, 3, all the way up to n. And then the analog of the rightmost vertex is just the final item. So the content-free statement we're going to work with here is either the last item belongs to the optimal solution, capital S, or it doesn't. We'll again start with the easy case when it doesn't. What we argued in the path graph problem was that the max weight independent set in the analogous case 1 has to be optimal if we just delete that rightmost edge from the graph. So here the analogous claim is that this set S should still be optimal if we delete the final item n from the knapsack instance. The argument is the exact same near-trivial contradiction. If there was a different solution S star amongst the first n-1 items with weight even bigger than that of S, well, we could regard this equally well as a superior knapsack feasible solution back with all n of the items, but that contradicts the purported optimality of S. So let's go through the slightly trickier case 2 together using a quiz. So suppose the optimal knapsack solution does in fact make use of this final item n. Now we want to talk about this being somehow composed of an optimal solution to a smaller subproblem. So if we're going to delete the last item, then we can't talk about S, right, because S has the last item. So we need to remove the last item from S before we talk about its optimality. That's analogous to back in the independent set problem. We removed the rightmost vertex from the optimal solution before talking about its optimality in a smaller subproblem. So the question then is, if we take capital S, the optimal solution, we remove item n, in what sense is the residual solution optimal? Put differently, for what kind of knapsack instance, if any, is that an optimal solution for? All right, so the correct answer is C. So back in the independent set problem, what we said is that if we remove the rightmost vertex, then what's left is optimal for the residual independent set problem we get by plucking off the rightmost 2 vertices. Here, when we remove the nth item from the optimal solution S, the claim is what we get is optimal for the knapsack problem involving the first n-1 items and a residual knapsack capacity of capital W minus little w sub n. So the original knapsack capacity with space reserved or deleted for the nth item. So before I give you a quick proof, let me just briefly explain why a couple of the other answers are not correct. So first of all, answer B, I hope you could rule out quickly. It just doesn't type check. So capital W, that's the knapsack capacity, so that's in units of size. Little v sub n, that's the item's value, so that's in dollars. So it doesn't really make sense to talk about the difference between those two. They're just, it's apples and oranges. Part D, if you are worried about feasibility at any point, so if you take capital S and remove the nth item, what have you done? You've taken a set of items whose size was at most capital W by feasibility of S, and you've removed an item with size Wn from it, so what remains has total size at most capital W minus little w sub n. So S minus n would indeed be feasible for this residual knapsack capacity, capital W minus little w sub n. A much more subtle point is part A. That's a very natural one to guess. That turns out to not be correct. So it turns out there might be smarter ways of using the first n-1 items than S minus item n if you had a full knapsack capacity of capital W to work with. So that's a subtler point, and it's a good exercise for you to actually convince yourself that A is wrong. That there's no reason that when you take out item n from S and you still keep using the original knapsack capacity that this has to be optimal. That's not going to be true. All right, so why is capital C correct? Well, this is going to have the same spirit of case 2 of our weighted independent set thought experiment. So let me give you the proof. The proof is going to be the usual contradiction analogous to case 2 of our argument in the weighted independent set problem. So suppose there was something better than S with n removed with the residual capacity capital W minus little w sub n. Call that supposedly better solution S star. So what can we do to get a contradiction? Well, let's just take S star, which involves only the first n-1 items. Let's add item n to it. Since S star has total size at most capital W minus little w sub n, and item n has size w sub n, the result has total size at most capital W. So it's a feasible solution to take S star and extend it by item number n. And if S star had more value than S with n removed, then S star with n included has more value than S. So for example, if S had total value 1100, 100 of which was coming from the nth item, then S with n removed had value 1000. If S star was better, it had a value 1050. Well, then we just put n back in and it has value 1150, which contradicts the purported optimality of S star, which had total value merely 1100. So notice what's going on here. So in taking away W sub n from the knapsack capacity before we look at the residual problem, we're in effect reserving a buffer for item n if we ever need it. That's how we know we're feasible when we stick n back into this solution S star. That's analogous to deleting the penultimate vertex of the path, again as a buffer to ensure feasibility when we include the nth vertex back in the independent set problem. So what was the point of this whole thought experiment, which we've now completed? Well, again, the point was to say the optimal solution, whatever it is, it has to have only one of two forms. We've narrowed the list of candidates down to two possibilities. Either you just inherit the optimal solution with one less item and the same knapsack capacity, or you look at the optimal solution with one less item and less knapsack capacity by W sub n, and you extend that by item n. But those are the only two possibilities. So again, if we only knew which of these two cases were true, if we only knew whether or not item n was in the optimal solution or not, in some sense we could recursively compute the rest of the solution. So just as that was enough to get us going with a dynamic programming algorithm for weighted independent sets, so it goes with knapsack, as I'll show you on the next video. So now that we understand the way in which optimal solutions must be composed of optimal solutions to smaller subproblems, we're well positioned to turn that into a recurrence and then a dynamic programming solution for the knapsack problem. To compile our discussion from last time into a recurrence, let me just introduce a little notation. So by capital V sub I x, what I mean is the maximum value you can get of a solution that satisfies two constraints. First of all, it should make use only of the first I items. Second of all, the total size of the items that you pick should be at most x. The analog of this notation in the independent set problem was G sub I, the graph with the first I vertices. We're now using two indices instead of one because subproblems have two different ways in which they can get smaller. Recall case 2 of our thought experiment. When we look at a smaller subproblem, there was both one less item and there was also less capacity. So when thinking about a subproblem, we need to keep track of both. We need to keep track of how many items are we allowed to use, and we need to keep track of what's the total size that we're allowed to use. So let's express our conclusion of the last video in this notation. What did we figure out last video? We figured out that the optimal solution has to have one of two forms. Either you just inherit the optimal solution from the knapsack instance with one less item. That was the first case. Or you take the optimal solution to the subproblem which has one less item and less capacity by the weight of the current item, and you extend it to an optimal solution for the current subproblem using the ith item. So V sub I comma x, the optimal value for the current subproblem, it's the better of the two possibilities. So we take a max. The first possibility is just the optimal solution with the same capacity and one fewer item. We're using that solution. The second one is you commit to using item I, you gain value Vi. And you combine that with the optimal solution using the first I minus 1 items and the reduced capacity of x minus the weight of the current item. So one quick edge case, if the weight of the ith item is bigger than our permitted capacity x, then of course we can't use it, and then we're forced to use the first case. We're forced to be in case 1. This then is our recurrence for the knapsack problem. So that completes step 1, where we think about the optimal solution structure and use it to devise a recurrence. Now in this step 2, we're going to precisely nail down what exactly are the subproblems we have to care about. Well, in our maximum weighted independent set example on path graphs, remember the reasoning. Every time we recursed, every time we needed to look up a subproblem solution, it was obtained by plucking vertices off of the right of the graph. And for that reason, all we ever cared about were the various prefixes of the graph. In one dimension, we've got something similar going on here. Whenever we look at smaller subproblems, it's always with one fewer item. We're always sort of deleting the last item before we do our lookup. So again, we need to worry about all possible prefixes of the items. So subproblems of the first I items for all values of I. For the knapsack problem, however, there's a second sense in which subproblems can be smaller. And remember case 2 of our thought experiment. When we want to know the optimal solution that's guaranteed to use the current item I, we have to reduce the capacity before looking up the corresponding optimal solution of a subproblem. That is, we're not just peeling off items, but we're also sort of peeling off parts of the knapsack capacity. Now here is where we're going to use our assumption that I told you at the beginning in our input, that sizes are all integers and that the knapsack capacity is an integer. So the knapsack capacity starts at capital W every time we peel off some integer amount of capacity from it. So at all subproblems, we're going to be working with integral knapsack capacities. So therefore, in the worst case, what are the various subproblems that might arise? Well, perhaps each choice of a residual capacity 0, 1, 2, all the way up to the original knapsack capacity, capital W. So now we're in great shape. In step 2, we figured out exactly what subproblems we care about. In step 1, we figured out a formula by which we can solve bigger subproblems given the solutions of smaller ones. So all that remains now is to write down a table and fill it in systematically using the recurrence, beginning with the smaller subproblems, ending up with the largest subproblems. So here's the pseudocode. It's again going to be very simple. In this algorithm, the array A that we're going to be filling in has 2 dimensions, in contrast to the 1 dimension in the weighted independent set problem. That's because our subproblems have 2 different indices. We have to keep track both of which set of items we're allowed to use and also what capacity we need to respect. So the 2 independent variables indexing subproblems forces us to have a 2D array that we're going to go through now in a double for loop. So in the initialization step, we fill in all the entries where I equals 0, where there's no items. There, of course, the optimal solution value is 0. And then we just go through the subproblem systematically. When we get to a subproblem, we use the recurrence that we developed to compute the entry in that table, using, of course, the entries that we've previously computed in earlier iterations. So for a given subproblem where you're allowed to use the first I items and the residual capacity is X, what do we know from our thought experiment? This can only be one of 2 things. We're just going to do brute force search through the 2 possibilities. The 2 possibilities, well, we have case 1 where we just inherit the optimal solution with 1 fewer item and the same capacity. Or if we're going to actually use item I, then we compose that with the optimal solution from the first I items that leaves enough space for item I. And in that case, we get the value v sub I for including this ith item. So this code doesn't quite make sense in the case where the weight of the current item wi is strictly bigger than the capacity x. That would give us a negative array index, which of course is a no-no. But in that case, amongst friends, we just interpret it as ignoring the second case of the max. So, I'm not going to write down the extra code, but what you would write down is if wi is strictly bigger than x, then you just define a of I comma x to be equal to a of I minus 1 comma x. And one crucial point is that, by the time we need to solve subproblem with a given I and a given X, we have at our disposal the solutions to all of the subproblems that we need. In particular, in the previous iteration of the outer for loop, we computed the solutions to the 2 relevant subproblems for evaluating this recurrence. They're there waiting for us, available for constant time lookup. So after this double for loop completes, sitting there waiting for us in in the entry n comma capital W is the solution that we wanted. That's the max value solution that can use any items that it wants and that can use the entire original knapsack capacity capital W. That's what we want to return. So that's it. That's the whole dynamic programming solution for the knapsack problem. Just to make sure this makes sense, in the next quiz, I want to ask you to analyze the running time of this dynamic programming algorithm. All right, so the correct answer is the second one, and the running time analysis is as straightforward as it was for the max weight independent set problem. We just count out the number of subproblems and look at how much work we do in each. So how many subproblems are there? Well, they're indexed by both I and X. There are n+1 choices for I. There are capital W+1 choices for X. So that gives us theta of n times W different subproblems, and all we do for each is a single comparison amongst previously computed solutions. So we just do constant work per subproblem, giving us the overall running time of n times capital W. So a couple other quick notes which play out in exactly the same way as for the max weight independent set problem, so I'm not going to discuss the details here. So first of all, correctness. Again, it's exactly the same template as in the previous dynamic programming algorithm and in our divide and conquer algorithms. You just go by induction on the problem size, and you use the case analysis or a thought experiment to justify formally the inductive step. So this algorithm suffers from a similar drawback to the max weight independent set algorithm for path graphs that we looked at. Namely, it computes the value of an optimal solution, not the optimal solution itself. It returns a number, not an actual subset of items. But just like with the independent set problem, you can reconstruct an optimal solution from the filled-in array just by tracing backward. So the intuition is, you begin with the biggest subproblem and you look at which of the two cases was used to fill in that entry. If case 1 was used, you should exclude the last item. If case 2 was used, you should include the last item. And also which of those two cases tells you which subproblem you should trace back to continue the process. So I encourage you to spell out the details of this reconstruction algorithm in the privacy of your own home. That'll give you some nice practice with this reconstruction aspect of the dynamic programming paradigm. At the beginning of the course, we talked about the sequence alignment problem, a problem which is fundamental to modern computational genomics. And we talked about the need for an efficient algorithm for solving that problem, for finding the best alignment of two strings. I'm pleased to report that at this point we're well prepared to give such an algorithm. Indeed, such an efficient solution will readily fall out of the dynamic programming recipe that we now have quite a bit of practice with. So let me briefly jog your memory about the sequence alignment problem. So the goal here is to compute a similarity measure between strings, a similarity measure defined as the total penalty of the best alignment, also known as the Needleman-Wunsch score. So for example, if you're given as input the strings AGGGCT and AGGCA, a natural candidate alignment would be to stack them one on top of the other, inserting a gap in the shorter string after the two G's, that in some sense represents the missing G. This is a pretty good alignment that suffers from merely two flaws. So first of all, we did resort to adding a gap in the second string. Second of all, there is a mismatch in the final column. The A and the T get mismatched. In general, we evaluate the alignment by summing up the penalties of all of the flaws, and there's some penalty per gap and there's some penalty per mismatch. So a bit more precisely, as input in this computational problem, we're given two strings. I'm going to call them capital X and capital Y. I'm going to use little x and little y to denote the individual characters of these strings. Let's say the first string capital X has length m and the second string y has length n. In addition to the two input strings, we assume we're given as input the values for the various types of penalties so that we know exactly how much it costs each time we insert a gap, and for each possible mismatch we need to know exactly what's the cost of that mismatch. In principle, you could be given a penalty for matching a letter with itself, but typically that's going to be a penalty of 0. The space of feasible solutions are just the ways of inserting gaps into the two strings so that the results have equal length. I should emphasize that you're allowed to insert gaps into both of the strings. In the example, we only inserted into one of the two strings. But in general, you might have an input where one string is 7 characters longer than the other, and it might turn out that in the optimal alignment, the best thing to do is insert 3 gaps at various places in the longer string and 10 gaps at various places into the shorter string. And the goal, of course, is just to compute amongst all of the exponentially many alignments the one that minimizes the total penalty, where total penalty is just the sum of the individual penalties for the inserted gaps and the various mismatches. So let's not be unduly intimidated by how fundamental this problem is, and let's just apply the dynamic recipe, the programming recipe that we've been using all along. Now remember, the really key insight in any dynamic programming solution is figuring out what's the right collection of subproblems. And if you're feeling like you're up to the black belt level in dynamic programming, you might just want to try to guess what are the right collection of subproblems for sequence alignment. But I don't expect you to be able to do that at this point. And so as usual, we're going to derive the correct collection of subproblems, and we're going to do it by reasoning about the structure of an optimal solution, narrowing it down to a small number of candidates composed in various ways from solutions to smaller subproblems. Once we've figured out the small number of possibilities for what the optimal solution could look like in terms of solutions to smaller subproblems, we'll be able to derive a recurrence, which in effect just does brute force search through the small number of candidates. And from the recurrence, we'll be able to back out, we'll be able to reverse engineer what are the various subproblems that we actually care about and that we have to solve. So let's do a thought experiment. What does the optimal solution have to look like? And again, remember, this is exactly what it is that we're trying to compute, but that's not going to stop us from reasoning about it. If someone handed to us on a silver platter the optimal solution, what would it have to look like? So consider any old pair of strings, capital X and capital Y, and an optimal alignment of them. Let's visualize this optimal alignment as follows. Let's write down the string X plus whatever gaps get inserted into it on top. And right beneath it, we'll write down the string Y with whatever gaps are inserted into it. These two things have exactly the same length. So to figure out the various cases of the structure for this optimal solution, let's reason by analogy with the problems we've already solved. So back when we were looking at independent sets of line graphs, our case analysis was, well, either the final vertex, the rightmost vertex of the path, is in the optimal solution, or it's not. In the knapsack problem, we said, well, either the last item is in the optimal solution or it's not. So we always looked at sort of the last part of the optimal solution, in some sense the rightmost position. And happily, staring at this alignment, we see we can once again focus just on the action in the rightmost in the final position. So now I have a question for you. So in the independent set problem, there were two cases. The last vertex was either in the optimal solution or it's not. In the knapsack problem, there were also two cases. The final item was either in the optimal solution or it's not. So my question for you is, in the sequence alignment problem, when we focus on what's going on in the final position of the optimal alignment, how many relevant cases do we have to study? So the answer I'm looking for is B, 3 relevant possibilities for the contents of the final position. Let me explain my reasoning. Let's start with the upper part of the final position. Observe that if that's a character of this string capital X, it can only be the very last character. It can only be little x sub m. That's because that's where this string ends. Now, we don't know that little x sub m is in the final position. There might be a gap. Similarly, in the bottom part of this final position, there's two possibilities. There's a gap, or if it's a character of y, it has to be the final character, little y sub n. So that would seem to suggest 4 possibilities, 2 options for the top, 2 options for the bottom. But the hint of talking about relevant possibilities is that it's totally pointless to have a gap in both the top and the bottom. Why? Well, the penalty for gaps is non-negative. So if we just deleted both of those gaps, we get an even better alignment of x and y. And in studying an optimal solution, we can therefore assume that we never have 2 gaps in a common position. So that leaves exactly 3 cases. It could be there's no gaps at all, that in fact this alignment matches the character little x sub m with little y sub n. Or it could match the final character of capital X with a gap. Or it could match the final character of capital Y with a gap. So the hope behind this case analysis is that we're going to be able to boil down the possibilities for the optimal solution to merely 3 candidates, 1 candidate for each of the 3 possibilities for the contents of the final position. That would be analogous to what we did in both the independent set and knapsack problems, where we boiled the optimal solution down to just 1 of 2 candidates, corresponding to whether either the final vertex or the final item, as the case may be, was in the optimal solution. Another way of thinking about this is we'd like to make precise the idea that if we just knew what was going on in the final position, if only a little birdie would tell us which of the three cases that we're in, then we'd be done by just solving the some smaller subproblem recursively. So let's now state for each of the three possible scenarios for the final position what is the corresponding candidate for the optimal solution, the way in which it must necessarily be composed with an optimal solution to a smaller subproblem. So who are going to be the protagonists in our smaller subproblem? Well, the smaller subproblem is going to involve everything except the stuff in the final position. So it's going to involve the strings capital X and capital Y, possibly with one character remaining. So let's let X prime be X with its final character peeled off. Y prime is going to be Y with its final character peeled off. So let me just remind you how I numbered the three cases. So case 1 is when the final position contains the final characters of both of the two strings, that is when there's no gaps. Case 2 is when little x sub n gets matched with a gap, and case 3 is when little y sub n gets matched with a gap. Alright, so suppose that case 1 holds. This means that the contents of the final position includes both of the characters little x sub m and little y sub n. So now what we're going to do is we want to look at a smaller subproblem, and we want to look at the subproblem induced by the contents of all of the rest of the positions. I'm going to call that the induced alignment. Since we started with an alignment, two things that had equal length, and we peeled off the final position of both, we have another thing that has equal length, so we're justified in calling it an alignment. Now, what is it an alignment of? Well, if we're in case 1, that means what's missing from the induced alignment are the final characters little x sub m and little y sub n, which means the induced alignment is a bona fide alignment of x prime and y prime. And certainly what we're hoping is true is that the induced alignment is in fact an optimal alignment of these smaller strings x prime and y prime. This would say that when we're in case 1, the optimal solution to the original problem is built up in a simple way from an optimal solution to a smaller subproblem. We're of course hoping that something analogous happens in cases 2 and 3. The only change is going to be that the protagonists of the subproblem will be a little bit different. In case 2, the thing which is missing from the induced alignment is the final character of x, so it's going to be induced alignment of x prime and y. Similarly, in case 3, the induced alignment is going to be an alignment of x and y prime. So this is an assertion, this is a claim. It's not completely obvious, though the proof isn't hard, as I'll show you on the next slide. But assuming for the moment that this assertion is true, it fulfills the hope we had earlier. It says that indeed the optimal solution can only be one of three candidates, that one for each of the possibilities for the contents of the final position. Alternatively, it says that if only we knew which of the three cases we were in, we'd be done. We could recurse, or we could look up a solution to a smaller subproblem, and we could extend it in an easy way to an optimal solution for the original problem. So let's now move on to the proof of this assertion. Why is it true that an optimal solution must be built up from an optimal solution to the relevant smaller subproblem? Well, all of the cases are pretty much the same argument, so I'm just going to do case 1. The other cases are basically the same. I invite you to fill in the details. So it's going to be the same type of simple proof by contradiction that we used earlier when reasoning about the structure of optimal solutions for the independent set and knapsack problems. We're going to assume the contrary. We're going to assume that the induced solution to the smaller subproblem is not optimal, and from the fact that there's a better solution for the subproblem, we will extract a better solution for the original problem, contradicting the purported optimality of the solution that we started with. So when we're dealing with case 1, the induced alignment is of the strings x prime and y prime, x and y with the final character peeled off. And so for the contradiction, let's assume that this induced alignment, it has some penalty, say capital P. Let's assume it's not actually an optimal alignment of x prime and y prime. That is, suppose if we started from scratch, we could come up with some superior alignment of x prime and y prime with total penalty P star strictly smaller than P. But if that were the case, it would be a simple matter to lift this purportedly better alignment of x prime and y prime to an alignment of the original strings x and y. Namely, we just reuse the exact same alignment of x prime and y prime, and then in the final position, we just match xm with yn. So what is the total penalty of this extended alignment of all of x and y? Well, it's just the penalty incurred in everything but the final position, and that's just the old penalty p star, plus the new penalty incurred in the final position, and that's just the penalty corresponding to the match of the characters x, m, and yn. P star being less than p, of course p star plus alpha xmyn is less than p plus alpha xmyn. But the second term is simply the total penalty incurred by our original alignment of x and y, right? That alignment incurred penalty capital P just in the induced alignment of x prime, y prime, and its total penalty was just that plus the penalty in the final position, which is this alpha xmyn. But that furnishes the contradiction. We suppose that we started with an optimal alignment of x and y, yet here is a better one. So with that contradiction, it completes the proof of the optimal substructure claim. So now that we understand that the optimal solution to the sequence alignment problem has to be only one of three candidates, we're going to be easily able to formulate a recurrence, identify the relevant subproblems, and derive an efficient dynamic programming algorithm for the problem. So here is the culmination of our work on the previous video. We thought about an optimal alignment of some pair of strings x and y, and we noticed that there are three cases for the contents of the final position. Either there's no gaps, or there's a gap on top, or there's a gap on the bottom. In case one, where there's no gaps, xm and yn get matched, and we proved that the induced alignment, which is of the smaller strings x prime and y prime, has to be optimal in its own right. In the second case, where the character little x sub m gets matched with a gap, the induced alignment, this time of x prime and y, has to be optimal in its own right. And in the third case, where little y sub n gets matched with a gap, the induced alignment, now of x and y prime, must be optimal. So one way to think about this kind of assertion is it says that the optimal solution to a problem, to a sequence alignment problem, depends only on the solutions to three different smaller subproblems. One involving x prime and y prime, with characters peeled off of both of the strings, one involving x prime and y, and one involving x and y prime. But in all of the cases, all that we care about are subproblems in which a single character was peeled off from the right from one or both of the strings that we started with. And the situation is very similar to in our previous two examples, weighted independent sets on line graphs and the knapsack problem. In the independent set problem, whenever we only cared about subproblems obtained by plucking off either one or two vertices from the given line graph. So all we ever cared about were prefixes of the original line graph. In the knapsack problem, we got subproblems by plucking off the last item and perhaps also reducing the knapsack capacity by some integral amount. So there were two dimensions in the knapsack problem for which subproblems could decrease in size, the number of items and the residual knapsack capacity. So we used two parameters to keep track of the subproblems. And what we cared about were all possible prefixes of the items and all possible residual integral capacities at most the original knapsack capacity. So what's up in the sequence alignment problem? Well, here, subproblems get smaller by plucking a character off of the first string and or the second string. So again, there are two ways in which the subproblem can get smaller, either the first string or the second string. So we'll again use two different parameters, one to figure out how much we've plucked off of the first string, the second one to figure out how much we've plucked off of the second string. But all we care about, the only relevant subproblems, involve prefixes of the two original input strings x and y. That is, the only subproblems that we care about have the form xi, yj, where xi denotes the first I letters of capital X, some prefix of x, and yj denotes some prefix of y, the first j letters of y. So let's now move from the subproblems we're going to use in our dynamic programming algorithm to the recurrence that we're going to use. And the recurrence, really all it does is compile our understanding of the optimal solution and how it depends on the solution to smaller subproblems into an easy-to-use mathematical formula. So I'll use the notation p sub ij for the value of the optimal solution to the corresponding subproblem, the one involving the prefix xi and the prefix yj. And so for a given set of positive values for I and j, what is pij? Well, there are three possibilities. Case one is where the final position of the optimal alignment doesn't have any gaps. So it matches the final character of x sub I, that is little x sub I, and the final character of the prefix capital Y sub j, that is the character little y sub j. It matches them together and just reuses an optimal alignment for the smaller strings xi minus 1 and yi minus 1. Case 2 is where the last letter of the first string, that is little x sub I, gets matched with a gap. In that case, the penalty of the corresponding alignment is the penalty of a gap plus whatever the optimal alignment is of the first I minus 1 letters of capital X plus the first j letters of capital Y. The symmetrically, case 3, we pay for a gap, and then we pay whatever the optimal alignment is of all of the first I letters of capital X with the first j minus 1 letters of Y. This is the case where the last letter of the second string gets matched with a gap in the final position of the optimal alignment. So we know that the optimal solution has to look like one of these three things. We don't know which, so in the recurrence we'll just in effect do brute force search among the three outcomes. We just choose the minimum of the three possibilities. So that's the formal recurrence. Its correctness really just follows immediately from the work we already did, understanding what the optimal solution has to look like. So before we state the algorithm where we systematically solve all of the subproblems using this magical formula, let's just make sure we get the edge cases, the base cases where I or j equals 0, correctly sorted out. So specifically, what is the value of p I comma 0, and also it turns out p of 0 comma I, where I here is just some non-negative integer. All right, so the answer to this question is the second one is B, and I hope if you could keep the notation straight, then the answer was fairly clear. So let's remember what does Pij mean? That's the total penalty of an optimal alignment between the first I letters of X and the first J letters of Y. So consider Pi 0. So now we're asking about aligning the first I letters of X with the first 0 letters of Y, that is with the empty string. Well, the optimal way to match any string to the empty string is you're just going to insert gaps into the empty string to equalize their lengths, and so if your string has length I, you need to insert I gaps. What's the penalty of that alignment? It's just I times the penalty for a single gap, and that's the answer here in B. So we're ready now to give the algorithm, and as with all these dynamic programming algorithms, once you know the subproblems and once you know the recurrence that relates their solutions, there's really nothing to do. All you do is systematically solve all of the subproblems, moving from smallest to largest. So we're going to use an array A to keep track of the solutions of all of these subproblems. A is going to have two dimensions. The reason for two dimensions is we have two independent parameters which are keeping track of the subproblem size, one for how many letters of X we're dealing with, and a second dimension for how many letters of Y that we're dealing with. That's analogous to the knapsack problem, where we also had two dimensions to keep track of the number of items in play and the residual knapsack capacity. We just figured out what the base case is, so we just solve those in a pre-processing step. So if one of the two indices is 0, then the optimal solution value is just the gap penalty times the non-zero index. And now we just go to our double for loop. It's a double for loop because we have two indices into our array, and whenever we get to a subproblem, we just evaluate the recurrence, invoking the solution to the already computed smaller subproblems. So one sanity check you should always apply when you're writing out the code for a dynamic programming algorithm. When you look at the right-hand side of your recurrence, when you look at these purportedly already solved subproblems whose solutions you're using to solve the current subproblem, make sure you have actually already solved those subproblems. So in this case, we're good to go because the indices of the subproblems are only less than the entry that we're filling in right now. So indeed, all three of the relevant subproblems, A I minus 1 J minus 1, A I minus 1 J, and A I J minus 1, they've already been computed in earlier iterations of our double for loop, so they're just hanging out waiting to be looked up in constant time. And as usual, once you've actually figured out the key ingredients for the dynamic programming solution, namely the subproblems and the recurrence, it's pretty much self-evident why the thing's going to work, and it's also self-evident exactly what its running time is going to be. So why is the algorithm correct? That is, why does it terminate with every entry aij equal to the true optimal penalty pij of the corresponding subproblem? Well, this just follows because our recurrence is correct. That's where all the hard work was. And then we're just systematically solving all of the subproblems. So formally, if you like, it would be a proof by induction. So the running time is completely trivial to evaluate. In each iteration of this double for loop, we do a constant amount of work. We just need to look up three strings in constant time and make a couple of comparisons. How many for loops are there? Well, m iterations of the outer for loop, n iterations of the inner for loop. So we suffer the product m times n. That is, the running time is proportional to the product of the lengths of the two strings. So depending on the application, you may be content to just have an algorithm compute for you the NW score, the total penalty of an optimal alignment, or perhaps you're actually interested in the alignment itself. And just as we discussed with independent sets and line graphs, by tracing back through the filled-in table, you can indeed reconstruct an optimal solution. So let me just give you the high-level idea of how it works. It's going to follow the same template, and I'll let you think through the details of why this really works in the privacy of your own home. So assume that you've already run the algorithm on the previous slide, that you've filled in all the entries of this 2D array capital A. Now we want to trace back. So where are we going to start tracing back this filled-in table? Well, we're going to start with the problem that we actually care about, namely the largest problem, a of m comma n. That's what we want the alignment for. Now, we know this optimal alignment is one of three candidates. We know there's three possible situations for the contents of the final position of that alignment. Moreover, when we filled in this entry of the table, we explicitly compared the three possibilities to figure out which one was the best. So, perhaps on the forward pass, we actually cached the result of the comparison, or in the worst case, we can just go back and recompute and figure out which of those three cases was used to fill in this entry. And depending on which one of the three candidates won, that tells us what should be the contents of the final position of the optimal alignment. If case 1 was used to fill in this entry, we should match little x sub m and little y sub n. If case 2 was used to fill in this entry, we should match little x sub n with a gap. If case 3 was used to fill in this entry, we should match little y sub n with a gap. If there's a tie, we get to pick any of them arbitrarily. All of them will lead to optimal alignments. Then, of course, after figuring out what to do in this final position, we have an induced subproblem involving x prime and or y prime. That tells us a previous entry of the table to go to, and we just repeat the process. We again figure out which of the three cases was used to fill in this entry. That tells us how to fill in the next rightmost position of the alignment, and we just keep going until we fall off the table. So what do you do when you fall off the table? Well, once one of the indices I or j gets all the way down to 0, now you have no choice. So now one of the strings is empty and the other one has some number of symbols. So you should just insert the appropriate number of gaps to equalize the lengths. One thing that's pretty neat is that this traceback procedure is efficient. In fact, it's way more efficient in general than the forward pass. For the forward pass, you have to fill in every single one of the m times n entries. But in this traceback procedure, each time you trace back, one of the two indices at least will get decremented. So that says you're going to complete this traceback in O of m plus n time with an optimal alignment of the original two strings. In this next sequence of videos, we're going to study a slightly more intricate application of the dynamic programming paradigm, namely to the problem of computing optimal search trees that minimize the average search time with respect to a given set of probabilities over the keys. So I'm going to assume in these videos that you remember the basics of this search tree data structure. So if you need to jog your memory, you might want to review the relevant video from part 1. So search trees, they contain objects. Each object has a key drawn from some totally ordered set. And the search tree property states that at each node of a search tree, say it contains some object with a key with value x, it better be the case that everything in the left subtree of that node has keys less than x, and everything in the right subtree under the node with key x has to have keys bigger than x. So that has to be true simultaneously at every single node of a search tree. The motivation for the search tree property is so that searching in a search tree just involves following your nose, just like binary search in a sorted array. So if you're looking for, say, an object with key 17, you know whether to go left or right from the root just based on the root's key value. If the root has key value 12, you know a 17, if it exists, has to be in the right subtree, so you recursively search the right subtree. If the root has value 23, you know a 17 has to be in the left subtree, so that's where you recursively search. Something we originally discussed in the context of balanced binary search trees like red-black trees, and I'm going to reiterate now, is that for a given set of keys, there are many, many valid search trees containing those keys. So just to remind you how this works, let's even just suppose there were only 3 keys in the world, x, y, and z, with x less than y less than z. One obvious search tree would be the balanced one, so that would put the middle element y at the root. It would have left child x and right child y, but there's also the 2 chain search trees containing these 3 keys, one with the smallest element x at the root, the other with the largest element z at the root. So given the multiplicity of solutions, all of the different search trees one could use to store objects with a bunch of keys, an obvious question is which one is the best? What's the best search tree to use out of all of the possibilities? So I don't blame you if you've got a sense of deja vu. We did already ask and answer this question in one sense when we discussed red-black trees. There we argued that the best thing to have is a balanced binary search tree that keeps the height as small as possible and therefore the worst case search time, which is proportional to the height, as small as possible, namely logarithmic in the number of objects in the search tree. But now let's make the same kind of assumption that we made when we discussed Huffman codes. That is, let's assume that we actually have accurate statistics about how frequently each item in the tree is going to be searched for. So maybe we know that item X is going to be searched for 80% of the time, whereas Y and Z will only be searched for 10% each. Could we then improve upon the perfectly balanced search tree solution? So let me make this question more concrete just by asking you to compare 2 candidate solutions. On the one hand, the balanced tree, which has y at the root and x and z as children. On the other hand, the chain, which has x as a root, y as its right child, and then z is the right child of z. Z is the right child of y. So what is the average search time in each of these 2 search trees with respect to the search frequencies I told you? 80% for x, 10% for y, and 10% for z. And when I say the search time for a node, I just mean how many nodes do you look at en route to discovering what you're looking for, including that last node itself. So the search time for something that's at the root, for example, that would be a search time of just 1, because you only look at the root to find it. All right, so the correct answer to this quiz is the 4th option, 1.9 and 1.3. So to see why, let's just compute the average search time in each of the 2 proposed search trees. In the first one, with y at the root, well, 80% of the time we're going to suffer a search time of 2 whenever we look for x. We have to look at the root y, then we look at the x. So we pay 2 80% of the time. That contributes 1.6. 10% of the time we get lucky, we see a y, that contributes a 0.1. 10% of the time we see a z, that contributes another 0.2, for a total of 1.9. By contrast, think about the chain that has x at the root. Here, 80% of the time we get lucky, and we only have to pay 1 for every search for x. So that contributes only 0.8 to the total. It is true, our worst case search time has actually gone up. When we see a z, we suffer a search time of 3, which never ever happened in the balanced case. But we pay that 3 only 10% of the time, that contributes a 0.3. The remaining 10% of the time we suffer a search time of 2 to look for y, so that gives us a total of 1.3. And the moral of the story, of course, is that this example exposes an interesting algorithmic opportunity. So the obvious quote-unquote solution of a perfectly balanced search tree need not be the best search tree when frequency of access is non-uniform. You might want to have unbalanced trees like this chain if it gets extremely frequent searches closer to the root to have smaller search time. So the obvious question is then, given a bunch of items and known frequencies of access, what is the optimal search tree? Which search tree minimizes the average search time? So that brings us to the formal problem definition. We're told n objects that we got to store in a search tree, and we're told the frequency of access of each. So let's just keep things simple and the notation straightforward. Let's just say the items are named from 1, 2, all the way up to n, and that is also the order of their respective keys. So P1 is the frequency of searching for the item with the smallest key, and so on. You might wonder where these frequencies come from. How would you know exactly how frequently every possible key will be searched for? It's going to depend on the application. And there will be applications where you're not going to have these kinds of statistics. And that's where you'd probably want to turn to a general purpose balanced binary search tree solution, something like a red-black tree, which guarantees you that every search is going to be reasonably fast. But it's not hard to think about applications where you are going to be able to learn pretty accurate statistics about how frequently different things are searched for. One example might be something like a spell checker. So if you implement that by storing all of the legally spelled words in a search tree, and as you're scanning a document and every time you hit a word, you look it up in the search tree to see it's correctly spelled or incorrectly spelled, you can imagine that after scanning through a number of documents, you would have pretty good estimates about how frequently different things get searched for, and then you could use those estimates to build a highly optimized binary search tree for all future documents. If you're in some other kind of application where you're concerned about these frequencies changing over time, so for example, if they're privy to trends in the industry, you can imagine rebuilding the search tree every day or every week or whatever based on the latest statistics that you've got. In any case, if you're lucky enough to have such statistics, what you're going to want to do is build the search tree, which on the one hand is valid, it should satisfy the search tree property, and on the other hand should make the average search time as small as possible. So let me go ahead and write down a formula for the average search time. It's the one that you would expect it to be, and also introduce some notation, namely capital C of T will denote the average search time of a proposed search tree T. So for these lectures, we're going to focus on the case where all searches are successful. The only thing that ever gets searched for is stuff that's actually in the tree. But everything we'll talk about in these lectures and the algorithm is easily extended to accommodate the case where you also have unsuccessful searches and statistics about how frequent the various unsuccessful searches are. But if there's only successful searches, then we average only over the n elements that are stored in the tree. So we sum over each of the items I. We weight it by the probability or the frequency of its access p sub I, and then that gets multiplied by the search time required in the tree T to find the item I. And as we discussed in the quiz, the search time for a given key I in a given tree T is just the number of nodes that you have to visit until you get to the one containing I. So if you think about it, that's exactly the depth of this node in the tree plus 1. So for example, if you're lucky enough that the key is at the root, the depth of the root is 0, and we're counting that as a search time of 1. So it's the depth plus 1. So one minor point, it's going to be convenient for me to not insist that the PIs sum to 1. Of course, if the PIs were probabilities, they would sum to 1. But I'm going to go ahead and allow them to be arbitrary positive numbers. And that, for the same reason, I'm going to sometimes call capital C of T the weighted search time rather than the average search time, because I won't necessarily be assuming that the PIs sum to 1. But that said, go ahead and think of that as the canonical special case in your mind as we go through these lectures. So for example, in the case where these are probabilities, where the PIs sum to 1, we could always, as a reference point, use a red-black tree as our search tree. But as we've seen, when these PIs are not uniform, you can generally do better. And so that's the point of this computational problem. Exploit the non-uniformities in the given probabilities to come up with the best possibly unbalanced search tree as possible. So I'm sure many of you will have noticed some of the similarities between this computational problem of optimal binary search trees and one that we already solved back in the greedy algorithm section, namely Huffman codes, which amongst all prefix-free binary codes minimize the average encoding length. So let's just be precise about the similarities and differences between the two problems, and in particular why we can't just reuse the algorithm we already saw off the shelf to solve the optimal BST problem. So what's of course super similar in the two cases is the format of the output. In both problems, the responsibility of the algorithm is to output a binary tree, and the goal is to minimize the average depth, more or less, where the average is with respect to provided frequencies over a bunch of objects that we care about. Characters from an alphabet in the case of Huffman codes, and a bunch of objects with keys from some totally ordered set in the binary search tree case. And it is true that in the optimal BST case, we're not really averaging depths, we're averaging depths plus 1. But if you think about it, that's exactly the same thing. More important is to understand the differences between the problem solved by Huffman codes and the computational problem that we have to solve here. In the Huffman code case, we had to output a binary code, and the key constraint was that it be prefix-free. And in the language of trees, what that meant is that the symbols that we're encoding had to correspond to the leaves of the tree. Symbols could not correspond to internal nodes of the tree that we output. Now, in the optimal binary search tree problem, we do not have this prefix-free constraint, so we're going to have a label that is an object at every single node of our tree, whether it's a leaf or not. But we have a different, seemingly quite a bit harder constraint to deal with, namely the search tree property. So remember, back in the Huffman code case, we didn't even have an ordering on the symbols of the alphabet. There wasn't a sense that one of them was less than another. It wouldn't have even made sense to talk about the search tree property in that context. Here, by contrast, we're given these keys, and there's this total ordering on them, and we better satisfy the search tree property in the tree that we output. That is, at every single node in the tree that we output, it better be the case that all keys in the left subtree are less than the key at that node, and all keys in the right subtree are bigger than the key at that node. That's a constraint that we have no choice but to satisfy. This constraint is harder in the sense that no greedy algorithm, Huffman's algorithm or otherwise, solves the optimal binary search tree problem. Rather, we're going to have to turn to the more sophisticated tool of dynamic programming to design an efficient algorithm for computing optimal binary search trees. That's the solution we'll start developing in the next video. So now that we've motivated and formally defined the optimal binary search tree problem, let's think about how to solve it. After settling on dynamic programming as the paradigm we're going to try to use, we're going to proceed in the usual way, turning to the optimal solution for clues, asking in what way is it composed of optimal solutions to smaller subproblems. So let me just remind you of the formal problem statement. There's n objects we got to store in a search tree, and let's just name them in the order of their keys. And let's name them 1, 2, 3, all the way up to n for simplicity. And we're also given frequencies or weights reflecting how often the different objects are searched for. So that's p1 up to pn, positive numbers. Canonically, we think of these summing to 1 being probabilities, but I actually won't use that fact, so that in general, they're just arbitrary positive numbers. The goal is to output a search tree. It should satisfy the search tree property. It should contain all of these objects 1 through n. And amongst all such search trees, it should minimize the weighted search time. So the sum over all of the items I of the probability of I times the search time for I, namely its depth in the tree plus 1. Now, in case you're feeling cocky about the fact that the greedy algorithm worked to solve the seemingly similar optimal prefix-free binary code problem in the form of Huffman's algorithm, I want to spend a little time pointing out that greedy algorithms are not sufficient, are not correct to solve the optimal search tree problem. So if we were to design a greedy algorithm, what kind of intuition would motivate a particular greedy rule? Well, staring at the objective function, it's very clear that we want the objects that have high frequency of access to be at or near the root, and we want items with low frequency access to be in the bottom levels of the tree, like the leaves. So what are some ways we can compile this intuition into a greedy algorithm? Well, one, perhaps motivated by the success of Huffman's algorithm, is we could think about a bottom-up approach. Now, I'm not going to define what I mean here precisely, but informally, we want to start with the bottommost levels, with the leaves, and the nodes we want to put there are the objects that are accessed the least frequently. Any reasonable way of implementing this kind of body-up greedy rule is not going to work. Let me show you a simple counterexample. So let's just assume we have 4 objects, 1, 2, 3, 4. What I'm showing here on the right in pink is 2 possible search trees valid for those 4 keys. And let's assume that the frequencies are as follows. Object 1 is searched for 2% of the time. Object 2 for 23% of the time. Object 3, the bulk of the time, 73%. And object 4, only 1% of the time. Any greedy algorithm which insists on putting the lowest frequency objects in the very bottommost level of the tree is not going to produce this tree on the right, which has the 2% object below at a lower level than the 1% object. Instead, such a greedy algorithm would presumably output a search tree like the one on the left, which has the 2 as the root, and then the object 4 at the lowest level at depth 2. But you should be able to easily convince yourself that For these probabilities, it's the tree on the right, which is the one you want. That's optimal. Because the object 3 is the one searched for the bulk of the time, that's the one you want at the root, as opposed to the object 2. So I realize I'm being a little informal here, but I hope you get the idea that a naive bottom-up implementation of a greedy algorithm, which if you think about it is really what we did in Huffman's algorithm, is not going to work here. The same can be said about a top-down approach. Perhaps the simplest top-down approach would be just to take the most frequently searched for object and put that at the root, and then recursively develop appropriate left and right subtrees under that most frequently accessed element. So let me show you again informally just the same kind of counterexample. We're going to use the exact same 4 objects, the exact same 2 trees. I will, however, change the numbers. Now let's imagine that object 1 is searched for almost never, just 1% of the time, and each of the other 3 objects are searched for roughly a third of the time each. But let me sort of break ties so that the object number 2 is the most frequently one searched for, 34%. So then in that case, the greedy algorithm will put the 34% node up in the root. When really what should happen is you want a perfectly balanced subtree for the objects 2, 3, and 4, because each accounts for roughly a third of the searches. So let's give object 3 33% of the searches, and object 4 32% of the searches. And again, I'll leave it for you to convince yourself that this is indeed a counterexample. The tree spit out by the greedy algorithm on the left would have an average search time of roughly 2, whereas the search tree on the right would have an average search time of roughly 5/3. So we'd like to produce the tree on the right, but the greedy algorithm proposed here will spit out the tree on the left. This, of course, doesn't exhaust the list of potential greedy algorithms. You could try others, but it's not going to work. There's no known greedy algorithm that successfully solves the optimal binary search tree problem. So in particular, if we focus on the top-down approach, the choice of the root, the choice of what to do at the uppermost level, has very hard to predict repercussions for what the 2 different subproblems look like. So this is what stymies not only the top-down greedy approach, but also a naive divide-and-conquer approach. So for example, if we just wanted to split the keys into the first half and the second half, recursively compute an optimal BST on each of those 2 halves, and then put them back together, the search tree property would say that we have to unite those 2 subsolutions under a root which is the median in between the 2 subproblems. And who's to say that the median is a good choice for the root? Again, because of ramifications further down the tree, maybe that's a stupid root. But boy, is it tempting to try to solve this problem recursively, right? We're trying to output this binary tree. It has recursive structure. If only we knew which root we should pick, we would love to recurse twice, once to construct an optimal left subtree, once to construct an optimal right subtree. Okay, so if only we knew the right root. This is starting to sound familiar, actually. How did it work in all our dynamic programming solutions? We always said, oh, if only a little birdie told us this one little piece of the solution, well, then we could sort of look up or recursively compute the rest of the solution and extend it back to one for the original problem easily. So maybe the same thing's true here. Maybe if only a little birdie told us what the root was, then we could look up or recursively compute optimal solutions to smaller subproblems and paste everything back together and be done. That would be great. So as usual, we want to make this precise with an optimal substructure lemma. We want to understand the way in which an optimal solution to an optimal BST problem must necessarily be constructed from optimal solutions to smaller subproblems. So in the following quiz, I'm going to ask you to guess what the appropriate optimal substructure lemma is. And then after that quiz, once we've identified the right statement, at that point I will show you the proof. Okay, so the answer I'm looking for is the 4th one is D, which is the strongest statement of all. So the first point is that each of the trees, T1 and T2, now as subtrees of a binary search tree, these of course are themselves binary search trees, valid for the trees that they contain. And not only can they be viewed as search trees on the keys they contain, but the claim, which we'll prove on the next couple slides, is that they are indeed optimal. They minimize the weighted search time over all possible search trees for the objects contained in those two trees. So that gets us down, it rules out A, it rules out B. We can say something stronger than that. But we can even say something stronger than C, that each of the two trees is optimal for the items that they contain. We actually know exactly which items are in T1 and which items are in T2. And this is by the search tree property. The search tree property says that at every node, and in particular here at the roots, everything to the left of the root is less than it, everything to the right of the node is bigger than it. So the root being R by assumption, we know the objects 1 through R minus 1, well, they got to be somewhere. The only way they can be is in the left subtree T1. So that's exactly the contents of T1. Similarly, the contents of T2 are precisely the objects R plus 1 through N. So the two subtrees are optimal, and we know exactly which keys they are. It's everything less than R on the left, everything bigger than R on the right. Okay, so here's where things stand at the end of this quiz. We've identified the statement that we're really hoping is true. We're really hoping that an optimal BST, binary search tree, must necessarily be composed in this way of optimal binary search trees for the key sets to the left of the root and the right of the root. If that's true, hopefully with the experience we now have, we can sort of envision what a dynamic programming algorithm might look like. I'll fill in the details in the next video. If this weren't true, if we didn't have this optimal substructure, honestly, I have no idea how we'd get started. It's really not clear what an algorithm would look like if this weren't true. So in the next couple of slides, I want to prove this to you. The format, will not be radically different than the ones we've already seen. I don't think there'll be any big surprises. But it's so important, this really is the whole reason why the algorithm is going to work. I'm still going to give you a full proof of this optimal substructure lemma. So let's take any old optimal binary search tree for keys 1 through n with frequencies p1 through pn. The thing we're trying to prove asserts that the left subtree T1 should be optimal for its keys 1 through R minus 1, and the right subtree T2 should be optimal for its keys R plus 1 through n. So we're going to proceed by contradiction. We're going to assume that's not true. What would that mean? That means for one of these two subproblems, either 1 through R minus 1 or R plus 1 through n, there's a binary search tree with even smaller weighted search cost, search time, than T1 or T2 respectively. The two cases are totally the same, whether in our contradiction we assume T1 is not optimal or whether T2 is not optimal. I'm just going to prove it in the case that T1 is not optimal. So if T1 is not optimal, there's got to be a search tree on its keys 1 through R minus 1, which is better. Call that purportedly better solution T star 1. Now, as usual, the thing which we're going to try to contradict to get the final proof is we're going to exhibit a search tree on all of the keys 1 through n, which is even better than T. But T was supposed to be optimal, so that would be a contradiction. So how do we get our superior search tree for all of the keys? Well, we're just going to take T, and we're going to do cut and paste. We're going to do surgery on the tree T, ripping out its left subtree T1, and pasting in this subtree T star 1. Call the resulting tree T star. So to complete the contradiction and therefore the proof of the optimal substructure lemma, all we have to show is that the weighted search cost of T star is strictly less than that of T. That would contradict the purported optimality of T. So that's precisely what I'll show you on this next slide, and it's going to be evident if we do a suitable calculation. Here it is. So let's begin just by expanding the weighted search time of our original tree, capital T, the purportedly optimal one. Let's expand its definition. So you have one sum n for each of the items I, and the weight we give to a given item is just its frequency p sub I, and we multiply that by the search time for I in T. So let me now pause to tell you the point of this calculation we're about to do. So we start with the weighted search time in T, and that's of course expressed in terms of search times in this tree T. What I want to show next is that that can equally be well expressed in terms of search times in the subtrees T1 and T2. That is, there's a simple formula to compute the search time in T if I told you the search times in T1 and T2. That's what's going to allow us to easily analyze the ramifications of the cut and paste, and to notice that in cutting and pasting in a better tree for the subproblem, we actually get a better tree for the original problem. So to write weighted search time in T in terms of the weighted search time in T1 and T2, it's going to be convenient to bucket the items into three categories. Those that are in the left subtree T1, i.e. 1 through R minus 1, those in the right subtree T2, R plus 1 through n, and then of course left over is the root R itself. So let's just break down this sum into its three constituent parts. So the sum n corresponding to the root r contributes the frequency of r times the search time for r, namely 1 because it's the root. And then we have our sum over just the items up to r minus 1 of their frequencies times their search times, and similarly those r plus 1 up to n, their frequencies times their search times in t. So for the next step, let's observe it's very easy to connect search times in t with search times in the subtrees t1 and t2. Suppose your example, you were searching for some key in t that was in t1, so some key that was less than r. What happens when you search for this item in the tree t? Well, first you visit r. It's not r, it's less than r, so you go left, and then you just search as appropriately through the search tree t1. That is, the search time in the big tree t is simply the search time in the subtree t1 plus 1. 1 because you had to visit the root r before you made it into the subtree t1. So that is, for any object I other than the root, we can write its search time in the big tree t as simply 1 plus the search time in the appropriate subtree. So now let me expand and group some terms just to clean up this mess. So now that the dust has settled, let's inspect each of these three sums. We actually have a quite simple understanding of each of them. So the first sum is just the sum of the pi. So for example, in the canonical case where we're dealing with actual probabilities, this is just 1. The point is, whatever the pi's are, this first sum is just a constant, meaning it's independent of the tree t with which we started. What's the second sum? So that's the sum over the objects from 1 to r minus 1, the frequency of I times the search time for I in the search tree t1. Well, we have a much better, shorter nickname for that sum. It's the weighted search time of the search tree t1 for the objects it contains 1 through r minus 1. Similarly, this last sum from I equal r plus 1 to n of the frequency of I times the search time in t2, that's just the weighted search time in the search tree t2. So we did this computation with the purportedly optimal search tree capital T in mind, but if you think about it, you look at this algebra, this applies to any search tree you like. For any search tree, the weighted search cost can be expressed as the sum of the pi's plus the weighted search cost of the left subtree of the root plus the weighted search cost of the right subtree of the root. In particular, that's true for this tree T star we got by cutting and pasting the better left subtree T star 1 in for T1. So applying this reasoning to T star, we can write its weighted search cost as the sum from I equal 1 to n of all the pi's plus the weighted search cost of its left subtree of its root, which remember by construction is T star of 1, and then it has the same right subtree as the tree T does, namely T2. And the point of all this algebra is that we now see in a very simple way what are the ramifications of cutting and pasting in this better left subtree. We get a better tree for the original key set, contradicting the purported optimality of the tree T that we started with. That completes the proof of the optimal substructure lemma for optimal binary search trees. So now that we understand the structure of optimal solutions for this optimal binary search tree problem, that is, we understand how an optimal solution must be one of a relatively small number of candidates, let's compile that understanding into a polynomial time dynamic programming algorithm. Let me quickly remind you of the optimal substructure lemma that we proved in the previous video. Suppose we have an optimal binary search tree for a given set of keys 1 through n with given probabilities, and suppose this optimal binary search tree has the root r. Well, then it has two subtrees, T1 and T2. By the search tree property, we know exactly the population of each of those two subtrees. T1 has to contain the keys 1 through r minus 1. As usual, we're assuming these are in sorted order. Whereas the right subtree T2 has to contain exactly the keys r plus 1 through n. Moreover, T1 and T2 are in their own right valid search trees for these two sets of keys. And finally, and this is what we proved in the last video, they're optimal for their respective subproblems. T1 is optimal for keys 1 through r minus 1 and the corresponding weights or probabilities, and T2 is optimal for r plus 1 through n and their corresponding frequencies. So let's now execute our dynamic programming recipe. So now that we understand the way in which an optimal solution must necessarily be composed in a simple way from solutions to smaller subproblems, let's take a step back and ask, well, given that at the end of the day we care about the optimal solution to the original problem, which subproblems are relevant? Which subproblems are we going to be forced to solve? For example, with independent sets and line graphs, we observed that to solve a subproblem, we needed to know the answers to the subproblems where we pluck either one or two vertices off of the right-hand side. So overall, what we cared about was subproblems corresponding to prefixes of the graph. In the knapsack problem, we needed to understand subproblems that involved one less item and possibly a reduced residual knapsack capacity. So that led to us caring about solutions to subproblems corresponding to all prefixes of the items and all integer possibilities for the residual capacity of a knapsack. In sequence alignment, when we looked at subproblems, we were plucking a character off of one or possibly both of the strings. So we cared about subproblems corresponding to prefixes of each of the two strings. Now, here's one of the things that's interesting about the binary search tree problem, which we haven't seen before, is that when we look at a subproblem in the optimal substructure lemma, there's two that we might consider. We don't just pluck off from the right. We care about both the subproblem induced by the left subtree and that induced by the right subtree. In the first case, we're looking at a prefix of the items we started with, and that's like we've seen in our many examples. But in the second case, the subproblem corresponding to t sub 2, that's actually a suffix of the items that we started with. So put differently, the subproblems we care about are those that can be obtained by either throwing away a prefix from the items that we started with or throwing away a suffix from the items that we started with. So in light of this observation that the value of an optimal solution depends only immediately on subproblems that you obtain by throwing out a prefix or a suffix of the items, what I want you to think about on this quiz is what is the entire set of relevant subproblems. That is, for which subsets S of the original items 1 through n, is it important that we compute the value of an optimal binary search tree on the items only in S. So before I explain the correct answer, which is the third one, let me talk a little bit about a very natural but incorrect answer, namely the second one. Indeed, the second answer seems to have the best correspondence to the optimal substructure lemma. The optimal substructure lemma states that the optimal solution must be composed of an optimal solution on some prefix and an optimal solution on some suffix united under a common root R. So we definitely care about the solutions to all prefixes and suffixes of the items, but we care about more than just that. So maybe the easiest way to see that is to think about the recursive application of the optimal substructure lemma. And again, relevant subproblems at the end of the day are going to correspond to all of the different distinct subproblems that ever get solved over the entire trajectory of this recursive implementation. So I mean, just think about one sort of example path in the recursion tree, right? So in the outermost level of recursion, you've got the whole item set. Let's say there's 100 items, 1 through 100. You're going through and trying all possibilities of the root. So at some point, you're trying out root number 23 to see how it does. You have to recurse once on items 1 through 22 to optimally build a search tree for them, and similarly for items 24 through 100. Now let's sort of drill down into this first recursive call, where you recurse on items just 1 through 22. Now here again, you're going to be trying all possibilities of the root. There's 22 choices. At some point, you'll be trying root number 17. There's again going to be 2 recursive calls. And the second recursive call is going to be on items 18 through 22. It's going to be the items that were passed to this recursive call, a prefix of the original items, and then the second recursive call here locally is going to be on some suffix of that prefix. So in this case, the items 18 through 22, a suffix of the original prefix 1 through 22. So in general, as you think through this recursion multiple levels, at every step, what you've got going for you is you're either deleting a chunk of items from the beginning, a prefix, or you're deleting a chunk of items from the end. But you might be interleaving these two operations. So it is not true that you're always going to have a prefix or a suffix of the original set of items. But what is true is that you will have some contiguous set of items. It's going to be, if you have I as your smallest item in the subproblem and J is the biggest, you're going to have all of the subproblems in between. And that's because you were only plucking off items from the left or from the right. So that's why C is the correct answer. You need more subproblems than just prefixes and suffixes. All right, so that was a little tricky, identifying the relevant subproblems, but now that we've got them in our grubby little hands, the dynamic programming algorithm, as usual, is just going to fall into place. The relevant collection of subproblems unlocks the power in a very mechanical way of this entire paradigm. So let's now just fill in all the details The first step is to formalize the recurrence, that is, the way in which the optimal solution of a given subproblem depends on the value of smaller subproblems. This is just going to be a mathematical formula which encodes what we already proved in the optimal substructure lemma, and then we're going to use this formula to populate a table in a dynamic programming algorithm to solve systematically the values for all of the subproblems. So let's have some notation to put in our recurrence in our formula. We're going to be indexing subproblems with two indices, I and j, and this is because we have 2 degrees of freedom, where the contiguous interval of items starts, I, and where the contiguous interval of items ends, j. So for a given choice of I and j, where of course I should be at most j, I'm going to denote by capital C sub ij the weighted search cost of an optimal binary search tree just on the contiguous set of items from I to j. And of course the weights or the probabilities are exactly the same as in the original problem, they're just inherited here, pi through pj. So now let's state the recurrence. So for a given subproblem, Cij, we're going to express the value of an optimal binary search tree in terms of those of smaller subproblems. The optimal substructure lemma tells us how to do this. The optimal substructure lemma says that if we knew the root, if we know the choice of the root r, which here is going to be somewhere between the items I and j, then in that case, the optimal solution has to be composed of optimal solutions to the 2 smaller subproblems united under the root. Now we don't know what the root is. There's a j minus I plus 1 possibilities. It could be anything between I and j inclusive. So as usual, we're just going to do brute force search over the relatively small set of candidates that we've identified. So brute force search we encode by just explicitly having a minimum. So we choose some root r somewhere between I and j inclusive. And given a choice of r, we're going to inherit the weighted search cost of the optimal solution on just the prefix of items I through r minus 1. So in our notation that would be C of I r minus 1. Similarly, we pick up the weighted search cost of an optimal solution to the suffix of items r plus 1 through j. And if you go back to our proof of the optimal substructure lemma, you'll see we did a calculation which gives us a formula for how the weighted search cost of a tree depends on that of its subtrees. And in addition to the weighted search cost contributed by each of the 2 search trees, we pick up a constant, namely the sum of all of the probabilities in the items we're working with. So here that's sum of p sub k, where k ranges from the first item in this subproblem I to the last item in this subproblem j. So one extra edge case we should deal with is if we choose the root to be the first item, then the first recursive term doesn't make sense. Then we would have C, I minus 1, which is not defined. Similarly, if we choose the root to be j, then this last term would be C of j plus 1j, which is not defined. Remember, indices are supposed to be in order. So in that case, we just interpret these capital C's as 0. And so why is the recurrence correct? Well, all of the heavy lifting was done in our proof of the optimal substructure lemma. What did we prove there? We proved the optimal solution has to be one of just j minus I plus 1 possible things. It depends only on the choice of the root. Given the root, the rest is determined for us. The recurrence is, by definition, doing brute force search through the only set of candidates. So therefore, it is indeed a correct formula for the optimal solution value in terms of optimal solutions to smaller subproblems. So now that we have our magic formula, our recurrence, all that's left to do is to systematically solve the subproblems. As usual, it is crucial that we solve the subproblems in the right order, from smallest to largest. How should we measure the size of a subproblem in the optimal binary search tree problem? The natural way to do it is the number of items in the subproblem. So if you're starting at I and you're going till j, the number of items in that subproblem is j minus I plus 1. And that's going to be our measure of subproblem size. So let's bust out our trusty array. The number of dimensions of this array is going to be 2. That's because we have 2 different degrees of freedom for indexing subproblems, one for the start of the contiguous interval, one for the end. So the outer for loop is going to control the subproblem size. It's going to ensure that we solve all smaller subproblems before proceeding to larger subproblems. Specifically, we'll be using an index s, and in the iteration of this outer for loop, whatever the current value of s is, we're only going to consider subproblems of size s plus 1. So you should think of s as representing the difference between the larger index j and the earlier index I. The inner for loop controls the first item in the contiguous interval that we're looking at. So that's just I. And now all we have to do is rewrite the recurrence in terms of the array entries and with this change of variable where s corresponds to j minus I. That is for a given subproblem starting with the item I and ending with the item I plus s. We just, by brute force, pick the best root. So the root here is going to be somewhere between I and I plus s. Regardless of the choice of the root, we pick up the constant, the sum of the pk's, where here k is ranging from the first item I to the last item I plus s. And then we also look at the previously computed optimal solution values for the two relevant subproblems, one starting at I, ending at r minus 1, the other starting at r plus 1 and ending at I plus s. So a couple quick comments about the two array lookups on the right-hand side of this formula. So first of all, if we choose I to be the root to be the first item I, then the first lookup doesn't make sense. If we choose it to be the last item, the second array lookup doesn't make sense. In that case, it's understood we're just going to interpret these lookups as 0. Of course, in an actual implementation, you'd have to include that code, but I'll let you take care of that on your own. So the second comment is just our usual sanity check, and again, you should always do this when you write out a dynamic programming algorithm. When you write down your formula to populate the array entries, make sure that on the right-hand side, whenever you do an array lookup, that is indeed already computed and available for constant time lookup. So in this case, whatever our choice of the root is, the two relevant subproblems are going to involve strictly fewer items than what we started with, and therefore the two subproblem lookups on the right-hand side will indeed have been computed in some previous iteration of the outer for loop. Remember, the outer for loop is ensuring we solve subproblems from smallest number of items up to largest number of items. And of course, after the two for loops complete, what we really care about is the answer in A of 1 comma n. That is the optimal binary search tree value for all of the items. That's the eventual output. Some students like to think about these double for loops pictorially. So let's imagine A, the 2D array, is laid out as a grid. So imagine the x-axis corresponding to the index I, that is the first item in the set of items we're looking at, and the y-axis corresponding to j, the last item in the current set. And let me single out the diagonal of this grid. So these are subproblems corresponding to I equals j, that is subproblems with a single element. Now we only ever solve problems where j is at least as large as I. So that means we're really only filling in the upper left or northwestern part of this table. So we never bother to fill in the southeastern, the bottom right part of this table. We just sort of think of it all as 0. Now, in the first outer iteration, so when s equals 0, that's when our dynamic programming algorithm solves, in turn, each of the n single item problems. So in the first iteration of this double for loop, it's going to solve the subproblem A11, and the next iteration of the inner for loop is going to proceed to A22, then A33, and so on. In each of those, both of the array lookups are going to just correspond to 0, and we're just going to fill in this diagonal with the base cases where AII is just the probability of item I. Then, as the dynamic programming algorithm proceeds, we're going to be filling in the upper left portion of this table diagonal by diagonal. Each time we increment s, the index in the outer for loop, we're going to march up to the next northwesternmost diagonal, and then as we step through the possible values of I, we're going to fill in that diagonal one at a time, moving from southwest to northeast. When we're filling in the value of a subproblem on one of these diagonals, all we need to do is look up the value for two subproblems on lower diagonals. Lower diagonals correspond to subproblems with strictly fewer items. So that's it. That's a dynamic programming algorithm that computes the value of an optimal binary search tree given a set of items with probabilities. I'm not really going to say anything about correctness. It's the same story as we've seen in the past. All the heavy lifting is in proving the optimal substructure lemma. That gave us the correctness of our recurrence. Given that our magic formula is correct and we're just applying it systematically, correctness of the dynamic programming algorithm follows in a straightforward way just by induction. Let me, however, make some comments about the running time. So let's just follow the usual procedure. Let's just look at how many subproblems got to get solved and then how much work has to be done to solve each of those subproblems. So as far as the number of subproblems, it's all possible choices of I and j, where I is at most j. Or in other words, it's essentially half of that n by n grid. So this is roughly n squared over 2. Let's just call it theta of n squared. So a quadratic number of subproblems. Now, for each of the subproblems, we have to evaluate this recurrence. We have to evaluate the formula, which conceptually is a brute force search through the number of candidates that we've identified. And a distinction between this dynamic programming algorithm and all of the other ones that we've seen recently, sequence alignment, knapsack, computing independent sets of line graphs, is there's actually kind of a lot of options for what the optimal solution could be. That is, our brute force search for the first time is not over a merely constant number of possibilities. We have to try every possible route. Each of the items in our given subproblem is a candidate route, and we try them all. So given a start item of I and an end item of j, there's j minus I plus 1 total items, and we have to do constant work for each of those choices. So there will be some subproblems that we can evaluate quickly and only say constant time if I and j are very close to each other. But for a constant fraction of the subproblems we have to deal with, this is going to be linear time, theta of n time. So overall, that gives us a cubic running time, theta of n cubed. All right, so I would say this running time is sort of okay, not great. So it is polynomial time, that's good. It's certainly way, way, way faster than enumerating all of the exponentially many possible binary search trees. So it blows away brute force search, but it's not something I would call blazingly fast or for-free primitive or anything like that. So you're going to be able to solve problem sizes with n in the 100s, but probably not n in the 1000s. So that will cover some applications where you'd want to use this optimal binary search tree algorithm, but not all of them. So it's good for some things, but it's not a universal solution. On the other hand, here's a fun fact. And the fun fact is you can actually speed up this dynamic programming algorithm significantly. You can keep with the exact same 2D array with the exact same semantics. Again, each index is going to correspond to the subproblem with the optimal binary search tree between items I and j inclusive. But you can actually fill up this entire table, all n squared entries, using only a total of n squared time. That is, on average, constant work per subproblem. So this fun fact, it's very clever. It's certainly more intricate than what we've discussed in this video here, but it's not impossible to read. So if you're interested, I encourage you to go back to the original papers or search the web for some other resources on this optimized speed-up version of this dynamic programming algorithm. I mean, at a very high level, sort of from 30,000 feet, the goal is to avoid doing this brute force search over all possible routes in every single subproblem. And it turns out there's structure, nice structure in this optimal binary search tree problem that allows you to piggyback on the work done in smaller subproblems. So in smaller subproblems, you already searched over a bunch of candidate routes, and it turns out using the results of those previous brute force searches, you can make inferences about which subset of the current set of routes might conceivably be the ones that determine the recurrence. And so that lets you avoid searching over all of the possible candidates for the routes, instead focusing just on a very small set. In fact, on average, constant number of possible routes over all of the subproblems. And needless to say, this speeding up of the running time from cubic to quadratic really significantly increases the problem sizes that you can now apply this algorithm to. So now instead of being stuck in the hundreds, you'd certainly be able to solve problem sizes in the thousands, possibly even in the 10,000s using this quadratic time algorithm. Very cool.